kind of relationship can be found out from this? Let's say in this particular data, I want to look for a relationship like if x is increasing, whether y is increasing, or if hello guys, hello guys, hello guys, variable. So we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about a very important topic which is called as covariance and correlation. In this video, the agenda will be that we'll try to understand about covariance, what exactly covariance is used for. We will be seeing multiple examples. Then we will be seeing what exactly is correlation, what is the differences between covariance and correlation, and some of the amazing use cases how we can use it as a data scientist or a data analyst. So all those things will be specifically covered in this video. So first of all, we'll go ahead with the definition. So over here, the definition is pretty much simple. So covariance and correlation are two statistical measures used to determine the relationship between two variables. This is really very important. If you really want to find out the relationship between two variables, and specifically these variables are continuous variables, both are used to understand how changes in one variable are associated with the changes in another variable. Okay. So for both this, if we really want to quantify this relationship between two variables, we can actually use covariance and correlation. Now first, we will go ahead with covariance. We'll understand the formula. We'll solve some problems over here, and then we will further go ahead and understand about correlation. So again, covariance definition is given over here. Covariance is a measure of how much two random variables change together. If the variable tend to increase and decrease together, the covariance is positive. If one tends to increase when the other decreases, the covariance is negative. Okay. So here, when it is positive and when it is negative. Okay. So initially, as usual, let's consider an example. Let's say I have two random variables x and y. Okay. Now in this x and y, this can be a features in the data set also. Let's say I have some values. I have like 2, 4, 6, 8. Okay. And let's say in my y, I have 3, 5, 7, 9. Okay. So here specifically I have two random variables x and y. Okay. And with respect to this x and y, every record I have some data over here, right? I have 2, 3, I have 4, 5, I have 6, 7, I have 8, 9. Okay. Now, if I really want to find out a way to quantify the relationship between x and y. Now, when I say quantify, what does this basically mean? I will take this x and y variable or random variable and I'll try to find out some relationship between them, right? Now, what kind of relationship can be found out from this? Let's say in this particular data, I want to look for a relationship like if x is increasing, whether y is increasing, or if x is decreasing, whether y is increasing, or if x is increasing, whether y is decreasing, or if x is decreasing, whether y is decreasing. So this kind of relationship I really want to find from this particular data, okay? And in order to find out this relationship in some numerical format, we can specifically use covariance and correlation. But here, since we are starting with covariance, now let me take a very good practical example. Let's say I have a feature which is called as the size of the house, okay? And the other feature that I have, price of the house. So let's say this is my data set. Now in this data set, let's say if the size of the house is somewhere around 1200 square feet. Let's say the price is 45 lakhs. Okay. If I increase this to 1300 square feet, let's say over here I will go ahead and at 50 lakhs, right? If I keep on increasing again, 1500 square feet, let's say over here I have 75 lakhs. So do you see some kind of relationship? As the area of the house, as the size of the house is increasing, the price of the house is also increasing. So this is the relationship with respect to this particular data. Not only that, if the size of the house decreases, then this price will also decrease. So both this scenario is basically getting satisfied from this data set that we have. But at the end of the day, we need to find out a way to find out the relationship between x and y, and we should be able to give some numerical number to it, right? That is what I'm talking about. That is nothing but quantifying the relationship. Now, let's take this all relationship and build some diagrams over here. Okay, so I'll create some scattered plot. Let's say this is my x comma y. Okay. Let's say over here I have my x, I have my y. Now let's focus on this x comma y. What kind of relationship this data is basically following? See, when x is 2, y is 3. When x is 4, y is 5. When x is 6, y is 7. When x is 8, y is 9, right? So if I just see this data set, right, and if I just keep on plotting, don't you think we are following this specific pattern, right? As x increases, so here two important patterns we are seeing. When x increases, y is also increasing, and when x decreases, y is also decreasing, right? So these two patterns we are able to see from this specific data set. Okay, this is really much important to understand. Okay, the other pattern, one more pattern that we can specifically have. Okay, let's draw the other pattern, which is possible with respect to this x and y random variable. Let's say I have x and y. Now this time, let's take one example. Let's say I have my x and y over here. I'll say, hey, this is 7, y is 6. Let's say this is 5, this is 4, this is 3, this is 2, this is 1, this is 0. Now in this scenario, when x is decreasing, see one. Okay, this is. Let me just change this particular example a little bit. Okay, so here, one scenario was that when x is increasing, y is increasing, right? So when x is increasing, y is increasing. When x is decreasing, y is decreasing, right? One example can be, let's say if I go ahead and write like this: 7 is equal to 10, 6 is equal to 12, 5 is equal to 14, 4 is equal to 60. Now in this scenario, don't you see the relationship looks something like this? When x is decreasing, y is increasing. Yeah. When x is decreasing, y is increasing, right? 10, 12, 14, 16. When y is decreasing, do you see x is increasing, right? If from 16 to 14 it goes, at that point of time your x increases. So this relationship is basically satisfied by this, right? If I probably consider this data set, it satisfies this relationship. Now similarly, if I try to plot it, my data points will look something like this, right? Let's say I'm just plotting it like this. And this satisfies this particular relationship, right? Now usually if we go ahead and use covariance, okay? And covariance actually helps you to quantify the relationship between x and y, okay? That is two random variables. Usually, when we apply covariance for this kind of relationship where x is increasing, y is increasing, x is decreasing, y is decreasing, here you get something called as a positive covariance. Positive covariance basically means if you calculate the covariance, I'm going to get some positive value. Why? Because x is decreasing, y is x is increasing, y is increasing, x is decreasing, y is increasing. For this kind of relationship, if I go ahead and try to calculate the covariance, I get a negative covariance because it is opposite. When x is decreasing, y is increasing. So this here you're going to get a negative value. Okay. Now you may be thinking, Krish, how you're saying positive covariance and negative covariance? Let's do it with the help of calculation. Okay. So usually, if I go ahead with the covariance formula looks something like this. Okay. So if I just go ahead and write covariance x comma y is nothing but summation of I is equal to 1 to n. I'm just taking a sample size n. Okay, sample size n. I cannot consider population because it is difficult. We do not have the entire population data. Let's consider that. Then here I will go ahead and write x of I minus x bar. Okay. Then you have y of I minus y bar divided by n minus 1. Okay. So this is the entire formula for covariance. Now you may be thinking this formula looks a little bit different, a little bit similar. Okay. To what? Okay. And this can be a really important interview question. Do you remember if instead of finding covariance of x comma y, if I go ahead and write covariance of x comma x, now in this scenario what will happen? X of I minus x bar. This will become, so let's go ahead and write summation of I is equal to 1 to n. X of I minus x bar and this y side is also x. So if I'm trying to find out x, relationship of x with x, right? Relationship of random variable x with x, it is nothing but, if I go ahead and take this, it will be the same thing, and this will be divided by n minus 1. And this is nothing but, this is equal to variance of x. So covariance of x comma x is nothing but it is equal to variance of x. Please try to understand this, okay? And this is what we have actually proved. If you remember, what is this formula? This is nothing but variance of x only, right? How do we write variance of x? Nothing but summation of I is equal to 1 to n x of I minus x bar divided by n minus 1 whole square, right? This was my variance formula. So covariance of x to x, that means if I want to find out the relationship with respect to x, it is nothing but variance of x. So this in short is talking about the spread of the data, right? But if you need to find out the relationship between one random variable to the other, then this is the formula that we specifically use. Okay, so let me just go ahead and write more about this. So here I'm going to go ahead and write x of I. X of I is nothing but my data points of random variable x. Okay, then what is x bar? X bar is nothing but sample mean of x. I hope this is really similar and simple for you all to understand. Y of I, what it is? Data points of y. Data points of random variable y. Okay, now if I go to the next data point, it is nothing but y hat. Y hat is nothing but sample mean of y. Now let's see whatever I have said till now. Okay, whatever I have actually said till now. If this follows this particular thing, do we get a positive covariance? If this follows this particular relationship, if x and y follows this relationship, do we get a positive covariance? If x and y follow this relation, do we get a negative covariance by using this formula? That is what we're going to see. So let's solve one basic example and let's see how things work out. Okay, so here let's consider one example of, I have some data of some students. Okay, now this data has something like this. Let's say over here I'll go ahead and write hour studied. This is nothing but number of hours studied. Let's say this is my x, and this is nothing but exam scores, which is my y. Okay, so in this scenario, let's say if the person is studying for 2 hours, the person has got 50 marks. This person has studied for 2 hours daily. Let's say this person has studied for 3 hours daily. This person has got 60 marks. Then 4, then I've got 70 marks. 5, I've got 80 marks. And 6, I've got 90 marks. Right? Now, just by seeing the specific data, you know that what kind of relationship this is following. This is nothing but when x is increasing, y is increasing, and x is decreasing. Y is decreasing, right? This is the relationship that it is following. And we have already seen this will definitely follow some kind of positive covariance. The final output that we are going to get is getting a positive covariance. Why? Because x is increasing, y is increasing. When x is decreasing, y is decreasing. So x is directly proportional to y, right? So let's go ahead and calculate this entire formula, right? So I will take this entire formula and we'll go ahead and calculate it. Let's calculate and let's see whether we'll get a positive covariance or not. And I hope so we get it, right? If my calculation is absolutely perfectly fine. So first thing first, what we need to calculate? The first thing that we need to calculate is x bar, right? Over here we need to calculate x bar, y bar. What is x bar? X bar is nothing but 2 plus 3 plus 4 plus 5 plus 6 divided by 5. It is nothing but, if you see this, it will be 4. Okay, second thing that we need to calculate is nothing but y bar. See, 5, 9, 14, 20, 20 divided by 5 is 5. Okay, y bar, in order to calculate y bar, I have to go ahead and write 50 plus 60 plus 70 plus 80 plus 90 divided by 5. That is nothing but this will be equal to 70. I've done the calculation, you can just check it out. So I've got my x bar and y bar. Okay, now let's go ahead and calculate the covariance of x and y. Okay, so now I will just go ahead and write covariance of x comma y is nothing but, first of all, x of I minus x bar. What is x of I minus x bar? And it is summation. Please remember this, it is summation. Okay, summation of this from I is equal to 1 to n. So this is my I is equal to 1, 2, 3, 4, 5, like the total 5 records. Okay, so first I have 2 in x of I, and y of I have 50. So I'll go ahead and write over here 2 minus, what is my x bar? 4. Y bar I know it is 70, and the first value that I have is 50. Right, so 50 minus 70. Now I'll go to summation. I have to go to I is equal to 2. I is equal to 2 is nothing but 3 and 60. So here we will go ahead and take 3 minus 4. And then here you will go ahead and write 60 minus 70. Okay. Similarly, I will go ahead and write my third number 4 minus 4, 70 minus 70. Okay, you can go ahead and see to it. Then you have 5 minus 4. It is nothing but your 80 is there. 80 minus 70. And finally, 6 minus 4 multiplied by 90 minus 70. Right? This is all divided by n minus 1. What is n? N is nothing but. So if you go ahead and probably see to it, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And it is n minus 1. So we'll go ahead and calculate this with 4. Okay. So just do the calculation. I think I've done the calculation. It will be somewhere around 20. Okay, and just let me know in the comment section whether the calculation is right or not. But I think this should be the right answer. Okay, now see, I'm getting a positive value. So here, this positive value indicates the positive covariance. Positive covariance. It indicates the number of hours studied increases the exam score. Increases the exam scores also. Right? So this is true, right? Over here, definitely. And if I have some other kind of data, you just go ahead and calculate, you may also get a negative correlation. That basically means if your x is increasing, y is decreasing. If that kind of relationship is there, then you get a negative value. But here we got a positive value. Okay. So let's say if I have also some data like this. Let's say I have x and y. Let's say consider that I have 7, 10, then I have 6, then I have 12, 5, 14. Just go ahead and calculate the covariance for this. And this you'll be getting a negative value. This indicates that when x is increasing, y is decreasing. And when y is increasing, x is decreasing. This indicates this relationship. If it follows this relationship, you're going to get a negative covariance. Okay. So I hope you got an idea about covariance, right? What exactly is covariance and how do we specifically use covariance? Okay. Now let's talk about some very good advantages and disadvantages of using covariance. Okay. So first of all, let's go ahead with the advantages. Now, first advantage is that you'll be able to quantify the relationship between x and y. This is one of the major advantages between x and y. Okay. Now let's talk about the disadvantage, which is also really important. Okay. And obviously this is good. And I'll tell you the real application of this. What happens if you're able to quantify the relationship between x and y. Okay. So the disadvantage is nothing but over here. I'll go ahead and write. Covariance does not have a specific limit value. Limit value. Now what does this basically mean? Let's say if I go ahead and calculate my covariance, this value may range between minus infinity to plus infinity. There's no specific limitation. Okay. Like it will be ranging between this value itself. So what happens because of this? Let's say I have 3 variables. Okay, 3 random variables. Let's say if I go ahead and find out the relationship between A and B. Let's say if I get plus 20. And let's say if I go ahead and calculate B and C, I may get plus 30. Okay. And let's say that if I go ahead and calculate A and C covariance, let's say I get plus 40. Now here you can see that if I'm trying to find out this particular relationship, okay, I will not be able to tell that the covariance of A comma B will be greater than, let's say over here, covariance of A comma B is 20, okay, and here, let me just remove this. I've calculated covariance of B comma C. I have 30, right? Now, if I have 30 value over here, if I have 20 value over here, I cannot say in this scenario that covariance of B comma C is greater than A comma B. The reason is very simple, because here we are not restricting. The limit value is not at all restricted. Okay, it can be plus 300 also. It can be plus 300. It can be plus 100, right? We cannot say that which one is stronger. If it is minus 300 and this is also minus 200, we cannot say which one is much more stronger. The reason is very simple, because covariance does not limit that covariance value, how much positive or how much negative. This is the major disadvantage, right? And at the end of the day, we should always try to restrict this covariance value to some limit. If I'm able to limit it between minus 1 to plus 1, then it would be great. Why? Because let's say if I say A, my covariance of, let's say my covariance of A comma B and covariance of B comma C, if this is, let's say 0.98 and this is 0.96, here I can say, hey, this covariance is more than this. But in this scenario right now, we do not have any limit. And there is no way that we can say, hey, even though this shows 300, I cannot say, hey, this is stronger than this. The covariance is stronger than this in this scenario. This is the major disadvantage of having covariance. So for this, what we do is that we specifically use another type of the statistical analysis techniques, which is basically called as correlation. So the second type, which we specifically have, is something called as correlation. Now in correlation also, you have two types. One is Pearson correlation coefficient. And the second type is basically called as Spearman rank correlation. Spearman rank correlation. Now let's go ahead and talk about Pearson correlation coefficient. So this is the first topic that we're going to discuss about. It is nothing but Pearson correlation coefficient. Okay. So this is the first topic that we'll talk about. Now what does Pearson correlation coefficient do is that it limits the values between minus 1 to plus 1. Okay. That is what it is basically doing. Now before in covariance, I used to get this limit between minus infinity to plus infinity. It can have any value. But what Pearson correlation coefficient is doing is that it is limiting all the values of relationship between x and y between minus 1 to plus 1. So for this, let's go ahead and see the formula. So this is my rho. This is how we write Pearson correlation is equal to covariance of x comma y. So here also we go ahead and calculate covariance, but we divide by standard deviation of x and standard deviation of y. Once we divide this by standard deviation of x and y, this entire value will get limited between minus 1 to plus 1. Okay, and because of this, we can now clearly say that which correlation is very stronger compared to what. Okay, now understand over here. Here I will go ahead and write some important point. The more the value towards plus 1, the more positive correlated x and y is. Okay. Second point over here, right? The more the value towards minus 1, the more negative correlated it is. Okay, specifically x and y. Okay, and this is all possible because of Spearman. Sorry, this is all possible because of the Pearson correlation coefficient. Now you take the same problem, right? Here we got the covariance as 20. Okay, so if you probably go ahead and see this particular formula, covariance we have calculated it as 20. Now this 20 will be further divided by standard deviation of x and standard deviation of y. Okay. Now, if I'm able to, you can probably do the calculation, guys. Then the final you'll be getting this value will be ranging between minus 1 to plus 1. Specifically, this will be more than 0 because I've got a positive correlation over here, but it will be between 0 to 1. Specifically, this particular value will be coming between 0 to 1, right? Because this is already positive correlated. Okay. Now, this is one amazing important thing about Pearson correlation coefficient. Okay. Now, there is also one more technique which is called as Spearman rank correlation. Okay. So let's talk about this particular technique. Spearman rank correlation. Okay. Spearman rank correlation. Now for this, what I will do is that I will quickly show you one amazing thing. That is Wikipedia. Okay, and let's go to the Wikipedia and let's talk about Spearman rank correlation. Okay, so here you'll be able to see the first link is Wikipedia only. Now please observe on this figure. Okay, please observe on this figure. And let's talk about this figure. Now in this figure that you'll be seeing, I have this kind of data. Okay, when I have this kind of data, okay, and let me just show some more thing over here. Let me just go ahead and write a Pearson correlation coefficient. Okay, and again I will go to my Wikipedia. Wikipedia is amazing, guys, and let's observe this. So in Pearson correlation coefficient, let's say all the points are in one line, just like this, right? And you can see over here it follows this particular relationship wherein x increases, y is decreasing, right? So this Pearson correlation coefficient you are getting minus 1. If I go and calculate for this when my point is scattered here and there, you'll be able to see that my Pearson correlation coefficient for this is between minus 1 to 0. Okay. Similarly, if you have this when x is increasing, y is increasing, x is decreasing, y is decreasing, that relationship, your value ranges between 0 to 1 plus 1. And if all the points are in the straight line but it is in the increasing order, so when x is increasing, y is increasing, when x is decreasing, y is decreasing, you'll be getting like this. And if you have a scattered point somewhere like this where there is no relation at all, then your Pearson correlation will be 0. More example you can see over here. Let's say all these data points are in straight line, I'm getting 1. If these data points are in this line, I'm getting 0.8. If it is in like this, then 0.4, then 0, minus 0.4, minus 0.8, minus 1, right? Then with respect to this kind of data point 1, 1, 1, 1, then you have minus 1, minus 1, minus 1. Why? Because here x and y are inversely proportional. Here they are directly proportional. And with respect to this, here we don't have any kind of pattern. So all the values which we calculated with the help of Pearson correlation coefficient is probably coming as 0. Okay? Now let's understand when do we use this Spearman rank correlation coefficient. Really important topic altogether. Let's understand about this. Now see, for this particular data points, you can see over here, it follows one kind of relationship. Okay. And let me do one thing. The best way will be that I will just try to take a screenshot of this. Okay. Let's take a screenshot. Okay, I'll copy it over here. I'll paste it over here so that you can also refer it. Okay, and this will be really helpful for you all to understand. Let's say I have this data point. Let's observe this data point. Observing this data point is important. Okay. Okay. Now let's see this. Okay. Over here, if I probably consider every data point. Okay, every data point. What kind of relationship it actually follows? So here you can see that when x is increasing, y is increasing. When x is decreasing, y is decreasing. Obviously, for this scenario, I know that for every data point of x, there is a y data point and it is in the increasing order, right? So based on this, even this is a scenario in Pearson correlation coefficient. If you go ahead and calculate this, you're getting the value as 0.88. Over here you can see, you're getting it as 0.88. Now why you may be getting as 0.88, but you can see for every data point it is increasing, it is following this particular relationship, right? But why still you're getting it as 0.88? You should have got as 1, right? Because x and y are directly proportional. For every data point when x is increasing, y is also increasing. For every data point when x is decreasing, y is decreasing. But over here, if you see this region, there are some data points which is increasing in a slower rate, right? In this particular region. And because of this, your Pearson correlation is coming as 0.88. Now, one problem with Pearson correlation is that if you just have a linear data, let's say if you have data points which looks like this, which are just in one line, for this, if you go ahead and calculate with the help of Pearson correlation, I will be able to get 1. But if I have non-linear data, if I have like this, if I have non-linear data, something like this, see in this data, I have something like this kind of graph, right? I have this kind of graph. Now, in this scenario, this value will be ranging between 0 to 1. But we know that for every data point, when x is increasing, y is increasing only, right? So, Pearson correlation will not be able to capture, Pearson correlation is not able to capture the correlation for non-linear data. For non-linear data. What does non-linear data basically mean? Let's see this example. In this scenario, when I have my x and y, this is my x and y, right? In this, my data points look something like this. Let's say my data point looks something like this. Now, all the data points are not in straight line, right? With respect to every data points here, you'll be able to see that there is a change, right? Here, there may be less degrees of x and y, but here there may be more, right? So, Pearson correlation is not able to capture this information very much properly. And that is the reason you're able to see that if you try to find out the value, it is coming as 0.88. But exactly it should be 1 only, because at every data point this is increasing. And this is what Spearman correlation actually does. Right? Disadvantage is basically solved by Spearman rank correlation. What is the full form of what is the formula in actually calculating the Spearman rank correlation? It is nothing but R of S. Here, instead of calculating the covariance of x and y, we calculate the covariance of rank of x and rank of y. Okay? And this will specifically be divided by standard deviation of rank of x, comma, multiplied by standard deviation of rank of y. Now, what exactly is this rank? Let's consider that I have my x, y coordinate. I have 1, 2, 3, 4, 5, 6, 7, 8, and then you have 0, 7, right? So if I go ahead and calculate the rank of x, so here you'll go ahead and see, right? 0 is given which rank? Right? What 0 value will be given, which rank it will be given, right? Or 7 will be given what rank? So here 7 is the highest number, so rank can be given as 1, right? Or let me do in this way, right? Which is the smallest number here, 0. So this will be given the rank as 1, right? Less value. Then you have 1. This will be given the rank of 2. This will be given the rank of 3. This will be given the rank of 4. This will be given the rank of 5. Now here we are going to consider the rank, right? And based on that, we are going to sort the numbers, right? Rank of 5 is nothing but which is the smallest number 2. So here I will give it as 1. And then you have 4. Then you have 3. Then you have 4. Then you have 5. Right? So just by giving the specific rank, you know that now your values, when you try to calculate with respect to this, you'll be able to capture this non-linear properties also. And because of this, your Spearman correlation will be always equal to 1. Even though you have less deviation from here, where your x is increasing, y is also increasing by lesser amount, at any point of time, it will be able to capture this entire information. Okay? And that is how you are able to get that non-linear properties getting captured. Very simple. With the help of Pearson correlation coefficient, you're not able to capture this non-linear thing. That is the reason you can see in this diagram. When we have this kind of data, whereas x is increasing with this, it is following this relationship also, but your Pearson correlation is just giving 0.88. The reason is that at this point of time, right, when x is increasing, y may not be increasing that much when we compare to this particular data points. So because of that, your Pearson correlation does not capture the entire non-linear information. Yes, for linear information, it will be able to capture. It will give you exactly 1. So similarly, what we do is that we use Spearman rank correlation, and here this is the specific formula wherein we just don't directly calculate the covariance with respect to x and y. Instead, we focus on rank of x and rank of y. Rank of x and rank of y is nothing but the numbers, a specific number based on the number itself. A specific rank is given. Let's say the smallest number will be given a smallest rank, the largest number will be given a larger rank, right? And that is how you probably go ahead and do it. Now, still, the main important question comes that, Krish, how do we use this in real world scenario? In data science, when you do EDA or when you do feature engineering, there's a concept called as feature selection. Now, in feature selection, let's say I have some parameters, like I have some features like size of house, right? Number of rooms, okay? And let's say I have price, okay? Let's say that if I increase the size of the house and then the number of rooms increases, then you can know that there's a direct correlation over here. So the price will also increase, right? Let's say that I go ahead and add another parameter, another feature over here, location. So if the location changes to a new city, then also we know that the price will still increase, right? Yeah. So this information, because of this information, this is increasing. So we can definitely say that this is directly correlated, this is directly correlated, this is directly correlated with respect to the output feature, that is price. Because we need to predict this specific output, right? Now these 3 features are very important and it is directly correlated to the price. If this is going to increase, this price will also increase. If this is going to decrease, this price will also decrease. Okay. Now let's say that I go ahead and add another feature. Let's say whether the house is haunted or not. If the house is haunted, then what will happen? If the house is haunted, the price is going to decrease, right? So here you can see that there's a negative correlation, right? If the house is haunted, definitely the price is going to decrease because everybody will say in the market, hey, there is some ghost in that particular movie, in that particular house, so it is not better that you buy it, right? So because of that, what will happen? Negative correlation will be there, so the price will decrease. Now let me say that there is one more feature, which is called as number of people staying in the house. Do you think this feature will be directly proportional to the price? The answer is no. Why? Because in one house, any number of people will be probably staying, right? So this and this feature are not at all correlated, right? So if I go and try to find out the correlation between this and this, it will be approximately equal to 0, right? This will be exactly equal to 0. Why? Because this is not an important feature. How can number of people staying in the house become a very important feature? Now what we can do is that with the help of correlation, we can find out what is the correlated value. If the correlated value is approximately equal to 0 or near to 0, I can directly delete this feature. I don't want it because this is not playing a very important role to predict my price. But these all are very important features, right? Because these are all positively correlated. This is negatively correlated. This will actually help me to determine the price of the house in a proper way. And this is what feature selection is all about. In data science, what we do, as a data analyst, what we do is that what are the important features that we really need to consider for our model building or for our use case solving. And right now here, I can definitely see that this particular feature is not that important, right? So yes, I hope you got an idea about it. In this video, I have discussed about all the important things about covariance and correlation. In correlation, we have discussed about 2 important things. One is Pearson correlation coefficient and Spearman rank correlation coefficient. In covariance, we do not have a specific limit value. With the help of Pearson correlation coefficient, the value is between -1 to +1. Spearman rank correlation will also be able to capture the non-linear properties of x and y features, whereas in Pearson we were not able to do that. So I hope you were able to understand this entire video. I hope I was able to explain it in a much more better way. Please go ahead and revise it again so that you'll be able to get a clear understanding. So yes, this was it from my side. I'll see you in the next video. Thank you. So guys, we'll continue the discussion with respect to statistics, and now in this topic we're going to discuss about probabilities. Now probabilities are pretty much important because in machine learning, when you're actually doing some kind of classification algorithms, at that time you get your output based on probabilities, and based on a threshold value you decide like which class it may probably belong to. But in probabilities, we'll try to understand some of the important information that are important in terms of statistics. Over here, we're going to see what is the introduction, what is the additional rule in probability. For a mutual exclusive event, we're going to understand what exactly is mutual exclusive event. Then we're going to see non-mutual exclusive event, and there is also a multiplication rule which is specifically for independent and dependent events. Probably this video will be divided into two parts. In this particular part, I'll just try to show you the basic introduction to probability, and then we'll try to discuss about this additional rule for both mutual exclusive and non-mutual exclusive event. So let's proceed and let's try to first of all get a brief introduction about probability. So first, I'm going to just define a probability. What exactly is probability? If you really want to define in front of a recruiter, you can just write it that it is about determining the likelihood of an event, or an experiment, anything. Now let me take an example. Okay, suppose I toss a coin. So what are the possible outcomes whenever I toss a coin? I may either get head or tail. So if I say that what is the probability of getting a head when I toss a coin, obviously the sample space is 2, so I will basically divide by 2. And what is the possibility in one single toss that I may get head? It's obviously 1, right? So this 1 by 2, which is nothing but 50% probability, will definitely there to basically get a head. Similarly, if I go and basically try to find out what is the probability of getting a tail when I'm tossing a coin, it will also be 1 by 2, which is nothing but 50%. Let's take another example. Suppose if I am rolling a dice, what are the possible outcomes that I have when I'm rolling a dice? There are 6 different outcomes. Then suppose if I say that what is the probability when I'm rolling a dice, I'm actually getting 1. Let's consider that I'm denoting this 1 by a random variable x, because here is a process which can generate, just by rolling a dice, you can generate the 6 numbers. So what is the probability of getting x is equal to 1? Then now you should understand that what are the total number of outcomes that you can actually get. Obviously it is 6. And what is the outcome that you're looking at? 1. In a single toss of a dice or roll of a dice, you may either get 1 time 1 by 6, so this will definitely become 1 by 6. Similarly, you can actually find out the probability of x is equal to 2, then also it will be 1 by 6. So if I'm considering this is how you can basically calculate probability, right? Very simple definition. But just understand that this is the basic part of probability. But the most important thing is based on this additional rule. First of all, let's define or let's understand what is mutual exclusive event. So here I'm just going to write a topic which is called as mutual exclusive event. Mutual exclusive event. Now, what exactly is mutual exclusive event? Let me just define it. So I may say that two events are mutual exclusive if they cannot occur at the same time. Okay, if they cannot occur at the same time, right? This is a very simple definition. If I talk about non-mutual exclusive event, that basically means they can occur at the same time. Let me take an example. If I'm tossing a coin, right? If I'm tossing a coin, if I toss a coin, I may not get heads and tail at the same time, right? So the outcomes that we are getting out of tossing a coin is mutual exclusive because we cannot get head and tail at the same time. This is a perfect example of mutual exclusive event. Similarly, if I roll a dice, at a time I will not be able to get 1 and 5 or 1 or 6 at the same time. So that is actually mutual exclusive event. If I try to draw a Venn diagram, the Venn diagram will look something like this. Suppose I'm tossing a coin, I may either get head or tail. There will be no overlapping, right? So in this particular case, suppose if I have given a problem statement, suppose I'm tossing a coin, suppose I say what is the probability of x? What is the probability of x? Or let me just write it in a much more better way. What is the probability from this specific event of getting a head or a tail? Then how do we define this entire formula? You know that this is entirely a mutual exclusive event. So you don't see any kind of intersection. So in order to get this, you can just write probability of head plus probability of tail. This process is basically called as additive rule. Additive rule for mutual exclusive event. So what this exactly is called is additive rule for mutual exclusive event. Now you go and calculate what is the probability of h. So probability of h is nothing but getting a head when you're tossing a coin is nothing but 1 by 2. Similarly, probability of tail is nothing but 1 by 2. So when you add this 1 by 2 plus 1 by 2, your answer will be 1. So what is the probability of getting a head or a tail in this kind of scenario? At that time, you'll be able to see that you will apply an additive rule. Suppose if I take another example, okay, where I'm rolling a dice. So in this particular case, the sample space, that the number of outcomes I may have is 6, right? So what is the probability of getting 1 or 5? Then obviously it will be probability of 1 plus probability of 5, because this is also a mutual exclusive event, and this is nothing but 1 by 6 plus 1 by 6, which is nothing but 2 by 6, which is nothing but 1 by 3. So this is basically the probability of getting 1 or 5, right? Now here we have pretty much focused in a mutual exclusive event. Now what about a non-mutual exclusive event? So let's take the next topic, non-mutual exclusive event. So this event basically says that two events can occur at the same time, right? Now let's consider some examples, right? Let's say that taking a card from a dice, from a pack of cards, or from the deck, you can actually say like this. If I'm taking out a card from a deck, let's consider that I get a king's card. Suppose if I'm getting a king's card, I may also get a kings of heart card, right? So two possible events is possible. I may either get a king's card, I may also get kings which is of a heart of kind, right? So here you can see that this is completely non-mutual exclusive. Two events can occur at the same time, right? So if I say that, what is the probability? What is the probability when I pick up a card from the deck? What is the probability of K or heart? What is the probability? I'm just making some heart shape. What is the probability if I take out a card from the deck? That card will be K or heart. Okay, this is also kind of additive rule. But understand, over here, when I'm taking out the card, so initially my total number of cards will be 52. If I'm taking out of a card, this card can be K also, it can also be K and heart. It can be the combination of both, right? So how do we apply an additive rule for a non-mutual exclusive event? So for this, the formula will be probability of K plus probability of heart, right? Minus probability of K and heart. So what are the possibilities? If I go and consider a Venn diagram, I may get a card which will be specifically of k. I may get a card which will be specifically of heart, and I may get a card which will be of k of heart. Right? Suppose this is k, this is heart card. Right? I may also get a possibility that I'm getting k of heart. Right? So guys, let's go ahead and compute this. So what is the probability of, whenever I take out a card from a deck, what is the probability of getting k? It is nothing but how many number of k's will be there? There will obviously be 4 k's, right? So 4 divided by total number of cards, 52. Then what is the probability of getting a heart symbol heart symbol card, right? So there are around 13 possibilities divided by total number of cards, right? And then 1 minus, we have over here k and heart. The combination of k and heart, right? Since this is a non-mutual exclusive event, 2 events can occur at the same time. So how many cards will be available like this? It will be hardly 1, and from the total number of cards, it will be 52. Now, once I go and compute this will be 17 by 52 minus 1 by 52, which is nothing but 16 by 52. So this is basically the probability of getting k or heart, right? And remember, this is again the additive rule for non-mutual exclusive events. Again, I'm going to write it over here. This is a non-mutual exclusive event, right? So this is just the understanding. What all we discussed over here? We discussed 2 things. One is the introduction to probability, and then the addition rule for mutual exclusive event and for non-mutual exclusive event, right? So these 2 topics. What is non-mutual exclusive event? 2 events can occur at the same time. So I have actually taken this particular example where I am taking a card from the deck and I'm saying that it can be a k, it can be a heart. Okay. So what is the probability of getting k or a heart, right? So both this combination. Right? So, in order to take this, I'm just going to use a simple additive rule, that is probability of k plus probability of heart minus probability of k and heart. Obviously, I know how many number of k's are there. 4 by 52 plus 13 by 52 minus 1 by 52. Finally, I get 16 by 52. Very, very simple, very, very simple understanding. In the next part, I'm actually going to discuss about the multiplication rule. So thank you, and please make sure that you revise this if you're not able to understand. Thank you. So guys, we're going to continue our discussion with respect to statistics, and in our previous session we have already seen about the introduction to probability, and we had seen addition rule specifically for mutual exclusive event and non-mutual exclusive event. Now in this session we are going to discuss about multiplication rule, and this will be specifically for independent and dependent events. So let's first of all understand what are independent events. So if I talk about independent events, I can basically write 2 events are independent, right? If they do not affect one another. Okay. Now let's take one example. Okay. Suppose if I take an example of tossing a coin, and when I'm tossing a coin, suppose I get for the first time heads and then tails, right? Now during this particular scenario, what will be the probability of head during the first time? It will be almost same, right? 1 by 2. After that, even though after tossing the coin as head, and then if I toss tail also, it is not going to impact the probability of tails, right? That time also my probability of tail will be 1 by 2 only, right? So this specifically is like independent. These events are actually independent. Once, suppose in the first toss I get a head, and then if I try to get a tail, the probability is not going to change. Similarly, if I take another example, rolling a dice. Now in this particular case also, if I say that, what is the probability of getting 1 and then getting 2, right? At that point of time also, this will be considered as an independent event because probability of getting 1 will not affect probability of getting 2, right? All the time, probability of 1 or probability of 2, they will be having the same probability, that is 1 by 6, right? So this is one specific example. Now if I consider dependent events, suppose if I have a dependent events, and I'll give you a very good example with respect to this too. Now what is dependent events? 2 events are dependent, right? If and only if they affect each other. They affect each other, right? Now let's see. Suppose I give you a task. First of all, you draw you take out a king card from the deck, and then the queen card from the deck, and then the queen card from the deck. Now just think over it, guys. Will this become a dependent event or not? Obviously, this is going to become a dependent event because initially the total number of cards, right? How much it will be? 52. Now, suppose my task is that during the first take, I take out a card and probably I get king. And then after that, what is the probability of taking out the queen card? So initially, suppose if I take out the card as king, then what will be my probability? It will be 1 by 52. Sorry, not 1 by 52, 4 by 52, because there are 4 kings. Now suppose if I take out the king card and do not put back inside the deck, then what will be the probability of queen after taking out the king's card? After taking it out, I take out one card which is of king. Then what will be the probability of q? Then this will be 4 by 51 because one card has already been taken out. So this kind of event is called as a dependent event, right? So if I talk about the multiplication rule, so let me just write down the formula for multiplication rule, and let's take the same example. First one is for an independent event. Independent event. So suppose if I say what is the probability of taking out, let's take the same example, that is tossing a coin. Now suppose if my question is that what is the probability of getting a heads and then getting a tail? At that point of time, this multiplication rule for an independent event becomes something like this: probability of h multiplied by probability of tail. So what is probability of h? 1 by 2 multiplied by 1 by 2, which is nothing but 1 by 4. Now in this case, since the events are independent, right? Since the events are completely independent, it is not going to affect the probability. In the additive rule, we used to use OR, right? In multiplication rule, we use it as AND. Now what will happen in the case of dependent event? The formula will change a little bit more. Dependent event. Now suppose I am given a task that what is the probability when I take out a card from the deck? What is the probability of first of all getting K? And then if I take out one more card, what is the probability of taking out Q? That is queen's card. Let's consider this. In this particular case, my formula will become something like this: probability of K multiplied by, remember this is a dependent event. Once if I take out the K card, the remaining number of cards will be 51, right? So the probability will change somewhere here, right? So in this particular case, I will say probability of K or probability of Q given K, right? Because I'm trying to find out probability of Q and I've already removed the K card, right? So this particular formula This particular formula is also called as Bayes theorem. So this is like the idea towards Bayes theorem. There's a machine learning algorithm in naive Bayes, right? We will be using this kind of formula there also. So that is the reason why I'm actually teaching you about this dependent event. Later on, when you learn about the naive Bayes theorem in machine learning, you'll be seeing this. This is also called as conditional probability. Conditional probability. So if I go ahead and calculate this, what is the probability of k? Because the total number of cards in the deck is 52. So here you will be having 4 by 52 multiplied by 4 by 51 because I have not put the k card back. After I remove the k, then there is going to be some impact if I'm trying to take out q to find out that specific event. So this will be my total probability when I have this kind of dependent events. And this is what is called as conditional probability. A very, very important topic. Probably most of the interviews also they have basically asked. So this is nothing but it is a multiplication rule with respect to independent and dependent events. A very important thing in terms of probability to really understand. Right? So I hope you have understood this. These things we have learned in the school days, guys. You should definitely be able to recall it. In the case of independent event, this is how my formula will look like. In the case of dependent event, this is how my formula will look like. And this conditional probability will also be used in naive Bayes machine learning algorithm. So I hope you have understood this. If not, please do make sure that you revise the video. Overall, in this particular video, we have covered all the topics: introduction, additional rule for mutual exclusive event, non-mutual exclusive event, and similarly we have done it for multiplication rule in the case of independent and dependent events. Right? So yes, I'll continue the session, and in the upcoming videos, we are going to discuss about permutation and combination. Thank you. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we're going to cover a very important topic that is about probability distribution functions. Now this is a really important topic. With the base of this, we'll be able to understand different distributions of data that we specifically have, and through that we will definitely be able to solve a lot of problems when you understand about that particular data. So first of all, we'll try to understand the definition. What exactly is probability distribution function? So here probability distribution function describes how the probabilities are distributed over the values of a random variable. Let's consider we have a random variable called as ages, okay, and it has some data. Now, initially, if we really want to create a PDF, that is probability distribution function, considering, let's say that this is a continuous random variable, okay? It is a continuous random variable, okay? So what we basically do is that with respect to this particular variable, we go ahead and construct our histograms, right? And I hope everybody knows how do we construct a histogram. Let's say if our histogram looks something like this, okay? And on the y-axis, you will specifically be having frequency, in the x-axis, you will be having ages, right? Now, in order to, if I say that, okay, I have this particular histogram, I've already explained that. If I smoothen this histogram, then I will get some kind of distribution which looks like this. That basically means this entire random variable can be represented in the terms of probabilities in this distribution way, right? And once we probably convert this, or once we smoothen this histogram, the y-axis then becomes something called as probability density. We'll discuss more about it, what exactly is probability density and how these values are actually calculated. So in this probability density, you'll be having some values like 0.01, you may have 0.02, then you may have 0.03, then you may have 0.04, right? And let's say this tip value, right, with respect to this particular mean, let's say this is my mean or median, right? If I really want to take ages, let's say over here the median is somewhere around 55, okay? And if I just plot 55 over here, you'll be able to see that I'm getting the probability density equal to 0.04. What does this basically mean? We'll discuss about this, how these values are actually derived. We'll discuss each and everything as we go ahead, right? But understand, once we get this kind of distribution, right? Once we get this kind of PDF function, we'll be able to understand about this data a lot, because based on different data sets, we usually get different kind of distribution. We may have one kind of distribution like this. It may be right skewed. We may have another distribution which may be left skewed, right? And each and every distribution of the data is really important for us, because as a data analyst or as a data scientist, this kind of distribution says some basic information about this particular data, and you can assume some of the conclusions out of it, okay? What are the different kind of distribution we'll discuss as we go ahead, right? But this probability distribution function helps us to understand how the probabilities are distributed over the value of a random variable, okay? Now let's further go ahead and discuss. Probability distribution function are of two types, okay? So there are two main types of probability distribution function. Probability distribution functions. Now what are this type? Number one, it is basically called as probability mass functions. Okay, probability mass function. Now why this probability mass function is specifically used? This is also denoted as PMF. Okay, this kind of distribution or functions are basically created for, it is used for discrete random variable. Let's say if your random variable is discrete, a whole number, at that point of time we will be using, in order to represent the distribution, we will be using probability mass function. The second type that we specifically use is called as probability density function. Probability density function. And this is also represented as PDF. And this PDF is basically used for continuous random variable. So if you have a continuous random variable, in order to show the distribution, you will specifically be using probability density function. Now let's go ahead and discuss about probability density function separately and probability mass function separately. Okay, so let's go ahead and talk about probability density function. So first of all, I will take probability density, then we'll go with probability mass. Okay, or I can also go ahead with probability mass function. Let's go ahead with probability mass function. Okay, now as I've already told, probability mass function is a kind of distribution that we specifically use for discrete random variable. Okay, discrete random variable. Let's take a specific example, and based on this, we will try to construct the PMF. Okay, how does a probability mass function is basically created? Let's take a basic example: rolling a dice. See, when I try to roll a dice, how many different outcomes I have? 1, 2, 3, 4, 5, 6. And this is like a fair dice. Okay, fair dice. That basically means the probability of getting 1 is equal to probability of getting 2, is equal to probability of getting 3, is equal to probability of getting 4, is equal to probability of getting 5, is equal to probability of getting 6. Since I'm saying this as a fair dice, whenever I roll this dice, the probability of getting each and every number are same, and that value is nothing but 1 by 6. Right? If I want to probably get the probability of 1, so there are 6 outcomes, so it will be 1 divided by 6. I hope this is a simple probability rule. Okay. Now, based on this, probability, since this is a fair dice, how do we construct our PMF? Let's discuss about that. That is probability mass function. So in order to construct it, I will go ahead and construct something like this. This will be my x-axis. The x-axis is nothing but the outcomes with respect to my dice, right? And the outcomes are nothing but it is 1, 2, 3, 4, 5, and 6. Okay, 1, 2, 3, 4, 5, 6. In the y-axis, you specifically have probabilities value. Okay, and as you all know, right, probability of getting 1 is nothing but 1 by 6. So I will just go ahead and write 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, and finally 1. Okay, so these are my various probabilities, let's say. But as we all know, the probability of getting each and every number, so the probability of getting 1 is nothing but 1 by 6, probability of getting 2 is nothing but 1 by 6, probability of getting 3 is nothing but 1 by 6. So like this, all the probabilities with respect to 6 is 1 by 6 itself. So based on this probability mass function, how do we construct this? The probability of getting 1 is nothing but 1 by 6, so we'll go ahead and construct the building like this. Probability of getting 2 is nothing but 1 by 6, 3 is nothing but like this, 4 is nothing but like this, 5 is nothing but like this, 6 is nothing but like this. And here you can see probability of getting this for all the numbers is nothing but 1 by 6, right? This is a basic example. And I'll talk about what kind of distribution this is. Okay, we will discuss in depth about distribution as we go ahead. Okay, now this is the basic way of creating a probability mass function for a discrete random variable. Now let's talk about one more very important thing, which is called as cumulative density function. Cumulative density function, which is also called as CDF. The reason why I'm telling you about CDF, because through this we will be able to probably assume lot many things. Okay, we'll be able to do much more calculation. We'll be able to get more information. So what exactly is cumulative density function? So let's talk about it. So here I will just go ahead and write this is my 1, 2, 3, 4, 5, 6. So these are all my outcomes of my random variable. On the y-axis, you will be having, in the case of probability density function, is nothing but cumulative probability. Okay, and here you specifically have, let's say, I will also go ahead and write 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, and this is 1. Okay, now let's understand what exactly CDF is, or cumulative density function is. Cumulative density function basically means we need to combine all the probabilities as we go from 1 to 6. Okay, so what is the probability of getting 1 in this case? It is nothing but 1 by 6. So I'll go ahead and draw this particular building. Then what is the probability of getting 1 and 2? 1 and 2, right? So if I'm trying to calculate the probability of 1 and 2, it is basically nothing but I'll add up 1 by 6. Then for probability of 2 also I'm getting 1 by 6. So this 2 will get added and I'll be getting 2 by 6. So this basically shows the cumulative probability of 1 and 2, right? Similarly, what is the probability of 1, 2, and 3? So it is nothing but we'll go ahead and add up these three probabilities, 1 by 6, 1 by 6, 1 by 6. So it is nothing but 3 by 6. Similarly for 4, it will become 4 by 6. Similarly for 5, it will become 5 by 6. And finally, this value will be 6 by 6. So overall, if I probably consider this cumulative density function, the value will be between 0 to 1, right? It cannot go above than 1, right? And this is what is the differences between the PMF, and similarly, I've constructed the cumulative density function of this particular experiment of rolling a dice. Okay. Now the question rises, Krish, what kind of problem statement will be able to solve over here? Let's say that I'll go ahead and ask one question. What is the probability of this random variable to get less than or equal to 2? If I'm rolling a dice, what is the probability of this experiment to come with the value less than or equal to 2? It is very much simple to calculate it. What we'll do, we'll just go ahead and write probability of x is equal to 1 plus probability of x is equal to 2. X is equal to 1 and x is equal to 2. This means rolling a dice with 1, rolling a dice with 2. What is the probability? So once I do this, I will just get 1 by 6 plus 1 by 6, which is nothing but 2 by 6, which is nothing but 1 by 3. So this is how I'm able to get the answer. And what does this basically indicate? This indicates that the probability of getting 1 and 2 is nothing but 2 by 6, which is nothing but 1 by 3. Right? Similarly, I can go ahead and ask what is the probability of rolling a dice and probably I get the value less than or equal to 6. Okay, so all the possible ways. So here what I will do, I'll write probability of x is equal to 1 plus probability of x is equal to 2, like this, up to probability of x is equal to 3, x is equal to 6. Once I do this, I'll be able to do the calculation. At the end of the day, the overall sum over here when I'm doing it will be 1. Right? This is the probability. So I hope you're able to understand whenever we have a discrete random variable, we can use probability mass function to showcase this entire distribution. Right? And as said, what exactly is probability distribution function? It describes how the probability are distributed over a random variable. And in this case, my random variable is nothing but discrete random variable. And since we're talking in terms of probability, the value, maximum value will be 1 if I cumulatively add it up. Right? Now let's talk about the next type, and very important type, because this specifically applies to a continuous random variable. It is nothing but something called as probability density function, which is nothing but PDF. Okay, PDF. Okay. Now first thing first, this is basically used for the distribution, to showcase the distribution of a continuous random variable. Continuous random variable. Let's say I have x. This is my random variable of ages. Okay, it has some values over here. Okay. Now let's usually draw this distribution, and now this is really important because I'll make you understand. On the x-axis, you basically have your x, that is random variable. Let's say this is your mean 165. Okay, 165. Sorry, this is ages, right? So let's make it to somewhere around 40. 40 is my mean. Let's consider. Okay. Now what I'll do based on this particular mean, I will just draw this probability distribution. Okay. Let's talk about this. How do we draw this? It is very simple. We first of all create a histogram, then we smoothen it. Right? We smoothen this diagram. Okay. Let's draw it more properly. Yeah, perfect. Okay. Now this is my mean. Okay. Now on the y-axis, usually we have something called as probability density. Now we'll understand what exactly this probability density mean. Let's say this is my age 45. If I go one standard deviation to the left, let's say it is 35, then you have 30. Similarly, you have 45, you have 50. Okay, this is how my distribution is. And let's consider this is a symmetrical distribution. That basically means 50% of the distribution of this random variable are present over here, and 50% of the distribution of the random variable are present over here. Right? Now, on the probability density side, on this y-axis, you will be having some values. Let's say that you have some values like 0.01, you have some values like 0.02, then you have 0.03, then you have 0.04, and let's consider you have 0.05. Okay. Now, when I say a probability of random variable of x is equal to 40, here just by constructing this, if I just go ahead and populate this, I'm actually getting a value 0.05. Now what does this basically mean? Does this mean that the probability of a random variable equal to 40 is nothing but 5% probability? No, right? This does not mean that. Okay, and this is where you really need to understand how this probability density is basically derived. Okay, here with respect to this PDF, I will also talk about one very important concept which is called as area under the curve. So one, I will be talking about area under the curve. And the second thing that I will discuss about over here is that I will discuss about a very important topic with respect to this, like what exactly is this probability density and how this value is basically calculated. Okay, so these two things we'll discuss now. Okay, so these two topics. Now, in order to discuss this, right now we know this is my probability density function of a continuous random variable. We will try to convert this into cumulative density function. Now, let's first of all convert this into cumulative density function. Okay, so on the x-axis, you basically have a random variable x. On the y-axis, you specifically have a cumulative probability. Now, as the term says, cumulative. Okay, cumulative. That basically means you need to combine. Again, this cumulative probability. Remember, this ranges between 0 to 1. Okay, because it cannot be more than 1. Whenever we talk about probability, it is 0 to 1. And this cumulative probability usually takes a S shape. Okay, what it does, it basically takes a S shape. It takes a S shape. Now, what does this basically mean? Okay, see guys, if I probably consider what is the probability of x is less than or equal to 40. Okay, let's consider this. I'm just asking a question by seeing this graph. What is the probability of the ages to be less than or equal to 40? Okay, and here you know that less than or equal to 40 basically means this region. I'm talking about this particular region, right? And we really need to find out the probability, right? What is the probability of this random variable to be in this particular region? How do we specifically calculate it? Now see, over here, you know that your mean is nothing but it is 40, right? Now, if I go ahead and construct with this respect to 40 in this particular cumulative probability, let's say this is my 0.5. Why 0.5? Right? Because this is my median. You know that 50% of the distribution is present over here, 50% of the distribution is present over here. So if I go ahead and ask what is the probability of a random variable to be less than or equal to 40, specifically we are saying that whether this x will be available in this specific region. So we are just talking about this region, right? So if we just go ahead and calculate it, what is the probability of x to be less than or equal to 50? Just by seeing this cumulative probability, I can just say that hey, it is 50%. 0.5, which is nothing but 50%, right? Because we are talking about this specific region, right? And 40 is basically when you plot it, you'll be able to see it is coming over here, right? Now this is very much simple, right? Similarly, if I go ahead and say, hey, what is the probability of 35 of x to be less than or equal to 35? If I say x less than or equal to 35, I'm basically going to consider area under this curve, right? This particular part. So this area under the curve. And if I probably see 35 over here, if I plot it, so what is 35? It is nothing but it's coming over here. I'm talking about this area. When I talk about 40, I'm talking about this area. So this area, nothing but 50% of the distribution is present over here. Similarly, if I go ahead and say it for other numbers, let's say 45. If I go ahead and say with respect to 45, if I go ahead and plot it, so here I'm going to get some values. Let's say this particular value is nothing but 0.8, right? So I hope you're able to understand this, right? When I ask this specific question through cumulative probability, how I am able to understand where does a specific random variable fall, right? Which area under the curve we really need to focus. And this basically says, if I say, hey, what is the probability of x is less than or equal to 45? Now I have drawn this particular curve. This area under the curve is nothing but 80%. So it is 0.8, which is nothing but 80%, right? This basically says that this random variable has 80% probability to fall under this particular curve, right? So I hope you are able to understand. But still, there rises one specific question. Okay, how did we get this probability density? Let's consider for 40. How did we get this 0.05? Now for 40, what is the point? We are specifically considering this point. Let's consider this point. Okay, let's consider this particular point. In order to calculate the probability density, we need to find out the gradient, right? Gradient or slope of this point. Slope of this point. So the slope of this point in this particular scenario is highest, right? When I say slope, this line you can see it is very steep, right? This line is really, really steep, right? So if I probably go ahead and calculate the slope of this, it should be maximum. So that is the reason in the middle one that you see, like 40 number, which is my mean or median. If I try to go ahead and calculate the slope of this particular point, I should be getting the highest value since the steepness is very high. Let's say if I go ahead and calculate the slope for 50 points, so 50 point is somewhere over here, right? Here the steepness is very less, right? So obviously the slope will be less. So if you probably go ahead and see with respect to 50, I'm getting the slope somewhere over here, which is a small number. Let's say this is nothing but 0.15. Okay. So wherever the steepness will be high, that slope will be highest, and that is the reason the middle number is basically having the highest probability density. And this is how the probability density is basically captured. Okay. Now, in order to show you how this slope may get created, okay, let's consider over here. Let's say I want to go ahead and calculate the probability density for 40. So this point, we are just going to calculate the slope. In order to calculate, we'll take the previous point. Let's say this is my previous point. Okay, this is my previous point, and this is the above point near 40. We'll take the nearest point out of it. Okay, let's say this value is 166. Oh, sorry, this value is 44. This value may be 38. Okay. So how do we specifically calculate this? Okay, and with respect to this particular point, we also go ahead and calculate the slope. Now, in order to calculate the slope, it is very simple. Okay, we take the nearest point, that is nothing but 44 minus 44. Sorry. Okay. So let's see this. Okay. So first of all, what we'll do, we'll first of all go ahead and calculate what is the probability for this. What is the probability for this? Okay. For this 38 and 44. For 38, let's say I'm getting a probability of 0.45. Here I'm getting a probability of 0.65. Okay. So the slope will basically be calculated by 0.65 minus 0.45 divided by whatever numbers that I have over here. 44 minus 38. Right. This is the slope formula. Okay. So let's say that I got some number, whatever number that I'm able to derive it from here, I'll go ahead and write it over here. Or whatever calculation, I've just put some random values over here. But if I put the original value based on this particular diagram, here you'll be able to see that I'm getting 0.05. Okay. So whatever calculation you do, just do this particular division and you should be able to get your probability density. I'll just not write 0.05 over here. I know the calculation is not 0.05. So by this, you'll be able to get your probability density. Now you may be thinking, what did I do over here? Simply I calculated slope. Let's say if I have 2 points like this, in order to calculate the slope, this is mentioned by x1, y1. Let's say this is mentioned by x2, y2. So in order to calculate the slope, the formula is very simple. Right? x2 minus x1 divided by y2 minus y1. So this is the formula that we usually use to calculate a slope between 2 points. But we need to calculate the slope with respect to a single point. So we can take the 2 nearest point and we can calculate it. So this is the formula that we have specifically used to calculate the slope. We can also say the slope as gradient. Okay, this as gradient, and that is how we calculate this probability density. Probability density. So if in an interview they ask you, hey, what exactly is probability density? Okay, what exactly is probability density? Then here you can basically go ahead and just define. It is nothing but it is a gradient. Gradient basically means derivative. Gradient of cumulative curve or cumulative density function. Right? And that is the reason this cumulative density function is really important. It is nothing but it is a gradient of cumulative density function. So I hope you're able to understand. You also understood about these two terms, area under the curve and how to calculate the probability density. Okay? And this is how you can probably represent any distribution with the help of probability density function. So yes, this was the video. 3 important topics we have discussed over here. I'll also go ahead and write the third topic, which is necessary to understand about probability mass and density function, which is nothing but cumulative, distribution function. Okay, cumulative basically means we're just combining. Okay, and this is nothing but this is represented by CDF. So I hope you like this particular video. This was it from my side, a very important video. And in the next video we are going to see the different types of distribution. Before closing up, I also want to represent some mathematical representation for probability density function. Okay, so probability density function. So let's talk about some of the properties over here. Okay, some of the properties. Okay, I'll write like this. I'll write PDF properties. PDF properties. Okay, so the first property is nothing but it is always non-negative. What is non-negative? Non-negativity. Okay, so here the function that will be used to create this entire probability density function. See, there should be one function which will take this number and should be able to create your probability density. I know this is how gradient is basically calculated and we get the probability density, but mathematically we use a specific function. So here I'm going to denote it by f of x of 0. So for all x values. Okay. Second thing, the total area under the PDF curve, I'll explain the first point in much more detail right now, is equal to 1. Okay. And what does this basically indicate? See, this is how we basically denote it. Okay. So an integration value from infinity to minus infinity to infinity. This is the limit. Okay. We use a function f of x, d of x is equal to 1. That basically means this notation represents area under the PDF curve. This entire area under the PDF curve. This entire area. It is nothing but this area. So this distribution is basically created by this particular function f of x. Okay. This can be different things. See, I may have a distribution which may look like this. I may have a distribution which may look like this. Right. I may also have a distribution which may look like this. Right. So this distribution is basically created by this function f of x. And as we know, when we do this, when we use this notation from a specific limits, right, the total area is just going to be 1. The total area of this, the total area of this, the total area of this is just going to be 1. Okay. So with respect to different distribution, so here I'll go ahead and write with respect to different distribution, your f of x function will change. The f of x function is going to change. Okay. And that is what we'll be discussing when we discuss about different distributions, different distribution types. There are around 8 to 10 distribution types, like normal Gaussian distribution, you have normal distribution, normal Gaussian distribution, you have log normal distribution, you have binomial distribution, you have Bernoulli distribution. And all this kind of distribution is basically used to represent your random variable in the form of probabilities. And there, in order to calculate the probability density or probability mass function, we specifically use a function. And this function f of x will be different for different types of distribution, right? Let's say if I have this kind of distribution, right? So there will be a different f of x function which will be creating this. Based on this, I will be getting a probability density over here. If I have this kind of distribution, this is also called as a log normal distribution. Okay, in this log normal distribution, the f of x function will be different to calculate the probability density. And that is what we are going to discuss in the upcoming video. Okay, so but remember this particular notation: f of x dx is equal to 1. Okay. So I hope you like this particular video. This was it from my side. I will see you all in the next video. We'll discuss more about the further topics. Thank you. Hello guys, so we are going to continue the discussion with respect to statistics. In this video, we are going to discuss about types of probability distribution. Already in our previous video, we have already seen about PDF, we have seen about PMF, we have seen about CDF, right? We saw with multiple examples, we saw what is the relationship between PDF and CDF, what is the relationship between PMF and CDF. Now, whenever we work with a data set, guys, we may have many features. It may be like we may have a random variable like ages, we may have like weight, we may have, let's say, like salary. So these all are some random variables, right? Let's say ages may follow some kind of distribution. So this is the distribution that ages may follow, right? If I probably consider about salary, salary may follow this kind of distribution, right? There may be weights may follow this distribution again, right? If you probably work as a data scientist or data analyst, there are real number of chances that whenever you get a data set, this data set usually follows different, they usually follow a different distribution, right? And there are some set of distribution that everybody should know. Set of distributions that everybody should know, right? And that is what we are going to see in the upcoming series of video. What are the different kind of distributions specifically with respect to our data, right? So let's consider, right? And the types of probability distribution of data that we are going to see is number 1, right? We'll be talking about something called as Bernoulli distribution. So Bernoulli distribution over here, here the outcomes, if I probably talk about the Bernoulli distribution, here we'll be working with data where the outcomes are completely binary. They're only binary. That basically means your value can be 0s or 1. One example that I can probably say is tossing a coin. And to construct the distribution, we have to use a PMF function, because when I say outcomes are binary, this is nothing but it is a discrete random variable, right? Discrete random variable. And whenever we have a data set, let's say I have a data set with 10 features, one of the features can follow Bernoulli distribution. Second one that we are going to probably see something called as binomial distribution. So this is also a very important distribution that you'll be seeing. And binomial distribution is also it is for a discrete random variable. So here also we are going to specifically use PMF. Okay. Let's talk about another distribution, a very common distribution that most of the data set follows, which is called as normal or Gaussian distribution. And this distribution specifically is created with the help of PDF, that is probability density function. And just one example, if I probably consider your distribution which has this kind of bell curve, this is nothing but it is a normal or Gaussian distribution. Now, why this distribution is important? Because based on this distribution, there are some set of properties or assumptions that this distribution will follow. And because of this, we'll be able to assume that particular assumptions and we'll be able to train our model much more efficiently, right? Even with respect to data analysis, for a data analyst, this will be very helpful. Okay. Coming to the next distribution, right? Let's talk about this particular distribution. The fourth distribution that we may be discussing about is something called as Poisson distribution. Poisson, I'll not say Poisson, but Poisson distribution. So in this also we will be constructing PMF. With the help of PMF, we basically construct this entire distribution. One very common distribution that is available is called as normal distribution. Some of the data set also follows this kind of distribution. I'll be talking about some of the examples over here. And here we basically use PDF because it is for a continuous random variable. Wherever PDF is written, that is for continuous random variable. Wherever PMF is written, that is basically called as that is for discrete random variable. One more distribution that we will be probably discussing about is something called as uniform distribution, which is again a very amazing distribution. And here you'll be seeing multiple examples. That will be my target. See, my target will basically be to cover as many as distribution and also showcase multiple examples. But why this is really important? Let me just give you an example. Let's say as a data analyst or as a data scientist, you will be given a data set. Let's consider that I have a house price prediction data set, and I want to probably analyze this particular data. Okay. Let's say I have one of the feature like the size of the house. Okay. This is one of the feature. Let's say another feature is number of rooms. Let's say another one more feature is that location. Okay. One more feature is that floor, right? Floor number, like what floor you are in specifically. One more feature is that is this near C side or B side? Okay, this will be like a binomial feature, like the outcomes will be binary, zeros or ones. And finally, I have this price, right? Now here, you know that every feature, this feature can be a numerical feature. It will be a continuous random variable, right? Continuous random variable, right? Why? Because the values will be continuous. Here, it will be discrete, right? If I talk about location, we can convert this into discrete or fixed number of categories. Floor, it will be a discrete number again. I cannot say 4.5 floor or 5.5 floor, right? C side, yes or no. So this can be a Bernoulli distribution, right? It can be having values like zeros or ones, right? Then price will be a continuous random variable, right? So if I know, and these all features may follow some kind of distribution, right? Let's say this Bernoulli distribution, I may use a PMF. For this, I will be using a PDF. For discrete, I may go ahead and use my PMF, right? Continuous random variable, I may go ahead and use PDF. Then I will be able to understand the relation. I'll be able to understand the entire distribution. And based on different types of distribution of data, we can definitely make a lot of assumptions. And based on that particular assumptions, it will definitely help us in EDA and in feature engineering, which is the most important step, let's say, as a data analyst or a data scientist. Because at the end of the day, we are just analyzing data. We are able to understand about the data. We are able to create reports on the data, and we are able to send that reports to the stakeholder. This is really important. So in the upcoming series of video, one by one, we will be seeing this entire distribution. And remember, for all this distribution, this f of x function will be different, right? F of x function is basically used to create the probability density function or probability mass function, right? Probability density or probability mass, right? So for Bernoulli distribution, the f of x function will be different, right? Then again, if we just go ahead and take the gradient of the cumulative density function, we'll be able to get a probability density based on this particular function. For binomial, it will be different. For normal or Gaussian distribution, it will be different. For Poisson distribution, it will be different. So we will go ahead and discuss each and everything. So yes, this was about the type of probability distribution. I hope you're able to understand this particular video. I'll see you in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to talk about Bernoulli distribution. Already in our previous video we have seen all the types of distribution. Now one by one we will try to understand about this kind of distributions. And the major thing about this distribution is that in this distribution you'll be able to see that each and every distributions are different, and over here you'll be having a lot of parameters. The most important thing about the distribution is that how is the distribution basically getting created. We'll try to understand how to probably calculate the mean for this distribution, how to calculate the standard deviation of this distribution, how to calculate the variance of this distribution, and what are the examples that probably leads to this kind of distribution. Everything will be specifically getting covered. Now in the upcoming series of video you'll also be seeing different kind of distribution, and I will try to make sure that I'll try to provide you real world examples so that you'll be able to understand. Okay. So first of all, we are just going to go ahead and discuss about Bernoulli distribution. Now let's go ahead and just understand the definition of Bernoulli distribution. So Bernoulli distribution is the simplest discrete probability distribution. Now since this is having a discrete random variable, in order to create this distribution, we will be using probability mass function. Okay, it represents the probability distribution of a random variable that has exactly two possible outcomes: success with probability P and failure with probability 1 minus P. It is also used to model binary outcomes such as coin flip or yes or no question. Okay, so if I probably go ahead and just see the definition, first of all, this entire distribution is for a discrete random variable. This is the first and the foremost important property. Since this is a discrete random variable, the kind of distribution we will be creating will be using probability mass function. Coming to the second point. Here, with respect to this, you perform any trial or experiments. The outcomes are binary. The outcomes are binary. That basically means the values can be either zeros or one. So let's see some of the examples over here. So first example is that, let's say that I'm tossing a coin. So in the case of tossing a coin, I will be getting heads or tail. So there are only two binary outcomes. So let's say if I go ahead and say what is the probability of a random variable x to come as head, I can mention it as 0.5. Why? Because I'm considering this as a fair coin. So what is the probability of getting head? It is nothing but 0.5. Similarly, what is the probability of getting tail, right, of this random variable x to get tail? It is very much simple. It is nothing but 1 minus 0.5. Let's consider that I'm going to mention this as p. Then this will be 1 minus p, right? So when I say 1 minus p, I'm actually going to get 0.5, which I can also denote it as q. Okay. So here you'll be able to see I'm having two important parameters. One is p and one is q. Here q is nothing but it is 1 minus p. Since the outcome is binary, if for one outcome the probability is this much, for the other outcome it will be just 1 minus for that particular outcome, right? So this is one kind of example. Second example, I can go ahead and say whether the person will pass or fail. What is the probability? So in this scenario, if I go ahead and write, hey, the probability of the person to pass is 0.4, then the probability of the person to fail will be nothing but 1 minus 0.4, which is nothing but 0.6, right? So I hope you are able to understand the specific examples. Here, the experiments or the trials that we are going to perform, the outcomes are going to be binary, and there are two important parameters. So let me just talk about the parameters that are used over here. Parameters that are used over here. Okay. So one is nothing but 0. So first of all, we will be using these two parameters, that is p, comma q, right? Always remember your p value will always be ranging between 0 to 1. Right? Since we're talking about probability and it is a binary outcome, it will always be ranging between 0 to 1. And if I probably consider about q, it is nothing but 1 minus p. Now let me go ahead and take one important parameter which is called as k, and this value will be 0, 1. And why I'm actually writing k? This indicates my two outcomes. Two outcomes. Okay? That is 0 and 1. I will consider 0 as success, or 1 as success, or 0 as failure. Right? So I can also go ahead and just write probability of success and probability of fail. When I say probability of success, I'm basically talking about k is equal to 1. Let's consider this. If I'm talking about probability of fail, I'm just going to talk about k is equal to 0. Okay? So these are the basic things. Now let's go ahead and see this diagram. Okay? Now here, let's consider this is one of the trial. So this is one of the trial. In this trial, which is denoted by this red line, probability of x is equal to 0, right? Of one of the event is 0.2. So for the other event, that is x is equal to 1, it will become 0.8. So this is one of the red line and this is the other red line, right? And we are going to use probability mass function to construct this. Similarly, when probability of x is equal to 0 is 0.8, then probability of x is equal to 1 will be 0.2, because 1 minus 0.8 is 0.2. Similarly, the third trial, you'll be able to see probability of x is equal to 0 is 0.5. So if this is 0.5, this will also be 0.5. Okay? But still, we really need to understand how with the help of probability mass function, we can create this particular plot. Okay? So let's go ahead and let's understand this. Okay? So here now, we're just going to go ahead and understand about probability mass function. Now let's consider an example. Okay? A company has launched a phone. Okay? Launched a new smartphone. Okay? Let's consider the smartphone name is A. Okay? A. Now, what we have actually done is that, let's consider that I'm probably providing a review for this phone A. Okay? And let's say that I will just go ahead and probably mention that I am satisfied, or I'll just use two terms. Good product, I'll say, hey, this is 60% good, let's say according to my rating, okay? And I'll say bad, or instead of writing good or bad, I'll say I will use, okay? So I will say use, I may say that, hey, 60% I may use it, okay? Not use, then what will happen with respect to not use? It will be nothing but 100 minus 60, which will be my 40%. So these are my two scenarios, right? These are my two values. This can be P, this can be Q. Q is nothing but 1 minus P, right? Now with respect to this, see, if we go ahead and construct a probability mass function, why we are doing probability mass function? Because this is a discrete value, right? So here I have two 1. One is zeros and one is 1. Let's consider not use is basically the 0 value, and this is 1 value based on K, because K, two outcomes we have for every try. So over here you'll be able to see for 0, I may go ahead and construct a building. This will probably give the value as 0.4. Let's say I'm just going to construct it over here. In my y-axis, let's say this is 0.4 and this is 0.6, okay? Then for the one event, you'll be able to see that I will be getting this value, right? So that is what we have constructed like this, right, over here, right? This is basically saying 40% I may not use this phone, and this value is basically 60% I'm using this particular phone. This is the kind of probability that I'm actually mentioning, that I may like this phone, I may not like this phone, okay? And company has launched this smartphone, and it is we're just trying to show you an example with respect to Bernoulli distribution, okay? Now, in order to construct this graph, we basically use PMF. So let's go ahead and talk about this PMF. Now the PMF notation, mathematical notation that is specifically given over here, we'll go ahead and write down this notation, and then I will try to simplify this notation over here, okay? So for this notation, it is basically given as probability of K multiplied by 1 minus probability 1 minus K, okay? So this is the formula to probably create this PMF, that is probability mass function, and with respect to this, we will be getting this distribution, okay? Now let's talk about this, what exactly this is. Let's say if my K value is equal to 1, if my K value is equal to 1, then you know what is my P value? My P value is nothing but 0.6, right? So let's consider over here. So here I will go ahead and write what is the probability for K is equal to 1. It is nothing but P to the power of 1. Then I will go ahead and write 1 minus 1 minus 1. So this entire thing will become 0. So this answer that I'm actually going to get is P. So here you can see when my K is equal to 1, I'm actually getting the P value, right? P value. That basically means when my probability of K's success, I'm actually going to get the P value, okay? Similarly, if I go ahead and calculate the probability with K is equal to 0, which is my other outcome. Now if I go ahead and apply this formula, then I'll get P to the power of 0 multiplied by 1 minus P. Then it is 1 minus K, it is nothing but 1. And this I'm actually getting it as 1 minus P, which is nothing but Q. So this is what this diagram is all about, right? When my probability of K is equal to 1, which is my success, I'm going to get the probability of P value, right? But when my probability of K is equal to 0, I'm just getting 1 minus P, right? So if I say, hey, my probability of, instead of X, I've told as K, okay, I've given the notation as K. If the probability of K is equal to 0 is 0.2, then the probability of K is equal to 1 will be 0.8. That is nothing but 1 minus P, right? So this is what I have probably proven from this particular formula, right? And this formula actually helps you to construct this entire distribution that we have seen, right? So let's say for this, in this scenario, I'll say, when the probability of success is 0.2. So here, if this is my P value, this will basically be my 1 minus P value, which is nothing but 0.8, right? I hope you're able to understand. And that is what we have proved it over here. So please make sure that you remember this formula, okay? P to the power of K multiplied by 1 minus P to the power of 1 minus K. For both the outcomes, if K is equal to 1, I'll be able to get P. If K is equal to 0, which is for the fail rate, I'll be able to get Q, okay? Now I can also go ahead and write a simplified format to construct this PMF. The simplified format will be that this will basically be my PMF, and this is denoted by Q is equal to 1 minus P if K is equal to 0, and P if K is equal to 1. This is the same thing, right? From the same formula, we are able to get the same thing. If the K is equal to 0, then I'm just going to get the Q value. If K is equal to 1, I'm going to get the P value, right? So this is how you specifically go ahead and determine your entire PMF function, and through this how you construct this entire distribution, okay? Now let's go ahead and talk about the next one. As you all know, for every distribution, we need to know about the parameters that are basically going to be used, what are the outcomes, whether PDF or PMF function is basically used. But since this is a discrete random variable, here we are just going to use the PMF, that is probability mass function. Then how do you construct this probability mass function? For that, there will be a separate formula, okay? We'll not go in proving this, okay? Proving will probably take additional 10 to 20 steps. I feel proving is not that important based on the syllabus, but we really need to know about the data, how the data looks like, how the data distribution is basically created, what formula is basically applied. Now since we already calculated the PMF, now let's go ahead and calculate let's find out how to calculate the mean of this Bernoulli distribution. Now this is really important. How do we calculate the mean of Bernoulli distribution? For every distribution, you have some kind of mean, median, mode, right? Variance, standard deviation. So let's go ahead and talk about this. What is the mean of this Bernoulli distribution? Now understand one thing, guys. If I probably take this as an example, okay? Let's take this as an example based on my feedback, right? I'm saying, hey, 60% I'm liking this product, 40% I do not like this product, okay? Now in order to compute the mean, right? And understand, let's first of all go ahead and compute the mean. In order to construct the mean, we basically calculate the expected value of X, and the formula is very simple. It says that, hey, So here, what I will basically do is that I will just go ahead and write one formula. I'll say, hey, summation of I is equal to 0 to K. So K value is either 0 or 1. K multiplied by P of K. Okay. Now you know what are the K outcomes? The K outcomes are 0, 1, right? So the K outcomes are 0, 1. Okay. The P of K is nothing but what is the probability of, let's say, not liking the product? It is 40%. And what is the probability of liking the product? It is 60%. So when I say K is equal to 0, right? When I say K is equal to 0, or let's go with this way, okay? Since we need to do the summation, here my next step will be, right? I will just go ahead and write for K is equal to 0, right? For this K value equal to 0 to K, okay? K basically means 0 to 1 also I can write because this is the binary outcome. So let me just go ahead and write 0 to 1, okay? When the value of K is equal to 0, so I will take K is equal to 0. What is the probability of 0? Probability of 0 is nothing but 40%. So here I will just go ahead and multiply 0.4, right? So this is nothing but 0 multiplied by 0.4 plus, when I say K is equal to 1, this is 1 multiplied by probability of 1. What is probability of 1? It is nothing but 0.60. Now here, you'll know that this value will be 0 and this will be 0.60. Now when I'm getting 0.60, what exactly this is? This is nothing but my P value itself, right? This is what is my probability of 1, right? Which is nothing but it is equal to P. What is P over here? P is nothing but 0.6 and Q is nothing but 0.4, right? That is what we are basically calculating. And this, when we say P is equal to 0.6, what does this basically mean? Probability of 1 is 0.6 and here probability of 0 is 0.4. So when we calculate the mean with respect to this distribution, you'll be able to see that the expected mean that I'm actually going to get is nothing but P value, right? So this is how we probably get the mean of the Bernoulli distribution, okay? So based on this distribution, guys, if I'm getting the mean of this Bernoulli distribution as 0.6, I can probably note it over here. So somewhere here, your 0.6 value will come, right? Now similarly, let's go ahead and compute the median, right? So now if I just go ahead and compute the median. Now for computing the median of Bernoulli distribution, let's go ahead and write it down, okay? Median basically means the central element, right? Here mean, what we have done with respect to the mean, we have taken the probability with respect to the outcome, and we are doing the summation with respect to the other probability with respect to the outcome. And finally, I'm able to see that here the mean of a Bernoulli distribution value is P. Okay. Now, when I talk about the median, see, median is basically mentioned by this notation. So here, if I really need to compute the median, I will be depending on the p value. If the p value is less than half, that basically means if the p value is less than 0.5, okay, then you will be seeing that since in the median I need to take the central element. Okay. Now, since my p value is already less than half, then my median will be exactly equal to 0. Okay. Then if I say, hey, if p is equal to half, then my median, if p, the exact p value is half in the center, then I can have the median value of 0, 1. That basically means the median can also have a value like 0, or it can have a value as 1. Okay. I will talk more about it, why I'm saying like this, right? And similarly, if I say if my p value is greater than half, then you'll be able to see that I will be getting the median value to 1. So in short, what we are doing is that if any of my p value is greater than 0.5, I'm moving towards this 1 probability. So I'm actually getting the output as 1. If it is less than this, I'm going to go towards 0. And if my probability value is exactly, if my p value is exactly 0.5, right, then I'm probably depending on both of them to probably show the output. Okay. Now you may be thinking, Krish, why you have specifically done in this way? Okay. What is the main aim over here? If I really want to simplify this entire thing, I can also go ahead and write something like this. The median will be equal to 0 if q is greater than p. The median, since we are dependent on the central element, median is equal to 0.5 if q is equal to p, and median is equal to 1 if q is less than p, right? So this and this are almost equivalent, right? Here, whatever q value is, like if the q value is greater than p, here you are going to get the median as 0. If the q value is equal to p, you're going to get the median as 0.5. If q value is less than p, you're going to get a value of 1. When I say, hey, it can be dependent on 0 and 1, in short, I'm just trying to pick up the middle element with respect to the probability, right? But usually in most of the scenarios with respect to probability, and even in some of the machine learning algorithms, if you see, like logistic and all, we keep a threshold value. If a value is greater than 0.5, we probably move towards 1. If the value is less than 0.5, we probably move towards 0. Okay, something like that. So I hope you are able to understand. Now, similarly with respect to the mode, so I will also go ahead and write for the mode, right? The mode for the Bernoulli distribution, and here also it will be very simple. If the p value is greater than q, then p will be the mode. Or else q will be the mode. Whatever will be the p value, that will be the mode. Because with respect to mode, we basically select the most frequent occurring element, right? But here, since it is more about a probability distribution, if the p value is greater than q, we will consider this as the mode, else q will be considered as the mode. Now let me do one more thing. Let me just showcase about variance. Now variance is also really important, and you need to understand this. How do we go ahead and calculate the variance and standard deviation? Now guys, variance over here, if we probably see at the formula, variance is nothing but how far we are away from the mean, right? For every k outcome, right? So here, if I go on to go ahead and compute the variance, you know the k value is 0 and 1, okay? And your p value is nothing but 0.4, sorry, not p. The probability of k is equal to 0. So what is the probability for k is equal to 0? It is nothing but 0.4. And what is the probability of k is equal to 1? It is nothing but 0.6. Now we know that this is p, this is q. Let's consider that. Okay. So in order to compute the variance, the formula will look something like this. We will take this probability for k is equal to 0. Let's go ahead and consider it. It is 0.40 multiplied by. We will take the outcome 0. And how much far it is away from the mean? The mean is 0.6, and we're just going to do the square. Okay. Similarly, we will take the next probability with respect to k is equal to 1, 0.6. Then we'll take this 1 value. Okay. Since the outcome is 1, k is equal to 1, and we'll see how much far it is away from the mean. And then we're going to do the squaring it up. Now here, if you go ahead and compute it, 0.40 multiplied by, if you see this value, right, 0.6 whole square, it is nothing but 0.36. Then you're going to get this 0.6 multiplied by 0.16, right? Because 1 minus 0.6 is 0.4. 0.4 whole square is 0.6. Now 1.6. Now if I go ahead and do the calculation, I'm going to get it as 0.4. Now 0.24. Don't you think this one 0.24 is nothing but it is the probability of k is equal to 0 multiplied by probability of k is equal to 1, right? You know that probability of k is equal to 1 is indicated by p, and this will also get multiplied by q. So in short, your variance is nothing but it is the multiplication of p and q. And similarly, if I need to go ahead and compute the standard deviation, it is nothing but square root of p and q. So these two formulas are specifically used to calculate the variance and standard deviation. Okay. Now, for this example, I have almost shown each and everything, right? How this distribution looks like, what is the mean properties of this distribution. You really need to have a discrete random variable. The outcomes are binary. Some of the examples that I've shown. And for every distribution, you'll be having some set of parameters. You'll be seeing that how this distribution is constructed. It can be either PMF or PDF. Then, with respect to this, if this is a PMF, what is the formula basically used to construct this entire distribution? Then, we have also seen how to calculate the mean of the Bernoulli distribution, how to calculate the median of the Bernoulli distribution, how to calculate the mode, variance, and standard deviation of the distribution. And obviously, you have also understood what is the examples of Bernoulli distribution. Any distribution that has an outcome that's binary. So I hope you're able to understand this video. This was it. Now, as we go ahead, we'll also be seeing about different distribution, which will be quite amazing, right? So yes, this was it from my side. I will see you all in the next video. Hello guys, so we're going to continue the discussion with respect to statistics, and in this video we're going to see about a new distribution which is called as binomial distribution. Already in our previous video we have also understood about Bernoulli distribution. Now let's go ahead and first of all see the definition of binomial distribution, and I've taken this definition from Wikipedia. The entire credit goes to Wikipedia along with the diagram, along with the definition. Okay, it is always a good practice you try to see Wikipedia because over there the content is quite precise and you'll be able to understand things. So over here in probability theory and statistics, the binomial distribution with parameter n and p. Okay, there are two important parameters n and p. Is the discrete probability distribution of the number of successes in a sequence of n independent experiments, each asking a yes or no question. Okay, so here you have a success of an independent experiment, each asking a yes or no question, and each with its own Boolean valued outcome, success with a probability p or a failure with a probability q, which is equal to 1 minus p. Okay, now here you are just seeing that just by the definition, right? You're saying, hey, it is a sequence of n independent experiments, and for every experiment the outcome is yes or no. The best example will be like tossing a coin 10 times, right? So in short, binomial distribution, if you probably read more about it, a single success or failure experiment is also called as Bernoulli trial or Bernoulli experiment, and a sequence of outcome is called as Bernoulli process for a single trial. that is n is equal to 1. The binomial distribution is a Bernoulli distribution if this n is equal to 1, right? So it's like binomial distribution is nothing but it is having multiple Bernoulli distribution, right? With respect to the outcome, zeros and ones. So in short, I can also define in a simple way binomial distribution is a group of, you can probably say that if I combine a group of Bernoulli distribution in sequence whose outcomes are either zeros or ones, then I can call that as a binomial distribution. Now, since we know that the outcome is like yes or no, it is again a binary outcome. So obviously we also need to use a probability mass function to construct this specific diagram. Okay. Now let's go ahead and discuss some of the important things. The reason, again, binomial distribution, as you know that for each and every experiment, the outcome is zeros and one. So specifically, we are also working on discrete random variable. So binomial distribution, specifically, we are working with discrete random variable, right? This next important point is that every outcome of the experiment is binary. Next important point. These experiments are performed for n tries. As I said, n tries. Here you can see that we basically work on sequence of n independent experiments. So here, that's the reason we are saying that these experiments are performed for n tries. Okay. One of the example can be tossing a coin for 10 times. Now, you know, tossing a coin, if I just consider this as a single experiment or single trial, here my output is heads or tail, right? So the outcome is binary, right? But when I'm tossing it for 10 times, so my n is equal to 10 value it becomes, right? That basically means I'm working it for n tries. Now, before I go ahead and probably show you multiple examples, let's first of all write some important notations that are used over here and what are the parameters that are specifically used, okay? And then we will talk about the formula how to construct this PMF, that is probability mass function and all, okay? So here you can see PMF. Here if I say my probability is 0.5 and n is equal to 20 tries, I will be getting this blue color something like this. With respect to p is equal to 0.7 and n is equal to 20, you'll be able to see over here. So and with p is equal to 0.5 and n is equal to 40, you'll be able to see some distribution that I'm actually getting over here, right? How this distribution is basically constructed, for this we use a PMF function, and for PMF function of a binomial distribution, the formula looks a little bit different. So first of all, we need to understand the notations. So the notation for binomial distribution is denoted by b, n, comma, p. Now first of all, we'll understand what is b, okay? So let me just go ahead and define the parameters. So first of all, n, I will go. It belongs to 0, 1, 2 to some value. This is nothing but this is my number of trials or experiment, right? Understand what exactly is binomial distribution. I am performing an experiment multiple times, and the outcome of every experiment is 0 or 1, right? The outcome is binary. Like I'm tossing a coin 10 times. So for every toss, I may get a head or a tail, right? And if I'm tossing it for 10 times, so that basically becomes my n value. Here, my p value, it belongs to 0, 1. Okay. This is nothing but this is my success probability for each trial. It's like when I'm tossing a coin every time, I may get heads or tail. I may denote it as zeros or ones. Okay. Then if you know p is this, then q will be what? 1 minus p. Now, additionally, there is one more support parameter that we specifically use. And this support parameter is nothing but k. And it belongs to nothing but 0, 1, 2, 3 up till n. And what does this basically mean? It shows number of successes. So number of successes. If I'm tossing every coin, let's say if I say tail is a success, right? How many number of times I may get tail? For n time, max to max, I can get n successes, right? So number of successes basically denoted by k. You know? So number of successes basically means when I'm tossing a coin, I'm probably getting tail or head, which may be a success for me, right? So for every trial, like how many number of successes I can achieve, right? For n tries, so I can basically achieve n successes, right? So considering all this parameter, we will go ahead and take the PMF and we'll see that how we can construct this PMF. So for this PMF, we will go ahead and write probability of k, and PMF is nothing but we are just trying to find out the probability for k, n, p. We'll define like this. It is nothing but n ck. This is nothing but combination p to the power of k 1 minus p n minus k. This formula I hope you know it, right? P to the power of k 1 minus p n minus k. If k is equal to 1, you know that if my trial is just 1, right? My number of trials is just 1 n, then I used to replace 1 over here, and this basically becomes a Bernoulli distribution. But since this we are doing it for n trials, so now my formula looks something like this: n ck, which is nothing but combination p to the power of k 1 minus p and to the power of n minus k. So here I will go ahead and write for k is equal to 0, 1, 2 up till n, right? K value goes from there to there, and here further if I take this n ck, I can go ahead and write n factorial divided by k factorial n minus k factorial. Okay, so this is how we specifically go ahead and compute the first component. Okay, so this is what all the things are there with respect to this PMF, right? And just by using this values of parameter of n, p, and k, I will be able to construct this. So I just require p is equal to 0.5, n is equal to 20, and k value will be almost same. Considering all the success over here, I'll be able to see this. Okay. Similarly, if I go ahead and compute the mean of the binomial distribution, the mean is specifically given by n multiplied by p, and variance is nothing but it is given by n multiplied by p multiplied by q. Okay. And if I probably consider standard deviation, it is nothing but square root of n p q. Now guys, I'm not going to derive this because I feel that this is not that important as a data scientist. You just need to know about the distribution and you need to know the assumptions. Okay. Now this was about all the formulas that we specifically discussed. Now let's go ahead and solve some problems. Then you'll be able to understand in a much more better way. Okay. And when I probably consider this is called as binomial coefficient. Okay. Let's go ahead and talk about this. Okay. So let's say I will just go ahead and take an example of coin flip, the basic example. So in coin flip, let's say the number of trials I'm performing this experiment for n is equal to 5. The probability of success, as you all know, what is the probability of success for a fair coin? That is my p. It is nothing but 50%, right? So 0.5, since the coin is fair. Okay. Now I'll go ahead and write number of successes. Now number of successes is nothing but it is denoted by k value. It can vary from 0 to 5. Okay. Now let me just go ahead and tell you what kind of question may come as a data analyst. What is the probability of getting exactly 3 heads in 5 flips? Now, please observe this. Now you'll be able to understand what exactly all this parameter meant. Okay. What is the probability of getting exactly 3 heads in 5 flips? So here, my n value is obviously 5. K is number of success, which is nothing but 3, right? 3 heads I need to get, right? So I'm just going to try to calculate what is the probability of x is equal to 3, right? And it's very simple. I will just go ahead and write phi c3, right? Because I have to use this formula. Phi c n ck phi c3. Okay. Then p to the power of k is nothing but probability is 0.5 to the power of 3. Then I have 1 minus 0.5. Then I have 5 minus 3. right? N minus 3. And if you go ahead and calculate this, you'll be getting 0.3125. This is the beautiful answer that you can actually get. And this is the kind of question that you may get as a data analyst or in any interviews. What is the probability of getting exactly 3 heads and 5 flips? So 5 flips is basically a continuous binomial distribution, right? And for every trial, I'm getting an outcome of 0 or 1. I need to probably find out how many heads we'll be able to get it. Okay. Let's take one more example. And this, I have solved this example, okay? And personally, in my experience, when I was working for one of the company, I visited the factory and it was something about quality control, okay? Quality control. So let's see this example. So let's say I have a scenario inspecting 10 items in a factory. So let's say you're inspecting 10 items in a factory where each item has a 10% chance of being defective. So what is the chance of being defective? It is 10%. Let me go ahead and write like this. Defective. Okay. Now in this scenario, what kind of questions may come? Okay. So let's say first of all, here I'm going to just put some information. Number of trials. First of all, these are the information that I have. My n value will be 10. Then probability of success, which is nothing but P. Let's say 10%. So 0.1% is my defective chances. So this is basically my defective item, right? Out of 10. Then probability of success. Probability of success basically means the item being defective. Okay. Then number of successes. Here my K value will be varying from 0 to 10, right? 0 to 10. Because out of that 10 item, all the 10 can be defective, right? And each item has a 10% chance of being defective. So the probability of success is 10%, but number of success, defective item may come from all items. Okay. Now my question will be, what is the probability? What is the probability of finding exactly 2 defective items in a sample of 10? Okay. So here my question is that what is the probability of finding exactly 2 defective items? I know my 10% is the defective chance. Each item has a 10% chance of being defective, but I really want to find out exactly 2 defective items in a sample of 10. So if I go ahead and calculate the probability, it's nothing but probability of x is equal to 2. Then I will say 10 C2, right? Then this will be 0.1 square because the probability of success is this. Then 1 minus 0.1 square to the power of 10 minus 2. Same formula. I've just applied this formula and I've replaced all the values over here. And if you further do the calculation, this will be approximately, I've done the calculation, so it will be nothing but 1.937, right? So this is what it looks like, and through this you'll be able to see that how you're able to calculate it. And this is an example of binomial distribution, right? 10 items. If I'm examining each and every item, it can have an outcome of 0 or 1, saying that whether it is defective or not. So I hope you like this particular video. This was about binomial distribution, and this is how the distribution looks like. If I keep on combining this, then I will be getting the cumulative distribution, but the value will be between 0 to 1, right? But I hope you have understood how did you get this probability mass over here on the y-axis. It's just by using this formula, right? So here I've already calculated it, right? 0.13. How am I able to get 0.31, right? So this is how we basically calculate the probability. So I hope you like this particular video. This was it from my side. I will see you all in the next video. Thank you. Hello guys, so we are going to continue the discussion with respect to statistics. In this video, we are going to discuss about a very important distribution that commonly occurs with respect to data. That is nothing but Poisson distribution. So first of all, we'll go ahead and see the definition of Poisson distribution, and then we will try to see whether it is getting applied to a continuous random variable or a discrete random variable. Then we'll try to see when do we use this kind of distribution. Along with that, we'll try to see that how this PMF, specifically over here PMF is created, that is nothing but probability mass function. How this entire graphs are basically created, how this entire distribution is basically created. We'll try to understand that also. And based on the PMF, what is the function that we specifically use in order to create this particular PMF? So to begin with, first of all, we'll go ahead with the definition. So let's go ahead and see this. In probability theory and statistics, the Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time. This is really important. It expresses the probability of a given number of events occurring in a fixed interval of time if these events occur within a known constant mean rate and independently of the time since the last event. So let me just make you understand this properly by writing some points. First of all, this is nothing but it is a discrete probability distribution. Whenever we say it is a discrete probability distribution, that basically means it gets applied to a discrete random variable. Now, since this is a discrete probability distribution, we specifically use something called as PMF, right? PMF to get this entire probabilities. Okay. The second important point over here is that it expresses the probability of a given number of events occurring in a fixed interval of time. Okay, so here I'm going to go ahead and write it describes the number of events occurring in a fixed interval time, fixed time intervals. Okay, fixed time intervals. Now let's take some example in order to understand it. Let's say I have an example: number of people visiting hospitals every hour. So if I have this kind of data, this will follow a Poisson distribution. Okay. Another example will be like number of people visiting banks every hour. So here also you'll be able to see that this will specifically follow a Poisson distribution. Why? Because here you can see it expresses the probability of a given number of events occurring in a fixed interval of time, right? So number of events will be occurring in a fixed interval of time. So if you take the specific two examples, number of people visiting hospital every hour, number of people visiting banks every hour. So there is a number of events that is occurring in a fixed interval of time. Okay. So to explain it more properly, I will give you multiple examples and we'll also try to solve some problems with respect to this. Okay. So let's consider that here I'm just going to take a specific data. Okay. Let's say I'll just go ahead and plot a kind of histogram over here. Let's say this is nothing but I'm just trying to show you number of people visiting the bank. Okay. Number of people visiting the bank, or instead of writing number of people over here, let's say I will just go ahead and write over here. This is at 12 p.m. This is at 1 p.m. This is at 2 p.m. This is at 3 p.m. This is at 4 p.m. Okay. And let's say there is also one more time we'll consider. That is nothing but 5 p.m. So 5 p.m. So these are my time intervals, the fixed time intervals of a bank. Okay. And here we will go ahead and probably write the frequency of people. See, over here we are just going to find out number of people visiting. So instead of frequency, I can also say, hey, how many number of people are visiting in this bank? Okay. At a specific time interval. So number of people visiting. Okay. So the value can be 1, 2, 3, 4. Let's consider this many number of values. 1, 2, 3, 4, 5. Okay. Now let's say that from during 12 p.m. There were there was a person that visited this bank. In 1 p.m., let's consider that there were 2 people who visited this bank. At 2 p.m., let's say there were 3 p.m., 3 people that visited this bank. Then let's go ahead and, at 2 p.m., 3 people visited. Let's say at 3 p.m. also, 3 people visited. Okay. Let's say 4 p.m., there was 4 people that visited the bank. And in 5 p.m., there was again 1 person who visited the bank. So whenever we have this kind of distribution during this particular, in this way, right, here you'll be able to see a number of events is occurring in a fixed interval of time. So if I'm just considering number of people visiting hospital every hour, over here 1 people is attending, 1 people is coming to this hospital or bank. Let's say 2 people are coming, 3 people are coming at 2 p.m. So we have some fixed interval every hour, right? And every hour we are seeing that some people are visiting in this specific bank. Okay. Now after this, you know that this is my histogram. But at the end of the day, you'll be able to see that we'll be able to create this like a PMF, right? Why PMF over here? Probability mass function, because it is following a discrete random variable. Here you can see the horizontal axis is the index k, the number of occurrences, right? So the horizontal axis over here is the index k, the number of occurrences. Lambda is the expected rate of occurrences. I'll talk about what exactly is this lambda, okay? But if I really want to convert this histogram into this kind of graph, then we need to use some probability mass function. Now before going ahead and understanding more about the probability mass function, in this there will also be a parameter that will be used, which is called as lambda. Now let's say that if I go ahead and write lambda is equal to 3. So here lambda is equal to 3 is nothing but it is the expected number of events occurring at a time occurring at a time at every time interval. Now what does this basically mean? If I say lambda is equal to 3, I'm just saying that with respect to this particular use case, at least at every time interval, right? 3 people should be visiting the bank. Okay. And that is actually defined by this lambda value. Okay. So lambda is nothing but expected number of events occurring at every time interval. Okay. So this is the minimum number of events that may be occurring. Okay. Now finally, we will try to take this entire thing and we'll try to see what is the PMF that is basically used over here, the probability mass function, in order to create this graph so that I get the probability on the left hand side. Because what kind of question that I may get? Okay. I will get a question. What is the probability of a person visiting at the 5th hour? Okay, 5 p.m. hour. Okay, so that is the kind of question that I can get, right? So let's say with respect to this, what is the probability of person visiting at 10th hour or 5th hour? 5th hour, you can see it is 0.15, right? For this particular graph. For this graph, you can see for 5, it is somewhere around 0.05. This is the probability, right? For 5, I'm just considering this as 5. But according to my data, I have 12 p.m., 1 p.m., 2 p.m. like that, right? So what is the probability of a person visiting the bank at 5 p.m.? So for this, we use a formula, and this formula, again, we will not go ahead and derive it because our main aim as a data analyst or a data scientist is to understand about the distribution, right? And how we can construct that particular distribution. So with respect to coding, this will hardly take 3 to 4 lines of code, right? But the main thing is to understand about the theoretical intuition. So the formula is e to the power of minus lambda, lambda to the power of x divided by x factorial. Now in this particular case, you know that. Let's consider my lambda is equal to 3. This is the minimum number of people coming to the bank at every time interval. That is what we are considering. Expected number of people arriving at every time interval. Lambda is equal to 3. And x is nothing but my value, that is 5. Okay. So if I go ahead and write over here, e to the power of minus 3, lambda is nothing but 3 to the power of 5. And here I will go ahead and divide by 5 factorial. So if I go ahead and do this calculation, I will be getting 0.101. So this is nothing but 10.1% probability, right? Again, your lambda value may change. Okay, it depends on the problem statement what you can specifically take different lambda value. Now, with respect to every value, we'll be able to calculate the probability by just using this formula. So here, if you see lambda is equal to 1, right? You can actually see that I'm getting one kind of distribution over here, right? With lambda is equal to 4, you can see another distribution over here. With lambda is equal to 10, you'll be able to see another distribution over here. Now compare with respect to lambda. As the lambda is increasing, do you see my distribution is moving towards this side, right? It is much more becoming a bell curve. Initially, it started from here. Then we are basically shifting it to here. And then finally, we are shifting it more towards it, right? So this is what is the impact of lambda value. And again, based on different problem statement, you'll be seeing different lambda values, okay? And again, lambda value is more of a experimentation purpose, okay? So for every point that you have with respect to the curve, right, you will be able to calculate it, right? So this is what is the question that we can basically derive, right? So I'm just trying to find out, hey, now what is the probability of a person visiting at this hour? Let's say I'll go ahead and write another question. What is the probability of a person visiting at 4 p.m. and 5 p.m.? So if I have this specific question, then what is the answer for this? It is very simple. I have to calculate the probability of x is equal to 4, right? Plus probability of x is equal to 5. This is what I really need to compute it. Then I can go ahead and just use this particular formula and calculate my final result. And this will basically give me the probability of a person visiting the bank at this hour or at this hour, right? So this kind of questions you can specifically ask. One more question you can say, hey, what is the probability of a person reaching in less than or equal to 3 p.m.? That basically means we are going to consider this, we are going to consider this, we are going to consider this, we are going to consider this. All is that we'll do the summation for this probability, this probability, this probability, and this probability. And that is how we are able to calculate our probability itself, right? So this was about the PMF. Now, let's go ahead and discuss 2 more important things. One is the mean of Poisson distribution. So the mean is basically computed by a simple formula. So mean over here is nothing but expected of value of x, which is nothing but mu lambda multiplied by t. Now you need to understand what exactly is lambda. Lambda I've already told you. Expected number of events occur at every time interval. And t is nothing but the time interval. So once we do the multiplication of this, we'll specifically get the mean. And variance is also given by this specific formula. Again, I do not want to derive this. We want to keep our knowledge limited in understanding about the distribution and how it is. Okay. So more, you can probably refer Wikipedia and get more information. It's always a good way that what you really need to do, open the Wikipedia page. You'll be able to see the distribution, be able to see cumulative distribution. So in Poisson, what all things you have this lambda value, the value can be between 0 to infinity. This is the PMF function, this is the CDF function. You can go ahead and explore some of the things, but most of the important things I'm actually telling you in this particular videos so that you can refer it later on, right? But our main aim is basically to understand about different distribution. So I hope you like this particular video. This was it from my side. I'll see you on the next video. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about a very important distribution that's called as normal or Gaussian distribution. Now there is so much amazing things to probably learn about this particular distribution because most of the common data that exists in this world follows normal or Gaussian distribution. So let's go ahead and understand about this. And first of all, we'll go ahead with the definition. So here you can see that in probability theory and statistics, a normal distribution or Gaussian distribution is a type of continuous probability distribution for a real value random variable. So this is the first time I think you're hearing about continuous probability distribution. Till now we saw about discrete probability distribution. So here the most important point is that this kind of distribution is basically created for a continuous random variable. One of the most amazing feature of this specific distribution is that you'll be seeing this distribution wherein you'll be getting your data in the form of bell curve. So this is the kind of bell curve we'll be getting. So all the Gaussian or normal distribution, if I consider x as a random variable, and let's say this x has some values of continuous random variable, this will follow a Gaussian or normal distribution. If this follows a Gaussian or normal distribution, then it usually follows a bell curve. Okay, and this is how your distribution will look like. Now there are a lot of assumptions we can probably consider from this particular distribution, which is normal or Gaussian distribution. So over here, first of all, in this center region, here we basically have our mean value. So the mean will be equal to median, which will be equal to mode. So usually in a normal or Gaussian distribution, this is one of the property that we'll be able to see. The mean of this particular distribution will be equal to the median, it will be equal to the mode. One more very important thing is that, let's say if x is a random variable which follows a normal or Gaussian distribution, this bell curve that we are specifically getting is a symmetric distribution. When we say symmetric distribution, that basically means 50% of the total values inside this random variable will be present in this side, and remaining 50% of the total distribution will be present in this side, right? Not only this, we'll still discuss many things about this normal or Gaussian distribution. So let's go ahead and let's talk about some of the notations that we are going to use. So one of the important notation that we use for a normal or Gaussian distribution, we say this is what we basically use for a normal or Gaussian distribution, n with some mean and variance value. Okay, so this is the notation that we specifically use. The next thing that you really need to understand are about the parameters. Now, what are the parameters that are used in normal or Gaussian distribution? One is mean. Mean belongs to a real value, which is nothing but mean over here. Then you have this variance. This variance also belongs to a real value, and it is greater than 0, so which we specifically say it as variance. And this x that we are probably considering with respect to our data set or random variable, whatever values we have, this will also belong to a real value, right? Now, here you can see one of the diagram that we are specifically using. Now, since we are using continuous random variable, we know that the distribution that we specifically create is for continuous random variable. So we are going to use something called as PDF, probability density function. Now, with respect to PDF, here you'll be able to see with respect to different mean and variance value. So here you can see variance as it is increasing. You can actually see, like let's say for the blue color, the variance is 0.2. The mean is 0, right? So 0 is the mean and variance is equal to 0.2. So here you are getting this kind of curve. When the variance increases to 1.0, you can see the spread of the data is also increasing. Similarly, when you see the variance is 5.0, still the variance is basically increasing, right? And in the case of variance of 0.5, you'll be able to see over here, this is my data, and here my mean is changing. Okay. So in short, this basically indicates as the variance increases, right, the spread of the data also increases. Right? One of the most common distribution of most of the data that you'll be able to see that it follows normal or Gaussian distribution. Some of the examples that I would like to consider, let's consider the ages of, or let's say instead of writing ages, I'll go ahead and write the weights of students in a class. Weights of students in a class. This may follow a normal or Gaussian distribution. The heights of students in a class. Right? This may follow a normal Gaussian distribution. One of the most common data set that you will be looking as in the form of, like if you're working as a data analyst or data scientist, one of the most common data set which is called as iris data set. So in this iris data set, you have 4 important features. So one is petal length, then you have sepal length, right? Then you have petal width and sepal width. Petal width and sepal width. And based on these 4 features, we need to predict what flower it is. Usually this petal length usually follows a normal distribution. If we take values of different sample of flowers, and if you try to construct this with the help of PDF, it will be creating this normal distribution. But still the question comes, right? With respect to your random variable x, for any values, how this entire probability density function is created. So for this, for Gaussian distribution or normal Gaussian distribution, we use a PDF function, and this PDF function formula is given by 1 by sigma multiplied by root of 2 pi e to the power of minus half multiplied by x of I minus mu divided by sigma whole square. Okay, so this is the formula that we specifically use to calculate the PDF. When I say x of I, this is with respect to different data points. Okay, this is how the PDF is basically calculated. The probability of a number with respect to the random variable x, I'll be able to calculate it. Okay, and this is the formula that is used with respect to PDF. Okay, again, I will not go ahead and derive it because it will not be that important for you all to probably since we really need to understand about the distribution, so it won't be that important. So please, and do not even by heart this formula, because with the help of coding, if you see, we'll be able to create this kind of distribution in a very easier way. Right, we'll be using histogram, we'll be using kernel density estimator and all. Okay, so this is one of the important thing. Okay, now similarly, if we go ahead and see the mean of this distribution, the mean of normal or Gaussian distribution. So in order to get this, the formula is very simple, and we have already discussed about this. Mean is equal to summation of I is equal to 1 to n, x of I divided by n, right? So this is the mean formula that we specifically use. Then let's go ahead and understand about the variance. Now in order to compute the variance, it is nothing but sigma square, and here again we'll go ahead and write I is equal to 1 to n, x of I minus mean whole square divided by n, right? So this is the formula for the variance. And finally for the standard deviation, it is nothing but square root of variance. So this is what we basically discussed in the initial time, right? So these are the important properties that we can actually see with respect to a normal Gaussian distribution. Okay, and here you can actually see that if you compare with respect to the probability density function, cumulative distribution function, for any probability density function, right, with respect to a continuous random variable, you'll be able to see that we'll be getting this kind of S curve. And I've already spoken about probability density function, talking about the area under the curve, right? So that entire information I've given it in the initial sessions. Okay. Now let's go ahead and talk about one very important thing. See, the reason we are understanding about all this distribution, because from this distribution we can make some basic and some meaningful assumptions. Now, one of the important assumptions about Gaussian or normal distribution, we basically say this as empirical rule. So let me just go ahead and talk about empirical rule of normal or Gaussian distribution. Okay. Empirical rule of normal or Gaussian distribution. Now, what is this specific empirical rule? And just by seeing this particular graph, you will definitely be able to understand. Okay, and this rule is basically called as 68, 95, and 99.7% rule. Okay, and here it basically says mu is over here, mu plus 1 standard deviation to the right, mu plus minus 1 standard deviation to the right left, mu plus 2 standard deviation to the right, mu with 2 standard deviation to the left, mu plus 3 standard deviation to the right, and mu minus 3 standard deviation to the left. Let's say I have a random variable, and in this particular random variable, I have around 50 data points. Let's consider, and we are considering, let's say that this follows a normal or Gaussian distribution. Let's say that when we say that this follows a normal Gaussian distribution, that basically means that And how do we say that this follows a normal Gaussian distribution? That will be seen in the upcoming video. We specifically use something called as QQ plot. And with the help of QQ plot, we'll be able to determine whether a random variable x will follow a normal Gaussian distribution. Okay, that we'll discuss about it. Don't worry. So if we consider a random variable and if we say that, hey, if it is following a normal Gaussian distribution, so there is some empirical rule that we can basically derive from it. And it is already derived, and these are the assumptions we can probably take. Okay, and these assumptions are related to probability. Okay, so these are something related to probability. So let's go ahead and discuss about this. So here, I will just go ahead and write probability of mu minus sigma. Okay, mu minus sigma basically means, let me just go ahead and write first of all, mu minus sigma less than or equal to, or random variable less than or equal to mu plus sigma. Okay, now what does this basically mean? This basically means a probability of a random variable, any random variable, to be between mu minus sigma to mu plus sigma, that is within the first standard deviation with respect to your mean, right? First standard deviation to the right, first standard deviation to the left. So within this first standard deviation, I'm just saying that, hey, what is the probability of a random variable to be between the first standard deviation? This is approximately equal to 68%. Okay, similarly, if I go ahead and write, this is what this rule specifies, 68, 95, 99.7. Similarly, if I go ahead and say the probability of a random variable to be present between two standard deviation, right, within this region, what is the probability? It is approximately equal to 95%. Similarly, the probability of a random variable to exist between three standard deviation, within the region of three standard deviation, this is approximately equal to 99.7%, right? So these are basically talking about the probability of a random variable to exist between first standard deviation, second standard deviation, and third standard deviation. I can also mention that, let's say if I have this random variable, let's say in this there are 50 numbers, and it follows a normal Gaussian distribution. Within the first standard deviation, 68% of the distribution will fall within the first standard deviation. Similarly, 95% of this distribution, 95% of this particular values or data points will fall within two standard deviation region. Similarly, 99.7% of this entire distribution will fall between this three standard deviation, right? Within the area between three standard deviation. And that is what is the empirical rule, right, of this normal or Gaussian distribution. Okay, so I've already spoken about all the examples, most of the data points. Probably if you will be seeing this kind of distribution follows a lot of data points, right? And I'm not saying this, okay? I'm not saying the weights of a student in a class will follow normal distribution. This is already proven. Proven by whom? By doctors. Okay, so doctors collected a lot of data for students with respect to weights, right? Similarly, this was basically done by doctors. I'm just taking an example. Similarly, in the case of IS data set, who collected this data? Researchers, when they were building the models, right? So most of the data points that exist in this entire universe, okay, actually follows a normal Gaussian distribution. Okay, not every, but yes, most of them. So this was mostly about the empirical rule. We also saw that this empirical rule is very important just to understand how much distribution is falling in which standard deviation and all, within the region of which standard deviation, right? So I hope you were able to understand about this normal Gaussian distribution. This was it from my side. I will see you all in the next video where we'll be discussing about more other types of distribution. So yes, this was it. I'll see you in the next video. Thank you. Hello guys, we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about standard normal distribution. Already in our previous video we have discussed about normal distribution or Gaussian distribution. In the standard normal distribution we are also going to discuss about a very important formula which is called as z-score. Now with the help of z-score, it will help us to identify that any value, like how much standard deviation it is away from the mean, right? I will just show you the entire formula, the working, everything as such. But first of all, let's understand what exactly is standard normal distribution. Now let's consider a random variable x, okay? It has some values, 1, 2, 3, 4, 5. And let's consider this is following a normal distribution, okay? And probably if you compute the mean will be 3, and the standard deviation will be somewhere around 1.414, okay? So if you go ahead and compute it, like 1 plus 2 plus 3 plus 4 plus 5 divided by 5 is nothing but 3, and the standard deviation is somewhere around 1.414 when you probably apply the variance and standard deviation formula. Now, one very important thing is that I will just, to make my calculation easier, let's consider this to be approximately equal to 1, okay? So I'm just saying that let's consider the standard deviation for this distribution is 1, okay? Something like this. Why I'm doing it? Just to make my calculation easier, okay? Now let's consider this is the entire Gaussian or normal distributed. So in short, if I probably draw my Gaussian or my bell curve, it looks something like this, okay? Now this is my bell curve. You know the mean element is 3, right? If you go one position to the right, since I've considered standard deviation as 1, so the next element will be 4, then this will be 5, then this will be 6. Similarly, here you have 2, 1, and 0, okay? So this is a normal distribution curve. Now let's say that this is my random variable, right? So over here, again, I'm going to write my random variable 1, 2, 3, 4, 5. Now whenever I have this kind of distribution, and let's say I want to convert this distribution in a way wherein my mean is equal to 0 and standard deviation equal to 1. Understanding Gaussian distribution, we can have any standard deviation, okay? We can have any mean. But if we take this distribution and try to apply a transformation technique wherein after we convert or after we change this random variable to something wherein I will be getting my mean is equal to 0 and standard deviation is equal to 1, then those kind of distribution we will specifically stay as standard normal distribution. Again, I'm going to repeat it for you guys. Let's say that I'm having a Gaussian distribution with some mean and standard deviation, and I want to convert this distribution into a different distribution wherein I get a mean is equal to 0 and standard deviation equal to 1, then we specifically say it as standard normal distribution. Now the question rises, how do we convert this? This, for converting it, right, we will specifically use a formula called as z-score. Now the z-score formula looks something like this: x of I minus mean divided by standard deviation. Okay, so by using this technique, we will be getting another random variable y, which will be how much? Let's see. Okay, so if I apply for every of this value, this particular formula, let's say for 1, I will go ahead and apply. So it will be 1 minus 2. Okay, 1 minus 3, because my mean is 3, right? So here you have 1 minus 3 divided by standard deviation is 1, so I'm going to get minus 2. So this 1 will get changed to minus 2. Okay, then coming to the second one, 2 minus 3 divided by 1, right? So it will be nothing but minus 1. So this 2 is getting converted to minus 1. Okay, and similarly for the third one, here you can basically see 3 minus 3 divided by 1, so this is getting converted to 0. So now see, initially the mean was 3, now this is getting converted to 0. Now are we getting the mean is equal to 0 by converting this entire distribution with this formula of z-score? Yes, obviously we are getting it, right? So it is minus 2 minus 1 minus 0, right? Then let's go to the next step over here in the fourth. What about the fourth element? 4 minus 3 by 1 is nothing but 1. So here I'm going to get 1, and if you do the same thing for 5, you're basically getting 2. So in short, for this distribution, when I applied the z-score, I got the outcome of another random variable where I have these values. Now this will be again this distribution will again be looking like this, but here your mean will be 0. Then one step to the standard deviation, you will be getting 1, then 2, then 3, then 4, like this. And similarly over here, you'll be having -1, -2, -3, -4. So what has exactly happened? We have converted one distribution, a normal distribution, to a standard normal distribution. Whenever we say a random variable belongs to a standard normal distribution, it basically says that its mean is 0 and standard deviation is 1. Okay. Now why it will be super important, I'll just let you know in some time. Okay. Just in this specific video itself. But again, let me write the notation over here. A random variable belongs to a standard normal distribution if its mean is equal to 0 and standard deviation equal to 1. Right. So any distribution, right? It basically belongs to a standard normal distribution that it basically says that its mean will obviously be 0 and standard deviation equal to obviously 1. Now, why will this z-score be super important? Okay, why this z-score will be super important? Let me give you a very good example with respect to z-score. Let's say that I have a specific question. Okay, I have a curve. Okay, over here. Let's say my mean is 4. Okay, and my standard deviation is 1. Okay, let's say that I have this. My mean is 4 and standard deviation is equal to 1. So initially, what I'll have 4 over here, then 5, then 6, then 7. Okay, then similarly, I'll have 3, 2, 1. Okay. Now, in this particular question, let's say this is my curve. Now, in this question, if I say how much is 4.25, okay, or I have a question over here. So my question is how many standard deviation 4.25 is away from the mean. So if this is a specific question that I get, so where does 4.25 fall? So if this is my mean and this is 5, so 4.25 will fall somewhere here, right? Somewhere here. So how do I find out like how many standard deviation away, like 4.25 is away from the mean? That is 4. Okay. Now in this case, here my x of I is nothing but 4.25. Okay, my x of I is 4.25. Now if I go ahead and apply my z-score formula, so what will happen? 4.25 minus whatever mean is there. What is the mean? 4 divided by the standard deviation, that is 1. So here I'm getting 0.25. Now this basically indicates that 4.25 is somewhere 0.25 away from the mean. Okay, something like this. So this is the area that you will probably be getting. In the future video, we'll also try to understand how to calculate this area. Okay, there's a generic table that is given for z table where you can also find the area under the curve, like how much area is probably present between 4 to 4.25. This kind of area also we can probably understand and we can find out. Okay, if many people are maybe thinking, what kind of practical application will come? Don't worry, I will explain that as we go ahead. When I give you those interview kind of questions and when I explain you like how this area will be coming, it will be super important for a data analyst, for doing exploratory data analyst, for understanding about that specific data. But one question that I specifically asked over here is that how many standard deviation is 4.25 away from the mean, right? So this is a very good question. Now similarly, if I say how much standard deviation 2.5 is away from the mean, then I will probably replace 4.25 by 2.5 minus 4 divided by 1. Then I'll probably get minus 1.5. That basically says minus 1.5 away from the mean, and since it is in a negative direction, I'll be getting over here, right? So let's say if I take my x of I variable as 2.5. Now what will be my z-score? My z-score will be nothing but 2.5 minus 4 divided by 1. So in this case, it will be minus 1.5, right? Now when I say 1.5 deviation, minus 1.5 deviation, it is somewhere here, right? And we can probably take that, we can probably conclude that this 2.5 is 1.5 standard deviation away from the mean on the left hand side. Okay. Now you may be thinking, why do we use this z-score and all? What for? Why we are specifically using standard normal distribution and all? Here also I'll give you an example. Let's consider a specific data set. Okay. Now in this data set, let's say that I have a variable which is called as age. I have a feature which is called as age. I have a feature which is called as weight. I have a feature which is called as height. I have a feature which is called as salary, right? Now, when I have all these features, let's say my age, I'm having some values like 24, 25, 26, 27, 30, 31, okay? Let's say weight, I have like 70, 60, 55, 40, 30, 25, right? And height, I have like 175, 160 centimeters, 150, 130, 175, 180, okay? And then salary, let's say I have 40K, 50K, 60K, 30K, 20K, and let's say 70K, okay? Now here, in all these features, understand one thing, units will definitely be different. Age is how do we compute? In the form of years. Weight, we compute in the form of kgs. Height, we compute in the form of centimeters. Salary, we can probably use a unit as INR or dollar. Now, whenever this kind of units are there, understand, whenever you solve a machine learning problem statement, whenever you create a machine learning models, the first rule is that we try to bring all these features in the same unit scale, okay? Now, in order to bring in the same unit scale, because see, if I probably take all these values and try to plot, right? Let's say if I'm plotting age and weight, right? If I plot age and weight with this big values, my data point will be scattered here and there, right? Like this, my data point will be scattered somewhere here and there, right? This kind of scenarios may happen, right? So what we do is that we really need to bring this in the same unit. Now, if we are able to bring in the same unit, there are many algorithms like clustering algorithms, linear regression, and all this kind of models, right? Require all the values to be in the same unit, so that the machine learning models will be able to optimize themselves in a better way to be able to give a better performance, right? Remember one of these things. So what we do is that we probably convert all these features by a technique which is called as standardization. Okay, standardization. Now, whenever we say standardization, it is basically applying a z-score formula on every feature. So for this particular feature, we specifically apply a z-score formula, right? We probably calculate the mean of the age. So here it will be x of I with mu of age, right? Divided by standard deviation. For this, when I'm computing, then it will be x of I minus mean of weight, right? Divided by standard deviation. Similarly, for the third, it will be mean of height, and for the fourth, it will be mean of salary, right? So what we do is that we apply z-score on this entire feature, and once we do this, we specifically get all the values based on the distribution, and we try to bring down this in the scale unit, right? So most of the values will be ranging between -3 to +3, right? All these values. See, once we convert this, right, all with respect to the standard normal distribution, you'll be able to see most of the values will be falling between -3 to +3. So all will get converted into the same unit, and we will get all these values between -3 to +3, right? It can be more than 3 if there is a specific outliers also, right? So by this, we are able to bring efficiency in the model. We are able to bring the performance of the model in a better way, right? So this is with respect to a specific data set, and this process is called as standardization. Later on, when we will be doing exploratory data analysis and feature engineering, creating ML models, we will be using standardization process. There's also a process which is called as normalization, which we'll probably discuss in the future lessons. But I hope you got an idea where specifically z-score is getting used. Like whenever we have any feature, some of the algorithms, like what are algorithms, they will be like, they are like clustering algorithms. Because in clustering algorithm, we try to find out the distance, right? And once we bring into the same unit, all the distance will be near. So the calculation will actually happen fast, right? The algorithms like linear regression, right? We specifically do standardization. The algorithms like logistic regression. So these all algorithms we'll learn in the future in depth, but there are definitely many algorithms where we specifically apply this kind of standardization. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to see about a new distribution which is called as uniform distribution. Now, in order to understand about this uniform distribution, there are two types of uniform distribution that you should really know. One is continuous uniform distribution, and as you see over here, it is written as continuous. So obviously, this distribution is created for a continuous random variable, and we specifically use a probability density function. Similarly, the second type is something called as discrete uniform distribution, and since the name is discrete, over here you have discrete random variable, so we specifically use a probability mass function. Now, in this video, we will go in depth. We will try to understand about continuous uniform distribution. We'll see multiple examples. We'll see about the notation and what all notations are specifically used. We'll understand about the specific diagram of this particular distribution. After that, we'll also go ahead and cover about discrete uniform distribution. We're also going to see multiple examples considering this kind of distribution. So first of all, let's go ahead and talk about continuous uniform distribution. And over here, first of all, we'll go ahead with the definition. As I have already told you, continuous uniform distribution basically means it is a distribution for a continuous random variable, right? So I'm just going to go ahead and write continuous random variable. Okay. So in probability theory and statistics, the continuous uniform distribution or rectangular distribution, it is also called as a rectangular distribution, or a family of symmetrical probability distribution. Such a distribution describes an experiment where there is an arbitrary outcome that lies between certain bounds. Okay, certain bounds. So here you'll be able to see two bounds, a comma b. So your entire distribution will be lying between these two. Okay, the bounds are defined by the parameters a and b, which are the minimum and the maximum value. Okay, so if I just talk about the notation over here, how do we denote this uniform distribution? It is basically denoted by a comma b. Here, what does a actually mean? It is the minimum and the maximum value. So I can consider this a and b as my parameters. Okay, so this a and b ranges between minus infinity to less than a to less than b to less than infinity, right? Always remember b will be greater than a, and this will be ranging between minus infinity to plus infinity. Now let's talk about the PDF function that is specifically used in order to create this particular distribution. Okay, so here there will be two scenarios. One scenario will be that if my x value, which is my random variable, it is either a comma b. Okay, if it is a comma b or between a comma b, then my PDF will specifically be used as 1 minus b minus a, 1 by b minus a. I will explain you about this by showing you example, but just right now, just consider that if my x value belongs to a comma b, then my PDF is basically created by 1 divided by b minus a. Okay, otherwise it will be 0. Okay, 0 otherwise. So here you can see if it is less than a, then it is 0. If it is greater than b, it is 0, right? And when it is between a and b, it is nothing but 1 divided by b minus a. Okay. Similarly, if I go ahead and construct the CDF, which is my below diagram. Now with respect to the specific CDF, here also you have three different scenarios. One is if the value of x is less than a. If the value of x is less than a, then here you'll be able to see that I'll be getting 0, right? And if the value is greater than b, you'll be seeing the value is greater than b, then again it will be, sorry, it will be 1, right? Over here it is 1. In short, cumulative basically means we need to sum up all the values with respect to the probability distribution, right? So these are my two scenarios for CDF. But what about in between, right? So if x belongs to a comma b, right? If x belongs to a comma b, then we specifically use something like x minus a divided by x minus a. See, x minus a, what does x minus basically a indicate, right? When you try to subtract x minus a, this is my entire x, right? Minus a. So you're basically talking about this region, right? So here x minus a divided by, if I do b minus a, b, this is my entire b, right? So what is b? And from this b, we are basically subtracting a, right? So we really want to get this specific region whenever x belongs to a comma b. So that is the reason we use this specific formula. X minus a divided by b minus a. X minus a will basically give me this region, and b minus a will be giving me this specific region over here, right? So with respect to this, I'm actually going to do the division, and I'm able to find out the CDF, right? And this is how my cumulative distribution function looks like. Along with this, you'll also be able to see the mean that is specifically used in order to calculate this distribution. It is nothing but 1 by 2 multiplied by a plus b. The median is also given by 1 by 2 multiplied by a plus b. And finally, the variance is given by 1 by 12 b minus a whole square. Now remember, I'm not deriving all these things, but it is good that we know these values. Again, derivation is not that important as suggested. We just need to understand about this specific distribution, and probably we'll get an idea like how this distribution looks like. But at the end of the day, I really want to specify multiple examples. So first of all, let's take an example and let's see what is a continuous uniform distribution. Let's say I have a problem statement. The number of candies sold daily at a shop is uniformly distributed with a maximum of 40 candies and a minimum of 10 candies. Okay, so my question will be that what kind of question as a data analyst you can basically ask is that what is the probability of daily sales to fall between 15 and 30? Okay, so this is my question, and this is how the entire question looks like. So what is the probability of daily sales to fall between 15 and 30? Let's understand the question. The number of candies sold daily at a shop is uniformly distributed with a maximum of 40 candies and a minimum of 10 candies. Okay, so what is the probability of daily sales to fall between 15 and 30? Let's take this as an example. So in order to solve this, first of all, we will go ahead and construct this particular graph, okay, the distribution by using PDF. So this will be my number of candies sold, right, which will be my x value, right? Here you know your minimum value is 10 and your maximum value is 40, right? So this is fine, right? And your number of candies is between this value to this value, okay? Now the reason why I'm drawing till here, because over here your probability distribution will be what? According to the PDF, right? According to the PDF, if my values range between 10, 40, then it should be 1 divided by b minus a. So 1 divided by b minus a is nothing but 1 divided by 40 minus 10 is nothing but 30, right? So here you are able to see this. Now my question is that what is the probability of daily sales to fall between 15 to 30? 15 to 30. Let's say this is 15, this is 30. I need to find out what is the probability of daily sales to fall between these values. Okay, so now I can go ahead and calculate it. I'll go ahead and write probability of 15 less than or equal to random variable x less than or equal to 30. This is what we really need to calculate, right? Now, in order to calculate this, it is very simple, and the kind of formulas that we will be specifically using if I want to probably calculate this probability, right? Now, in order to calculate this, first of all, we'll go ahead and define two variables. One is x1. X1 is nothing but 15. X2 is nothing but 30, right? Now, first of all, in order to do the calculation, we will do a difference of x2 minus x1. Then we will multiply by whatever probability that we specifically get over here, right? 1 divided by b minus a. So if we go ahead and just write it, so it is nothing but 30 minus 15 multiplied by 1 by 30. Okay, so here you'll be able to see it as 0.5. So the probability of sales, of daily sales between 15 to 30 is somewhere around 0.5. And this is how we specifically do the calculation over here. My another question may be, what is the probability of my daily sales to be greater than or equal to 20 candies? Now in this particular case, what we really need to do, if I'm considering this as my 20, okay, I need to find out this region, right? What is my probability of the daily sales greater than this, right? And less than 40. So in this particular scenario, what will be my x1, x2? My x2 will be 40 minus 20 multiplied by 1 by 30. So this will be nothing but 66%. Okay, which is nothing but 0.66. So I'm writing it as 66%. So here I'll be getting as 0.66, which is nothing but 66%. Okay. So I hope now you're able to understand with respect to any continuous uniform distribution how you will be able to calculate these things. Okay. Now let's go to the next distribution, which is called as discrete uniform distribution. Now whenever we talk about discrete uniform distribution, since we are talking about number one, that is discrete random variable. So here we are basically talking about discrete random variable. Okay. The second thing over here is that we basically use a PMF to showcase this entire distribution. So let's take an example for this. So example over here will be like rolling a dice. Now in the case of rolling a dice, the outcome is 1, 2, 3, 4, 5, 6. And you also know that probability of 1 will be 1 by 6. Probability of 2 will be 1 by 6. Probability of 3 will be 1 by 6. Like that. Probability of any number will be same. Why? Because we consider this as a fair dice. So just by seeing this probability mass function, you'll be able to see that my value will be ranging between a comma b, right? A comma b basically means 1 comma 6, right? So 1 comma 6. And in order to find out the probability, it is nothing but 1 by n. N is the number of outcomes, right? So if you probably go ahead and see how this n is getting calculated, right? We are basically using this 1 by n, right? That is the probability for every outcomes, right? So 1 by n, in this n will be calculated by using this formula, b minus a plus 1. What is b in this case? B is the number, like this can be b, this can be a, right? A, b, right? Because the outcomes is ranging between 1 to 6. So here I will go ahead and write 6 minus 1 plus 1, which is nothing but 6, right? And finally, you'll be able to see for every probability it will become 1 by 6, right? So what is the notation that is specifically used over here? So notation will be nothing but uniform a comma b. In this, you will be having the parameters. So parameters will be nothing but a comma b. Here, your b will be greater than or equal to a. Okay, that needs to be there because obviously the maximum outcome, the best outcome that you'll be seeing is with respect, not best outcome. Over here, you'll be able to see that this b is always greater than or equal to a. Okay, PMF is basically calculated by 1 by n. Okay, you really need to remember this. So if the x value is less than, it cannot be less than a, because at all the time for every outcomes, you'll be able to see that my probability will be almost same. And if I talk about mean and median, it is same like our uniform distribution or continuous distribution, that is nothing but a plus b by 2. Okay. So this is one example, and the reason we are basically getting the cumulative distribution is that we are adding up each and every probability. So when we keep on adding it, you'll be able to see that finally I'll be able to get 1. But always understand your so with respect to the definition, if I see in probability theory and statistics, the discrete uniform distribution is a symmetrical probability distribution wherein a finite number of values are equally likely to be observed. Every one of n values has an equal probability 1 by n. Another way of saying is that it would be known a finite number of outcomes equally likely to happen. Okay. So for every distribution, for every outcomes, you'll be having the same probability 1 by n. And this is how the entire diagram looks like. Okay. So in this example, I've shown you with respect to rolling a dice, or if we also want to probably consider Bernoulli distribution, like tossing a coin. I know the outcome is 2, right? But at all the time, you'll be getting 1 by 2 as a probability. Probability of head is 1 by 2, probability of tails is 1 by 2. Considering that it is a fair coin. So I hope you're able to understand about this 2 important distribution, which is called as uniform distribution. This was it from my side. I hope you like this particular video. I will see you in the next video. Thank you. Hello guys, so we are going to continue discussion with respect to statistics. In this video, we are going to discuss about log normal distribution. So this is specifically a new distribution that we are going to learn. In the previous video, we have already covered normal or Gaussian distribution. We saw in normal and Gaussian distribution, we usually get this kind of bell curve, and we obviously know the empirical rule, right? This empirical rule assumptions we also definitely know with respect to Gaussian or normal distribution. But what exactly log normal distribution is, what is the example of that, we'll be discussing in this specific video. And I will also be telling you like what all data set can probably fall in the log normal distribution, right? So let's first of all go with respect to definition. So in definition over here, you can probably see that in probability theory, a log normal distribution is a continuous probability distribution of a random variable whose logarithmic is normally distributed. Thus, if the random variable x is log normally distributed, then y is equal to log of x has a normal distribution. Okay. Now I know I've just read this, and that is what I usually do. First of all, I'll try to display the definition so that you can understand. Now let me just go ahead and explain you this. Okay. So over here it says that x, which is a random variable, will belong to a log normal distribution. Okay. So here what I'll do, I'll write it as log normal distribution. Okay. Log normal distribution with some mean and standard deviation. Okay. Now let's consider x is a random variable that belongs to a log normal distribution. Okay. And whenever we say about log normal distribution, one thing you need to understand in the left hand side, I have displayed a figure. Okay. In all this distribution, you can probably see over here, the mean is constant. Okay. The mean is constant like 0. But over here, you can also see with respect to other curves, the standard deviation is changing. Now, when standard deviation is changing with respect to the log normal distribution, you can see the right part of the curve. It is quite elongated, right? So we specifically say log normal distribution is a right skewed distribution, right? It is a right skewed distribution. And we know we have learned about right skewed distribution. We also know what is the relationship between mean, median, mode in a log normal distribution, right? So over here you can see with respect to every curve on the right hand side, the right side, it is completely skewed. Okay. So one example, let's say if I'm probably trying to draw, right? So this is what a log normal distribution looks like, right? So right hand side will definitely be skewed. Similarly, you can have different figures, but in all the figures over here, you'll be seeing that right hand side will be skewed. So this over here, you can see somewhat right hand side, right part of this particular curve is skewed. Here also you can see right part of this curve is skewed. Here also you can probably see the right part of this particular curve is skewed. Now let's consider x is a log normal distribution with some mean and standard deviation. Then if I probably try to do some transformation where I calculate a random variable y, and this y variable is calculated by using a formula log of x. Okay, so log of x, this log is specifically called as natural log. And in mathematics, we usually denote it as log to the base e. Okay, so whenever we have log to the base e, that is basically called as natural log. So over here, what we are doing is that if I have a random variable which belongs to a log normal distribution, now if I try to create a random variable y by applying this particular formula, that is log of x. So in this random variable, how many values are there? In all the values, I'm probably applying natural log. Then this specific thing, this specific variable y, which is a random variable, this will belong to a normal distribution. this will specifically belong to a normal distribution. Okay, so that is what this specific sentence says. If the random variable x is log normally distributed, then y is equal to log of x, which is natural log of x, has a normal distribution, and that is what the entire log normal distribution talks about. Now, equivalently, if y is equal to natural log of x, then I can also define as x, which is a random variable, and suppose let's say if I probably try to calculate x with the help of exponential of y. Exponential of y. Let's consider y is a normally distribution, right? Let's consider if I have a random variable y, which is log normally distributed, right? Sorry, which is normally distributed. Let's consider this y is normally distributed. Then if I apply exponential operation on top of y, right? On top of y, then I get x, and this x will be a log normally distributed. Log normally distributed. Okay, so this is what? This is just the inverse of this, right? Just the inverse of it. Before I had natural log of x. Now if I probably move this log to the left hand side, then it will become exponential of y. And finally I'll be getting x. So vice versa also you can get it, right? Let's say if x is a log normal distribution, and if you apply on top of it natural log, then you get a normal distribution. And then if you have a y, if you probably have a y which is normally distributed, and if you apply exponential on top of y, then you will probably get a random, random variable which will be log normally distributed. So these are the important conditions in log normal distribution. So about this, the second one, here you can see equivalently, if y has a normal distribution, then the exponential function of y comma x, which is nothing but exponential of y, has a log normal distribution. And that is what we have actually proven, right? So it is very simple. Let's say if I have a random variable which has this kind of distribution, right? Which has this kind of distribution. Then if I apply, let's say this is my x. If I apply ln of x, then I will probably get a Gaussian distribution. Okay, I will get a Gaussian distribution. So here I will probably get a Gaussian distribution, something like this. And vice versa, basically means that if I probably have this normally distributed, if I apply a function exponential of y, this is basically my y, right? And then I will probably get this kind of log normal distribution. So this is normal distribution, okay? And this is log normal distribution. But the question rises again, how do we check whether a distribution is normal distribution or not? For this, we specifically apply QQ plot. Okay, so in QQ plot technique, we get a technique to check whether the distribution is a normal distribution or not. Okay, so this was the entire understanding about log normal distribution. Now, let me just go ahead and talk about some of the examples. So first example over here, okay, which definitely follows a log normal distribution. Number one, the wealth distribution of the world, Okay, the wealth distribution of the world. So here I have the wealth distribution of the world. So usually in this scenario, what will happen is that, let's say if this is your distribution. Okay, so in this particular scenario, you'll be seeing that very less number of people will be having more wealth, right? So if this is wealth, okay, so in this scenario, you'll be seeing very less number of people will be having more wealth. Actually, in this world, right, where the entire wealth distribution, maximum wealth distribution is basically with that 1% of the richest people in the world. So in this area, you'll find people like Elon Musk, Adani, right? You'll find other people like Bill Gates and all, right? If you probably consider this region, specifically this region is basically the salaried class people. So definitely whenever we talk about wealth distribution, it definitely follows this distribution. Now the second example, and like this we have a lot of examples itself, in discussion forum, right? In discussion forum, okay, in discussion forum, you can probably see the length of the comments, okay? Now there will be many people who will be writing small comments. Like there'll be less number of people or more people who will be writing less smaller comments. There'll be also many people who writes, or there will be very less number of people who writes longer comments, right, in the discussion forum. So like let's consider a discussion forum. You'll find many people writing very small comments. There will be average number of people writing medium-sized comments, and there will be very less number of people writing very longer comments, right, where they are explaining something, where they are discussing something and all. So whenever we talk about the length of comments in the discussion forum, it usually follows a log normal distribution. Okay, some more examples with respect to this. So you can hear length of chess games, right? This also follows log normal distribution. There are also some other example like dwell time. Dwell time basically means the time that you spend on online articles, right? Online articles like jokes or news, right? This also probably follows a very good log normal distribution. Okay, so here are some of the examples. Most of the data set of this type usually follows a log normal distribution. Hello guys, so we are going to continue our discussion with respect to statistics, and in this video we are going to discuss about power law distribution, which is again a new distribution, which is not a Gaussian distribution, and we'll try to understand how this distribution basically works and what kind of data set probably follows this kind of distribution and what this probability distribution conveys, what kind of information it conveys of a specific data set. So without wasting any time, let's go ahead and first of all we will definitely start with the definition. So in power law distribution, the first thing you need to know is about the definition. Obviously, in statistics, a power law is a functional relationship between two quantities where a relative change in one quantity results in a proportional relative change in the other quantity, independent of the initial size of the quantities. One quantity varies as the power of another quantity. Now again, the definition as usual, it is complex. Every topic that we probably learn in statistics, the definition is quite complex. So it is better we learn it with the help of examples. I give you a lot of examples and then we'll try to understand. Okay, let's focus now on this diagram. Okay, so this diagram will actually help you understand about the power law distribution. Whenever we talk about power law distribution, you really need to remember 80-20% rule. Okay, now this is how a curve will look like. You know that for a normal distribution, my curve will look like this, right? For log normal distribution, my curve will look like this. You know about Bernoulli distribution, you know about binomial distribution and all, right? So this is specifically a normal distribution, this is specifically a log normal distribution. Now you know it. Now whenever you get this kind of curve, then you specifically talk about this, or you call this as power law distribution. Now why this curve is basically following a power law distribution? It follows this 80-20% rule. Now what is this 80-20% rule? Now you can see with respect to this variable and this variable, the relationship between them is like this is first of all covering 20% over here, and remaining this is basically covering the 80%, right? So here you can basically clearly see that how this 80-20% rule is with respect to two variables that are probably present in the x and y axis, right? So this is super important. It is just trying to show you the relationship between one variable to the other variable. Whenever when we say this particular variable, see, a relative change in one quantity results in a proportional relative change in the other. And if you probably see the last statement, one quantity varies as a power of another, right? So whenever you have this kind of relationship, it is basically called as 80 to 20% rule. Now with respect to this particular variable, you can see that it is trying to take up 20% of this entire area, right? And remaining all will be basically this 80% of this entire area, right? So this is how a relationship basically looks like. To the right, we specifically say it as a long tail, and to the left, there are few that dominate, so also known as 80-20% rule. Now, if I probably talk about some of the examples of a specific data set that follow power law distribution, because unless and until you don't understand these examples, you'll not be able to relate it, okay? I hope everybody has seen IPL, Indian Premier League, right? Can we probably talk about like 20% of team in most of the matches is responsible in for winning 80% of the match. Winning 80% of the match. So obviously this is true. This is my first example over here. Now let's talk about the second example. Now second example, what you can probably talk about. And see, in IPL, obviously you have seen, right? 20% of the team, right? They play absolutely fine to win the 80% of the match, right? Now the second example can be 80% of wealth, right? Are probably distributed with 20% of people, with 20% of the total population, let's say. Okay, so this can also be a very good example that may follow this kind of distribution that is basically called as power law distribution. Let's talk about the third example, right? Now if I probably consider about the third example, so you can probably say 80% of the total oil, okay, crude oil is with 20% of the total nations, right, of the nation, right? So this can also be a perfect example in understanding the specific power law. If I give you more examples, then also you'll be able to see. The fourth example, I can probably talk about the frequencies of words, right, in most languages. So this also probably follows an 80-20% rule, right? So like this, just think of different examples. What do you think with respect to 80 to 20% rule? Let's say in IT companies, what kind of example we can specifically say? We can probably say that 20% of the major defects, right, fixes the 80% of upcoming defects, right? So because of this 20% defects, other defects may also get raised, right, in a product, in a software product. So this can also be a perfect example, okay? Now, one very important thing that we specifically know, right? Whenever we have a log normal distributed, right? And if we apply logarithmic, right? Like log to the base e for this x random variable, then we will definitely get a normal distribution, right? Only if this particular distribution is follow a log normal distribution. Why do we do this? Because in machine learning algorithms, there are many machine learning algorithms which want the data to fall as a normal distribution, right? They want to specifically fall as a normal distribution so that the machine learning algorithm will be able to perform well, right? Similarly, what if I have a power law distributed data, which will look like this? Can we convert this into a normal distribution? So this is the question that we specifically have, and the answer is yes. For this, we specifically use Box-Cox transform. And again, don't worry, we will see this in the upcoming videos, how exactly Box-Cox transformation is done. This is also one kind of transformation, like how we have log transformation, we have probably standard normalization, like standardization, all this kind of transformation techniques, right? Now, whenever any data which follows this kind of power law distribution, we specifically call this as Pareto distribution. Okay, so in my next video, we'll try to understand about Pareto distribution. But in short, this basically follows again an 80-20% rule. Okay, it follows a power law distribution. And if we probably apply a Box-Cox transform to this kind of data, we will be able to get a normal distribution. In order to validate a normal distribution, we can use QQ plot, right? Hello guys, so we are going to continue discussion with respect to statistics. In this video, we're going to discuss about Pareto distribution. Now, already in our previous video, we have discussed about power law distribution. Power law distribution is nothing but it specifically follows this 80-20% rule. So any distribution that follows this power law is basically specifically called as Pareto distribution, right? And this is a non-Gaussian distribution, right? It is a non-Gaussian distribution. Now, obviously, we have seen a lot of examples with respect to power law, but mathematically, right, we really need to understand something very important about the Pareto distribution. Okay, so usually in this particular scenario, if I probably consider an example, so this can be a Pareto distribution. This shape can be basically a Pareto distribution. You can actually change this height also. This height can also be changing like this, right? It can also be something like this, right? But mathematically, you really need to understand one very important thing about the Pareto distribution. If I probably discuss with respect to probability density function. So here you have this alpha value, right? Now as the alpha value, so alpha is a value with respect to the probability density function, right? Whatever, as soon as you will probably be seeing that as the alpha value will keep on increasing, this line, you'll be seeing that it will keep on increasing, and finally you see that it is meeting to this particular line where it has this value as 1. Okay, so always remember, in types of Pareto distribution, it is specifically defined by this specific hyperparameter, that is alpha. And as the alpha value keeps on increasing, right? When it goes and it keeps on increasing, here you'll be seeing the height of this particular probability density function will keep on also increasing. But at the end of the day, you'll be able to see that it will be reaching this line of 1, right? With respect to any random variable that is present over here. Now, one important thing about Pareto distribution you need to understand, like let's see, like if we have a log normal distribution, right, which looks something like this, right? This is the log normal distribution. If we add log normalization, if we probably apply a log normalization transformation onto this, then we specifically get a Gaussian distribution, right? Gaussian distribution. So here you can see that this specifically log normalization that I'm specifically applying, it is basically called as transformation technique, right? It is a transformation technique. Now similarly, if we have a Pareto distribution, let's say if we have a Pareto distribution, can we convert this Pareto distribution by any transformation technique into a Gaussian normal distribution? Yes. And why do we do this? Because in most of the machine learning algorithms, we specifically use Gaussian distributed data because it will be able to increase the performance of a specific model. There are some assumptions for some of the machine learning algorithms which we'll be learning in the future, and through that you'll be seeing that how we can probably convert a Pareto distribution into a normal distribution, right? So here the technique that is specifically applied is something called as Box-Cox transformation. Okay. Now what is the formula of Box-Cox transformation? Right now, don't worry about it, because with the help of Python, I'll definitely show you that how you can probably do the Box-Cox transformation. But just understand this is a transformation technique which will probably convert a Pareto distribution into a normal distribution. Okay. Now let's go ahead and discuss about some of the examples and understand Pareto distribution has a lot of advantages. It is used in various domains, specifically in IT industry, right? If I probably consider, I can give you two amazing examples. One, saying that 80% of the entire project, okay, is done majorly by the 20% of the team, right? So you'll be seeing this in a specific IT company, right? The 20% of the team members, right, will specifically be doing more than 80% of the work, right? So always, specifically working in IT companies, we are overloaded, right? Now, if I probably go and show you the second example, right? 80% of the defects can be solved if we solve if we solve 20% of majority of the defects, 24% of defects. So let's say there are 20% of main defects that may lead to the rise of the 80% of the defects, right? So if we are able to solve this 20% of the defects, the remaining 80% can be easily solved, right? And similarly, there are different examples, right? Different examples in IT industry, in normal things. You can probably say that 20% of the entire people actually hold 80% of the weight. So this can also be there, right? You can also consider with respect to salaries, right? Like 80% of the companies that are probably giving the salary to the individuals, right? They are nothing but 20% of the entire individuals present in that specific company, right? So majority of the salary. So this all kind of examples are with respect to Pareto distribution. One important thing that you should always know: Pareto distribution always follow a power law distribution, right? Power law distribution, right? Hello guys, so we are going to continue discussion with respect to statistics, and in this video we are going to discuss about central limit theorem. Now, central limit theorem is a very important concept to understand some important things like what is sampling distribution, what are the properties of sampling distribution, and how you can also use it in the further case like to calculate probabilities, area under the curve. We'll also discuss about that. So first of all, let's go ahead and understand the definition of central limit theorem. Now here it says that central limit theorem relies on the concept of sampling distribution. Okay, we'll read the statement, understand the definition, and then I will be showing you with detailed examples and all. Okay, so central limit theorem relies on the concept of sampling distribution, which is the probability distribution of a statistic for a large number of samples taken from a population. Please make note of this kind of important point, right? Of samples taken from a population. The central limit theorem says that the sampling distribution of the mean will always be normally distributed, as long as the sample size is large enough, regardless of whether the population has a normal, Poisson, binomial, or any other distribution. Still, we have not discussed about Poisson, binomial distribution. We have discussed about normal, but just understand this: Poisson and normal distributions are a distribution of data which does not follow a Gaussian distribution. Okay. Now let me make you understand with the help of examples and what this entire statement basically says. Let's consider that I have a specific random variable which belongs to a normal distribution with some mean value and standard deviation value, right? So whenever we have this property, obviously, what kind of bell curve you will have? So you will basically have this kind of bell curve, okay? And this we specifically say it as a Gaussian distribution. This is for the scenario 1 when your distribution follows a normal distribution. So here you'll be able to see this will basically be my x of I, this will be my mean of x, right? The mean, population mean. So let's consider this as my population data. Okay, population data. Now what we will do is that now here you can basically see that central limit theorem relies on the concept of sampling distribution. Okay, so let's say if this is my population data and this is how it is plotted and this follows a normal Gaussian distribution, if we consider some sample data, so from this let's consider that I want to create some sample data like S1, S2, S3, S4 up to Sm, right? And this sample data size, let's consider some n value. This n value in the case whenever your population data is a normal distribution, it can be, this is basically the sample size, it can be of any value. It can basically be of any value. So let's consider this S1. So in this S1 I may select X1, X2, it may get selected X4. Like this, we are just taking some sample data from the population data, and this will basically be Xn. Why n? N is the sample data. And then after this we go ahead and compute the mean, the sample mean of S1, right? Similarly in X2 we will go ahead and probably select different elements. It can be randomly selected like this, and this will basically be my sample mean of 2, right? And similarly what we can do, we can select X3 bar, we can have different values, and finally I'll be having Xm bar. Okay, so like this, what we are doing is that from this population data we have selected some sample of some sample size, and this n value specifies our sample size, right? And n value can be anything. N value can be anything if your random variable follows a Gaussian distribution. Now what does central limit theorem say? Now let's go ahead and read this. Central limit theorem says that the sampling distribution of the mean. So here I have actually got the entire sampling distribution of the mean. Now what I will do, I will take up all this mean and plot it. And once we plot it, here you will be observing that according to central limit theorem, again, see this. The central limit theorem says that the sampling distribution of the mean will always be normally distributed. So if we take this x1 bar, x2 bar, x3 bar till xm bar, and we plot in this particular way where this is my x bar and this will be my mean of x bar, you will be seeing all the data points will be falling here and there, and it will probably follow a Gaussian and normal distribution. I'll not say probably, it will definitely follow a Gaussian and normal distribution. Normal distribution. So this is nothing but this is a sampling distribution of mean. Sampling distribution, right? So here you can basically sampling distribution of the mean. So this data will basically be following a Gaussian and normal distribution. So this is what a central limit theorem says. Again, let me repeat it. A central limit theorem says that the sampling distribution of the mean, of all the mean, right, from this particular population that we have selected as in the form of sample, will always be normally distributed as long as the sample size is large enough. Now this n, why I'm saying it can be of any value, because this is following a Gaussian distribution. Now this is where I come to the second scenario. In the second scenario, let's consider there is a random variable x and it does not follow a Gaussian distribution with some mean and standard deviation, right? So in this particular way, what may happen is that our distribution will not follow Gaussian distribution like this, right? It will not have a bell curve, but it will be somewhere like right skewed or left skewed. Now in this particular case, if I do the same thing, and here my n value should be greater than or equal to 30. Specifically, my sample size should be greater than or equal to 30 in order to this particular, basically, like if my n size is greater than or equal to 30, then if I probably pick up some S1 samples and calculate the X1 bar, S2 sample and calculate the S2 bar, and if we take the sampling distribution with respect to Xm bar, and if we plot it, then you'll be seeing that then this will also follow a Gaussian distribution. All the sample will also follow a Gaussian distribution. This is what a central limit theorem states. Okay. Now see, come to the next statement over here, right? Regardless of whether the population has a normal distribution or Poisson or binomial or any other distribution, the sample distribution of the mean will be normal. In this case, the n value, only when your random variable is not following a Gaussian distribution, then your n value should be specifically greater than or equal to 30. Okay. So again, let me repeat it. Very simple, two conditions that I've explained over here. If your random variable is following your normal distribution, let's consider this is my population data. Now, if I create a sampling distribution with some n sample size, right, and the n value can be any value for a normal distribution, for a random variable to be a normal distributed, right? And in this case, if we take all this sample mean and if we plot it, it will follow a Gaussian or normal distribution. This is what is possible with the help of CLT, right? CLT theorem states that, okay? It has proved that, okay? We don't have to go inside the proof, but again, if you probably consider, if you pick sample of data, if you do this, you'll be able to get it also, okay? And let's say if your random variable is not following a Gaussian distribution, it can be of any other distribution. And here in this case, my n size should be greater than or equal to 30 for making sure that whatever sample mean I take, here we probably get in the form of Gaussian or normal distributed, right? So this is what a central limit theorem states that, okay? So let me just go ahead and again read it. The central limit theorem relies on the concept of a sampling distribution, which is the probability distribution of statistics for a large number of samples taken from a population. The central limit theorem says that the sampling distribution of the mean, whatever mean we have calculated, will always be normally distributed as long as the sample size is large enough, regardless of whether the population has a normal, Poisson, or binomial distribution. When I say Poisson or binomial, it is basically not following a Gaussian distribution. Okay. Now this was one very important statement that we can probably come up with from the central limit theorem. Now the other thing that we can probably come out, okay, this is also very much important. Okay. So first thing, whenever let's say I have a normal distribution of the population, right? Normal distribution of the population. Now, whenever I have this, you will be able to see that I will be getting this kind of bell curve. This will basically be my x, and this will be my mean. Now, in this scenario, my random variable will belong to a normal distribution with some mean and standard deviation. But once we do the sampling distribution out of this, so obviously, with respect to sampling distribution of mean, right? Once we do this, right, of some n value, right, n small n value, and the outcome, that once we plot this mean, it will again follow a bell curve. But what will be the mean value? So this will basically be my x bar and mean of x bar, right? Now, in this scenario, here initially my mean was mu and my standard deviation was sigma, right? Once I do the sampling distribution, will my mean change? Or will my mean be something else? Or will my standard deviation be something else? So central limit theorem also says that once we do a sample distribution of a mean from a population data, my x will definitely belong to a normal distribution, and here my mean will be equal to the population mean. So this is nothing but my population mean, whatever population mean I had. Okay, whatever population mean I had. But my standard deviation will be equal to sigma by root n. What is n? N is nothing but the sample size. N is but nothing but the sample size, and sigma is nothing but population standard deviation. Right? So this is what central limit theorem also says, that whenever you're probably picking up sampling distribution of a mean from a population data which is normally distributed, then the new mean will be obviously equal to population mean, will be approximately equal to population mean, but your standard deviation will be nothing but standard deviation divided by root n. And this standard deviation is nothing but with respect to the population standard deviation. So this is the specific changes that are basically happening whenever we take sample distribution of a mean from a normally distributed data. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about estimates. Now till now, whatever topics in the previous sessions we were discussing, we mostly discussed about descriptive statistics. But now we will start learning about inferential statistics now. And one important thing about inferential statistics is that you make a lot of inferences for a specific population data. You do a lot of experiments over here. We'll be seeing so many things that are going to come up, right? In this video, we're just going to focus on this particular topic, which is called as estimate. Okay, so estimate, what exactly it is. Okay, so if I probably try to discuss about estimate. Estimate is specified observed numerical value. I'll be showing you different examples also with respect to that. So first of all, let me define the definition. Estimate is a specified observed numerical value used to estimate an unknown. This is super important. See this? It is used to estimate an unknown population parameter. Population parameter. Okay. So whenever we talk about estimate, so this estimate only, okay, it is a specified observed numerical value that is used to estimate an unknown population parameter. Okay. Now, if I probably take different types of estimate, the first type is specifically called as point estimate. Point estimate. So in point estimate, it is specifically a single numerical value. So I'm going to write the definition. I'm going to make you understand also. It is a single numerical value used to estimate an unknown population parameter. Unknown population parameter. Now let's discuss this with an example. What exactly is point estimate? Now one example can be a sample mean. Sample mean is a point estimate of population mean. Right? We can basically write this point estimate of population mean. So let's say that if I have a population data, okay, if I have a population data, let's say this is my population. If I probably consider a sample data out of it, okay, so this is sample and this specifically is population. So in this case, let's say with respect to population, I will be getting population mean, and with respect to sample, I will be getting sample mean. So I can basically say this sample mean is a estimate of population mean. This is specifically a point estimate because this is just one value. Okay, so we basically say this x bar is a point estimate of mu, which is basically the population mean. So again, let me repeat the definition. Point estimate is a single numerical value used to estimate an unknown population parameter. So suppose if I have a population and out of this I take a sample, this x bar what you're coming, right, it is basically a point estimate of this population mean, right? This sample mean will be using in order to represent the population mean. Okay, so this is with respect to what exactly is point estimate. Now coming to the second topic, like second type. What is the second type in estimates? We basically say this as interval estimate. Okay, interval estimate. Now in interval estimate, a range of values is used to estimate unknown population parameter. Unknown population parameter. Now see this guys. If I probably have this population data, I get a population mean, and if I take a sample, I get a sample mean. But only this specific point will not be sufficient to represent this entire population mean, right? So it is better we give some range of values. Like let's say if I have a population age mean, right, of somewhere around 65, right? And let's say if I consider sample and I probably got 60. Now you can see with respect to 60 and 65 there's a huge difference, right? So 60 cannot probably represent this entire population mean. So what we do is that we basically use this interval estimate to probably specify a range. Okay, range. Now in this case, what will happen is that it will be shown in this specific way. See this. What we can do is that we can actually use a point estimate. This is a point estimate, but along with the point estimate, right, we will be defining one range, right? And it basically says that plus or minus margin of error we can specifically have with respect to this particular point estimate. Now here we saw that my sample mean was 60, right? But the difference is 5, right? Now what I can do, I can keep a range between 55 to 65, right? So I can probably keep a range between 55 to 65. This range is specifically called as confidence interval, right? So whatever range we are specifically talking about, this range, right? This is basically called as confidence interval. Okay? We'll discuss more about confidence interval in the upcoming session, but understand over here, interval estimate basically says that we are specifying a range of value to estimate the unknown population parameter, right? So this range will basically be used to estimate the population parameter. We can probably say that the sample mean may be ranging between 55 to 65, right? In this case, we just had one value. I had one sample mean, but this can be very much less, or it can also be very much greater than the population mean. So this point estimate will not be a proper way to probably show an estimation of an unknown population parameter. But with respect to interval, we can specify a range of values. Hello guys, so we are going to continue discussion with respect to statistics, and in this video we are going to start a very important topic which is called as hypothesis testing. Now whenever we are talking about hypothesis testing, one thing that you really need to keep in mind, this is a part of inferential statistics, okay? Inferential stats. And what is the main aim of inferential stats? To come up with conclusions or inferences from a sample data about an unknown population parameter, okay? So let's say that I have a specific sample data. With the help of this sample data, I will try to make some conclusions about the population data, okay? And when I'm saying I'll make some conclusion, that basically means we make conclusion about some unknown population parameter. It can be mean, variance, standard deviation, because it is very much difficult to probably have the entire population data. So this data is specifically sample data, and this is nothing but my population data. And what is the main aim? We come up with some kind of conclusions or inferences. And how do we come with some kind of conclusions or inferences? So for this, we use something called as hypothesis testing. Okay, hypothesis testing. Now we will try to see how hypothesis mechanism happens, how many steps are there, what all steps needs to be followed, and I will be giving you with a very generic, simple example about hypothesis testing. So I will be giving you also a very simple example about hypothesis testing so that you can actually understand. So let's go ahead and let's understand about the hypothesis testing mechanism. Like what are the steps that is basically involved? The first thing that in hypothesis testing, whenever we start, we need to write our null hypothesis. Okay, null hypothesis. This is denoted by H0. Okay, and what H0 will have, what null hypothesis will have, the assumption you are beginning with. Okay, so I'm going to write over here the assumption you are beginning with. Whatever by default assumptions are, that will probably go with respect to the null hypothesis. I will give you an example, don't worry. Second step is to basically write our alternate hypothesis. Now in the case of alternate hypothesis, we use H1. So let me give you a very good example. Let's say a person has committed a crime, right? Now whether this person has committed a crime or not, what the police does, they take them to the court, right? When they take them in the court, initially, right, the judge will say that he's not guilty until proved, right? So by default, the person is not guilty, right, until proved, right? So that is how in court actually happens. So what is the default assumption? What is the assumption you take in the beginning? That we have to probably write over here. Alternate hypothesis basically says that it is the reverse of null hypothesis. So in this case, I can basically write the person is guilty. I'm just taking a generic example to probably make you understand. So over here, you'll be able to see alternate hypothesis is nothing but opposite of null hypothesis. Null hypothesis. Okay. Now coming to the third step. What is the third step? Here we perform some kind of experiments. Whenever I say experiments, that basically means we perform statistical analysis. Statistical analysis. There are different types of statistical analysis, specifically with respect to sample data and population data that we use, like Z-test, T-test, chi-square test, ANOVA test, F-test. All these things we'll be learning as we go ahead, right? But to give you in this case, in this problem statement, whether a person has committed a crime or not, here we collect proofs. Okay. What kind of proofs? Let's say a DNA test, right? Fingerprint test, right? Or it can be any kind of data. With this experiment, we can then conclude whether we should accept the null hypothesis or reject the null hypothesis. Or reject the null hypothesis, right? So this is how we perform different steps. Here, when I say statistical analysis, then we will be talking about the statistical analysis in our upcoming videos. What are the different types of statistical analysis? All those things will be understanding. But I hope you understood about how does the hypothesis testing basically happen. You have a null hypothesis, you have alternate hypothesis, then we perform the statistical analysis to prove whether this is true or whether we need to reject this. Okay, so this many steps. Now let me go ahead and show you an example. So here you need to determine from this question what is your null hypothesis and alternate hypothesis. Okay, so over here the question is there that colleges at district A states its average pass percentage of students are 85%. A new college opened in the district and it was found that a sample of student 100 have a pass percentage of 90% with a standard deviation of 4%. Does this school have a different pass percentage, or does this college have a different pass percentage? Now in order to find out this, whether it has a different pass percentage, first I will define my null hypothesis. And in null hypothesis, what it says, it is very much clearly given. H0 is nothing but your average pass percentage is nothing but 85%. So in the beginning, this is the assumption that is made by someone. It can be a college, it can be a school, it can be anything, right? And now if you go and probably see with respect to alternate hypothesis, it is just see this concluding statement or problem statement what they have told us to find out. So it says that does this college have a different pass percentage? That basically means mean is not equal to 85. It can be less than 85, it can be greater than 85. If the question was does this college have a pass percentage greater than 85, I could have written mu is greater than or equal to 85, right? But this is not equal to 85. So this is how you can talk about null hypothesis and alternate hypothesis. Now going forward, we'll talk about this experiments and all, because in this experiments I also need to discuss about two different values. One is p value and one is significance value. That I will do it in my next video, right? Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to define or understand what exactly is p-values and what is the importance of p-value in hypothesis testing. Now let me go ahead and let me explain about p-value. First of all, we'll try to see the definition, but p-value is super important in inferential statistics because it will help us to make some conclusions about some population data. Okay. Now before wasting any time, let me first of all go ahead with the definitions over here. A p-value is a number calculated from a statistical test that describes how likely you are to have found a particular set of observation if the null hypothesis were true. P-values are used in hypothesis testing to help decide whether to reject the null hypothesis. Okay. Not a worry, like if you're not able to understand, but I will give you very good examples regarding p-value. Okay. So let me go ahead and let me explain you. I hope everybody has probably used a keyboard, right? In keyboard you have a space bar. So this is how your space bar looks like, right? Most of the time with respect to this particular space bar, you touch it in this region, right? In this region, right? Most of the time you touch in this region, and specifically hardly you touch some of times over here, or here, or here. So if I probably try to see this touch distribution is also like a Gaussian normal distribution, something like this, right? Now within this kind of distribution, let's say one of the data point over here if I say my p-value is 0.2. Now what does this basically mean? This basically means out of 100 touches in the space bar, 100 touches, we touch around 20 times in this region specifically, in this region. This is in the layman term I've explained what exactly p-value is over here, right? P-value is basically talking about the probability of a specific outcome in a specific region in this case. Now if I say p is equal to 0.2, I'm basically saying out of 100 touches, we touch around 20 times in this specific region. Okay. Similarly, let's consider that in this region my p-value is 0.8. Now this basically means out of 100 touches, how many times I'm touching over here? Somewhere around 80 touches, right? So this is how we can just think of the p-value right now, okay? But let me go ahead and explain you with the help of hypothesis testing. Here I will also be taking an example for that, okay? So let's go ahead and let's talk about this hypothesis testing. Now as you know, in hypothesis testing, my first step is basically to write the null hypothesis, alternate hypothesis, and then we specifically perform a statistical analysis or statistical test. The outcome of a statistical test is p-value, okay? Now how it is related and all, I'll just talk about it. Let's take an example. Let's say I want to probably do hypothesis testing on a fair coin to just find out whether the coin is fair or not, okay? And probably I'll try to find this out by doing 100 tosses, okay? Now, let's say out of, or forget about 100 tosses right now, okay? Let's consider that the probability of head is 0.5 and probability of tail is 0.5. In this scenario, we know that even though we toss 100 times, let's say if we are tossing it for 100 times, if this is the probability based on the Bernoulli's theorem, or Bernoulli's distribution, sorry, not theorem, distribution, 50% of the time heads will come, 50% of times tails will come. So I can definitely say this coin is fair. Let's say if I probably go and say my probability of head is 0.6 and probability of tail is 0.4. Now in this scenario, I may consider, okay, fine, probability of head is 0.6, 60 times I'm getting out of 100 tosses. There may be a scenario like, okay, fine, sometime we may continuously get head 10 times, okay? But if I go to the next scenario where I say my probability of head is 0.7 and my probability of tail is 0.3, now you'll start thinking, okay, this is something wrong with the coin. The coin is not fair because 70% of the time it is basically coming as head. Now how we can probably confirm this experiment through hypothesis testing, and we'll try to see what exactly it is, okay? So in the first step in the hypothesis testing, we will first of all define our null hypothesis. So I will go ahead and define my null hypothesis. So this is my null hypothesis. Now in this null hypothesis, I will basically say this as h0, and this scenario I will write coin is fair. Because what is the basic assumption I'm going to take over here? The second scenario will be alternative hypothesis or alternate hypothesis. Alternate hypothesis. Okay. Alternate hypothesis. So here I will be having h1 and this will be coin is not fair. Okay, this will be the opposite one, right? Not fair. Now this is fine. Now coming to the third one, the type of experiment that I'm going to perform to solve this. Let's say the experiment that I'm performing over here, I will just toss it for 100 times. I will toss it for 100 times. I'll toss the coin for 100 times. Okay. Let's say the over here I'm just going to draw a diagram. I have 50 times over here as my mean. Okay, if I'm probably getting this x-axis is nothing but it is the how many times I'm getting head. Let's say. Okay. So this will be 50. Let's say standard deviation is 10. So I will write 70, 80, 90, and this will be 40, 30, 20, 10. I've defined like this. Okay. So with respect to this distribution, obviously you know that we will get this kind of bell curve. Okay, when I have this mean and standard deviation as 10. Now this is obviously the mean value that I have. Okay. Now the number of times, let's say out of this, if I'm probably getting 50, number of heads that I'm getting 50, then I can definitely say the coin is fair. Okay. Let's say if I get number of times of head is 60. Now here also I told you right in the above scenario, we told that okay, fine, it is fair, 60 times it can come and 40 times tail it can come. But now what will happen if 70 comes? Like if I toss the coin 100 times and probably I get the 70 value. Now it is a concern. Now there is a problem saying that okay, fine, 70 times head is coming, 30 times tail is coming, this coin may not be fair. So what we do is that we define a confidence interval. We basically make sure that we define a confidence interval. The confidence interval can be between 30 to 70. Let's say. How do we define confidence interval and all? I'll talk about that. Domain expertise is definitely used over here. Okay. So in this scenario, let's say I am saying that if I'm tossing the coin and if it is between 30 to 70 number of heads in this region, okay, in this specific region, then what I will do is that I will consider that my coin is fair. So in this region, if any number comes, I will consider the coin is fair. Okay. Let's say if I do the number of tosses, now if in this region I'm coming or in this region I'm coming, I will basically say the coin is not fair. Okay. Coin is not fair and coin is not fair. Coin is not fair. Now, how do we define this confidence interval? There is a very important parameter which is called as significance value. Okay. Again, we'll learn more about the significance value. The significance value is denoted by alpha. If I say alpha is 0.05, then what it is saying is that we have to find out a confidence interval by taking this entire area 1 minus 0.05. So 1 minus 0.05 is nothing but 0.95. So this area that you're seeing, right? If I'm saying for this particular problem, my significance value is 0.05. Now you may be thinking, who will set this significance value? Okay, and how it is related to p-value? I'll explain about that everything. Okay. Now in this alpha value, significance value is decided by the domain expertise. Based on problem statement, this value may differ. Okay. For health problem statement, your significance value may be less, it may be more. For different problem statement, we basically define it. Okay. Now in this scenario, when I probably try to calculate the confidence interval, I'm getting 0.95. So this area is basically 95% confidence interval, and remaining 0.05 will be divided between these two areas. So in this area, the area under the curve is nothing but 0.025, and this will be 0.025. Okay. Based on this value, we get some confidence interval value. Okay. Based on this value itself, the area under the curve, we get some confidence interval value. I will show you how to calculate it. Now let's say I get a p-value. Okay, I get a p-value. Okay. Now and p-value is basically computed from the statistical experiment. Okay, we will be getting a p-value output. Let's say the p-value is somewhere coming over here in this region. Okay, or in this region. I will show you in the upcoming videos how to calculate p-value. There will be a z-test, t-test. We'll be doing that. Okay, and there is a specific set of specific formulas used to calculate the p-value. Okay. Now let's say I get a p-value and this p-value is less than this specific value. Let's say this value, whatever is coming in this confidence interval. If it is less than this and if it is greater than this, it will specifically come in this region. So if I say my p-value is less than my significance value, okay, or my p-value can also be greater than the significance value at this side. Okay. So either it is in this region or this region. Okay. In this scenario, I will say we have to reject the null hypothesis because it is basically coming in the extreme end, in this end, or in this end. In this end, we basically reject. This is basically my rejection area. Okay, rejection area. And similarly, in this region, it is my rejection area. So what I will say, if my p-value is less than significant value, we reject the null hypothesis. And let's say if it is present in this region, okay, if it is present in this region, else we fail to reject the null hypothesis. We basically mention it as fail to reject the null hypothesis. So I hope you're able to understand what's confidence interval over here. 95% confidence interval basically means with respect to any experiment that I perform, if it's coming within this region, I will accept the null hypothesis, or I'll fail to reject the null hypothesis. If it comes in this region, I will basically reject the null hypothesis in short, right? And this is what it is basically. How does p-value derived? There's a mathematical formula based on different problem statements like z-test, t-test, and all. We'll try to see that. Don't worry about it. We'll try to see when the p-value is less than significant value and all, and how to calculate this confidence interval. Also, we'll try to see everything, area under the curve, everything. We'll try to see. With respect to this point, we can calculate what is the area under the curve. With respect to this point, what is the area under the curve? We will definitely be able to calculate it. Okay. But at the end of the day, this is my conclusion. This is my conclusion. Whenever my p-value is less than significance value, that basically means it is either coming in this region or this region, right? So I will say reject the null hypothesis because in this region, it does not satisfy the 95% confidence interval. Who defines this? A domain expert. Hello guys, so we are going to continue the discussion with respect to statistics. Now we are going to start different statistical analysis, and we will be doing hypothesis testing. This will be super important as a data analyst, as a data scientist, whenever you probably take up a problem statement and you want to perform different kind of hypothesis testing. Now with respect to statistical analysis, there are various types. One is something called as Z-test. The second one is something called as T-test, right? Then we have something like chi-square test. We have something called as chi-square test, right? Chi-square test. Similarly, we also have ANOVA test, and there are many more tests as such, right? And which we will be discussing as we go ahead, right? Fourth is something related to ANOVA test, okay? Now, in all this tests, right, this both Z test and T test are specifically with respect to data that are dealing with average data, right? Sample average, population average. It will help us to find out with respect to the population. If I talk about chi-square test, this is specifically used for doing statistical analysis for categorical data. And ANOVA test is specifically for variance of the data, right? So all these things we will be using, and over here we will be trying to estimate a population parameter, a known population parameter, and we'll try to see just with the sample data can we come up with some conclusion regarding the population data. Now in Z test and T test we specifically use two tables, that is called as Z table, which we have already discussed, and there is also one more table called as T table. So in Z table we specifically try to find out the Z score value and the P value. Similarly, in the case of T table, we'll also try to find out the Z score and P value. But what is the exact difference between Z test and T test? We will try to understand that. Now in this video, we are going to focus on a problem statement that is related to Z test. One thing that you need to know about Z test is that whenever, number one, right, whenever your population data, let's say your population average, right, or your population mean, I'll not say population mean, let me just write it down. Whenever you want to use Z test, the first thing is that you really need to know your population standard deviation. And the second thing, your sample size should be greater than or equal to 30. If these two conditions are matching, then probably you can actually use Z-test. Okay. Whenever you know any of your data set, let's say if a problem statement is given where you know the population standard deviation and the sample size, whereas your sample size is specifically greater than or equal to 30, at that point of time you can basically use Z-test. Now let's solve a problem statement, and over here we will be doing multiple things. We will try to understand about the Z-test as such. Okay. So without wasting any time, let's go ahead and let's try to do this. Okay. Now let's read the question first of all. The average height of all the residents in a city is 168 centimeter. So over here the average height of a resident in a city is given as 168 centimeters. So my first data that I have is that I know the population mean. Here the population mean is 168 centimeters. Okay, 168 centimeters. Now let's go to the next question. With a standard deviation of 3.9. Now when I say with the standard deviation, this is nothing but population standard deviation. Now since population standard deviation is given, and if I have one more condition when n is greater than or equal to 30, I will probably be using Z-test. Okay. A doctor believes the mean to be different. So this is the hypothesis testing that we really need to find out whether the mean is matching the population mean or not, considering a sample of data. Okay. He measured the height of 36 individuals. So my sample size is 36, which is greater than or equal to 30. So that is the reason we are using Z-test. And found the average height to be x bar 169.5 centimeter. Now the first statement with respect to the hypothesis testing is that state null and the alternate hypothesis. And second question is that at a 95% confidence interval, is there enough evidence to reject the null hypothesis? Okay. So this is what we are going to check. And over here the confidence interval is 0.95. That is 95%. With the help of confidence interval, we can calculate my significance value. All I'll do 1 minus CI, it is nothing but 1 minus 0.95, which is nothing but 0.05. So 0.05 is my significance value. Okay, 0.05 is my significance value. Now let's go ahead and solve this both the problem statement, and let's see how we can do it with the help of Z-test and how we can refer the Z table and everything we'll try to see. The first step in the hypothesis testing is that your null hypothesis. What is your null hypothesis in this case? It is very much simple. What is the basic assumption that is given in the problem statement? The average height of all the residents in the city is 168 centimeters. So I will say my mean is nothing but mean of the height is nothing but 168 centimeters. Now coming to the next step, which is called as alternate hypothesis. We need to also specify our alternate hypothesis. My alternate hypothesis is H1, and here my H1 is basically saying the reverse of null hypothesis. It will be the inversion of null hypothesis. So we are going to check whether my mean is not equal to 168 centimeters. Okay. Now we'll try to test this null hypothesis with the help of statistical analysis. The third step is that based on confidence interval, what we will do based on confidence interval, we will draw decision boundary. Right? Now, how to draw this decision boundary? That is super important topic. We know what is our mean. Our mean is nothing but 168 centimeter. Now, with respect to the decision boundary, we know that, right? In a normal distribution, what is the area within the first standard deviation? What is the area within the second standard deviation? Now, what is the confidence interval that we are probably trying to consider is 95%. So 95% if I say from both the scenario. Why I'm saying both the scenario? Because this is a two-tailed test. Why I am saying is a two-tailed test? Understand what is the null hypothesis. Null hypothesis is mean is equal to 168 centimeter. And alternate is mean is not equal to 168 centimeter. So what I am testing for is that whether my sample height is greater than or is less than 168 centimeter. So we are checking in both the direction. And based on this both the direction, we are checking it for 95% confidence interval. Right? When I say 95% of the area is probably over here, then the remaining area, if we try to divide in the two extreme ends, it will be nothing but this area will be 0.025 and this area will be 0.025. Okay. So this is the area that we are probably testing. Now what we'll do based on the statistical analysis, let's say if we get any value that is within this confidence interval, then we will consider that the null hypothesis is accepted. Right? We fail to reject the null hypothesis. This is what the statement we specifically say. Okay. We fail to reject the null hypothesis. But from a statistical analysis, if we are falling in this specific area, then we will say that we have to reject the null hypothesis. Okay. This is what we are going to do. Now, with respect to this 95% confidence interval, we need to define the Z score value. Okay. Now, in order to define the Z score value, we need to see that how much area is basically present over here, 0.025, right? And over here it is 0.025. Let's calculate the Z score for this one. Okay. Let's calculate the Z score for this one. Whatever Z score we will get, since this is a symmetrical distribution, then the same negative Z score will come over here. Okay. Now, in order to find this, you'll be seeing this entire area is 1. And in order to find only this Z score, what I will do is that I will subtract 1 minus 0.025. 1, the entire area, and 0.025 is this area. So I will probably be getting this Z score value, which will determine the area under this entire curve. Okay. So over here you'll be seeing 0.9750 is my entire area. Right? Now with respect to this, what is my equivalent Z score I need to compute? Okay. It is very much simple to compute based on the area under the curve. This is basically my entire area. This is my area. And based on this, my Z score, we will try to refer it to this particular table. Okay. This table is again Z table. You can just search for Z table PDF. Okay. And just go over here. Now try to see this data that you see, right? This is basically the area under the curve. Okay. Now right now my area under the curve is 0.9750. So go and see for it. 0.9750. We have to see in the positive Z table where my all positive standard deviation are there because 97% of the entire area we are trying to check. So if you probably go and see over here, there will be one value which is 0.9750. See over here, 0.9750. And based on this, what is my Z score that I'm getting? I'm getting 1.9. And if I see for this particular table, it is 6. So 1.96 is the Z score for this area under the curve, right? So I will go back again over here. Okay, I will go back over here. And now my Z score will be nothing but it will be plus 1.96 for this region. And after this, you'll be seeing that whenever we try to see the left part, okay, whenever we try to see the left part, in the left part, what do you think we will be having? What do you think we'll be having? It is very simple. We will get minus 1.96. Now, any value from the statistical analysis, if it comes between this range of z-score, we will consider it as that the null hypothesis is true. So we fail to reject the null hypothesis. Let's say from the statistical analysis that we do, if it comes in this end, this extreme end, then we have to reject the null hypothesis. So I hope you are able to understand with respect to the decision boundary and all. And you know your alpha value also. Alpha value is nothing but 0.05, and that is the reason we are basically using 95% confidence interval. So this is nothing but this is my 2.5% of area. This is my 2.5% of area. Okay. Now what conclusion I will try to make with respect to this 1.96 and 1 plus 1.96. The new z value, let's say the new z score based on the data, if it is less than minus 1.96 or greater than plus 1.96, we have to reject the null hypothesis. Otherwise, we accept the null hypothesis, right? So this is what we really need to compute. Now, how this z will get calculated? This z will be getting calculated from the statistical analysis. Very much simple. So let's go ahead and let's compute it. Okay. So my next step is basically my z test that I'm going to perform. Okay. Now, in order to perform the z test based on the data, I'll write z of t. It is nothing but x bar minus mu. My mu is my population mean with respect to this height, divided by population standard deviation by root n. Now you may be thinking why this we are using, because the z-score formula that we learned till now was something like this: x bar minus mu divided by standard deviation. But understand, this was for the population data. According to central limit theorem, if I'm using it for sample data, my sigma will get changed to sigma by root n. So that is the reason I'm writing this. If you don't remember, guys, just revise the central limit theorem video. In that sample distribution, my mean will be equal to the population mean, but my standard deviation will be nothing but sigma by root n. Now we'll go and solve this problem. I know what is my x bar. My x bar is 169.5 centimeter. My mu is 168 centimeter. My sigma is 3.9 divided by root 36. So if I probably do this calculation, it will come somewhere around 1.5 divided by 0.65, which is nothing but 2.31. Now see, what is my z value coming? Z of d. Right? It is 2.39. We have written the conclusion. If z is less than 1.96, minus 1.9, greater than plus 1.96, we reject the null hypothesis. Is 2.31 greater than 1.96? Yes. So it is basically coming to the extreme end. Right? Now since it is coming to the extreme end, what do? We basically write 2.39 is greater than 1.96. So what we do? We reject the null hypothesis. Right? So this is what is my conclusion. Right? So we are rejecting the null hypothesis. So we can definitely confirm my p-value is less than 0.05, which is my significance value. But still, I did not get this p-value. How do I compute this p-value? Now we know that initially my z confidence interval was between plus 1.96 and minus 1.96, right? So I will go and take up this 2.31 and construct my new graph. Okay. So this is my 1.96 and this is my 2.31 and this is my 2.31. This will be negative. This will be positive. Now this is what I'm getting with respect to my new calculation. It was not 1.96. Okay. Now based on this, let's calculate the area under this curve till 2.31. So all I have to do is that again go back to my z table and probably check what is 2.31. Okay. So quickly I will go and see over here. So 2.31. So let's see, this is 2.3 and this is 1, right? So I am getting 0.98956. So I'll go over here. This entire area that you are probably seeing, it is nothing but 0.98956. I guess this is correct. Okay, right? This is the entire area. But what about this area that I want to get? And that is how I'm going to calculate my p-value, right? So in order to calculate this, all I will be doing is that I will be subtracting 1 minus 0.98956. Now if I subtract this 1.98956, here I'm going to get somewhere around, if I probably subtract it, let's open the calculator over here. Let's open the calculator. So over here I have my calculator. So I'm saying 1 minus 0.98956. So I'm getting 0.01044. So this area that you'll be seeing is nothing but if I see the calculator again, 0.01044. Now this area is equivalent to this area, so this area will also be coming as 0.101044. And the remaining area, if I probably take this entire one, right, entire one, so it will be nothing but this plus this subtract by 1, right? So if I probably say this plus this subtracted by 1, okay? So how much I'm going to get? So this is nothing but 0.97912, right? So this is what is the area under the curve, and this is the area from this particular left direction and right direction, right? On the left extreme and the right extreme. Now in order to calculate the p-value, so there are two ways. One is from z-score, which we have done it over here, and one is from p-value, right? Now my p-value is basically calculated by adding up these two regions. So it is nothing but 0.01044 plus 0.01044. So here you'll be seeing 0.02088. Now we'll go and check whether my p-value over here, whether my p-value is less than 0.05. So obviously 0.02088 is less than 0.05. So what do we conclude? We really need to reject the null hypothesis. What is the null hypothesis? That the mean is equal to 168 centimeters, right? But from the sample data doctor has collected, see, this is the assumed information. Doctor is trying to verify from the sample information. So doctor, if he has collected 36 individuals and the height was 169.5 centimeter with 95% of confidence interval, it is rejecting, saying that the mean was 168 centimeters. So over here you can basically conclude that we are rejecting the null hypothesis, and final conclusion will be that the average height is not equal to 168 centimeters. This is what we are concluding. Okay, but if you want more refined conclusion, since we are getting in the positive direction, that basically means my height is increasing, right? So based on the doctor, the average height seems to be increasing. Average height seems to be increasing based on sample data. This is what is the conclusion that I can definitely make. Sample height, right? So this is what is the conclusion that I have done. This was the first step where we specifically did with the z-test, and this was how we can probably come up with p-value also. Okay, so this is how you probably solve a z-test problem. One very important information about z-test is that whenever you want to apply z-test, this usually gets applied for average data. Okay, with respect to population data, you need two information. One is population data, and your sample size should be greater than or equal to 30. Both this problem statement satisfies this, so I am specifically using this with the help of z-test, and this is my statistical analysis. This is the formula that I have applied. I got my 2.31 and my standard deviation, and based on this, what we did, we calculated a p-value. P-value is nothing but what is the area under this, what is the area under this. We are summing it up, and if this both the sum is less than or equal to 0.05, we will basically say this as that we are rejecting the null hypothesis. If my p-value was coming, which is greater than 0.05, we say that the null hypothesis is accepted. We fail to reject the null hypothesis. At that point of time, we could say that the mean is 168 centimeters. So I hope you got an idea about this. We'll solve one more problem so that you'll be able to understand. But just try to solve this problem based on your understanding first of all. Pause the video and try to see whether you're able to solve it or not. Okay. So I will go ahead and explain it till now. Okay. Till then, just pause, try it out, and then let me know in the discussion forum. I will be solving this problem for you. So over here, a factory manufactures a bulb with an average warranty of 5 years and with a standard deviation of 0.50. So what is the information that I'm able to get? My mean is 5. Okay, my standard deviation is 0.50. If standard deviation is 0.50 and my sample is greater than 30, then we have to use Z test. So over here, n is nothing but 40. See, we test a sample of 40 bulbs. Sorry. So my n value is greater than 30, so I'm definitely going to use this Z test. A worker believes, let's continue the statement. A worker believes that the bulb will the bulb will malfunction in less than 5 years. Okay, so it is basically saying less than 5 years. It is not saying not equal to 5 years, less than 5 years. Okay, in the previous problem, my mean was not equal to 168 centimeters, then alternate hypothesis. This is the test that the doctor was doing. So we said it as two-tailed test because my mean can be greater than 168, it can also be less than 168. Okay, but in this scenario, you will be seeing that the bulb will malfunction in less than 5 years. He tests a sample of 40 bulbs and find the average time to be 4.8 years. So what is my x bar? It is nothing but 4.8. And what is my n size? 40. That is given. Okay. Now, as usual, first statement is that state your null and the alternate hypothesis. So my null hypothesis will be h0. My mean is equal to 5. Okay, this is what is my null hypothesis. What is my alternate hypothesis? Now my alternate hypothesis will be, what is the test happening for? See over here, if I probably go and see, a worker believes that a bulb will get manufactured in bulb will malfunction in less than 5 years. I will just write this as in, okay, in less than 5 years. In less than 5 years. So we are checking only less than 5 years, not greater than 5 years. So my alternate hypothesis will be mu is less than 5 years. Okay. Now with respect to this, you know that this will become only one tail test because you're only seeing on the left hand side, not on the right hand side. So this becomes a one tail test. Okay. Now we'll try to solve this problem. Okay. So over here, you'll be seeing that my next step will be creating a decision boundary because I need to specify my confidence interval. So guys, now we have understood about the null and alternate hypothesis. Now let's go ahead and understand what decision boundary. Now in decision boundary, as we have already discussed, this is a one tail test, right? So my mean is 5 over here, and I want to check my alternate hypothesis less than 5, right? Somewhere over here, less than 5, considering 98% confidence interval, and this is 0.02, that is 2% of confidence interval, right? 2% of confidence interval. I have to only check for this specific area, right? This area. So how do I do this? Okay, the next step will be I will perform a Z test. In the Z test, we will try to calculate the Z of B value. I'm giving some notation over here. The formula is x bar minus mu divided by standard deviation divided by root n. So here, x bar, what is x bar? 4.8, and then n is 40, and standard deviation is 0.50. Okay, so here I'm going to write 4.8 minus 5.50 divided by root of 40. So if you do this entire calculation, you're going to get minus 2.53. So based on this, the value that you're probably getting over here is nothing but, if I probably consider, here I'm not use only Z test, I will try to directly do with P value, okay? So that my calculation will be faster. Now with respect to minus 2.53, I will try to find out what is the area under this, okay? What is the area that I'm probably going to get? And based on that, I'm going to compare my P value, okay? So minus 2.53, I will go to my Z table, minus 2.53, right? So this is 3. No, not this, this is 3. It is nothing but 0.99430, area under the curve, okay? Area under the curve with respect to plus value. So if I'm probably considering over here, let's say, but I've got minus 2.53, okay? So what I will do, I will go and check for this, see, in the negative direction. Minus 2.53, it is nothing but 0.00570. This is what area under the curve is, right? So here, what I'm going to do, I'm going to get my entire area under the curve over here with this Z score value. So area under the curve with Z score, minus 2.53. I'm going to probably get how much value? I'm going to get 0.00570. Area under the curve with Z score is minus 2.53 is 0.0570. This is nothing but my P value. So my P value is nothing but 0.0570. Now we need to compare whether P value is greater or equal or less than the significance value. So compare P value with significance value. My significance value is obviously 0.02. So if I go ahead and compare 0.07570, whether this is less than 0.02, so this will basically be false because it is greater, right? So in this scenario, since it is greater than false, since it is greater than 0.02, that basically means it is falling in this 98% confidence interval, right? So this is my acceptance area. This is my rejection area. So we are definitely saying that my P value does not fall in this rejection area. Okay. So we are telling that, okay, it falls in the acceptance area. Why? Because my P value is not less than 0.02, which is my significance value, which is defined by this confidence interval. Okay. So what we do, we specifically say we accept the null hypothesis. We accept the null hypothesis. Or we can also say we fail to reject the null hypothesis. Why? Because it is falling in the confidence interval region. Null hypothesis. So yes, this was it from my side. I hope you like this particular video. I will see you all in the next video with the new test, which is called as T. Hello guys, so we're going to continue discussion with respect to statistics, and in this video we're going to discuss about student T distribution. Now already in Z stats, right, in our previous video where we learned about Z stats and Z test, right, we saw that whenever we need to compute or whenever we need to do any analysis, right, so here when we need to perform any analysis using Z score, what do we require? We require a population standard deviation. We require sigma, which is nothing but population standard deviation, right? And this is already known, like in our problem statement, this is already known, right? But understand, in many of the problem statements, right, one thing that you really need to understand over here is that population standard deviation is very difficult to get calculated or to get assumed also, right? It is very difficult to do that because we don't have the entire population data, right? So my question now is that how do we perform any analysis when we don't know the population standard deviation? If we don't know this, then how do we perform any analysis? Okay, so this is the question. And in interview, someone asks you, yes, for this kind of scenario, we use students T distribution, right? So in this case, whenever you don't have a population standard deviation, then you should definitely use student T distribution. Now with respect to this, how the formula changes. Initially, using Z score, my formula was something like this, right? X bar minus mu divided by standard deviation by root n, right? But in this case, based on the T distribution, my formula will look like this: X bar minus mu divided by sample standard deviation divided by root n. Okay, so this is how my new formula will look like. Over here, we don't have population standard deviation, and this S is nothing but sample standard deviation. Okay, so this is the formula we will specifically use with the help of t-stats. Okay, now one very important thing. Along with this, there is also one very important parameter, because see, in Z, when we are doing Z stats, we use something called a Z table to find out the area under the curve. And probably in this kind of scenario, in student t distribution, we will be using t table. I will show you how the t table will look like. And in t table, there is one more very important parameter, which is specifically called as degree of freedom. Okay, and degree of freedom, DOF, is basically given by the formula n-1. We'll not derive this, not that important, but I'll just give you a crux how a degree of freedom is basically coming up. Let's consider there are 3 people, and there are 3 chairs in a room. Okay, now when the first person comes inside the room, this person has 3 different options, right? So let's say that out of the 3 options, he has selected this chair. Then the second person will come, he'll have 2 options. Let's say he's selecting this chair. But what about the third person? In third person, he'll not even have any options. So in this case, when 3 people are there, only 2 people are having options. So in this scenario, my degree of freedom is nothing but 3 minus 1, 2. So this is how a degree of freedom is basically calculated. And this will be super important when we are probably using this in doing any analysis with the help of t-test. Okay, we specifically say this as t-test, or we can also call this as t-stats. Okay. Okay. So I hope you understood this. Now let me just quickly show you how my PDF will look like. Okay, this is basically my t-table. Okay, now in this t-table here you can probably see on this axis, right, I have whether it is a 1-tail or 2-tail test, and here you'll be able to see all the values based on the confidence interval, right? But on this axis, on the row wise, you can see there's a degree of freedom. So if you clearly see over here, there is a degree of freedom, and with respect to different sample size, you'll be able to calculate different values and area under the curve, right? So in the next video, we'll try to see how we can probably we solve a t-table problem, t-stats problem by using this t-table, and we'll try to see what kind of output we'll be able to get and what kind of analysis we'll be able to do. So yes, this was it from my side. I will see you all in the next. Hello guys, so we'll be continuing the series with respect to stats. In this video, we're going to discuss about t-stats and t-test. Okay, and already we have seen in a previous video about z-test, how did we calculate it, what formulas we used. Understand the point, the difference between z-test and t-test is that whenever you have a population standard deviation and when your n value is greater than or equal to 30, please try to use z-test. We have to use z-test. I'll not say please, but we have to use z-test to do any kind of analysis. But let's say if your population standard deviation is not given, then at that point of time you can use t-test. So let's quickly go ahead and let's try to understand with this particular question. And this question, in this t-test, there is a problem which is called as one sample t-test. We'll try to solve this. Okay, and by this you'll be able to get an idea like how you can solve or how you can do analysis using the t-test. So in the population, the average IQ is 100. A team of researchers wants to test a new medication to see if it has a positive or a negative effect on intelligence or no effect at all. So initially the average IQ is 100. Okay, so a team of researchers wants to try a new medication and give it to the people to see whether there is an effect on intelligence, whether it is increasing or decreasing. See, whenever I say increasing or decreasing, this becomes a 2-tail test. Okay, always remember that. A sample of 30 participants who have taken the medication has a mean of 140. See, initially 100 it was, and when we took a sample, it is nothing but 140 with a standard deviation of 20. Did the medication affect the intelligence? So this is what we really need to check. Okay, and over here we are going to initialize our alpha value, or I can also say my confidence interval value, to 95%. When I say 95%, my alpha is nothing but 0.05. Okay, now let's try to solve this problem and let's see what all information we can basically take out from it and what kind of analysis we can do. But in short, we are probably doing an analysis on this sample data to probably conclude whether the intelligence has increased or not. Okay, so let's start this problem statement. So first thing first, first step is always to write all the parameters that you have. Mu is equal to 100, so you can see the average IQ. So your population standard deviation is not given, right? If population standard deviation is not given, you have to use t-test. A team of researchers wants to test a new medication, blah 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 blah. A sample of 30 participants is there. So n is equal to 30. X bar is nothing but 140, and small s sample standard deviation is nothing but 20, right? So I have a mean of 140 with a standard deviation of 20. Okay, and we know our CI confidence interval is 95% and my alpha value is 0.05. So all this information is there. So the first step is with respect to what is your null hypothesis. Okay, very simple. So first step is basically talking about your null hypothesis. What is your null hypothesis over here? It will be h0. You can definitely see what is the basic assumption in this question. In the population average IQ is 100. So can I consider my null hypothesis to be mean is equal to 100, right? Now similarly, when I go with respect to the alternate hypothesis, this is nothing but h1, and over here my mean will not be equal to 100 because over here a team of researchers wants to test a medication to see if it has a positive or negative effect on intelligence or no effect at all. So either, like, from this analysis that we are going to do, probably we are going to get the average IQ more than 100, less than 100. So this becomes a 2-tail test. 2-tail test. Okay, now coming to the next one, very important step. Here you know your significance level, that is alpha 0.05, right? Now whenever you are given a t-test problem, I need to compute the degree of freedom, right? We have also discussed in student t distribution. Over there, with the help of this only, we will be able to see from the t-table, right, what is the area under the curve, right? So in this scenario, my degree of freedom is nothing but n minus 1, which is nothing but 30 minus 1, which is nothing but 29. Okay, now coming to the major step, which is called as decision rule. What decision rule we need to select based on the visualization diagram, right? So usually in this scenario, I will be getting a curve like this. Okay, let's say this is the curve. You know, you want 95% confidence interval. So this area will be having 2.5%. This area will be having 2.5%. Now we really need to find out the z-score by using t-table, right? And how much it is away from the mean. That we will try to find it out. Okay. Now in order to find it out, we'll use degree of freedom. We know what is my alpha. We know it is a 2-tail test. Now all I'll be doing over here quickly, I will go back to my t-table, right? So in this t-table, you'll be able to see that on the top here you have 1-tail, 2-tail. We know that it is 2-tail. My alpha value is 0.05. Now on this axis you see degree of freedom. My degree of freedom is 29. So if I probably go and select this last data is basically talking with respect to, not last, sorry, this one, 0.05 and 29. So I will be getting somewhere around 2.05, right? So this is basically my z-score value. In short, when I say z-score, how many standard deviation is away from the mean, right? That specific value, that 2.5% which is present in the extreme end. So finally I'll be able to see that it is having 2.045. So again, how did I do it? Degree of freedom 29. With respect to this, I'm seeing over here, and I'm probably checking out this, which is my alpha value. Okay. So again, repeating 2.0545, right? So I will go back over here. This will be my plus 2.045, and since this is symmetrical, I will be having minus 2.045. Right? Now when these values are there, now what is the assumption that we are going to make over here based on this decision rule? So this is basically very important assumption, right? The assumption is very much simple, guys. In this case, we will try to calculate the t-test, right? We will try to calculate the t-test, and based on the t-test, we need to really assume with respect to this decision boundary. So if my t-test is less than minus 2.045, that is in this region, or greater than 2.045, that is this region, right? Then what do? We reject the null hypothesis. In the last example, we did z-test when the population standard deviation is given. Now we will try to find out what is this t-test. Okay, so this is my decision rule. Okay, now let's go ahead and compute it. So my next step is calculating the test statistic. Okay, so here you have T formula, you know that we have discussed, sample standard deviation by root n. So we have all the values. X bar is nothing but 140 minus 100, sample standard deviation is 20 divided by root 30. So if I probably go ahead and calculate it, I've already done this calculation, you can try. I'm going to get somewhere around 10.96. Now this is my t test value, the t test value. So t is equal to 10.96. Now you know that this t, whether it is greater than 2.05 or less than 2.05, it is obviously greater than this. It is obviously in this scenario, right? It is obviously greater than this. So it may be falling in this specific region, right? So here I can write, since my t test value or my t value, since t is equal to 10.96 is greater than, how much is the value? Is greater than 2.045, right? 2.045. It falls in the extreme end, the rejection area, right? This area is basically a rejection area. You know this, right? It is a rejection area. This area is also a rejection area. And this area is basically my, this area that you will be able to see over here, this area is my approved area. So basically, my null hypothesis is 2 in this case, right? So I want to probably come in this particular area. But right now I'm getting somewhere around 10.96, which is greater than 2.045. So we have to reject the null hypothesis, right? So at the end of the day, what analysis we are able to make from here? That whatever medication has been used, that has affected the intelligence. So final conclusion is that medication used has affected the intelligence. Now since my t-test value is a positive value, which is at this end, and this median was basically my intelligence, right? 100 IQ, right? And we are getting somewhere over here. So definitely it shows this medication has increased the intelligence, right? So specifically, if you really want to know over here, the medication, I can also write, has increased the intelligence. And this is the conclusion we make out of this particular statement or this particular problem, right? So I hope you're able to understand about t-test. This problem statement is also called as one sample t-test, right? Further going ahead, we are also going to see examples with respect to chi-square, ANOVA, f-test and all. So yes, but I hope you got an overall idea with respect to this. You can definitely try with different problems. You can try with different confidence interval like 99% and all. That is up to you. But at the end of the day, you are doing some analysis, you are doing some kind of conclusions, right? So yes, this was it from my side. I will see you all in the next. Hello guys, so we are going to continue the discussion with respect to statistics. In this video, we are going to understand when to use t-test versus when to use z-test, okay? Already we have discussed about z-test, we have solved problems, we have seen how to basically check, how to come to a conclusions, the p-value, the significance value, there were so many things we discussed, right? Now let me make a systematic diagram for you so that you'll be always able to understand when to use t-test versus when to use z-test. First question, ask yourself, okay? Ask yourself whenever you see a problem statement. The first question should be that, do you know, let me write it in another color. Do you know the population standard deviation? Do you know the population standard deviation? Which is also, you can also specify this as sigma. Do you know this? Do you know the population standard deviation from the problem, from the problem statement that you have? So from here, I'm just going to make two routes. Okay, one is yes and one is no. Right? If it is yes and if it is no. Okay, if it is no, definitely go ahead and use t-test. Right? This is very much simple. So here I'm just going to specify use the t-test. Right? If it is yes, if you know your population standard deviation, then ask the question. Is the sample size above 30? If it is, then again over here, two scenarios, one is no and one is yes. Okay. If it is yes, if it is no, definitely use the t-test. Again, use the t-test. Okay. And if it is yes, use the z-test. This is just what you really need to follow. Now over here, one new thing that you're seeing, even though you have a population standard deviation, then you probably go ahead and check the sample size. Over here, the sample size n, if it is greater than 30, then use the z-test, otherwise use the t-test. So this is how you will be able to understand when to use t-test versus when to use z-test. So I hope you're able to understand. With respect to any problem statement, first of all, check whether population standard deviation is given. If it is given, go ahead and check whether the sample size is above 30. So with respect to all the previous problems that we have done, over there, you'll be able to see if population standard deviation is not given, we have used t-test. Even the population standard deviation is given and your sample size is greater than 30, then you have to probably go ahead and use z-test, right? So yes, in this video, this was a separate topic to discuss, and always it is good to know at what scenario what needs to be used. And it can also be asked in the interview. So I hope you like this particular video. I will see you all in the next one. Hello guys, so we are going to continue discussion with respect to statistics. In this video, we're going to discuss about type 1 and type 2 errors. Now till our previous videos, we have tested, we have done hypothesis testing with the help of z-test, t-test, and then we also made some amazing conclusions with respect to the hypothesis testing, considering whether the null hypothesis is true, whether we should accept it or whether we should reject it. So in reality, this is the thing, right? So see, over here I've written two important things, reality and decisions, okay? In reality, either the null hypothesis can be true or either the null hypothesis can be false. In decision wise, based on our hypothesis testing, we also find out whether we have to accept the null hypothesis, so null hypothesis will be true, or null hypothesis is false. So in reality, this is the condition. In decision, when we are doing the hypothesis testing, either of one of them are correct, okay? So let's go ahead and discuss about various outcomes that we may probably get. So let's say here I'm going to write outcome 1, okay? Understand one thing is, in reality, when we say, we are just saying that the null hypothesis can be true or it can be false. And then we say with respect to decision, that is based on our result of hypothesis testing. So in outcome 1, we can basically write, we reject the null hypothesis. Okay. When in reality it is false. So what the sentence is saying? We reject the null hypothesis. This is from our hypothesis testing. When in reality it is false. Fine. That is good, right? If in reality it is false, we are rejecting the null hypothesis. So this scenario is obviously a good scenario, right? Now what about the other scenario over here with respect to outcome 2? Okay. Now in outcome 2, I'm writing over here, we reject the null hypothesis when in reality it is true. See guys, in reality it is true, but we are rejecting the null hypothesis. So obviously there is a problem, and this is basically an error, right? This is an error because in reality it is true, But so for my hypothesis testing, I'm rejecting those null hypotheses. So this type of error is specifically called as type 1 error. Okay, type 1 error. This is super important because in machine learning there is a topic which is called as confusion matrix, and there also we'll be using this. Confusion matrix is used to calculate the error accuracy rate and all. Okay, so coming to the outcome 3 now. Outcome 3. Now in outcome 3, I can basically say we retain or accept the null hypothesis. We retain or accept the null hypothesis when in reality it is false. When in reality it is false. Okay. Now here, when in reality it is true, it had to be true. Okay. I wrote when it is true. Okay. Now in this scenario, we retain the null hypothesis when in reality it is false. So in reality it is false, but from our hypothesis testing, we are saying that let's accept the null hypothesis. Then this is also an error. So this specific error, we say it as type 2 error. Type 2 error. Now coming to the outcome 4. Okay. I'm also going to repeat outcome 2 guys because I made one writing mistake. We reject the null hypothesis when in reality it is true. In reality it is true, but we are rejecting the null hypothesis. For this kind of error, we say it as type 1 error. Now in outcome 4, we retain the null hypothesis when in reality it is true. When in reality it is true. So this is correct, right? In reality it is true, and from our hypothesis testing, we have accepted the null hypothesis. So this is also a good scenario, a correct scenario in short. Okay, correct scenario. So in this scenario, in both this scenario of outcome 2 and 3, we basically get errors, and these errors are basically called as type 1 and type 2 error. So this was about type 1 and type 2 errors. I hope you were able to understand. Now going forward, there's still many topics that we need to cover. Okay, we will be discussing about confidence intervals and all, how to create that range of confidence interval in the form of numbers. We're going to discuss about that. So yes, this was it from our side. I will see you all in the next. Hello guys, so we are going to continue discussion with respect to statistics. In this video, we are going to understand about Bayes statistics, and we are also going to understand about a very important theorem which is called as Bayes theorem. Now, Bayes theorem will be super important for machine learning algorithm which is called as naive Bayes, because this theorem is completely based on probabilities. Okay, so we'll try to understand what is Bayes statistics, and then we'll try to understand about Bayes theorem also. So to begin with, over here is the definition. Bayesian statistics is an approach to data analysis and parameter estimation based on Bayes theorem. So with the help of Bayes theorem, we will try to do data analysis. We'll try to even estimate the population parameter over here. Okay, so let's go ahead and understand with many examples about Bayes theorem and all. So in Bayes theorem, first of all, we need to discuss about the probability concept like independent events and dependent events. So whenever we talk about independent events, number one, we will talk basically about independent events. And obviously I will be showing you a lot of example independent events. Okay, so this will be independent event. The second one that you really need to know is about dependent event. Okay, so what exactly is independent event? So if I probably consider an example like rolling a dice, you know the outcome of a dice is 1, 2, 3, 4, 5, 6. Now from this you should know that the probability, whenever I roll a dice, the probability of 1 will be 1 by 6, the probability of 2 will be 1 by 6. Like this, any probability that you probably calculate with respect to any outcome, it will be 1 by 6. So here you can basically say all these events are independent because one event is not impacting the other event. The other example may be like tossing a coin. Right? Whenever we toss a coin, we get a probability of head. We get probability of head is equal to 0.5, and probability of tail we are going to get 0.5. So every time we toss, either one of this event will be coming. Okay, so the probability is equal. So one event is not impacting the other event. Like if probably head comes right now, the next event is not impacted. All the events are independent. Now if I talk about dependent events, this dependent events I can definitely show you with an example. Let's consider that I have a bag of marbles. I have 3 yellow marbles and I have 2 red marbles. Let's say in the first event, I try to take out a red marble. So what will be the probability of red? Right? So over here you have 2 reds and total number of marbles is 5. So you'll have 2 by 5. Now after taking out the red marble, let's consider that you want to take out a yellow marble. So now I want to take out a yellow marble. Now with respect to this, what will be the probability of yellow? Right? See, this event has already occurred. When this event has occurred, that basically means I'm taking out the red marble. So the total number of marbles that are left in the bag are 4. So if I now try to calculate what is the probability of yellow, it will be very much simple. It will be 3 by 4 because there are 3 yellow marbles and total number of marbles are 4. Now this kind of events are called as dependent event because after this event has occurred, you can see that it is impacting the other event since it has reduced the number of marbles from 5 to 4. Right? So in order to solve this dependent event, we basically use this. Right? How do we calculate a probability of red and yellow? That basically means first red event is occurring and then y event is occurring. So this one we can basically write it as probability of red multiplied by probability of yellow given red event has occurred. Okay, given this red event has occurred. So let me mark this in red color. Given red event has already occurred. This statement, this formula that we see is basically called as conditional probability. Conditional probability. Super important. Now based on this, so this is the equation that we have derived for a dependent event because one event is impacting the other event. Now what I'm going to do is that I'll write in a very generic format. Let's consider probability of A and B. Now I can also write this as probability of B and A because both are commutative, right? If I try to calculate it in this, now if I go ahead and calculate what is probability of red, it is nothing but 2 by 5 multiplied by 3 by 4. So this is nothing but 6 by 20. So this is the probability of red event and then occurring with after red, y event is basically happening. Okay, the yellow marble is basically here. Now let's go ahead and consider this. Probability of A and B, I can also write it as probability of B and A. Both are one and the same. Now with respect to this, I'll expand this equation. Now if I expand this equation, it will be probability of A multiplied by probability of B given A. Probability of B given A. Yes, we can expand this equation in this way based on this formula that we have. This will be equal to probability of B multiplied by probability of A given B, right? D event has already occurred. Now finally, I can probably write this as probability of B given A is equal to probability of B multiplied by probability of A given B, and this will go to the denominator. The probability of A will go to the denominator, right? So this equation that we get, right? This equation that we get, this is nothing but this is Bayes theorem. I'll make you understand what is the importance, okay, and what we can basically do with this. This equation is basically called as Bayes theorem. And the similar part of this equation I can also write like this. I can also write something like this. Probability of A given B is nothing but probability of A multiplied by probability of B given A. Why I'm writing like this? Because in most of the textbooks, they will be showing you this equation also. And this is also Bayes theorem. Okay, these both are one and the same with respect to different events. Here I've used A event and B event, both the notation. Okay. Now let's understand one very important thing. What are all these parameters? So first of all, A, comma B. These are nothing but events. Okay. And then if I probably write probability of A given B, it is nothing but probability of A given B is true. And I say B is true, that event has already occurred, right? Similarly, if I write probability of B given A, this is nothing but probability of B given A is true, right? So I've mentioned both of them, right? And similarly, if I probably write probability of A, comma probability of B, what are this? These are independent probabilities of A and B. right? Now let's go ahead and consider a data set. Okay, we'll try to understand in machine learning how it will be applicable, how it will be useful. Okay, let's consider I have a data set. Okay, this is my data set. Now I'll show you how this will be useful in machine learning. Let's say that I have some features like size of the house. Let's say I have something like size of house, number of rooms in the house, location. I have these three features, and I have one more feature which is called as price. Now, can I use this three feature to determine the price or to predict the price? Yes, we can do it with the help of machine learning algorithms. And this scenario over here, let me give a generic notation. Let's say that this is my x1, this is my x2, this is my x3, and this is my y. These three features that you see, like size of the house, number of rooms, and location, these are basically my independent feature, my independent or input feature, and this is basically my output or dependent feature. Right? We can use these three features to predict the price of this. Now, how using Bayes theorem I can basically use it, or I can predict price. So in Bayes theorem, we will go ahead and write the equation like this. Okay, and it is very much simple, guys. The same equation what was there over here in the same way I'll write. Right? Okay. So I'll go ahead and write what is the probability of y given x1, x2, x3. These events are already there. These inputs are already there. So I can write like this, and this will further be written as probability of y multiplied by probability of x1, x2, x3 given y, right? Divided by probability of x1, x2, x3. So this equation is a part of Bayes theorem. Okay, which is through Bayes theorem. Right? This entire equation is nothing but it is from Bayes theorem. And we will be probably using this to calculate the probabilities of y, which is my output feature, right? Super important formula. If you know this, the Bayes algorithm is done from your side. So I hope you are able to understand about Bayes theorem and how Bayes theorem equation looks like. So yes, this was it from my side. I will see you all in the next video. Hello guys, so we are going to continue discussion with respect to statistics. In this video, we are going to discuss about confidence interval and margin of error. Till now, with respect to confidence interval, we have discussed and we have solved problems with the help of z-stats, t-stats, t-test, z-test, right? Let's say if our confidence interval is 95%, right? Then we basically create this kind of line. If it is a two-tail test, we say that, okay, my values, if it is ranging between this range, this confidence interval, this part is 95%, this part is 2.5%, and this part is 2.5%. Now, whenever from a z-test or p-value, if it lies in this region, then we are going to accept the null hypothesis. Otherwise, we are going to reject if it comes in this two extreme end, right? But till now, we did not understand what value can come within this confidence interval, right? Initially, whenever we are trying to solve a z-stats or t-stats problem statement, there we have a sample mean, and we try to make some conclusion about the population mean, right? So in this scenario, I think we have discussed about this topic also, which is called as point estimate. Okay, if I talk about point estimate, let's say if I have an x bar value, this is my sample mean. X bar is the point estimate to probably estimate the population mean. Okay, to estimate the population mean. Now in this case, if I say my x bar is somewhere around 2.5. Okay, let's consider this is 2.5, and my mean is 3. Now 2.5 right now is less than 3, right? And sample mean x bar can also be greater than 3. Okay, some of the scenarios where we are picking up different samples. In both this case, you will be seeing there is a difference, and that is the problem of using point estimate. So what we should do is that we should define some range of confidence interval. I can basically say that my point estimate lies between 2 to 4. If I say like this, right, then probably we can represent this estimate of an unknown population parameter, right? So for this case, we specifically use important confidence interval. We basically say it as confidence interval. Okay. Now in this confidence interval, we are going to define some intervals with respect to the confidence level, right? Interval basically means some lower confidence to higher confidence. And for determining or for specifying this confidence interval, we use a formula. And the formula is very simple. The formula is point estimate plus or minus margin of error. Margin of error. Because we know that our point estimate will obviously be a little bit less, or it can also be more, or it can be approximately equal to the population mean. So for defining the confidence interval, we will specifically use this particular formula. Over here, the point estimate is nothing but x bar plus or minus. How do we calculate margin of error? So for this, we use z alpha by 2. This is just for a z test, so that we can actually look over the area under the curve by using that z table. And further, we multiply this by sigma divided by root n. If it is a z test. If it is a t test, then we will probably use t over here, t alpha by 2. And again, over there, you need to calculate the degree of freedom. Okay. Now, let me just show you one example, and let me just show you that how we can probably calculate it. I'll just take a very simple example, and we'll try to calculate the confidence interval. So the example is on the verbal section of CAT exam, the standard deviation is, now if population standard deviation is given, what I have to use? I have to use z test, right? Is known to be 100, right? A sample of 30 test takers has a mean of 520. Construct 95% confidence interval about the mean. Now we need to find out this range. And how do we find out this range? We'll try to see. Okay. Now on this, what we can basically do is that we can first of all assume the formula, right? Over here, we know my formula is x bar plus z alpha by 2, and this is standard deviation by root n. Now what is z alpha by 2? We know the alpha value is 0.05, right? So alpha by 2 will be nothing but z 0.025, right? So over here, let's go ahead and calculate, right? Now with respect to z alpha by 2, first of all, you need to know what is the z alpha by 2, right? This is basically, whenever we say alpha by 2, we are considering this as a two-tail test. This is 95% confidence interval. This is 2.5%. This is 2.5%. And we have seen so many times the z table. What is the area for this entire? If I really want to find out this area, what I will do? I will calculate this area minus this, right? Now with respect to this area, right? It is nothing but 1 minus 0.25. Sorry, 0.025. 0.025. And we know what it will be, 0.9750. And with respect to this, the area under the curve of 0.9705 is 1.96, which is my standard deviation, right? So over here, I'm going to get 1.96. How did this come? This is from the Z table. Just go and check where does 0.9750 area under the curve lie. You'll be able to see it is nothing but 1.96. If this is plus 1.96, then this will be minus 1.96, right? Now we'll go ahead and calculate. The first scenario is the lower confidence interval, lower CI. What is my x bar in this case? It is nothing but 520, right? The mean is that much. This will be 1.96 multiplied by 100 divided by root 25. So if I probably calculate, I'll be getting 480.8. If you go ahead and calculate this, 480.8. Now similarly, I will go and compute my higher CI. Higher confidence interval, it will be nothing but 520 plus margin of error, obviously 1.96, 100 divided by root 25. And here I'm going to get 559.2. Now this is saying that my confidence interval lies between these two values, that is 480.8 and 559.2, right? So the final assumption that I can probably make, okay, I'm 95% confident that my CAT score CAT exam score, the average CAT exam score will be lying between 480.8 and 559.2 because this is the confidence interval. This is what we are deciding. If my value is within this confidence interval and in this region, then we are going to accept the null hypothesis. If it is away, I'm going to reject the null hypothesis, right? So here finally, in conclusion, with respect to this, I can say that I am 95% confident about the mean. The CAT score is between 480.8 and 559.2, right? So I hope you're able to understand from this, from using the confidence interval and margin of error. This specifically is the margin of error. With respect to t-test, instead of using z-table, you'll be using t-table. The formula will be same like this, okay? So this is how you can probably calculate the lower confidence interval and high confidence interval by using the margin of error. So I hope you like this particular video. I hope now you're able to understand what exactly confidence interval is. How do you determine that value, that range, okay? So yes, this was it from my side. I will see you on the next. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about a new test which is called as chi-square test, an amazing test techniques for categorical variables. So we'll try to understand what exactly chi-square test does, and we'll also try to see with some examples so that your understanding becomes clear. In the next video, we'll try to solve a problem statement. Okay, so to begin with, first of all, chi-square test. We also say this as chi-square test for goodness of fit, right? For goodness of fit. We also say this specific word for most of the chi-square tests that we do. This test claims about population proportion. Okay. Whenever we talk about proportion, that basically means we need to think about categorical variable, okay? And if I probably try to define chi-square test, it is a non-parametric test. It is a non-parametric test that is performed on the categorical data, okay? When I say categorical data, two types of data we have in categorical specifically, ordinal and nominal data, okay? Nominal data. Now let's see some example, okay? And by that, obviously, you'll be able to understand what exactly chi-square test of goodness or for goodness of fit is, okay? Now, with respect to example, let's consider that there's a population, okay? There's a population of male who likes different bikes, who likes different color bikes. Okay. Now let's say over here, the first bike that we specifically have, let's consider that there is a so there are bike colors. So this is a yellow bike, okay, and this is a red bike, and let's say there is an orange bike. Okay. I know this color will want whether it exists or not. I don't know with respect to the bike, but let's see. Okay. Now with respect to this, there's a population of people male, and there's a theory. Let's consider there is a theory which says that. Theory about the population. Okay, it says that 1/3 people male like basically yellow bike, 1/3 is they like a red bike, and 1/3 they specifically like orange bike. Okay, orange bike. So here I will say orange bike. Let's say this is the theory. Okay, this is the theory about the population. Yeah, someone had made this theory. Okay, then what has happened is that they have probably collected a sample and they found out that from the sample 22 people specifically like yellow bike, 17 people like red bike, and 59 people like orange bike. Okay. Now, when this sample data is there, when the sample is present, right? Now, what we need to do with the help of chi-square test is that we will try to see whether the sample information is a goodness of fit test for the theory, right? So over here, specifically, the problem that we will be solving how the goodness of fit test. The goodness of fit test basically means with respect to the sample information that we have collected, does it supports the theory that is present over here? Okay. So this is what we are basically going to do with the help of chi-square test. The theory part that you probably see, right? This is nothing but this is called as theory categorical distribution. Okay, theory categorical distribution. And this part that you probably see, this is nothing but this is called as observed categorical distribution. Super important because by using this theory and observed only, we'll be doing the distribution or we'll be doing the goodness of it. Okay. Now let me just show you one very good example with respect to a problem statement so that you will definitely be able to understand more about it. But we'll not solve the problem statement right now. We'll solve it in the next session. Right? I don't want to make this video much longer. So let's talk about goodness of fit test. Okay. And I have a problem statement. Let's say in a science class of 75 students. Okay. 11 are left-handed. 11 are left-handed. Okay. Does this class, okay, fit the theory? Now see this is how the question will be asked. Fit the theory that 12% of the people are left-handed. So we definitely have a theory about the population saying that 12% of the people are left-handed. So how do we basically go ahead in calculating the theory categorical distribution and observed categorical distribution? The theory and observed information needs to be there. So first of all, the information that I have is specifically like this is left-handed. Okay, this is right-handed. Okay, so these are obviously my two categories. So here you can definitely see that it is basically saying 11 are left-handed. So observed is basically 11 are left-handed and remaining 64 are right-handed. So this is what I'm actually going to get the total 75 people. Now with respect to the observed, we have definitely seen that 11 are left-handed and 64 are right-handed. Now how do I calculate my expected value, right? So you can see, does this class fit the theory that 12% of the people are left-handed? So the expected value will get derived from here. How do I derive it? It's very simple. It is saying 12% of the people are left-handed. So if I probably write 12 by 100 multiplied by 75, then you will be able to see that what is the value that I'm going to get? 4 3s are 4 25s are 21 1s are 21 3s are. So total it will be 9 people, which will be the expected value. And remaining all will be right-handed. So definitely 9 plus 66 if we do, it will be 75, right? So this is my expected value based on the theory, right? This entirely is the expected value based on the theory. Now I need to do a chi-square test, making sure that whether this observed value is the goodness of fit for the expected values. Okay, this is what we are going to compare, and definitely there's a formula that we can probably use to do the chi-square test, which we will be doing a specific problem statement in the next video, right? But here, in short, whenever we talk about chi-square test, we are comparing two categorical variables, and this categorical variables will be in terms of theory categorical distribution, observed categorical distribution. So I hope you are able to understand about chi-square test and what exactly goodness of fit test is. In the next problem statement, we'll try to do it. We'll try to solve the problem, and after that, we'll also see how we can do it with the Python programming language. So yes, this was it from my side. I will see you all in the next video. Hello guys, so we are going to continue discussion with respect to statistics. In this video, we are going to solve a problem or perform hypothesis testing using chi-square test, which is also called as goodness of fit. Okay. Now let's go ahead with this particular question and let's see what all information we have, and then we'll follow step by step to solve this hypothesis testing. Okay. And for this, we really need to use a table which is called as chi-square table. Okay. So in 2010, the census of the city, the weight of an individual in a small city were found to be the following, right? Less than 50 kg, 50 to 75, greater than 75. Like less than 50 kg were 20%, 50 to 75 were 30%, and greater than 75 was 50%. Now in 2020, the weights of n is equal to 500 individuals were sampled. Now see, in 2020, you have sampled the weights, right, of some 500 individuals, and below are the results. Okay. Below are the results. Now in this particular case, you will be able to see that less than 50 is 140, 50 to 75 is 160, and greater than 75 is 200. If we sum it up, it is basically 500. Now, based on this sample, we need to see whether there is a population difference with respect to 2010 and 2020. Okay, so using alpha is equal to 0.05, would you conclude the population differences of weights has changed in the last 10 years? And remember, this is my sample data, and with this, I want to make an assumption of the population in 2020. Okay, this is what we are doing, and for this, we will specifically use chi-square test because I have 3 categories. Okay, now let me go ahead and let me show you how we can solve it. First of all, I will take this data. This is my 2010 data. Okay, this is my 2010 data. So let's go ahead and write it down over here. So this is nothing but my 2010 data, and this data I will say it as expected data. Okay, this is the original data or population data that we have with respect to the information. Right now, coming to the next one, which was this sample data. This data we usually say it as observed data. Okay, so this data is of 2020, and this is basically my observed data. Okay, and this is for sample n is equal to 500. Okay. Now, with respect to this observed and expected, see, expected is still in 20%, 30%, 50%. But if I say what would be the expected data in 2020 based on this sample, okay, so what I will do, see, I'll copy the same thing. See, or I'll make a bigger cell so that you'll be able to understand. So let's say this is my cell, and now I really want to form my expected data based on the new sample that I have. Right? If the sample was same, so less than 50, 50 to 75, and greater than 75. Now in this case, when I try to find out my expected data, how do I find out? See, in 2010, 20% was expected before less than 50 kg, and over here I have 140, right? From this samples, but original expected was how much? It was simple. I will just multiply 0.2 multiplied by 500. So this is nothing but 100, right? Now coming to the next cell, 50 to 75, right? Now in this scenario, you can see in 50 to 75, over here you'll be able to see from the sample 160 is there, but my expected was 30%, right? So I try to multiply 0.3 multiplied by 0.160. Okay, sorry, not 0.160, 500 because my sample size is 500. So here I will probably be getting how much? 150, right? And finally you'll be able to see over here it was 50%, so I'll multiply with 500. So the total I'm going to get is 250. Now this is my expected information, right? Based on this sample, considering the 2010 census, right? Now what I'm going to do over here is that based on this problem statement, I'm going to now apply chi-square test and find out whether whether there is a difference between 2010 and 2020 census with respect to the observation of weights. Okay. So the next step, what we'll do, obviously, we'll go ahead and write down null hypothesis. Now null hypothesis is very simple to write in this case. So my null hypothesis is saying that at 0, the data meets the expectation. Okay. Then what is my alternate hypothesis? So obviously my alternate hypothesis will be H1, and it will be the reverse of that. The data does not meet the expectation. It is the same thing, right? It meets the expectation, does not meet the expectation, right? That is what alternate hypothesis will be. Now the second information that I have, I always know my significance value. It is nothing but 0.05, so I can also derive my confidence interval. My confidence interval will be 95%. Okay. Now the next thing in chi-square test is that when you observe the chi-square table, you also need to calculate the degree of freedom. So the degree of freedom over here, in order to calculate, I have to take df is equal to number of categories minus 1. So how many categories I have? 3 minus 2, right? Minus 1 is just 2. 3 categories I have. 1 category, 2 category, 3 category. Okay. Now this is clear. Okay. Now the fourth step is basically called as decision boundary. Now see guys, in z-test and t-test, whatever things we used, we specifically use a symmetrical distribution. But in case of chi-square test, we don't have a symmetrical distribution. Instead, our distribution will look something like this. It looks something like this. Okay. Now we need to find out one critical value. Okay. Based on this, right? My critical value. Based on what? Based on my significance level. So this will be 0.05 and this will be 95% confidence interval. Okay. So I have to find out this critical value, and if my test statistics, whatever chi-square test statistics I apply, if it is greater than this critical value, then we reject the null hypothesis. If it is present in this particular area, then we accept the null hypothesis. So this part is basically called as rejection area, and this part is basically called as acceptance area, right? So this is what we are coming up with, and this thing, from where do we get the critical value? For that, we will be using degree of freedom and this alpha value, and we'll check it from our chi-square table. Okay. So let's go ahead and see with respect to the chi-square table, and you'll get an idea like how does the chi-square table look like. Okay. So this is how a chi-square table look like. You can just go and search for chi-square table PDF, and you'll be able to get this. Now here you can see on the top, you all have that significance level value. So right now my significance is 0.05. My degree of freedom over here is 2. So based on this, I'm going to get 5.991. Right. So over here, my critical value is nothing but it is basically 5.991. Now I can make an assumption saying that if my chi-square test is greater than, chi-square test notation is given like this, 5.99, we will reject the null hypothesis, else we fail to reject the null hypothesis. So what I'm saying that if I get a chi-square test greater than this critical value, so my critical value is nothing but 5.991, then we are going to reject the null hypothesis because we are coming to this extreme end. This area is the acceptance area. Okay. Now let's go ahead and calculate the chi-square test. So this is my fifth step. We calculate chi-square test statistics. Okay. Now in order to calculate, I have this value sigma observed minus expected whole square divided by expected. Okay. So this is the entire formula of chi-square test statistics. Again, I'm going to repeat summation of observed minus expected whole square divided by expected. So we are trying to compare the observed and expected values. So over here, what I'm going to do, I'll just copy this both data that I have and I'll paste it over here. Okay. Let's see. So for pasting, and I'll make it a little bit small so that we'll be able to see the data properly. So here is my data. Okay. Here is my data. So if I probably see this, here is my data. Now with respect to this, I will go ahead and do this. Okay. Understand this value is observed, this value is expected. Okay. So I'll write summation. So over here, 140 observed minus expected. So 140 minus 100 in the 50 range. Okay. So it will be whole square plus observed 160 minus 150 whole square plus 200 minus 250 whole square. Now every term will get divided by your expected value. So this will be 100, this will be 150, and this will be 250, right? Further we go ahead. So this will be 1600 divided by 100 plus it will be 100 divided by 150 plus it will be 50 square, 2500 minus 50 square divided by 250. So finally, you'll be able to see all my values over here, and we get nothing but 16 plus 0.66 plus 10. And overall, if I see the value, it will be nothing but 26.66. So my chi-square is nothing but 26.66. Now we'll go over here and again talk about my decision rule. Now my decision rule said that if my chi-square is greater than this 5.99, right? If my chi-square is greater than 5.99, we reject the null hypothesis. So what we are going to do, we are going to compare. Over here, 26.66 is obviously greater than 5.99. That basically means it falls in this region. See, 5.99 greater than 5.99 in this region, right? So what we do, we specifically reject H0, right? We reject the null hypothesis, right? So finally, what kind of, or we can also write like in this, right? Let's say if this value was less than this, we will say that we failed to reject the null hypothesis. Okay. So finally, our answer or our conclusion is that the weights of 2020 population are different than those expected in the 2010 population. So this is the assumption we are actually making, and obviously just by seeing the table also, right, you can understand that there is obviously a huge difference, right? In 2020 and in 2010, right, there is definitely a very good amount of difference, right? So yes, this was it from my side. I hope you like this particular session. I will see you all in the next session. Hello guys, so we are going to continue discussion with respect to statistics. In this video, we are going to discuss about analysis of variance, which is also called as ANOVA. Okay, a super important statistical method. First of all, we'll try to understand the definition, and we're going to understand the important components of ANOVA. Then in the upcoming video, we're going to understand about the assumptions and the types of ANOVA. So let me go ahead. Again, this series of ANOVA will be divided into many parts, guys. So be calm, study properly, because this is also a very important test which can be used for, when you become probably a data analyst or a data scientist. Okay, so first of all, let's go ahead and understand the definition. Okay, why is ANOVA test used and what is ANOVA in short? Okay, so ANOVA is a statistical method used to compare the means of two or more groups. Super important point which I've written over here. Okay, that is, it is used to compare the means of two or more groups. Now, till now, like if you have two means of two groups, right, or we specifically use Z-test, T-test, right? Now in ANOVA, like whenever you have a group, right, means of two or more groups, like let's say you have 3 groups, 4 groups, and you want to analyze or you want to compare those specific groups, you can definitely use ANOVA. Okay, so and again we'll see a lot of problems as we go ahead. But with respect to ANOVA, there is a very important 2 components. Okay, and probably we will be seeing in most of our questions. Okay, with respect to ANOVA, the first component is something called as factors. Okay, factors, and these factors can be independent, it can be dependent. Okay, and I'll talk about what is independent and dependent in the upcoming video when we talk about assumptions and types of ANOVA. But here I'm going to give you some examples so that you will be able to follow. Now coming to the second type, whenever we talk about ANOVA, right, after factors you have something called as levels. Now in order to understand this well, I will definitely take an example. Let's consider that I have medicines, right? Let's say a person is having medicines. Okay, specifically one kind of medicine. Okay, let's say that there's a medicine, and this medicine I can call this as a factor. Okay, factor. Now with respect to this medicine, right? Now you know that let's say there is a medicine. Some people will probably have 5 mg of medicine. Second people will have 10 mg. There are other group of people who has 10 who have this 10 mg of medicine, and there may be 15 mg of medicine. Now with respect to this, right? What is this? If I probably talk about this, these are nothing but dosage, right? Dosage, right? So this example, when I say medicine is a factor, this component that you probably see where you have multiple different dosage, these are my levels. Okay, so I hope you're able to understand, right, what exactly factor is, and within this factor you may have different levels, right? One more example, a very good example in the real world scenario, right? Mode of payment. Now when I talk about mode of payment, this is also a specifically factor. Okay, but with respect to mode of payment, you have different options. Like some people pay using Google Pay. Like if you don't know about Google Pay, it is a UPI transaction. Let's say you are doing it by phone pay, right? You have IMPS, you have NEFT, you have different ways like demand draft and all, right? Now in this particular case, mode of payment is definitely a factor, right? But when we talk about all these other things, these are nothing but these are levels, right? These are levels. Okay, so I hope you have understood what is the difference between factors and levels. I still did not talk about what is the difference between independent factors and dependent factors. That I will probably do it in my next video after we discuss about the assumptions. But I think you've got an idea about what exactly is ANOVA with respect to definition to compare the means of 2 or more groups. And in this, you specifically have factors and levels, and that is how our data set will be available in that form. Okay, so I hope you were able to understand this video. I will see you all in the next video where we discuss about the assumptions of. Hello guys, so we are going to continue the discussion with respect to statistics, and in this video, we are going to see the assumptions in ANOVA. Already we've understood with the help of ANOVA what we can do. We've understood about factors and levels. Now there's some assumptions. If your problem statement satisfies these assumptions, you can definitely go ahead and use ANOVA. Okay. Now usually when we discuss about Z-test and T-test, we consider, right, some of the assumptions like a sample distribution will probably be normally distributed, and along with that we saw in chi-square test, right, your distribution was right skewed. Similarly in ANOVA, you have many more assumptions. Many more basically means 3 to 4 assumptions which you definitely need to know. This can also come in form of interview questions for all of you. Okay. Now coming with respect to the first assumption. The first assumption is something called as normality of sampling distribution. We'll make you understand what exactly this is. Normality of sample distribution of means. Whenever you think about, or whenever you hear this term, sampling distribution of mean, right? And when you think about normality, it's definitely central limit theorem should be coming in your mind. What does this basically mean? This basically means the distribution of sample mean is normally distributed. Okay, super important. And I hope you all know what exactly when I say normally distributed basically means. You should follow a Gaussian distribution. Coming to the second point. Now, absence of outliers. This is also super important topic, right? Absence of outliers. Now, the outline score, even though you have outliers in your data set, it needs to be removed, right? So outline score need to be removed from the data set. Okay, so even though you have an outlier, you have to remove the outlier from the data set, and it can be through multiple techniques like box plot, interquartile range, many more things are there. In future engineering, we'll be discussing about that. Okay, now coming to the third topic, right? Third important assumption, that is nothing but homogeneity of variance. Okay. Now homogeneity basically means homogeneous, right? So whenever we talk about population variance in different levels of each factor, in different levels of each independent variable or factor, independent variable, it should be same, right? Same, right? Are equal. I'm basically writing as equal. So in short, I can also give this notation as sigma 1 whole square is equal to sigma 2 whole square equal to sigma 3 whole square, right? Let's say if I'm considering this in the form of 3 levels in an independent variable, then your population variance should be same. Okay. So again, I'm repeating it. Population variance in different levels of each independent variable are equal. Okay. We'll talk about more independent variable, but just a generic term, independent basically means one variable not impact on the variable, right? So this is basically called as independent variable. Okay. Now coming to the fourth and the last assumption, which is also very important, that is samples, whatever samples are taken, they are independent and they are randomly selected. Okay, so I will write and random. So these are some 4 assumptions in ANOVA. Remember these assumptions because this can be asked in the interviews. I've heard about some of the students getting this question in the interview itself, and it is better that you basically know these assumptions. Again, I'm repeating it. First one is normality of sampling distribution of mean. This basically means the distribution of sample mean is normally distributed. Second, absence of outliers. So this basically means outlying score needs to be removed from the data set. Third, homogeneity of variance. Population variance in different level of each independent variable are equal. Fourth, finally, which is the last one, that is samples are independent and random. Hello guys, so we are going to continue discussion with respect to statistics, and in this video we are going to discuss about types of ANOVA. Now already we have seen about factors, levels, you've got some understanding about the assumptions. Specifically whenever I talk about types, there are specifically 3 types of ANOVA, and with respect to this kind of types, you will definitely be getting in a problem statement, okay, which we will probably solve in the next upcoming videos. Number 1, which we specifically say as one-way ANOVA. Now in one-way ANOVA, right, with respect to the data set, you have one factor with at least 2 levels, and these levels are independent. I will show you one example so that you'll be able to understand now what does this independent basically mean. Okay, so let's consider this. Okay, let's consider a doctor. Okay, I'll give you this example. Doctor wants to test a new medication, okay, to decrease headache. So you have a headache and doctor wants to try a new medication. So what they split the participants in 3 conditions. Okay, or 3 groups, we can basically say. One is with 10 mg of dosage, one is with 20 mg of dosage, and one is with 30 mg of dosage. Okay, so they are definitely a new medication, but with this many number of dosage. Okay, then doctor also asked the participants. So doctor asked the participants to rate the headache between 1 to 10. Okay, so this is basically what the doctor specifically wanted. Okay, now in this scenario over here, obviously with respect to the factor, when I talk, medication will be your factor, and with respect to the medication, let's say the dosage that you are probably seeing, this will basically be my levels, right? So these are my levels. This is the medication is the factor. And one more very important thing is that the levels are independent. See, this dosage of medicine is independent to this dosage. There's no way relationship. These both are different medication. Now with respect to this, there will be some sample of people. Let's say they had this particular medicine and they're giving the rating as 5 between 1 to 10. This can give 7. This can probably give 2. This can give 3, 4, 6. They can give different values based on the effect of the medicine, right? So this is what specifically we talk about when levels are independent. Okay, and medication over here is definitely the example of that. Now let's go to the second type. Okay, second type is basically called as repeated measures ANOVA. Okay, now repeated measures ANOVA, here you have one factor with at least 2 levels, and here you can basically say levels are dependent. Okay, so I hope you have understood this. Levels are dependent. Now let's see with respect to this particular example. Let's consider I'm talking about running. Okay, now this running, well, let's consider this is a factor. Now with respect to running, right, if I've selected a sample of people and I'll tell that try to run day 1 and day 2 and in day 3. So the same person is actually running for in the day 1, day 2, day 3. So here now you can see the levels are dependent because the same person is running. First day he or she may run 8 kilometers, second day 5 kilometers, 4 kilometers, like that. We go to the next row. Let's say the next person probably runs 7 kilometers the first day, then 4, then 9. So this kind of combinations, they may have different data, right? But in this case, you can see these levels that you see, right? These are my levels. These levels are dependent, right? Because day 1 probably your performance may not improve in the day 2, it may improve in the day 3. Like this, you have some data, right? And obviously at least 2 levels are there. So here you have more than 2 levels, 2 or more than levels, right? So this is with respect to the example of repeated measures ANOVA. Now coming to the third type, okay, which is basically called as factorial ANOVA. So this kind of data sets will be available to you. Factorial ANOVA. Now in the case of factorial ANOVA, you specifically use 2 or more factors, each of which with at least 2 levels. Okay, with at least 2 levels, and these levels can be independent or dependent. Okay, so here what we are basically saying, 2 or more factors. Obviously when we say factors, let's consider an example. Now the same example I can consider, right? Let's consider this running example. So I have this data, or I have this data. Let's say this is my running data, and this is the running data. One factor is present over here. I will have different values like 9, 4, 3, 2, 4, 6, 7, 8, 3, right? Let's consider this. Now this is one of my factor, obviously, and these are my levels. Now we can have one more factor over here, right? Let's consider gender as one factor, and here I'll try to split the gender based on male and female. let's consider that this data that you see over here, the top two data specifically with respect to the mean. So this is definitely one factor. This is my another factor, right? Now with respect to this particular factors and levels, gender is one factor. So this is specifically one factor, and these are my levels, right? And over here running is one factor, and these are my levels, right? Day 1, day 2, day 3. So level can be independent and dependent. So here you can see that it is dependent. Here you can probably see it as independent. Male and female are completely separate entity. So two or more factors obviously you have taken an exam. So whenever you get this kind of data set, probably we can definitely consider it as a kind of factorial ANOVA. So I hope you got an idea about the three types of ANOVA. Again, a very important interview question. Whenever someone asks you with respect to that, you should be able to explain this, right? So this was it from my side. I will see you all in the next video. Hello guys, so we're going to continue the discussion with respect to statistics, and in this video we're going to discuss about how to perform hypothesis testing in ANOVA. So I can also give it something called as partitioning or variance in ANOVA. So already you know in ANOVA what do? We specifically compare mean of two or more groups, and we consider variance in that specifically. We'll discuss about like how the hypothesis testing is performed step by step, and we'll also solve a problem with respect to this. Okay, so to begin with, what happens is the first step is that we basically define our null hypothesis. So null hypothesis, as you know, we compare the mean of two or more groups. So my null hypothesis is nothing but mean 1 is equal to mean 2 is equal to mean 3 based on how many number of samples we have, mean k, right? So this is basically our null hypothesis where we are comparing whether all the means are equal or not. Okay. Now coming to the alternate hypothesis. Now alternate hypothesis is specifically, we can also go ahead and write it like h1, and here we are basically going to say at least one of the mean is not equal. Okay. One of the sample mean. Okay. One of the sample mean is not equal. Okay. Is not equal. Now you may be thinking, Krish, why can't we just write a notation something like this? Mu1 is not equal to mu2 is not equal to mu3 or up to mu k, right? Is not equal. Can we write like this? Understand one thing, guys, we cannot write like this because in this case, right, we are strictly saying that all the means are like one mean is not equal to the other mean is not equal to the other mean. But here above I've just written at least one of the mean is not equal. Okay. Now with respect to performing this, we specifically use a test statistics which is called as F test. Okay. So the kind of test statistics we use, it is basically called as F test. So here we basically use F test, and the formula is very simple, guys, but it will definitely take a lot of steps to basically do the F test itself. So F test is nothing but it is basically the variance between samples. Variance between samples divided by variance within sample. Okay, within sample. I will make you understand what exactly this means. Okay, variance within the samples. Okay, so this is basically the F test. Now let me go ahead and explain you. Let's say that I have three samples: x1, x2, x3. Okay, and let's consider with respect to this x1, I have 1, 2, 4, 5, 3. Okay, these are the elements that I specifically have. In x2, let's consider that I have elements like 6, 7, 3, 2, 1, and in x3 I have probably 5, 6, 3, 2, 4. Okay. Now let's consider this three samples, and I need to probably test whether the mean of the sample is equal or not. Okay. Like I really need to compare all the means with respect to the sample. Okay. And perform probably a F test as such, right? Now in order to make you understand about this two important thing, that is variance within the sample and variance within the sample. At the end of the day, this mean is basically getting compared based on the variance that is present, right? So when we say variance within the sample, what does this basically mean? This is basically the differences between variance between your samples over here, right? So here this is nothing but variance between samples. Okay. So in short, you probably calculate the variance of each sample, and then you probably try to find out the difference with one sample and the other sample. Okay. Now similarly, we can probably go ahead and talk about this, right? This over here, we can also say variance between, not between, within samples. Now variance within samples means what? Okay. Understand these things. Let's say that I have probably calculated the mean. Let's say this x1 bar for this is like 1 plus 2 plus 4 plus 5 plus 3 divided by 5. It is nothing but 3. Okay, you probably calculated. X2 bar is 7 plus 6 plus 3 plus 2 plus 1 divided by 5. Quickly if I do it, it is somewhere around 19 by 5. And similarly, if I go ahead and write S3 bar, it's 5 plus 6, 11, 14, 20, and this will be nothing but 4. Okay. Now in this case, when you say variance within the sample, so within this particular sample, if I have, see at the end of the day, what is standard deviation? Standard deviation basically means like variance is basically given by sigma square, right? If I talk about standard deviation, it basically says that a specific point, how much far away it is from the mean, right? With respect to variance, we basically talk about the spread, right? Now variance within the sample basically means with respect to this particular mean, how much these numbers are far, or how number is different. Basically, when we have this x1, right, I'm calculating the mean 3, right? Oh yeah, x1 bar is 3. But if we consider all these numbers, right, 1 is less than 3, 2 is less than 3, 4 is greater than 3, 5 is greater than 3, 3 is greater than 3. Now in this case, what is the difference when compared to the mean? That specifically talks about your variance itself, how different it is, right? So this is what we basically consider in order to calculate the F test in short, right? So for this kind of problem statement, obviously my null hypothesis will be nothing but x1 bar is equal to x2 bar is equal to x3 bar. And in the case of h1, it is nothing but at least one sample mean is not equal. And then we can probably go ahead and do it. Okay. Now what we will do is that I will try to show you one problem statement. Now this, when we say variance within sample, between sample and variance within sample, right? This is not a very simple step, right? There are multiple steps that is involved. We really need to calculate multiple things and then probably come to a conclusion. So please, I will show you one problem and then we'll try to see step by step. If you're stuck in something, I would suggest please rewatch the video. Then only you'll be able to understand. So we'll take a problem with respect to one-way ANOVA. Now, whenever we say one-way ANOVA, it basically means one factor with at least two levels, and these levels are independent in short, right? So let's check this problem statement, and you will probably be able to get a complete idea. Trust me. If you're not able to get it, I will suggest please revise. See, it will be complicated because this is the biggest test that we have in statistical analysis. Well, this will probably take more time, not with coding, but at least with understanding the theoretical part. Okay. Now over here you can see doctors want to test a new medication which reduces headache. Okay, which reduces headache. They split the participants into three conditions. One is 15 mg, 30 mg, and 45 mg. Later on, the doctor asked the patient to rate the headache between 1 to 10. So after having that particular medicine, three conditions based on that, three different medicines, three dosage. I would suggest this is dosage, right? And medication is basically my factor. This is my levels, right? Now later on, the doctor asked the patient to rate the headache between 1 to 10. So they are basically, if they rate 10, that basically means the headache is completely gone. If they rate 1, the headache is there. Okay. Are there any differences between the three conditions using alpha as 0.05? Now this alpha is super important because we will try to find out the values of the F. Will basically refer the F table to find out the critical value also. And these are my data. Like we have 15 mg, 30 mg, 45 mg. This is with respect to 1%, 2nd%, 3rd%, 4%, 5th%, 6%, 7%. So total 7 people are there in this particular data set. Okay. And again, this rating is between 1 to 10. Now in this case, what is the first step? First step is basically we define the. Now we want to compare this three samples in short, the mean of the samples, right? And we will probably be using variance, right? So define null and alternate hypothesis. So this is the first step. define null and alternate hypothesis. Now in this case, H0 is nothing but mean of 15, that is 15 mg, is equal to mean of 30 mg, mean of 45 mg. So this becomes my null hypothesis. Alternate is that on at least, or not all means are equal. Like we can say like this, or not all means are equal. Okay, or at least one mean is not equal. Like that you can basically say. The second step that we probably see with respect to significance value, which defines our confidence interval. So this is nothing but alpha 0.05, confidence interval is 0.95, right? So this is with respect to the second step. Now coming to the third step, which is super important, which is called as degree of freedom. So here I will try to calculate the degree of freedom. You have to follow the steps, guys, and based on that we will be able to calculate the variance. Now with respect to degree of freedom, first of all I will consider two important ways. The total sample size, like how many sample I have. So if you probably consider 3 rows, 1 2 3 4 5 6 7, 7 into 3 21. So the total sample is 21. If I probably consider the sample size n, which is nothing but 7, and we also consider one value which is called as a, and this value is nothing but it is saying how many number of categories are there. Because this 3 will be super important in calculating the degree of freedom. Degree of freedom needs to be calculated between the 3 samples and within samples, right? So for this, what we do is that first of all we really need to calculate degree of freedom between samples. And between samples, how do I do it? Because I'm considering with respect to 3 samples. So it will be very simple. A minus 1, which is nothing but 3 minus 1, which is nothing but 2. And then we'll go ahead and calculate degree of freedom within. Now degree of freedom within the sample, obviously it is simple. What you can do is that you can basically use this n minus a, right, with respect to the 3 categories. Okay, so this will be nothing but 21 minus 3, which is nothing but 18. And then finally you have degree of freedom total. Obviously this is very simple, n minus 1, which is nothing but 20. Now see this. Usually we used to use this degree of freedom total, right? And I'm getting the 20 value. If I combine this both, 2 plus 18, it is nothing but 20, right? In any ANOVA test, we try to find out these two things: degree of freedom between and degree of freedom within. So your range of values will be between 2, 18. Okay, so this will basically be your DF1 and this will be your DF2. And this is what is specifically used in Z table. Not Z table. We basically say F table. Okay, F table along with your significance value 0.05 to find out the critical value. Now what exactly is this critical value? So fourth step, we basically construct a decision boundary, because we need to understand when to reject the null hypothesis and when to accept, or when to accept the null hypothesis, which also say that we fail to reject the null hypothesis, something like this in technical terms. Okay, so usually whenever we try to apply an F test, it usually follows this kind of distribution. The right hand side is elongated, and what we do is that this region, we basically define this region as our 0.05 region, and this is basically our 0.95 region, the confidence interval. In short, this is my rejection area, and this is my acceptance area. Now, based on this particular F table, I need to calculate what is this area. Okay, what is this critical value? Okay, so what I'm going to do, I'm going to probably quickly just minimize this and probably open my F table. Okay, just go and search F table in Google. I know you're not able to see it because I'm not showing you yet. So here you go. In F table, you can probably go and click this. Now in F table, you have for 0.10, you have for alpha is 0.05. So I'll go ahead and consider this. See, this type of distribution is right skewed distribution. Okay, here you have DF1. Obviously, my DF1 value is nothing but 2, and DF2 value is nothing but 18. Right. So this is what is the value that I'm probably getting from this F table, which is my critical value. Okay. So what I will do, it is very simple. I will write 3.5546. Okay. So I'll make this. So this critical value is nothing but 3.5546. Now, when we do this, right? It's very simple. We probably talk about the decision rule now. Now the decision rule basically says that if my F calculated value, like the F test statistics I'm going to apply, if that F value is greater than 3.556, sorry, 3.5546, then it falls in this region, right? So what we do, we reject the null hypothesis. Very simple. We reject the null hypothesis. That is what we are basically going to do. Now is the most difficult thing that we probably need to calculate the test statistics. So finally, if you probably see the step 4, 5th, and 6th, so I will go and calculate my 5th step. So here I will go ahead and calculate the F test statistics. Okay, F test statistics. Now let's see how F test statistics will be calculated. Okay. Now with respect to this formula that we have, right? I hope everybody have seen this formula, the variance between the sample and within the sample, right? So I'm just going to copy and paste it over here so that this will always be there so that we can refer it. Okay. Now this was the formula to calculate this. Now to get this right, there's so many things we really need to get. Okay. First thing that I'm going to find out is something called as sum of squares. Now sum of squares, I need to find out for between. Then within, when I say between, that basically means between samples. This basically means within samples. Sum of square actually helps you to find out the variance, okay? And then total, okay? The second thing that I really need to compute is about DF. Then the third thing is about MS. And finally, we get the F value, okay? Now, whenever we say MS, it is nothing but mean square, okay? Now, first thing, let's go ahead and calculate this first row. SS between, SS within, and SS total, okay? And we'll try to understand what is the formula. Before that, I will take this also so that I will have this table reference, okay? So I'm just going to copy it over here. It's quite big, but don't worry, I will make it small, okay? Okay, so this is my table, okay? Now, first of all, I told you I need to compute. Now, let me just use this. Oops. Just a second, guys. I will use this over here. Okay. Now the things that we need to calculate over here. Okay. See, SS between. First of all, we try to calculate SS between. Number 1, SS between. Sum of square between samples. So formula of this is basically given by summation of AI whole square minus T square divided by n, and this will be small n. Now what is this A of I, right? Now in order to tell you about A of I, right? So okay, this will be sample. In order to talk about A of I, right? See how I'll calculate the summation of AI whole square. Okay. First of all, we go ahead with 15 mg. Now with respect to 15 mg, AI, summation of AI basically means I will sum this entire sample. So it will be nothing but 9 plus 8 plus 7 plus 8 plus 8 plus 9 plus 8. So if I probably calculate this, it is a 24, 18, 8, 32. So it will be somewhere around 57. Okay. And then if I probably go ahead and take about 30 mg, and if I try to calculate over here, it will be nothing but 7 plus 6 plus 6 plus 7 plus 8. This 6 is over here. I think it's got swapped over here. So this will be 6. Okay. 7 plus 8 plus 7 plus 6. So if I do the summation, it will be nothing but 7, 13, 7, 8, 8, 3, 21, 18, and 14. Okay. So this will be nothing but 47. Okay. So I hope I'm doing the calculation right. Okay. Just write out. But I think I've already done this kind of calculation. So it needs to be right. Okay. And then with respect to 45 mg, I basically have 4 plus 3 plus 2 plus 3 plus 4 plus 3 plus 2. So this is nothing but 21. Okay. So this is how I have calculated summation of A of I. Okay. With respect to this, in short, I've just done the summation of all the sample values. Okay. Now the next step that we specifically do over here is that we basically write it as summation whole square. Right. Summation of A of I whole square. So this will be nothing but 57 square plus 47 square plus 21 square divided by what is small n is nothing but 7. And this side t square basically means that I will take this value, the summation of all the samples, and I'll square it up. 57 square plus 47 square plus 21 square divided by 21. Remember guys, through this technique we are able to calculate the sum of square, the error in the variance between the samples, okay? And with the help of this we will be getting this particular value, okay? So it is nothing but 98.67. I know this is a little bit cumbersome, but understand if you follow the steps you will be able to get it, okay? Now this is far done. I have calculated SS between. Now we'll try to calculate SS within, sum of square within the samples. So second one that we have is nothing but SS sum of square within samples. And this is given by the formula summation of y square minus summation of a of I whole square divided by n. Okay, we have already calculated this. This is nothing but this. But what about summation of y square? So summation of y square is nothing but what we do is that we take every value in the sample, we square it up. Okay, we just square it up. So probably you can just write like this, right? First sample 9 square plus 8 square plus 7 square. So if you probably see like this 9 8 square plus 8 square 7 square plus 8 square plus 8 square. So like this you can probably do the calculation. So like this, take all the values and just do the squaring, and here you are probably going to get 853. So this will be nothing but the sum of square within will be nothing but 853 minus 57 square plus 47 square plus 21 square divided by 7. So here the total value that I'm going to get is nothing but 10.29. Okay. So once we do this, so let me put all these values. So it is 98.67 over here, 98.67 and 121. So this will be nothing but 108.88. Okay. So this is what specifically we are going to get the value with respect to this. Okay. So I think 108 so that is 10.21 or 29. Sorry. So 10.29. So this will be 188.95 or 96. Okay. Okay. So what I will do, I will just copy this entire thing and paste it downwards. Okay. So it will be easy for me to write it over here. Now this is done. Specifically 98.67 is one calculation with respect to this. 10.29 is the other calculation. And finally, I'll be able to get these all values. Okay. Now degree of freedom, obviously between, if you probably see degree of freedom between. So if you go and see over here, degree of freedom between is nothing but 2 and then 18. Okay. So here I'm going to get 2, 18, and this will be 20, right? Summation if you do. This, if both we divide it, see mean square is very simple. We just take this value and divide this with this value, right? So here I'll be getting 59.34 and this will be nothing but 0.54. This also we are trying to divide by this. And once it is done, you can also sum it up and you can get it. And finally, now if I talk about this value, right? F test. So here, F test is nothing but this specific thing, like variance between the sample. But in this case, what we do with respect to F test, we just take this MS between, which is equivalent to this variance within the sample, and then we have MS within, which is equivalent to variance within samples. So finally, when you take this and you just divide 49.34 divided by 0.54, here you're specifically going to get 86.56. So finally, this is my F test value. Now we know that if F is greater than 3.546, I guess, right? Let's see. It is very difficult. 5546, okay. 3.5546. Then what we do? We reject the H0, right? So in this case, obviously 86.56 is greater than 3.5546. So we reject the null hypothesis. So in short, the conclusion that you can probably make from this thing is that, are there any differences between the three conditions? Obviously there is differences within these three conditions that you have. So your null hypothesis is getting rejected, right? This is not true. So not all are equal, or not any one of them are equal, right? At least one of them are not equal. In short, you can basically make those kind of conclusions. This series that we are probably going to discuss, like coming 4 or 5 videos, will be on feature engineering techniques, right? So the first thing that we are going to discuss is that how to handle missing values. Now, it is very much important that you just understand and think, like whenever you are trying to solve a data science project, or it can be a deep learning project or machine learning project as such, the first thing that is required is specifically data. And always remember that, guys, in a real world scenario, when you're working for companies and all, you will be getting a lot of messy data. You know, the raw data, it'll be a bad data, it'll be having a lot of missing values. So in this video, I'm going to talk about all the techniques that we can probably perform to handle the missing values. Okay. Now, why does missing value actually occur in a data set? You know, let's say I'll give you an example. I have given a survey form to fill to some population or some sample. I'll not say population, but at least for some sample of people. Now, let's say if somebody is not comfortable in filling that survey, right? So they'll just keep that field empty, right? So because of that, you can just see that when that data set is basically created, there will be getting a missing value. So this is just one of the reasons, right? So in short, whenever we talk about missing values occurs in a data set when some of the information is not stored for a variable. And there are 3 mechanisms why specifically missing values happens. And we'll discuss about that. And then we'll go and do a lot of examples. I'll write the code in front of you to show you that how we can probably handle missing values. So the first mechanism why missing values occurs, which is called as missing completely at random, which is also called as MCAR. Now, missing completely at random is a type of missing data mechanism in which the probability of being missing is unrelated to both the observed and the missing data. That basically means missing completely at random basically means that the data, if it is present missing, right, there's no such reason as such, right? There's no such reason, right? It is just available, right? Some data is missed. It may be an error from the data entry operator, or it may be an error from any machine. Probably they are not able to create that particular data. You know, no such specific reason. So in other words, if the data is MCAR, the missing values are randomly distributed through the data set, and there is no systematic reason for why they are missing. Let me show you an example. Like over here, in a survey about prevalence of certain disease, the missing data might be MCR because if the survey participant with missing values for certain questions was selected, right? So probably, you know, the survey people, you know, they have missed some data to fill, right? Knowingly or unknowingly. I'll not say knowingly, but at least unknowingly, right? There is no such specific reason. It may be an error. Mostly we consider it as an error, right? So that is the reason we say it as missing completely at random. So at the end of the day, tomorrow when you're working in, with respect to any data set, right? These 3 reasons will be there why some data is missing. Okay. Coming to the second type, missing at random, which is also called as MAR. Now, missing at random is a type of missing data mechanism in which the probability of value being missing depends only on the observed data, right? So it is basically dependent. Why that specific missing data is there? It is dependent on some other data. Probably in that specific column, in that specific field, or in that specific columns, there will be different columns. So because of that, there may be a missing data available in the other column also, right? So in other words, if the data is MAR, the missing values are systematically related to the observed data. There is some relationship. One example I can talk about, right? The basic example I talk about. Let's say if someone is given me to fill the survey and I'm not comfortable. Usually men are not comfortable to disclose the salary, right? Women are not comfortable to disclose the age, right? So this kind of survey, right? When we are probably filling, if there is an income field, I'll not fill. So you will be able to see that probably male are not filling the incomes, women are not filling their age, right? So here there is some relationship. So this is basically called as missing at random. You can definitely see both these examples which I have written over here. Okay. Now coming to the third type, missing data not at random. random. So here, it is a type of missing data mechanism where the probability of missing value depends on the value of the missing data itself. Okay. In other words, if the data is MNAR, the missingness is not random and is dependent on observed or unmeasured factors that are associated with the missing values. Obviously, there is 3 liners that I have actually written, but it is better we probably try to see the definition. It is also saying over here that the missingness is because of some other reason, and there may be multiple factors also. Like here, you can see, suppose you're collecting data on the income and job satisfaction of the employee in a company. If the employee who are less satisfied with the jobs, okay, are more likely to report the income. Let's say I'm not satisfied with my job, so I'll not put the income, right? So then the data is not missing at random. In this case, the missingness is dependent on job satisfaction. So it is basically dependent on multiple factors, right? So that is specifically called as missing data not at random. Okay. So these are the 3 types. Now what we are going to do is that we're obviously going to see some examples and how to handle all the missing data. There will be multiple techniques that I will probably show you. Okay. So first of all, let's go ahead and import C1 because I'm going to use a data set. Let's say I'm going to use a data set which is called a load data set, right? Now inside this load data set, I'm going to use a data set which is called a Titanic data set. I hope everybody's seen the Titanic movie, right? Why I'm taking this? Because this data set has a lot of missing values. And for our problem statement, when we are discussing the 3 scenarios, we can come to a conclusion. At least two reasons can get satisfied from this. Okay. So let's go ahead and let's see df.head. This is there. If I want to check missing values, So for checking missing values, I can basically write df dot is null. Okay. So if I write is null, so here you'll be seeing wherever there is a missing value that will become true, and remaining all wherever there is a value that will become false. If I really want to see the sum, so I can probably see the sum. There's an error. So if I write dot sum, so here I'll be able to see this. This basically shows that in which column how many null values are there. So here you can majorly see in H column there are 177 data points that are having null values. And in deck column, you have 688 data points which are having null values. And embarked town is also there. Embarked is also there. 2 are there. Okay. Now this is the data set over here. Age, embarked, deck. Deck is just like a seat number if you see Titanic movie. Okay. So these are basically having the null values. Now, one easiest way of probably removing the missing values is that delete the rows or data points, right? Data points to handle missing value. But what is the problem with this? You will lose a huge amount of data. Right now, if I write df.shape and see it is 891 data points are there. But now if I say df.fill NA, or sorry, not fill NA, drop NA. I'm just dropping it, right? And I'm dropping with respect to data points. Wherever there is a missing value, drop that entire data point. Now if I go and see the shape, you'll be able to see that how much data points it will be left. Only 182. Before it was 891. Now I'm just having 182. So this dropping feature that we are specifically doing is bad because we're losing huge amount of data, right? Now over here we should definitely not go with this. Okay, it's not a very good idea about to go with this because unless you have a very huge data set. But right now we had 891, but because of dropping all the NaN values, you have now 182, right? So this is a blunder. We should not do that. Okay. Now can we do column wise? You may be thinking, can we do column wise, right? Because over here you can see each column is having 177 data points that are having null values. Deck is having 688. Now total number of data points are 891. So I can probably go and delete this deck column. Yes, it is a suitable way because you have so many NaN values. But age, we cannot drop it as a column, right? But if you feel that okay, if there are many data points that are having null value, in this case like deck, you can delete that column, right? So column wise deletion for this, we can write df.drop NA and just change the axis value to 1. So once you're able to do this, it will drop all the features that are having NaN value. So age and embark column you can see over here, it is dropped, right? So you can probably also write in place is equal to true to make it a permanent operation, right? It is up to you. Right now I'm not making it and I'm just trying to show you all the ways. Now this way we can probably delete the rows, we can delete the column, but we'll try to see some imputation techniques, okay? We'll try to see some imputation techniques. Now with respect to imputation techniques, just give me a second. So with respect to imputation techniques, I will just write a comment. Imputation techniques basically means how we can handle the missing values. So I will basically say imputation missing techniques, missing values, or I can basically write this as imputation missing values. And now I'll make this as a markdown. And first technique that I'm probably going to follow is basically called as mean value imputation, right? So mean value imputation is a technique which we will specifically be using over here. And with respect to mean value imputation, as the name suggests, mean value, that basically means we are going to replace the missing value with the mean of that specific column, right? Now, what I can do, obviously we have imported C1, right? So I will write sns.displot, and let's say I take an age column because it is a numerical column. And if I try to execute this, now here you'll be able to see that I'm probably able to get this specific diagram, right? Displot. If I probably say histplot, and let me make my KD is equal to true, right? So here you can see that this looks like a normal distribution somewhat, right? Not exactly a normal distribution, but it looks somewhat, right? Now you know that in age you have 177 data points which is having null values, right? So can we handle this null values by replacing it with the help of mean value, right? So for that, what we can do is that we can just write df dot fill NA, right? df of age, okay? df of age dot fill NA, and in fill NA, what I'm going to give, I'm going to basically give df of age dot mean. By this I will be getting my mean. And let me just go ahead, and this mean is basically a function, so please make sure that you remember this, and I will save this in my age underscore median, right? So once I do this, you will be able to see now my df, okay, will be like we have created a new column which is called as age underscore median. Just a second, median, comma, age. Now, if I probably see this, you'll be able to see that the NaN value will get replaced with mean, right? So over here, my age underscore median, here you can see in age, there is a NaN, and this has got replaced by 29.699, okay? This basically means that we have replaced the NaN value with the mean of the age, right? Sorry, this should not be median. Sorry for that. It should be mean, okay? I just wrote it by mistake. It should be mean, okay? So, apologies for those mistakes, but I think age underscore mean is not an index, not a worries. I will execute this, and now we will be having this. So here you can see that the NaN value is getting replaced with the mean value, okay? So I just named it as median, so don't get confused with that. So this way, we can probably see mean. And when should we use this? We should definitely use this. This will work well. Mean imputation works well when we have a normally distributed data, okay? Normally distributed data, right? But what if, now the question rises, what if you have a different kind of distribution? You have a right skewed or left skewed. So for that case, you know that outliers will definitely be there. So you can replace the NaN values with median, right? So for that, the second method that we are probably going to see is called as median imputation, median value imputation, okay? I'm showing it in front of you guys, each and every techniques. So you can practice with any data set you want as such, right? So this is basically median value imputation. And why we are specifically using if we have outliers in the data set, okay? So how to do this again? So what I will do, I will write df of age underscore median, okay? And then we will try to replace a df of age dot fill NA, and I will try to replace this with df of age dot median, right? So once I do this, the execution happens. I can copy the same code and I can probably see this over here, right? And this will basically be my median, right? I can also go ahead and write about age underscore mean, comma, age, right? So this is how my data set looks like. Here you can see nan value has been replaced by 29.666699, and this is 29.69918. Okay, but here let's see, I have taken df.age of median. Okay, sorry, I created a variable before also, right? Capital A. So here this nan value has been replaced with mean over here in this column, which is age underscore mean. Now if I probably go and see age underscore median, it has been replaced by 28. So this will definitely work well if you have specific outliers as such. Okay. Now similarly you can use median, and now the third technique that we will probably go ahead with is basically called as mode imputation technique. Mode imputation technique. Okay, and this can be used with categorical variables. Okay, categorical values. So I'll show you an example over here. Now let's say that we have one column which is called as embarked. Okay, embarked, and if I probably see is null, okay, and probably what I will do is that I will just try to take out all the information which are having null, right? So here you can see in embarked column you have two nan values. Okay, now we'll try to handle this nan value. Now see, embarked is an example of missing completely at random, MCAR. If I probably say missing at random, there is some relationship, right? We can consider age also, right? We can consider age over here. Just a second, I'll show you. Age has been missing because see in Titanic, right? That boat had sank, right? And many people died, and we could not capture because those people died. We could not capture the age, the seat number, so deck is also completely empty, right? So here you have a lot of missing values. So one or the other example it will get related to, right? Now this example there is no relationship at all. There's no relationship at all. So this can be actually belonging to the first technique, missing data completely at random. Okay. Now in order to handle this, since this is a categorical variable, why I'm saying categorical variable? If I write df of embarked dot unique. So if I probably see unique function, I'll be getting these values like SCQ nan, right? Over here you have this nan value, right? Now what I need to do is that replace this nan with some of the values over here, categorical values, which I can probably find out through mode. Okay. So for that, how do I find out? So let's say I write df of df of embarked. So df of embarked, and there is a function which is called as not na. Now not na will give me all the output, which will basically be saying that wherever there is no nan values, okay, try to give that value as false and remaining all true. If there is a nan value, give me as false, not nan, right? Something like that. And if I want to get all the values which is not having nan also, I will be able to get it. I will just write like this, right? So these values here you'll be able to see in the embarked column, right? Wherever there is nan value, right, that will all get skipped. Okay. Now through this, now what I'll do, I will take my embarked column. So this will basically be my embarked column, and then I can probably apply mode. Now here if I'm applying mode, I get S. So let me take this value as my mode. Okay. So by 0, if I write index of 0, I'll get mode. So this is nothing but this is my mode value. Okay, mode value. So I will store this. Now in order to replace over here, what I can do, I can write df of embarked dot fill na, and I will try to replace this with my mode value. That's it. Mode value. Now once I do this, I will save this over here in the form of df of embarked underscore mode. Right. So this is my column name. I'm saving it over here. Now finally you'll be able to see if I write df of with two square braces, and I want to display both the column that I've created. So here I'm just going to write embarked mode, comma mode. Sorry, embarked. Okay, so these two columns I'm going to see over here, and where there is nan value, that has been replaced by the mode value itself, right? So you can probably see it. If you don't believe me, just do like this: df of embarked mode dot is null dot sum. Okay, so if I write like this, so here you'll be able to see zero null values. And similarly, if I probably go and see with respect to embarked, there will be two null values, right? Because there were two null, that got handled over here. So this way you can probably see this. There's also one more technique which is called as random sample imputation. In random sample imputation, you don't worry about anything. You select randomly any value from that particular column and replace the nan values, right? Now this way, what will happen is that this is basically this is called as random sampling technique. You probably select a random value, replace the missing values with that. Okay, and every time it can probably change. So I hope you got an idea with respect to how you can probably handle missing values. We wrote a lot of lines of code over here. We understood. We discussed about mean, median, mode, and there is also one more random sampling. Just try to do that random sampling. What you do, just select a random value from the column and then replace that missing value with that. Okay. So yes, this was it from my side. I hope you like this particular video. I will see you all in the next video. Thank you. Hello guys, so we're going to continue the series with respect to feature engineering, and in this video we're going to talk about handling imbalanced data set. Now, why should we handle the imbalanced data set? What exactly is imbalanced data set? We'll discuss about this. It's just to make you understand some of the things over here, but later, when we are developing projects, we'll be seeing all these things. Okay. Now, with respect to any problem statement that you may be working in machine learning and deep learning, initially you will be given a data set, right? Now, let's say there is a data set, and let's consider that you are trying to solve a classification problem. Now, whenever I say classification, supervised machine learning problem, that basically means the output is basically in the form of categories. Right? If you have two categories, we will say it as a binary classification. So let's consider this binary classification for instance to make you understand what exactly imbalanced data set is. Let's say I have 1,000 data points in my data set. Okay. Now with respect to this 1,000 data points, the output feature is basically a binary classification problem. Let's say my output can be something like yes or no. Right? Now out of this 1,000 data points, let's consider that I have 900 yes and 100 no data points. Right? Now this scenario, you can see that the maximum number of data points are basically saying yes, and there's a very minimal number of data points that are probably saying no. So if you probably see the ratio, so here 9:1 ratio is there. This kind of situation basically talks about an imbalanced data set, because out of the 1,000 data points, you have 900 yes and you have 100 no. What is the main problem if you have an imbalanced data set while you're solving a machine learning application? Your model that you are probably creating, which will be responsible in predicting, will get biased towards this maximum number of data points, right? Because of the imbalanced data set. So it is necessary that we fix this imbalanced data set and we try to make sure that both these data points become equal. And we can do this. There are techniques, there are two special techniques that we will be using. One is called as upsampling and one is called as downsampling. Okay. Now when we say about upsampling and downsampling, this is just like in upsampling, we try to increase the number of data points from here, which is basically minority. In downsampling, we try to reduce the data points from here, which is majority. So clearly, here you can basically see that there are two techniques, upsampling and downsampling, right? First, we'll perform upsampling and then we'll perform downsampling. Now, first of all, let me create that specific data set. So for that, I'll be just using some code, okay, which I've already created. Now let's understand this code. I've imported numpy and pandas, and then here you can probably see that I have also imported this np.random.c, so that whenever I'm randomly selecting some values, it should not change. Okay. Then we create a data frame with two classes. Okay. First, I'm taking 1,000 data points. Just for instance, you can take 10,000 data points also, not a problem. I'm saying that my class 0 ratio is 0.9. That basically means 90% class 0 ratio. And when I talk about this number of class of 0, that basically means I'll have 900 data points. So what I'm doing, I'm multiplying this 1,000 by 0.9. So here totally I'll be able to get 900. And remaining will go to my class 1, which is basically my other category. So total 100 data points will come over here. So if I probably execute this, now you'll be able to see that if I write n_class_0, comma n underscore class underscore one. Right? If I execute this, I'm having 900, 100 data points. Okay. Now this is very much clear. Now what I will do next step is that I will create my data frame. Okay. So I will create my data frame with imbalanced data set. Okay, this is super important, with imbalanced data set. Now for this, I'm again pasting one code. Now this is the technique of creating a data frame with two features, feature one and feature two, which is a normal distribution. This is also a normal distribution. This is mean, this is this. How many number of data points I want with respect to class underscore zero, that will basically give me this 900. And over here also feature one will basically generate 900 data points. And target, the zero will get multiplied by 900 data points. That basically means 900 zeros will get created in this class zero data frame. Okay. Similarly in class one data frame, I'm basically taking 100 data points over here. And similarly, I'm using this one as my target output 100 times, right? So if I probably execute this, and if I probably write pd.concat, sorry, I think I've used caps lock. So if I write pd.concat, and inside this, let's say that I am combining this class underscore 0, comma, class underscore 1. Okay. And along with this, I will also reset my index, because when I'm actually trying to combine this, I will be getting an index value. So I want to drop this also. So reset underscore index with drop is equal to true. So once I do this, I will be probably getting my df. So this is my df.head. Okay. This is my df.head, and this is what I'm actually getting. If you probably see df.tail, I will be able to see ones over here. And if I really want to see the value counts of target, so you can probably see over here, if I write target.value underscore counts, you'll be able to see that I'll be getting 900 and 100 data points. Okay. It is up to you. You can create any imbalanced data set. You can also have 10,000 data points and 900 data points, something like that. Okay. Now, the first technique, I will probably be using something called as upsampling. Now, in upsampling, what I'll do, I will try to increase this number of ones to 900. I'll create some artificial points, and that is what upsampling does. So in case of upsampling, as said, upsampling, okay, what I'm actually going to do is that, first of all, I'm going to create two data frames. One data frame is with respect to df.target, where my target is double equal to 1. Okay. So this will basically get me all the rows whose target is equal to 1. And you know that when 1 is there, that is my minority class, right? So I'm going to create my df underscore minority. Okay. Now similarly for majority, what I'm going to do, I'm going to basically add df underscore majority. Okay. Majority. Okay. And this target will basically be 0. Okay. So I've segregated this because I need to increase the number of minority over here. Now we will be using one library which is called as from sklearn.utils. I'm going to import resample. Now resample, what it does is that this basically creates, it extrapolates the point. That basically means whatever point is minority, right? It will try to create more new points for this, and it will try to equalize with respect to the majority. So resample, first parameter that we specifically give over here is something called as df underscore minority. Like for which sample I want to probably perform upsampling. The next important parameter is something called as replace is equal to true. Replace basically means that whenever I am performing the resampling over here, okay, whenever I'm performing the resampling, this sample that will get added, it will get added with replacement. So different new data points can be added over here. Okay, this was with respect to my second data point. Then how many I want to increase? So for that I will use n underscore samples, and here I will write length of df underscore majority, because I want to increase that much, right? 900 data points. So this is the next one, and then I'm going to use random underscore state, any random state value, so that the seed is fixed over here. And this I will save it in df underscore minority underscore updated or upsampled. Now you will be seeing that whatever df underscore minority underscore upsampled is there, this shape will be 900 data points. Okay, so that basically means I have actually created more data points over here, and all this particular data set is basically giving the output as 1. If you don't believe me, just write dot head and see you're getting 1, right? Now what we can do, we can again use pd.concat, and now we can combine df underscore majority along with df underscore minority upsampled, and then you can see the output over here. So this is my df underscore upsampled, right? Perfect. So here I'll execute this, and now if you see df underscore upsampled with dot of target of value counts, now you'll be able to see how many data points, 900 zeros, 900 ones. So that will be total 1800, right? So value counts. And if you probably see the output, so here I'm getting 900 zeros and 900 ones. This is how upsampling is done. Now if I probably consider downsampling, so in the case of downsampling, I'll be using the same code of creating the data set. Okay, the same data set, I can probably use it. For that, I'll just copy it, which I already have my data set over here. Okay. So let me go ahead and copy it over here so that you will be able to. So in short, I'm creating the same data set over here, whatever we did, right? 900 zeros and 900 ones. Now, with respect to downsampling, what we are going to do is that again, we're going to use everything same. So this same code will be there. Like upsampling will try to create like this. So downsampling also, first of all, we will create downsampling. All the steps will be same, guys. So I'm directly copying and pasting. So I'm creating two data frames, and now I will use df underscore majority, right? So I will use the same library. Now instead of writing minority upsample, here I will write majority downsample. I'm just giving one name, okay? And the first parameter will probably go with df underscore majority. Let's see, majority, yeah. Replace will not be true now because we need to reduce the data points, right? So this sampling with replacement will be removed because we want to reduce the data points. And this n underscore sample will now be the minority one because I want to reduce the data points to the length of the minority, right? So once I do this, so now if I probably see df of majority downsampled dot shape, you will be able to see 100,3. This is what the size is now. It has got reduced, and you can probably see over here. And finally, what I can do, I can probably combine like this and just write df underscore downsampled. So here I will write downsampled, and this will first of all go with the minority df underscore minority, and this will be df underscore majority downsampled, right? Underscore majority downsampled. So here we are basically downsampling things, right? So okay, one error is there, not a problem. Let me see. Okay, this one square braces is missing. Okay, so now if I write df underscore downsampled dot target dot value counts, so here we'll be able to see I'll be getting 100 data points. So this is how we can do downsampling. Downsampling is bad because we are losing data points. We can probably do upsampling and probably try to solve this particular problem whenever we are trying to train our model. So I hope you are able to understand about handling imbalanced data set. This was it from my side. I hope you like this particular video. I will see you all in the next. Hello guys, so we are going to continue discussion with respect to feature engineering. We have discussed in our previous videos about how to handle imbalanced data set by upsampling and downsampling. Now in this video, I'm going to discuss about one upsampling technique which is called as SMOTE. SMOTE full form is synthetic minority upsampling oversampling technique. Now, first of all, you see the definition. I'll just try to explain you the differences with respect to the upsampling technique that we learned in the previous video and what exactly is SMOTE. Okay, so SMOTE is a technique used in machine learning to address imbalanced data set where the minority class has significantly fewer instances than the majority class. SMOTE involves generating synthetic instances of the minority class by interpolating between the existing instances. Now, this is too much of definition. It's better that I probably explain it by writing something in front of you. So let me go ahead and let me explain you. Let's consider that I have a data set, okay, and I'll show you in a visualized manner. So let's say one of the feature is X and the other feature is Y. Now, with respect to this, let's consider that I have one category of data set, and this is basically plotted something like this. So here you can see that, okay, this will be my majority data points, okay, which are more. And let's consider minority data points, which are a little bit less, okay. Now, in this scenario, in my previous video, which I specifically discussed about upsampling, right? In upsampling, what happens is that since this is minority data set, and we really need to make the similar count as of the majority one. So what we do through the upsampling, on top of it only, right, more data points gets added, right? So we are increasing the similar data points again and again, right, with the help of upsampling technique. More data points are getting added in the same place, okay? Now, this technique is not that good because my data is still in that position only, nearly that position. The variance is not increasing at all. So in order to increase the variance, what we can specifically do, we can use the interpolating techniques, okay? Interpolating basically means we are creating our own synthetic data. So let's say if I have some data points, let's say if this is my majority data point, okay, using SMOTE, what we can do is that, let's say if this is my minority data point, okay, so what SMOTE does is that it tries to join the two nearest point and then it tries to add the data points in this line. Similarly, then it goes and joins the next two nearest point and then it tries to create a new data points in this line. So like this, the data will be created additionally. So now the data that is getting created, it also has variance, right? It is just not getting created like how it was getting created in the upsampling technique. So this is possible because of SMOTE, okay? So this is the overall funda behind SMOTE, like how it works. First of all, we create a data set by our side and we make sure that that specific data set has an imbalanced data set altogether. And then we try to apply SMOTE and then we see what is the final output that we get after applying SMOTE. That is, we specifically do through the synthetic minority oversampling, okay? So let me go ahead and let me first of all import, and again guys, for creating a data set today, I will be using another library. So from sklearn.dataset. So sklearn has this amazing library which is called as make, it is basically import make classification. So if you probably like sklearn.datasets, import make classification. So this make classification actually helps you to create a binary classification or multi-class classification dataset, okay? And with respect to imbalance, we're trying to fix that problem, right? So what I will do, we first of all take make classification, and here you can probably see the parameters also. Like you can probably consider how many number of samples you want in your dataset, like how many number of data points you want, how many number of features you want. Like let's say you want one feature, two feature, three feature, and then you also have some other features like how many number of classes you want, how many number of cluster per class you want. Like if you are considering one class, how many groups you want in that, right? You can have two groups as such. So there are various parameters which you can refer it over here. So over here, what I'm actually going to do, I'm going to first of all apply n underscore samples, and I'm going to take 1000 data points, right? And then I'm also going to consider number of features to 2, right? Just for simple analysis so that I can create that 2D diagram and see how my data is distributed. And there is also a parameter which is called as n underscore clusters per class, right? As said, I want one cluster per class, so I will put the value 1, right? You'll understand like how the data will be probably made. Then after this, we go to the next parameter which is called as weights. Now weights, here I'm assigning 0.90. That basically means one class should be 90% more than the other class with respect to the output feature. So this basically becomes an imbalanced data set, okay? And then finally, you can take up random state also if you want, okay? Random state will basically set up the seed. Let's say I'm putting it as 12 over here. Now if I execute this, so let's see, there is an error, okay? The error is something regarding redundant, number of informative and all. So there is a parameter over here which is called as n underscore redundant, this one, right? Now what this parameter basically says, and you can definitely use this amazing class or amazing functionality of make underscore classification. N underscore redundant is the number of redundant features. These features are generated as random linear combination. Currently, I don't want this, so I will remove the default value. So over here, what I will do, I will write redundant is equal to 0. I don't want that feature. Otherwise, if I have 10 features, I can basically create that. Okay. So this is what I'm actually getting. Now, if I execute this, you'll be able to see that I'm getting all my input features over here, and this is my target feature. So what I will do, I will create two variable x, comma y. Okay, and I will try to save this in x, comma y. So x is my independent feature, y is my dependent feature. This is till here we have done it. Now what I'm going to do, I'm going to create my data frame just to show you like how the data is distributed and all. So that is the reason why I'm creating. I can also use this numpy for clearly seeing the scatter plot, but let me just create it in the form of data frame and it'll look better. Okay, so first of all, my df1 will be like pd.dataframes. Okay, and inside this I'm going to take x and my columns will be, let's say, f1 comma f2, right? So two columns that I'm going to probably consider. Then df2, then this will be nothing but pd.dataframes with respect to y comma columns is equal to target, right? So I'm taking two features, right? So one is y is basically having my output feature, so I'm considering it as target, and this is basically f1 comma f2. Now what I'm going to do after that, I'm going to create my final underscore df, and I'm going to concatenate both those, right? In the axis is equal to 1, that is column wise, right? So once I execute this, and if I probably write final underscore df dot head, so here you'll be able to see that data frames, right? So here it should be data frame. Anyhow, so this is what I'm actually getting. So finally, if you go ahead and see final underscore df, and probably see the target count, like dot value underscore count, if you use value underscore counts, you'll be able to see that how many number of zeros and ones you have. So you have 900 zeros and 100 ones in the entire data set, right? So this is definitely an imbalanced problem, right? Now let me go ahead and use matplotlib, import matplotlib dot pyplot as plt, right? And if I write plt dot scatter plot, and inside the scatter plot, let me take my first feature, final underscore df, with respect to f1, that is my feature 1, and final underscore df with respect to f2 as my feature, and finally the color part, because in scatter you have c parameter also. So here I'm basically going to use final underscore df with respect to the parameter that is called as target. So once I execute this, here is how your data is distributed. So here you can see some of the 100 data points which is over here, and remaining all data points are here. Definitely this is the majority, this is the minority. Now we'll try to apply SMOTE and see that what all things we can basically do. In order to apply SMOTE, we will be using one library called as IMB learn, imbalance learn. So for that library, by default, it will not be available. So what I'll do, I will install this. In order to install, just write pip install, okay, pip install IMB learn, okay. So once I execute this, so here you'll be able to see all the libraries has got installed over here. Perfect. Now the next step is that I will import one class from IMB learn dot oversampling I'm going to import smart, right? I'm going to basically import smart, and this smart needs to be in capital letter, okay? And then the next step, we will transform the dataset using smart. Again, the concept I've already explained you. So internally, this library will be responsible in connecting all the dots and probably interpolating new points. So let's go ahead. So here I'm going to create oversample, which is nothing but smart. Okay, and this mode is there, and then I will be having x comma y. Then this oversample will basically do fit underscore resample, and then here I'm going to give this in resample. What we do, we probably when we are probably executing this, the first feature that we probably give is our independent features, right? So final underscore df is nothing but it is having this f1 comma f2, which is my independent feature, and finally after this I will also be given my target feature. This is what it requires just to interpolate the minority class. So finally I will be seeing this. Smart is not defined because I did not execute this, not a problem. From im. Okay, over underscore sampling. Okay, so this mistakes, I'm not going to edit it because you may also face it. Okay, so once I execute it, so this is my x and y. Now, if you see x dot shape, it is basically having 1800 data points. Why? Before the majority had 900, right? Now this one data points, right, with respect to that also, it has got increased to 900. This has been like, it has basically oversampled. They have oversampled using the smart technique. So if you probably see y dot shape also, so here you'll be having 1800 data points. Now, let's go ahead and let's see with respect to y, how many I have zeros and how many I have one. So if I write y double equal to 0, so it will basically give me true or false based on whether it is having 0 or not. And then if I write y of y equal to 0, then I will be seeing all the data points which has 0. Okay, and if I write length of this, so it will basically going to tell you that how many zeros you have in your data set, right? Similarly, if I go and execute this and write y with 1, then I'll be getting 900 data points. Perfect. So this is there, right? And it has been equal now, right? Before 1 was only 100 times present, right? Now what I'm going to do, I'll take this x and y and again create my axis. Let's say with the new data points, so 2 data frames and concatenation, I've done it. And here it is. This is my oversample df. Now I will just plot this oversample df and let's see the new plotted. So oversample df of f1, f2, and the color I'm basically going to use the target. Now you see something amazing will happen, right? See, all these dots are connected, right? So this is how you can see that you have increased the number of data points, which is quite amazing, right? Do you agree or not? See, all the data points has been increased. Now it is better that we can apply machine learning algorithm and probably solve a classification problem with respect to this particular data set. Initially I had something like this, but now here you'll be able to see we are having good number of data points, right? So this is what is all about smart. And in this video I've learned about smart and we've seen that how you can perform synthetic minority oversampling technique. So I hope you were able to understand this video. I will see you all in the next video. A very important technique in feature engineering. Try with some data sets and definitely have a look into that. Okay. In this video, we are going to see how we can construct box plot with the help of Python programming language. And then whatever things we discussed, right? Like Q1, how to probably calculate Q1, that is nothing but 25%. Then you probably have this 5 number summaries, right? Like minimum, maximum, and then you have Q1, Q3, and median, right? So these are the 5 different values we definitely need to calculate in order to get a box plot, right? So over here, you'll be seeing that we'll try to understand about the minimum value, okay, maximum value. Then probably we'll also try to see about the median. Then you have your Q1 and your Q3, right? And based on that, we'll go ahead and calculate my IQR also, right? So all these things will get covered in this specific video. Now, in order to calculate the 5 number summary, I've already shown you that we can import numpy as np, and then I can specifically use np.quantile, right? So we can use np.quantile. And inside this quantile, we will give our list of ages. Let's say I want to give my list of ages. These are from this particular values or list of marks. I can probably also get list of marks, right? And let's say the marks are like 45, 32, 56, 75, 89, 54, 32, 89, 90, 87, 67, 54, 45, 98, 99, and let's say 67, 74, something like this, right? So these are my list of marks, which I've actually considered over here. Now, what I'm actually going to do is that quickly try to find out my np.quantile. With respect to this, I want what all values. I want my 0th percentile, which will basically be my minimum value. Then you have 0.25, which will basically give. So with respect to that, I'll also assign a value over here on the left hand side. So first will basically be minimum, comma Q1, okay, comma median, comma Q3, comma maximum, right? So this many number of values I specifically want, right? So this is what 5 number summary is all about, right? Then I will go ahead and write 0.50, then comma 0.75, comma 1.0, okay? So all these values are here. I will go ahead and execute it. Okay. So these are my minimum value, Q1, median, Q3, and maximum value. Okay. Perfect. So if I probably go and see my minimum, so this is my value. If I probably go and see my Q1, this is my value. Like Q1 is 54, that is 25% out of this. And similarly, if I go and see my median value, this is nothing but 67. And similarly, if I go and see Q3, I will go ahead and see for Q3 and maximum, I will also be getting all these values. So this is my minimum value. This is my maximum value. Maximum value, obviously, you can see 99, right? So then you can probably see this is your Q1, Q3, and your median. Okay. Now, first of all, whenever you really need to create that lower fence and higher fence to detect if there is any specific outliers, right? And over here, you can definitely see there are no specific outliers as such, right? Here, definitely there is no such outlier. And with respect to the outlier, only we try to calculate the IQR and all, right? So anyhow, I have just let's consider that there is no such outliers over here, and now we'll try to compute what is the IQR and all. If there is an outlier, we'll get to know anyhow. Okay. So IQR, whenever we compute, right, it is nothing but Q3 minus Q1, right? So if I probably calculate this and if I print my IQR, so here is what is I'm getting, right? 35. So in short, I have subtracted 89 minus 54, for which I have actually got 35. Now, in order to calculate lower fence, which we discussed in 5 number summary, because I need to make sure that I need to get the range of lower fence and high fence. Anything that is greater than high fence will be considered as an outlier in this list. Anything that is lower than the lower fence, that will be considered as an outlier. So for computing the lower fence, I will write Q1 minus 1.5 multiplied by IQR. So this is the formula we specifically used. And similarly for higher fence, here you'll be seeing that we have used Q3 minus, sorry, it should be plus 1.5 multiplied by IQR. So once I probably get my lower fence and higher fence, so there's a syntax error. Let's see what is the error. Okay, so it should be multiplied and this should also be multiplied. Okay, fine. So this will basically be my lower fence. This is the value, and higher fence, right? So this will basically be my higher fence. So anything that is lower than 1.5 in this particular distribution of data will be considered as an outlier. Anything that is greater than 141, then obviously over here we don't have any value greater than 141, so it will basically be considered as an outlier. Okay, so if I probably take this list of marks, and now let's go ahead and compute the box plot. Now for creating the box plot, I will be using another library, and there is an inbuilt function for box plot also. So I'll say import cbon as SNS, right? So cbon has an inbuilt library called as sns.boxplot, okay? And this box plot, if I probably give just my list of marks, you'll be able to see, I will be able to get the entire box plot, right? So this is how a box plot looks like, right? And over here, you can definitely see this line is basically given, this is a vertical box plot, okay, not a horizontal box plot. Let's consider this as a vertical box plot. So now with respect to box plot, if I press shift tab, here you have to give your data, you can set different parameters like hui and all, which we have already discussed probably in the Python, right? So draw a box plot to show the distribution with respect to categories. So over here, you can basically see that I am not getting any outliers, right? So that is the reason I don't get dot on both the side. This is my minimum value, this is my 25 percentile, this is my 50th percentile, this is my 75 percentile, and this is my maximum value. Let's consider one more example. Here, I will just copy this code and paste it over here, and let me add some outliers, okay? Like on the larger side, I'm adding some outliers. On the lower side also, I'm trying to add some outliers like this, right? So let's say I can add some more outliers like -100 or comma -200, right? And obviously, when we try to compute it, we'll also be able to understand this does not belong to this entire distribution. This is somewhere away from that. Now, even though I don't have to calculate all these things, lower fence or higher fence, automatically your box plot will be able to do all these things. So if I execute it, if I execute over here, now you can see this is how your box plot looks like. All your values are till here, but the larger value will be shown in the form of dot. So let me just write this in a better way. So let's say I will write 150, 170, so that at least the figure should be visible properly, right? So here, if I write this one, now here you can see these dots that you see, right? These are specifically outliers. So in -100, outliers here, and this outlier is there. And with respect to this, you can see this is my minimum value, 25 percentile, 50 percentile, 75 percentile, and this is the maximum value. So this is how you can probably see how does the box plot looks like and all, right? So yes, I think I've explained you about the 5-number summary and box plot in a proper way. I've also shown you that how you can use various libraries like cbon in order to construct a box plot. And if you want to do manually, obviously you need to compute the lower fence and the higher fence, right? So yes, this was it from my side. I hope you like this particular video. I will see you on the next video. Thank you. Hello guys, so we are going to continue discussion with respect to feature engineering, and in this video we are going to discuss about data encoding. Now in data encoding, we are going to discuss about various types, that is nominal or one-hot encoded encoding, label and ordinal encoding, target guided ordinal encoding. Now first of all, let's understand why should you specifically do data encoding, okay? So let's consider that I have some data set, okay? In that particular data set, I have like experience, number of years of experience, and let's say I have degree, and based on this, I need to predict what is the salary. So let's say that I have these 3 features, and my main aim of my model is to predict salary based on these 2 features, that is experience and degree. Now in degree, you may have various values, like you may have BE, you may have PhD, you may have masters, you have different categories, right? So in short, in degree, if I probably consider degree, these are nothing but categorical variables, right? Categorical variables. Now in this categorical variables, if I directly give my model with this data, my model will not be able to understand, right, what exactly the specific values are basically talking about. Like let's say if I'm a human being, if someone says degree of B, I will be able to understand, right? If someone talks about PhD, I will be saying that okay, this guy has probably done such a huge amount of research, right? But with respect to a model, right, model there only mathematical equations will be working. Model only understands numerical values. So in this case, this degree feature, the model will not be able to understand. So what we should do is that we should try to convert this categorical feature into some meaningful numerical value, and this process is basically called as data encoding. Now, there are various techniques. Again, I'm repeating what exactly is data encoding. Data encoding basically means that we will be converting the categorical features into some numerical values so that the model will be able to understand for a specific purpose. Like in this case, I want to predict the salary, right? And I have to probably convert this degree into some mini numerical value, right? And we'll see that how we can actually convert this kind of categorical values into numerical values, right? So this was the whole idea behind the entire data encoding. And again, there are various techniques which we are going to specifically see. One is nominal or one-hot encoding. Then the other one is label or ordinal encoding and ordinal encoding. And the third one is target guided ordinal encoding. So first of all, we'll go ahead and understand what exactly nominal or one-hot encoded encoding means, okay? So let's consider over here. So I will again be talking about, let's say I have a color feature, okay? In this color, I have something like red, green, and blue. And let's say this data point is continuously getting repeated. So obviously this becomes a categorical feature, right? Categorical feature. So in order for my model to understand this, right, what we will do is that using one-hot encoding, which is also a kind of nominal encoding, we will try to convert this into numerical features. Now, how to convert this into a numerical feature, we'll try to understand that, okay? So this entire values of red, green, blue, right? Red, green, blue in my data set will be created as a new feature. So let me just show you over here. So this red, green, blue will be converted into 3 new features like this: red, green, blue. And in whichever data point there is red, this value will become 1 and remaining all will become 0. Wherever I have green as 1, wherever I have the value as green, that will become 1 and remaining all will become 0. And finally here you can see whenever there is blue, that will become 1 and remaining all will become 0. So this is how, by using one-hot encoding, we are actually converting a categorical feature into a numerical feature, right? And in this technique that we are specifically saying, this technique, how it is basically converting by creating some additional features, these are basically called as one-hot encoding. Now there are some disadvantages with respect to that. Let's consider that in one of my category, I have 100 different categories, right? Then what will happen? It will basically create 100 new features. So this is one of the disadvantage that is probably present in nominal or one-hot encoding, right? So if we have many categories within a feature, we should definitely not use one-hot encoding technique, because that is basically creating that many number of features itself, right? So the other disadvantage is that it is something about sparse metrics. Now, what exactly is sparse metrics? Sparse metrics basically means when we have number of ones and zeros a lot, right? Let's say over here in my categories, I have 10 categories, right? If I try to convert this into one-hot encoding, I will get 10 different columns. But in every column, I'll be having ones and zeros. So this ones and zeros, right? It is basically called as a sparse metrics. And when there is a sparse metrics, it usually leads to something called as overfitting, right? Overfitting basically means my model gets trained very well with the training data, right? So this is another problem with one-hot encoding. So you should not use one-hot encoding when you have various, like when you have a feature that has many categories in short, right? So let's go ahead and see that how we can basically do it with the help of Python programming language, and then we will try to see it over here, okay? So to begin with, again, I've given a definition. One-hot encoding, also known as nominal encoding, is a technique used to represent categorical data as a numerical data, which is more suitable for machine learning algorithms. In this technique, each category is represented as a binary vector, where each bit corresponds to a unique category. For example, if we have a categorical variable color with 3 possible values like red, green, blue, then we can represent this using one-hot encoding like 100010001, right? So let's go ahead and let's try to do this. So first of all, I'm going to import pandas as PD, and then I will also write from sklearn dot pre-processing, and in order to apply one hot encoding, so if you go and search for this sklearn one hot encoder, right? So here you'll be able to see this. There is this amazing library, amazing class one hot encoder in sklearn pre-processing, which will actually help you to perform this entire one hot encoding things, right? Where you get that many number of features, and then you probably wherever that data point is of that specific value, that will become 1, and remaining one will become 0. So we'll try to use this one hot encoder over here. So from sklearn pre-processing, I'm going to import one hot encoder, right? So once I execute this, now let's go ahead and create a data frame. So create a simple data frame, and I will just take one feature, and then we will try to understand that, right? Now what I'm going to do in order to create this data frame, so let's give in this way. So here pd.data frame, color is my feature name, and then I have red, blue, green, red, blue. Okay. So once I execute this, this is my df.head. So here is how my feature looks like: red, blue, green, red. Okay. So now let's see how we can convert this into some additional features by using one hot encoding. Now first of all, the first step is that we create an instance of one hot encoder. Okay. So here I have encoder is equal to one hot encoder. Okay. Now once we create this encoder, the next thing that we have to probably do is that obviously perform fit underscore transform in that specific values, whatever feature that I specifically have, right? Now again, first of all, we will perform fit and then transform. Okay, or you can also use the combination of both of them, right? So I will write encoder.fit underscore transform on df of, and again make sure that you have a 2-dimension on color, right? So once I execute this, this basically creates a sparse matrix. As I said, it basically creates a sparse matrix, and now if I probably try to convert into 2 array, you'll be able to see the value over here. Let's see. So here you can see 001. So what has happened? This red has converted to 001. Now, why this red has gone to last column? Understand over here. This is basically they've done this alphabetically sorting, right? So blue will be the first feature, green will be the second feature, and the third feature will be red, right? So wherever I have red, the last one will be 1. Now see, blue is basically in the first, so this will be 100. Green it will be 010. So this is how we can probably create this. And now what I'm actually going to do over here by using this, right? I can also try to let's go ahead and probably save this in one variable. So this will basically be my encoder values that I have. Okay, or I can write sorry, it should not be encoder, it should be encoded. So let me just go ahead and execute it. So here I have my encoded. Now what I will do, I will say import pandas as pd. Now see the difference, right? So if I write encoded underscore df, it is nothing but pd.data frame, and here I'm just going to write encoded data, comma, columns, whatever columns I will be using. In order to get the columns, I will write encoder dot get feature names out. Okay, so once I execute this, here you will be able to see my encoder underscore df. Okay, so this is how it looks. Color underscore blue, you can see 001, 100, right? And if you want, I can also do the concatenation with this one also, right? See, where there is red, there is last one, right? So I don't have to use any more this particular feature, but I have actually got this as my my own features and numerical features. Now I can actually send this entire data for training my model, right? So this way, we are basically converting a categorical features into numerical features. Now one more thing, whenever you get a new data, then how it is going to happen? So again, I will basically be using encoder dot transform, and remember the new data that should probably be coming, it should be red, blue, or green only. So if I probably write blue over here, okay, if I execute it, here you'll be able to see that again I'm getting a sparse matrix, and if I probably try to convert this into an array, so here 2 array with some brackets, so here you'll be able to see 100, right? So blue is basically 1, so I'm able to also get this for any new data, right? So here you'll be able to see that we are able to do it. How to take out all the features name? Just use this get feature underscore names underscore. So finally, what I will do is that just to make more of your work easy, I will just perform a pd concat operation and write df and the encoded, right? So what I'm going to do over here, df underscore encoded underscore df with axis is equal to 1, that is column wise. Now here you can see that color red has got converted to 001, blue has got converted to 100, green has converted to 010, green has converted to 010, red 001, blue 100. So like all these things are basically there. And now you can also do this with any other data set that you write, right? So what I can do is that I can give you one internal assignment, just try to work through it and try to see this. So I will import cbon as SNS. Here I will be using tips. Right, so this is the data set. I have total build tip, right? Let's say over here sex, smoker, and day time is there, right? All these are categorical features. So just try to do the same thing, right? By using this fit underscore transform and all, and let's see whether you'll be able to get it. So guys, now let's go ahead and understand about label encoding. Label encoding, how does data encoding happens? So here you can see that label encoding and ordinal encoding are two techniques used to encode categorical data as numerical data. Label encoding involves assigning a unique numerical label to each category in the variable. So let's say if you have 3 categories like red, green, blue, we'll be assigning labels like 1, 2, 3, right? So this kind of labels, when we specifically apply a simple numerical value, it will be a unique numerical value for every category. So that is how we can basically perform label encoding. Now let's go and see my df right now. So this is my df.head, right? So this is my df. Now let's say I have all these categories. Now how do I apply a label encoding on this? So for this, you just go ahead and search for sklearn label encoder, right? So here you'll be able to see this label encoder over here, right? Encoder targets label between value between 0 and n underscore class minus 1. So based on this number of categories, you'll be getting the value assigned like this, right? Between 0 to n underscore class is minus 1. So let's see this and how to do this, and we'll try to see. Again, from sklearn.preprocessing, I have to first of all import label encoder. So here I will go ahead and write from sklearn.preprocessing import label underscore encoder. Okay, and here I will just write lbl underscore encoder is equal to, I will initialize it to label encoder, right? And now it is very much simple. All I will be doing lbl underscore encoder dot fit underscore transform on the value of df of in 2 dimension. I will write it as color. Okay, so once I execute this, so here you can see that I'm getting 201120, right? Here you can basically see that b has got assigned to 0, green has assigned to 1, and red has been assigned to 2, right? Based on the alphabetical manner, right? In a sorted way, right? So in this way we can definitely apply label encoder. Now after doing this, again, if I use lbl underscore encoder, and whenever I give any values, something like this, let's say I'm giving as red, right? It will automatically so here it says, okay, I have to write dot transform. Okay, so once I do it for any new value, here you'll be able to get the output also. See, for red I'm getting it as 2. Similarly, if I do it for blue, right, I will be getting 0, right? And similarly for the next one, if I go ahead and write red, blue, and green, right? For green, if I go ahead and write, I'll be getting 1. So this is how label encoder is done. But understand, one problem with the label encoder is that whatever unique values it is assigning, right? Here, this unique label, numerical labels, here you can see that 0 and 1, right? 1 is greater than 0, 2 is greater than 1. So in short, what is happening in this specific feature is that since red has been assigned 2, my model may consider that red is greater than blue and green. If green is assigned 1, then my model will start thinking that because the numerical value is higher, right? And in any machine learning algorithm, when we use it, we use numerical values, all the calculation will be done. So the machine learning model will think that green may be greater than blue, it may be less than red, red may be greater than blue or green, right? So this usually does not occur in this case because these are nominal values. Okay, there we don't assign ranks. Yes, if we had a use case where we specifically need to assign ranks, so for that case, we can definitely use something called as ordinal encoding, right? So I hope you're able to understand ordinal encoding. Okay, understand the problem that we are facing over here. The problem mainly is that when we are assigning labels, right, the unique labels for this red, blue, green, right? So over here red has got 2. Now my model, when this data will come, it will start thinking red may have a higher value when compared to blue or green, right? So this should not happen because these are nominal values. But yes, if there is a situation where you need to assign ranks to these particular values, to these categories, we can definitely do it with the help of ordinal encoding. So let's go ahead and let's try to see what is exactly ordinal encoding and how we can perform ordinal encoding with the help of SQL and Python. So guys, now let's go ahead and continue the discussion with respect to ordinal encoding. Okay, now in label encoding, we already saw the most important thing is that when the ranks or labels were assigned, right? Let's say in the nominal categories also, machine learning models will definitely get confused because here the output that we are getting is that sometimes red will be greater than blue or green, green will be greater than blue, less than red. Right? This differentiator we don't want to create, right? But let's say you have a situation wherein you need to assign ranks, then for that we can definitely use ordinal encoding. Now in ordinal encoding, it is used to encode categorical data that have an intensive order or ranking. In this technique, each category is assigned a numerical value based on its position in the order. For example, if we have a categorical variable education level with 4 possible values like high school, college graduate, and postgraduate, we can represent it using ordinal encoding. Now see, high school has got the rank 1, college 2, graduate 3, postgraduate 4. Now if I probably consider over here, 4 is greater than 3, 2, 1, right? So postgraduate will have higher importance, right? Then graduate will have the higher importance, then college, then high school. Now let's go ahead and see that whenever we have this kind of example where my ranks are important, how I can perform ordinal encoding with the help of Python programming language. So first of all, what we are going to do over here is that it is very much simple. We are going to import. So this will be my ordinal encoding. First of all, we are going to import pandas. So I think pandas has already been imported. So for performing ordinal encoding, again, we will go and search for sklearn ordinal. Just let me search sklearn ordinal encoder. Okay. So this ordinal encoder will be responsible in assigning the ranks, and we'll be using this. You can definitely see out some of the examples, like how we can basically do and not, right, based on the ranks and all. But let me just show you with the help of Python programming language how do we do it. So from sklearn.preprocessing, I'm going to import ordinal encoder. And this ordinal encoder, what I'm actually going to do, I'll create a simple data frame. Okay, so here is my data frame. It looks something like this. So if I probably see df, I have a feature size, then I have values like small, medium, small, large. Okay, so these values are continuously getting repeated. Now what I need to do is that I will assign some rankings for this. Okay, so how do I assign ranking? First of all, I will create an instance. So here I will create an instance of ordinal encoder and then perform fit_transform. Okay, fit_transform, right? So here what I'll be doing, it's very simple. I will write encoder is equal to ordinal encoder, and here I will be having categories with some values. Okay, and here I'll be having values like small. Let's say I have all these values, right? The least rank I need to probably give it to small. So I will go and write small over here, and then I will write medium, and then finally I will go ahead and write large, right? So once I go ahead and execute this, you'll be able to see encoder.fit_transform. Now see, once I do fit_transform on df of size, see what will happen. Okay. Again, let me repeat. In ordinal encoder, there is a feature which is called as categories, right? Now in these categories, I will basically be saying that you need to give less rank to what value and highest rank to what value, like small, medium, large. I've given in this specific order. Now as soon as I do this, I will be getting something like this. See, small has got assigned to 0, so here was small. Then medium got assigned with 1, large got assigned with 2, right? So large needs to be given a very highest rank. So this is how you can simply so easily do it, right? And let's say later on you want to do event transform for the new data. All you'll be doing is giving the data something like this. Let's say I want to give it with small, right? So if I execute this here, you can see that I'm getting the value of 0, right? So now whenever I do this kind of encoding, this is with respect to the ranks, right? I know that I'm purposely giving less rank to small, medium, high, and large. Similarly, I can do it for degrees. I can do it for different values. So I hope you got an idea with respect to the ordinal encoding. Yes, this was it from my side. I will see you all in the next video where we'll be understanding about target guided ordinal encoding, right? So the third category that we have, target guided ordinal encoding, we'll be seeing about that. Okay. So yes, this was it from my side. I will see you all in the next video. Thank you. Okay, so we're going to continue discussion with respect to feature engineering, and in this video we're going to discuss about a new encoding technique which is called as target guided ordinal encoding. Now what exactly it is a technique used to encode categorical variable based on the relationship with the target variable. So let's say if I am having a categorical variable, based on the relationship with the target variable, we will try to convert this categorical variable into numerical variable. This encoding technique is useful when we have categorical variable with a large number of unique categories. Okay, super important. So what we do in target guided ordinal encoding, we replace each category in the categorical variable with a numerical value based on the mean or median of the target variable for that category. Okay, so let me quickly go ahead and show you one example. So for this, I will be creating this simple data set. So if you see this, this is a simple data set where I have two features like city and price. So guys, so here is a data frame with two features, that is city and price. Now this price, we will consider it as a target variable and we'll try to convert this categorical feature based on this target variable. Now how it is going to happen? Let me just read this last line for you. In target guided ordinal encoding, we replace each category in the category variable with a numerical value based on the mean or median of the target variable for that category. So let's say here I have New York and here also I have New York, right? And over here the price is 200, over here the price is 180. So what I'm going to do, if I want to replace New York with a numerical value, I will take the mean of this both value, okay? And then I will probably replace it. Now how we can perform this? It is very much simple. I will take this df dot and I will just do a group by, okay? Now once I'm doing a group by, I will do this group by based on city, okay? And then I will probably consider the price part over here, and let me just go ahead and find the mean. Okay, so if I execute it, here you'll be able to see with respect to London, I'm getting the mean as 150. So London over here is 150, only one value. Paris is 310. How? Because Paris over here is 320, over here it is 300. So if I try to calculate the mean value, it is going to come as 310. Similarly, Tokyo 250 is there. What I will do, I will also try to convert this into dictionary. So right, so I will say to dict, okay, and this I will store this as my mean price as my variable. Okay, so if you probably go and see this mean price, it will be in the form of dictionary. London is 150, New York is 190, Paris is 310, and Tokyo is 250. Okay, now after this, what I'm actually going to do quickly, we will just go ahead and write df of my new feature, that is city underscore encoded, and this encoding is basically based on the target guided ordinal encoding, right? Is equal to nothing but df of city dot map And here I'm going to specifically use something called as mean price. Now, as soon as I map with mean price, that basically means wherever I have London, right? First of all, let's see the output. Okay. So here I have DF, and if I execute, see, wherever I have New York, that got replaced with 190. So here it is basically 190 over here, because the mapping is basically happening with respect to this specific keys, right? Wherever I have those keys, it will be getting replaced by the mean price. So now you'll be able to see New York, I'm having 190, London 150, Paris 310, Tokyo 250, New York 190. Now I don't have to consider this feature, right? I will be able to just consider this two feature, right? That is price and city encoded, and I can probably give it to my model for the training purpose. So here I have city, and here I have specifically city underscore encoded, right? So here you'll be able to see these two features, sorry, city underscore encoded and price. Okay. I will be giving only these two features to my model for training purpose. And I have actually ignored this because I've converted this into some numerical values based on the target guided ordinal. Now, my model will be able to understand the importance, right, over here, because we have taken the mean with respect to these values that we have, right? So which one is basically having the highest price that may be given bigger importance when compared to others, right? So this technique is basically called as target guided ordinal encoding. Now, one internal assignment for you that I will be giving. So what you do is that import cbon just for practice purpose, because we will later have a lot of EDA dataset also, which we also need to try. So load dataset. So let's consider I'm going to load the dataset with tips, right? So if I probably see this dataset, right, I want you all to convert this time based on the total bill, right? Now just go ahead and try it out, and how you can probably do it. The same technique is very much simple. Just try it out and let's see whether you're able to get the output or not. So yes, this was it from my side. I hope you're able to understand the target guided ordinal encoding. Hello guys, so welcome to the class. Now we're going to start exploratory data analysis. And again, in this video, we're going to consider the red wine dataset. Now, if you don't know about red wine dataset, guys, this is basically present in UCI, machine learning repository. You can probably go and check out the dataset. You can check out what all information it specifically have, how many features it has. So just let me give you a brief overview, and then we'll try to understand what all we are going to do in exploratory data analysis. Till now, we have seen feature engineering, we have seen about outliers, we have seen so many things, right? Now, EDA is all about understanding the specific dataset that we have, right? So let me just go ahead and explain you about the red wine dataset. So this two dataset, the dataset are related to red and white variant of the Portugal's Vinho Verde wine. So this is a kind of a wine over there. So due to privacy and logistic issues, only physicochemical and sensory, the output variable are available. So if you probably see how many input features you have in this particular dataset, you have something like fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur dioxide. So you also have total sulfur dioxide, density, pH, sulfates, alcohol, and the output feature that you specifically have is something called as quality score. Okay, so you basically have this quality score as your output feature. Now what we are going to do is that if you want to probably see the dataset, I've downloaded the dataset, right? And in this dataset, you can see these are all my features: volatile, citric acid, residual sugar, chlorides, free sulfur dioxide, pH, sulfate, alcohol, and this quality that you will be able to see, this is my output feature. Okay, so there are different qualities based on the different kind of wines that are available. Okay, and based on that, a label is actually assigned. The higher the quality, obviously the quality of the wine also increases. Now the main agenda of this session is that we will try to perform EDA on this, and we'll try to perform in such a way that we'll try to understand about this particular data, right? So this data is already downloaded, I've kept it, and this will also be available in your resource section. So what I'm going to do, first of all, quickly let's start this, and we'll try to see what all things we can basically do. So first of all, I'm going to import pandas as PD, and this will be my dataset where I'll write pd.read_csv with respect to this, and this will basically be my red wine. Let me just see wine quality red.csv, right? And now if I probably go and see my df.head, you'll be able to see this is how my dataset looks like. Okay, now we are going to see most of the features are numerical over here, and this is basically my output feature. So let's go ahead and see that what all simple EDA we can probably do out of this particular dataset. Now, as we go ahead, if I probably write df.info, right? So this is going to give me all the features that I specifically have in my dataset. So here I have fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, these all are there. And here it is also saying non-null. That basically means here you can probably see that I think missing values is not there. And if you also see the data type of all these features, these are like float, and the last feature is basically an integer value. Okay, so this is what df.info says. If you press shift tab, you'll also be able to understand what it does, right? This functionality. So it prints a concise summary of the data frame, and here you'll be able to see this entire concise summary, and you can see all the features that is basically using, right? So you can definitely see in this particular way. So here, whenever you want to see the summary of the entire dataset, you can use df.info. So here I'll just write a comment. Summary of the dataset. Okay, so this is what we will be able to get. Now you will also be able to understand, like, see, there is a functionality which is called as df.describe. Okay, and if I probably press shift tab, here you can see that it generates the descriptive statistics. Now what are the most important things with respect to the descriptive statistics? Probably you want to see the 25 percentile, 50 percentile, you want to see the 75 percentile, the minimum value, maximum value, the standard deviation, all those information you can probably get it through df.describe. Okay, so here are again what all features are there. You can see that all these features you'll be able to get it and all, right? So once I probably execute it, here you'll be able to see that, see, in fixed acidity, what is the count? Count basically says how many total number of records are there. What is the mean for each and every feature, right? Each and every feature. So here quality has also been taken, but this quality will be my output feature, right? So what will be the mean? What will be the standard deviation? What is the minimum value? What is the 25 percentile? What is the 50 percentile, 75 percentile, and maximum value? And this is with respect to all the numerical features we are able to see, right? So here we are basically getting a descriptive summary of the data set, right? Isn't it amazing? So once I probably execute it, here you'll be able to see the descriptive summary. Perfect. Let's say you want to probably see how many number of records and columns are there. Just go and execute df.shape, right? Once you do df.shape, here you are able to understand that you are having 1599 records and 12 columns, right? So here also you'll be able to see. Let's say you want to list down all the columns, list down all the column names, right? Column names. So here what you can do, you can just write df.columns, right? So here you will specifically be getting all the column names that are available in this data set. See, I'm not thinking with respect to machine learning prediction right now. We'll just focus on EDA, that is exploratory data analysis, and we'll try to understand many things about the data, right? Now, as usual over here in the description only I've written the output variable is basically your quality, right? So if I go ahead and observe about df of quality, right? df of quality. So here you will be able to see that I'm able to see different values. But if I really want to understand how many different unique values are there, so I can just execute this unique function, and here you'll be able to see that I will be having this many number of qualities of wine. That is somewhere around 6, 1, 2, 3, 4, 5, 6. Where this eight value that is having, right? That is basically the quality of the wine. The more high the quality is, the more the better wine. So there are 6 different types of wine that is available over here, right? So through this way, you can basically find out the unique values that is probably present in your output feature. Okay. Now the next thing that we are going to see is that is there any missing values in this, right? So we want to check the missing values in the data set. Now in order to check the missing values in the data set, all I will do df.isNull dot sum, right? So if I do this, here you'll be able to see that I'm getting 0, 0, 0 values. That basically means there are no missing values as such. If there were some missing values, we have already discussed so many different feature engineering techniques, so through which we can actually fix the missing values. Yes, we have seen our mean imputation, median imputation, mode imputation, different kind of imputation techniques altogether, right? So over here, definitely there is no missing values. Now, I also need to check whether there is some duplicate records. See, if I have in my data set some data, right? So what will happen if I have duplicate records? It will be of no use, right? And what I can do, I can also drop those duplicate records. So in order to find out the duplicate records, how do I find out the duplicate records, right? So how do I find out probably all the duplicate records? That is what we are going to see. So now for this, you can basically write df dot, and there is a function which is called as duplicated. Okay, so here you can see duplicated. So if I execute this, here you'll be able to see wherever there is a duplicate, that will be true, otherwise it will be false, right? Now if I just want those records that are duplicate, what I will do, I'll just write on top of this my df values, right? So here you'll be able to see all these values. So total 240 records are duplicate, similar kind of values are present. Okay, so duplicate values are also a way of remove, like we can remove this, right? If I probably just write not of this particular thing, I will get all the records without any duplicates itself. So definitely you can remove the duplicates also. Now for removing the duplicates, because duplicates will not play a very important role, right? So remove the duplicates. For removing the duplicates, all I will be doing is that I'll write df dot drop duplicates. Okay, and if I want to make this operation permanent, so there will be a feature which is called as in place. So if I put this value in place is equal to true, so here you'll be able to see that my entire duplicates will get so see this df of duplicated, right? So if I probably see this df dot shape now, here now you have just 1359 records. Before we had 1499 records, I guess, or 1599 records. So that 240 records has been removed now, right? So through this way, we have simply removed the duplicates in this particular data, right? So I hope you're able to understand the way. I hope you're able to see what are things we are able to do it. Okay. Now let's go ahead and see about the correlation. How do I see the correlation? It is very much simple. All I will do is that I'll write df.corr, and if I probably execute it, this is what is the correlation with respect to each and every feature, right? All these values you'll be able to see. If you want to see in a visualized manner, right? In a visualized better manner, so I will import cborn as SNS, right? And I will write SNS dot. There is something called as heat map. Let's see, SNS dot heat map. And here in this heat map, I will just write df.corr, right? So by default, Pearson Coran correlation is there. Now here, you will be able to see that with respect to different colors, right? You'll be able to see the relationship. Now, if you want the values within this, if you want the values inside this, so what you can do in heat map, you have a feature which is called as anode. Okay, I guess this is only the anode part. So anode, right? So here, what I will do, I will just make anode is equal to true. That's it. Now, if I probably execute it, you'll be able to see this, right? But still, there is a problem because the values are like too much cubesummed. So what we can do is that we can probably set up the figure size with respect to the plotting, right? So here, if I search for plot.fig size, okay, fixed size in the Python, and let's see matplotlib. Okay, so I'll just see the official documentation. It is very much simple. plt.fig, and you can probably say the fixed size over here, right? So I'll do something like this, right? I will just import matplotlib, import matplotlib.pyplot as plt, right? And then I will say plt.figure, and here I will set up my fixed size. Fixed size is equal to, let's say 10,6. I hope so it works out. Fixed size, this is there. Now I will just import this over here and let's see the diagram. So now you can see that it's fit completely, right? So now my diagram looks pretty much better, right? So all I'll do is that I'll just go ahead and copy this over here on the top. So I've selected my I've basically selected my entire figure size, that is 10,6, and based on that you can just see that how good your figure is adjusted, and you'll also be able to see that how one feature is basically related to the other feature, right? So through this way we are able to see our data set in a better way, and we are able to see that how good it looks like with respect to this kind of implementation, right? So in this, but why we are doing this, it is very much simple, guys. We really need to understand how good this is. Are you able to understand about the data set itself? Are you able to understand about the features? Are you able to see some relationship? Is there some missing values? Are you able to drop the duplicate values? All these things will be there. Okay. Now further going ahead, what I can also do is that I'll just try to apply some more visualization. Okay, visualization. But I think we have practiced so many number of times now, different things. I've done feature engineering for you all, so many different examples we have seen. Now with respect to any data set, what are things you have to actually focus on? So if I write df of quality dot value counts, value underscore counts, right? So if I probably write value underscore counts, right? So here you'll be able to see that this fifth category is basically having 577 counts. So in your output feature. So this is definitely a imbalanced data set. In feature engineering, obviously, you know how to handle the imbalanced data set and all. You've seen about the smart techniques and all. So we can definitely apply all those things. But EDA, now here, you can definitely come to a conclusion. So what conclusion you're making over here? So I can basically write the conclusion over here also. Conclusion is that it is an imbalanced data set, right? So here definitely you're able to see this. Yeah. Imbalanced data set, because the number of categories is not at all equal with respect to all the output categories, right? So what you can do is that you can also, if you probably want to check out with the help of matplotlib plot. So I can also use a dot plot if you rules, and here I can also use a bar plot, right? So if I execute it, so let's see what is the error. Series plot should not be called an artificial keyword argument. Okay, not a problem. So here value underscore counts, then dot plot. Just a second. Kind is equal to. So now you'll be able to see this, right? Yeah, I did not put the parameter kind because inside this plot there are also other parameters. So it is telling to put positional keyword argument. So keyword argument is basically required, right? So here I can also put my x-axis and y-axis. So here let me put my x label. X label I can put it as wine quality, okay, and plt dot y label. Here we'll specifically put it as count. And finally this will be plot dot show. X label. So now here you can basically see the output and how it is basically looking, right? So there are different things with respect to this, okay? One more thing that you can specifically do is that you want to probably see the distribution of each and every feature, right? That also you can basically do. So guys, now let's say that I want to probably see the distribution of each and every columns that is available in the specific data set. So if I probably go and see df.head, right? So this is how it basically looks like, right? So if I want to see the distribution for each and every data set, so for I will just write for column in df.columns, right? And what I can do after this is that I can basically write sns.histplot, and here I can basically write my column name, okay? Df of the column name, df of that specific column name. Along with that, what I will do is that I will also make sure I will write it as kd is equal to true, right? So I hope all the parameters are right with respect to this. And if I execute it, here you'll be able to see for each and every features, this KD plot has got mapped, and this is how it is basically looking like, right? And every plot has basically been joined. So that is the reason there are a lot of overlapping in this, right? But if you want independently to see it, you can also write like this SNS dot his plot, okay? And here you can probably write df of some, let's say alcohol. You can probably see this. You're going to see with the help of histplot, you'll be able to see. So this way you can also check out all the distribution in a specific data set, and you can probably see how the histogram is or how the PDF function is. Okay. Finally, in Seaborn, there is also a very amazing thing. There's amazing functionality which is called as pair plot. Okay. And this pair plot will be super important for the purpose of univariate. So here you can write univariate, bivariate analysis, right? And obviously you can also check out multivariate analysis. Like you want to compare one feature with the other and then the other features with the other, then you can probably use this pair plot. And here I will just give my DF. So overall, you'll be able to see this particular diagram where it will probably show that how one feature is correlated with other features in a diagrammatical way. This will probably take some time for the execution because it is obviously, it'll take at least 20 seconds to execute because there's so many features, there's so many different data sets altogether, right? So yes, I think now it'll get uploaded. Till then, I will just go ahead and show you categorical plot also. That is the next thing that is going to come. So categorical plot till this gets executed. And yes, this will take time, guys. This will definitely take time because there's so many data points. So this is how you'll be able to see it will look like. This is just comparing one feature to the other, and based on that, you'll be able to see how your plots are, right? So negative correlation, positive correlation, based on that, that is how your data is basically scattered. Now I can also use categorical plot with respect to my output feature. So in Seaborn, you have something called as categorical plot, SNS.categorical plot, and here in my X value, I will give my quality, okay? And in my Y value, I'll give my another feature. Let's say I want to probably give alcohol or volatile acidity, anything you give, residual sugar. Let's say I want to give alcohol, right? So ALCHOL, alcohol, and then my data, which is my third parameter, will be my DF. And let's say I want to give it in the form of a box plot, okay? So here there will be another feature which is called as kind, and here I can basically give my box plot, right? So if I execute this, here you'll be able to see with respect to quality and alcohol. Over here, I'm getting a categorical. See, cat plot is basically just like a categorical plot. So if I press Shift Tab, you'll be able to say figure level interface for drawing categorical plots on facet grid, right? So here you can basically see alcohol based on this particular values. For this quality, here you definitely have outliers. On the fifth quality, you have a lot of outliers. On sixth also, you have some outliers. So this way, you'll be able to see this categorical plot itself, right? And if you probably want to see, just a second, file save error, no worries. Okay, I've saved it. Let's reload this. So this kind of problem may also occur. Not worries. I'll just reload it so that you'll be able to get it. Okay. So this is my categorical plots. Okay. So here I have to probably again use SNS.pairplot. You can probably execute it, and then you can also use categorical plot, right? So for the categorical plot, it was very simple. All I will be doing is that I will be writing SNS dot with kind of box. Now automatically I'll be able to see that specific plot. So when you are probably executing in this lab, right, P-2 skills lab, so sometimes this kind of issues will come, definitely reload it, but it's all about scaling. That will take care of it. Will probably be saving the file also. Okay. So then we got to saw about the categorical plot. We saw the box plot itself. You can also use scatter plot, right? So here in SNS you also have something called a scatter plot. Okay. So SNS.scatter plot. Let's say I want to see scatter plot with one feature like alcohol, a numerical feature. Specifically in scatter plot, we use numerical feature. So let's say alcohol, and the other feature that we probably want to use is Y. And let's say over here I have pH, right? And since quality is basically determining your output category, so here I can basically use Hui parameter, which will be a categorical value. So quality I can basically assign over here. Okay. And finally my data will be DF. So if I execute this, there's some error. Let's see. Could not interpret pH for parameter Y. Okay. Why pH is not there? Okay. Because the feature, if I go and execute this df.head, let's see whether pH feature is there or not. P capital H. Okay. Fine. P capital H. Now if I execute this is how my scatter plot looks like with respect to different qualities, right? With respect to 3, this is the color. With respect to 4, this is the color. I can also use another type over here with respect to this also. So I hope you got an idea with respect to executing or performing an EDA with respect to the red wine data. So yes, this was it about this, and we'll again see different examples with respect to exploratory data analysis. But again, at the end of the day, just try to understand that EDA helps us to understand about the data, the missing values, the duplicates column that is available, or duplicate features, not columns, but at least duplicate data points that is available, the relation, the correlation between them. You'll also be able to see bar chart, you'll be able to see categorical plot, you'll be able to see pair plot. So different kind of plots, you can definitely check it out with respect to that, right? So I hope you were able to understand this particular video. I will see you all in the next video where we will be performing EDA for another data. Hello all. So guys, we are going to continue the EDA series. In this video, I'm going to take a new dataset which is called as flight price prediction, and we're going to perform exploratory data analysis and feature engineering. Now you'll be getting a complete idea that before machine learning model training, right, how much work we specifically need to do with respect to EDA and feature engineering. Because whenever you get the data, right, it will not be very clean data. It will be just a raw data itself. You'll be having a lot of category features. You'll be having different numerical features and all. And unless and until we don't clean that data and convert into a better numerical format, we will not be able to provide it to the model for the proper training. Okay. So as said, please make sure you practice this well, because the dataset that I'm taking is a difficult dataset. It is not a very simple dataset. It is a difficult dataset, flight price prediction. You'll be seeing different features and the values that is present over there. You'll find a difficulty. Now you need to think that how can I probably clean this dataset, or what all exploratory data analysis I have to specifically do. Okay. So as usual, what I'm actually going to do over here is that. So here the dataset info is basically given. So this is nothing but flight price prediction. So this is the dataset that is basically present over here. Okay. And you'll be able to find out all the information regarding this particular dataset, what all features you specifically have, and the target feature is basically price. Okay. So all this information is basically present. So what I've actually done, I've copied this entire features. I put it over here. Okay. So this is my features that are basically present, right? If you want to probably see the dataset, I will also be downloading the dataset for you. So here is the dataset that is already there. Okay. So let me just open this. Probably you will not be able to open it because it is an XLS file. But if I try to open it from the file, you'll be able to understand. But let me just read that specific file and let me just show you how the dataset will look like. Okay. So as usual, initially what I will do is that I will be importing some important libraries. So for this, I will quickly copy and paste it so that you'll be able to see this. So pandas, numpy, matplotlib, and Seaborn is there, right? And I'm going to basically import all these libraries. Then what I'm actually going to do, I will be using pd.read, and this file is basically present in the Excel format. So I'm going to use Excel. Then this will be flight price XLS, and this I will try to save it in my DF value. Okay. And then let's see the top 5 records. Now you'll be getting an idea how my dataset looks like. So my dataset has features like airline. See, this is a flight price prediction. Okay. So flight price prediction is there over here, and here you have features like airline, date of journey, source, destination, route, departure time, arrival time, duration, total steps, additional info. So these are all my input features. And based on this, we need to predict the price. Okay. Now, one very important thing that you will probably see in this data set, you have so many different features. See the value, how it is present over here. See, time is there, right? If I directly give this particular data to my model, it will not be able to understand. So till we give the model training, right? Till we give the specific data set for the model training, what all specific ED and feature engineering we need to do. And for this, I will take column by column, every feature, and we'll try to clean it. Okay. So all the things we are basically going to do in this particular video. So I'm telling you guys, if you practice this, right, you will be able to crack any EDA part, any EDA with respect to any kind of data set that you get in the future. Okay. So this is the top 5 records you'll be able to get over here, and this, if I write df.tail, this is the last 5 data records that you'll be able to see, right? And this is the data over here, Asia, India, all these things are specifically there. Our main aim is to basically predict price. Okay, so this is what we are going to see later on, but we're not doing the prediction. We'll just do ED and feature engineering and we'll clean the data. Now, quickly to get the basic info about the data, So what all things you need to do? I will basically write over here as df.info. So once you write df.info, so here you'll be able to see that how many columns are there. There are 11 columns, and total number of entries are 10,683. So these are all my features, right? And one thing you can observe, all these features are object type. Only the last feature is basically price type. So if you're probably converting this into a numerical value, we may also have to do typecasting into int or float, right? So many things are there. Just keep on observing what all things we'll be doing. Okay, and if you want to probably see with respect to df.describe, since there is only one numerical feature, you'll just get the information of price itself. Okay, because df.describe will basically give you mean, standard deviation, mean, 25%, 50%, and all. And this usually happens for numerical features itself. Okay, now let us go ahead and let's just do the feature engineering and EDA parallelly, right? So this is what is my df.head, and now let's take one by one. Okay, see, airline is there, definitely. Date of journey is there, source is there, destination is there, route is there, departure time, arrival time, so many things are there. Now first, let's forget about airline. We'll go ahead and see how to handle this date of journey. And right now, you probably see over your date of journey is basically in the object type, right? So guys, now let's go ahead and see that how I am going to probably handle this, that is date of journey, right? Because this, you can see that it is a proper date, right? Date format. Right now it is an object and we can convert that into date, but still date model will not be able to understand. So with the help of feature engineering, what I will do is that I will try to separate the date, month and year completely separately. Now how I will do it with the help of Python programming language. So this will be my first feature engineering process, and trust me guys, if you learn this well, let any feature be coming, right, you will be knowing what you really need to do. You need to probably clean the data properly, convert that into numerical values and keep it ready for your model training. So here, what I'm actually going to do, feature engineering process, we are basically going to start. So here I'm going to write final df of date. So I'm going to create a new column, and what I'm actually going to do, I'm going to take the date of journey. So if you could go and see, this is the date of journey. And if I write .str.split, right? So here, what I'm doing, I'm splitting that particular data, and I'll split it with this /, right? Then I will be able to get the first element that I'll be able to get will be the date, right? So if I split this, and here I'm specifically going to use a separator that is /, and if I get .str of 0, if I just take the first element, it will basically be giving me the date. If you don't believe me, I'll just execute this separately, right? And you can probably see over here, all these are the dates of all the column rows over here, right? So 24, 1, 9, 12, like this, we are able to see this. And this all, I will try to store it in my date column. So this is what I'm actually doing. Now, similarly, what I can do for the second one, I want to capture the month, right? So for capturing the month, what I can do is that I can probably also do the same thing, but this time after splitting it, right? This will be my str of 1, the first index. So this will basically be my month, right? So str of 1, right? And finally, the last one is which is basically the year. So here I will do for this to get the year, I will just write str of 2, and the feature that I'm actually going to create is basically year. Okay. So here I have my entire df. Okay. Now if I probably go and see df.head, okay, here you can probably see, if I just scroll to the right, here you'll be having date, month, year, right? But there is one problem in this, right? What has actually happened, right? If I probably go and search for, see, price, date, month, and year has already been coming, right? Over here as a new feature. So I have all the values. But if I go ahead and write df.info, right? And if I go and see df.info, you'll be seeing the 3 additional features that have got created, right? Date, month, and year. These are still object type. So I have to now convert this into numerical, right? If I don't convert it into numerical, it will be in that object state only. When we say object, it is basically a string value. So how do I probably convert this? So it is very much simple. What I will do is that I will just take df of date, okay? df of date, and I will just write df of date dot as type. So I have to convert this data type itself. So if I write df of date as type of int, it will basically convert my entire date value, which is an object, into a numerical value. And this I will show it back into my df of date, right? So this will be with respect to that. And similarly, the next feature what I will do is that I will write df of year, month, and here I will go to write df of month dot as type, and here I'm going to basically use int. Okay, and finally df of year, which will again go as my df of year dot as type, and this will basically be my int. So I'm basically converting all my object type into a integer type, right? So once I execute this, this is got executed. Now if I probably go and see my df.info, the last 3 columns that you'll be seeing now it has become int64, right? Now this is what we are able to do, right? Now since we have converted this date of journey into date, month, and year, I can drop this particular column because this column will nowhere be required. So in order to drop, so here I'll be writing drop date of journey column, right? So in order to drop this, because I'm nowhere requiring it, I will write df.drop, and here I will just give my date of journey, date underscore of journey, and this will basically be with access equal to 1, comma in place is equal to 2. So I'm just doing this as an in place operation, and if I probably see df.head, you'll be seeing that now I will not have that particular column. Instead, I will be also having the other 3 columns, that is date, month, and year, which is in the numerical format. This is so perfect, so nice. I've handled one column successfully. Now similarly, we have to go ahead and do for the other column also. Now similarly, like how we did it for date of journey, similarly arrival time is also there, right? Now here arrival time, you'll be able to see that I'll be able to get this kind of hours. March 115 is there, then 425, 10 June is there. So we also need to find out how we can probably try to do this, or how we can probably take out month and year, month and days. Sorry, not month and days, but time, right? The arrival time with respect to hours and the seconds or minutes. Sorry, hour and minutes. How we'll be able to take out from this, because this all information is not that important, like 22 March and all. But the time is super important because here it is basically saying this is 1:15 p.m. right? So I will probably be getting 13 value and 15 value separately as a 2 column, right? One can be the hour column and one can be the minutes column. So how do I do that? How we can probably do that? We'll try to see. Okay. Again, similar thing like how we did it over here, like str.split. Here also what we can do is that we can basically split this, right? And the major split is basically with respect to this kind of colon, right? You'll be seeing that in every data point the colon will be there, right? So I will be able to divide the particular data time, that time with respect to hours and minutes. Okay. So for that, what I will say df of arrival hour. So I'll create a new feature with respect to arrival hour, and I will probably write very simple df of arrival time, and here I will basically do again str.split. And here the split will basically happen with respect to colon. I will take the .str of 0, which is my first value. Okay. I will copy this again for the arrival minute, it will be str of 1, right? So this will basically be my str of 1. So now if I probably go ahead and execute it, and let's go and see the top 2 records. Okay, so here you can see that if I go into the right, this is again arrival hour 0113, arrival minute. Okay, so this minute is basically creating a problem over here, right? Because the reason is that we are getting that entire thing in this particular column. We are getting this 1022 March. So we can also handle this. So first, what I will do, okay, let's do one thing. Let me just execute this because okay, arrival time and this is there. Okay, fine. So what I'm actually going to do before this, I'm going to write one more code. So I will say df of arrival time, and let me go ahead and apply one lambda function. Okay, so dot apply. Okay. To fix that particular problem, what I'm actually doing is that I will use a lambda function. I hope a lambda is very much clear with respect to Python. And then I will do x.split on the empty braces, and I will take the first 0 element. What does this basically mean? Is that whenever I have this kind of scenario, right? First of all, I just need to take the hours and minutes in every values. Right now I have 10 June over here, 22 March over here. So with the help of this specific code, when we're splitting with the blank, whatever will be the first elements, we'll get that. So if I execute this here, you will be seeing that I'm able to get all the time. So this additional things is not getting captured, like 22 March, 10th June, and all are not getting captured. So this, first of all, I will try to update this in my df of arrival time. Okay, and then later on we can apply this thing. So df of arrival time. So here I'm able to get this. Now if I do this str out of split of 0 and 1, I'll be getting my hour and minute. So now you think see over here, arrival, hour and time, minute. This issue is fixed. Now you'll just be getting hours and minutes because we have removed all this 22 March and 10 June, everything from there. Okay, so here I'm able to see my df.head. Now the next thing is that obviously this column that is getting created, this is in the form of objects. So quickly, what I'm actually going to do, again, copy paste this code and make it as an integer. So here I'll just take this code and just say df of arrival hour as integer. So this will also get converted to arrival hour, and this will be arrival minute. I'm just trying to convert this into this, and this will basically be my arrival minute. Okay, so once I execute this, finally I can just go ahead and drop my arrival time. Now I will not be requiring this, right? So it will be arrival underscore time. I think the spelling is correct. Arrival underscore time, and this will basically be with access equal to 1 because I nowhere required this now. So same step, I've done that. So finally, if I go and see my df.head on the top 2 records, I will not have my arrival time also. So finally, see, so many additional numerical columns we have created. So we are actually cleaning the data, and this is all about feature engineering, right? This is entirely about feature engineering, what we really have to do, right? So guys, now till now with respect to feature engineering, we have handled 2 features, right? Now still we have more features over here. Similar kind of thing we have with departure time, then we have with duration. So what we are specifically going to do, again, let's go ahead and handle departure time also. For doing this, again, the simple way is that, again, I'll be using str.split because there is directly colon over here. So over here in departure time, so departure hours and departure minutes, we can basically convert this. So quickly what I'll do, I will say departure df of departure underscore time. So I hope this is getting executed. Okay, fine. Departure underscore time. And here I'm just going to write departure underscore hour. Okay, and this will be basically departure underscore minute. Right? So once I execute this, now I will probably be able to see df.head. And finally, here, if you go and see downwards over here, you have departure hour and departure minute. Okay. So again, if you want to probably check whether this new feature that we have created is of object type or integer type. So this is integer and object. So what I'm actually going to do quickly is that, again, departure hour, I'm just going to convert this as type int. Okay. So departure hour and departure minute, I'm just going to convert this as hour. So quickly, I'll just copy and paste it as type, and this will basically be int. So instead of writing comma, I'll write like this. So this will be nothing but departure hour. Okay. Departure hour underscore hour. Now see guys, slowly, right? Every feature is basically getting converted into a meaningful numerical feature, right? That basically means we are going in the right path, right? So similar departure min, I'll just copy this entire thing and paste it over here. So this will be nothing but departure underscore min. There's nothing but respect to departure underscore min as type, right? So here is it, and then if I probably go and see my df.info, so this will basically get converted into numerical value. So see, date, month, year, arrival hour, arrival minute, departure hour, departure minute is all done, right? Now what we can do, this departure underscore time can be deleted, right? So again, what I will do, I will write over here as df.drop, and here I'm just going to write departure underscore time, okay? And this will be with respect to access is equal to 1 in place is equal to true. So done. So this is finally my df.head if I just see the top 2 records. So good. This is amazing. We have done almost all the things. Our new features are getting created, and we're also getting it very much easily. Okay. Now the thing is that now let's go ahead and pick up any other features. Like over here you have total stops. Over here you have duration. For the duration also you can probably use this, convert this into like how many hours of duration is there. Or what you can do is that you can also convert directly this into minutes, right? Minutes or hours, it is up to you. Okay. So let me just show you some more features. Let's take some categorical features. Right now till date time features we have actually seen. So categorical features, let's start with total stops. So total stops, what I'm going to do, I'm just going to write df of total stops dot unique. So if I probably see dot unique, here you'll be seeing that I'm having non-stop, 2 stop, 1 stop, 3 stop, nan is also there, 4 stops. So all the specific values are there with respect to so many things, right? Now understand one thing, guys. When we say non-stop, that basically means no stops are there from place A to place B with respect to the flight. So we can be assigned some kind of labels over here. Like what I'll do for non-stop, if it is a non-stop flight, usually the flight rates are cheap, right? If you probably have a little bit of domain knowledge regarding airlines. If there are 2 stops, still the price will keep on increasing. If there's 1 stop, then the price will keep on increasing. And 3 stops also, the price will keep on increasing. So over here you also have nan values. So nan values we need to see that how we can probably handle with respect to the total stops, right? If nan values there, then obviously you have missing values. So we need to handle this kind of missing values, and we'll try to first of all find out how many nan values are there. So in order to find out, I will just write df of total underscore stops. Okay, and here I'm going to specifically say is null. Okay, dot is null. I'll just execute it. So over here, definitely just by seeing this, you're not able to see this, right? So what I will do on top of it, if it is null, then only I want that specific record. So here I can see only 1 record is there with nan value and total stops. So now what we're going to do is that we're going to replace this nan value with 1 stop. Okay, so let's see that how we can probably do it. And for this again, we'll be using some map function. So what I'm actually trying to say is that I will say, okay, find df of total underscore stops, right? Total underscore stops, and this we will try to replace with df of total underscore stops dot map of this to this. Now here mapping will be basically non-stop will get replaced with one, stop will get replaced with one stop will get replaced with non-stop will get replaced with zero because there is no stops. One stop will be replaced with one label. Okay, so one label, one integer value label. Then two stops will be getting replaced with two, three stops will get replaced with three. Now here main purpose why I'm doing that because I want to convert this categorical feature into a numerical feature, and why I'm giving ordinal labels, right? Understand one thing that because when we have more number of stops, right, the price of the flight will keep on increasing. So I'm purposely making sure that I give ordinal labels to this so that my model will be able to understand and it will be able to find out the relationship with respect to the price. So quickly, what I'm going to do, I'm just going to copy all these things and paste it over here. Now you see this, the mapping will happen something like this. So yeah, here we are non-stop with zero, one stop with this, four stops with this, and I'll copy this over here, something like this. Four stops will get replaced with four, and finally my np.nan, which is nan, right, it'll get replaced with one because maximum number of mode when we see with respect to total stop, it is one stop, right? So let's see whether this will get executed or we'll get some kind of error. So three stops, three, so one stop, one, fine, this works fine. So finally you'll be able to see now if I probably go ahead and see with respect to is null, we should be getting empty. There is a lot of nans that we are getting. It's okay. We will just try to execute it because I think I've executed it 2 times. So I'll just execute it once more. Okay. Because I think I've executed it 2 times. So I had replaced it. So that is the reason it is coming something like that. But I've understood the problem. Now it will be perfectly fine. Okay. So I'm executing it once again over here. So done. This is done. And now here you can see that over here, all my data points is non-filled, the NaN value is handled, right? So here, that is what we have done. You just try to execute it for the first time and it will come. I think by mistake, I executed it 2 times. So that is the reason I was getting that so many different NaN values altogether. Okay. So please make sure that you watch that with respect to this, right? Now, if I probably go and see with respect to df.head, right? Or df.head of 2, right? So here, you'll be able to see total stops will have the specific labels. Now, there is also one column which is called as route. Route is basically having the source and destination. I can drop this because I have 2 separate features like source and destination. So I can write df.drop of with respect to 2 features, or I'll just use 1 feature. So one feature is basically, which is the feature route with axis equal to 1. And here I'm just going to make in place is equal to 2. So once I execute it, so now if I go and see df.head of 2, so I'm able to find out route is gone. Okay, perfect. There is also a feature called as duration. Now just think over it how you can handle duration. I'll just show you one way. You just write out. Okay, here with respect to duration, I require this hour separately, minutes separately at separate fields. Now in order to get hours, it is very much simple. What I will do, I'll just use this. See, very simple. I will say df of duration.str.split with respect to blank. Then when I write str of 0, I'll be getting 2 hours. Then from this 2 hours, I also have to remove this h. So I'll write .str.split of h.str of 0. Right. So let me just go and show you over here. So if I write .str of 0 after doing the split, I will be getting like this 2 hours, 7 hours, 19 hours, 5 hours. Now I want to remove this h also. So how do I do it? So I'll say .str.split with respect to h value. Okay, and then I will say str of 0. So done. These are all my values, input values, 2, 7, 19. All these things are basically there, right? So this way I'm able to get hours. You try to do it with respect to minutes. Okay, and it is very simple. I don't think so there should be a problem. So minutes, just write 1 minutes. This NaN should be replaced with 0. This is one additional task that you need to give, right? If there is no minutes over here, that basically means there is 0 minutes, right? So this should be replaced by that. Okay, now it is up to you, and then you can just try to do it. Okay. So perfect. This is done. Do a handle for the duration. This will be an internal task for you. Now the final thing that I will do is that I have these features, right? Airline, source, destination, and additional info. These are my categorical features, right? And these are definitely having some categories. So if I probably say df of airline, right? And if I write dot unique, if I execute it, so this many number of airlines are there, right? So I can definitely do one hot encoded. If you remember one hot encoded, how do you do it? I'll just show you again. Okay. So if I probably see with respect to source and destination also, you can basically see source dot unique. This many different sources are there. There is also a column which is called as additional info. I can also take that additional info. So this many number of columns I specifically have with respect to additional info also, right? Now what I'm actually going to do quickly is that what we can do is that we can convert all these category features into numerical features by using one hot encoder. So here already one hot encoder is there from sklearn.preprocessing. I hope everybody remembers this. We have done it separately. So what I'm actually going to do quickly is that from sklearn.preprocessing, I'm going to import one hot encoder. So this will basically be my encoder, which is equal to one hot encoder. Okay. So these are my features with respect to the encoder, and then I can just write encoder dot fit underscore transform, and I will give all my df of values like airline. Then this will basically be source. Then the next one will basically be destination, and this I will give it in the form of 2 dimension, right? So once I do this, you'll be able to see, I'll be able to get a sparse matrix. If I try to convert this into 2 array, so here is my output, right? Now with respect to this particular shape, right? This is basically for all the features that I have, for all the values I have basically done one hot encoding, right? It'll be suitable for this. Now, if you want to convert this into data frame, I can basically write pd.dataframe, okay? And here I'm just going to give this just a second, sorry, z, and I will just use this 2 array data, and I can assign my column names as column is equal to encoder dot get feature names out. So here is how my output looks like. So quickly, here you go, right? So this is how all my columns will get converted. All I have to do, I have to merge this with my previous data frame and drop all these 3 columns. That's it. And I can also drop duration after I probably convert this into minutes. So this is all about this specific ADA. But at the end of the day, you can see that we have created all our category features, we have converted all the category features, all our object features into numerical features, and now it is basically ready to give it to my model for the training purpose, right? And this is what you really need to do with respect to feature engineering. So I hope you are able to understand with respect to this particular tutorial. I've written so many lines of code. So yes, this was it from my side. I'll see you in the next video. Have a great day. Thank you and all. Hello guys, so we are going to continue the discussion with respect to ED and feature engineering, and in this video I'm going to take a very new dataset, and this dataset is quite amazing. This is nothing but Google Play Store dataset. Now in Google Play Store dataset, here you will be finding the dataset in a completely different way. Now how many datasets I'm actually selecting, right, for performing EDA? These all are varieties of dataset to just give you a new perspective to think like how we can probably clean the data, how we can probably analyze the data, and how we can actually perform the feature engineering of that specific dataset. So these all things we'll be covering. First of all, let's go ahead and understand what this specific dataset is all about. So here you can see problem statement today. 1.85 million different apps are available for users to download. Android users have even more from which to choose, with 2.56 million available through the Google Play Store. These apps have come to play a huge role in our life. Our objective is to find the most popular category. Let's say find the app with the largest number of install. So this kind of information that you can probably see, right? The app with the largest site, etc. So this is all information we'll try to find out from this particular dataset. And if I talk about this particular dataset, consists of 20 columns and 10,841 records. So this is a very good amount of data that is actually present. Now, what are things we are going to do? First of all, we'll start with data cleaning. Now always remember, whenever you get a data set, it will definitely not be that clean, So you have to probably clean the data. There will be some additional information that will be available, So what all information will be there, we'll try to see it after probably seeing the data set, only we come to know. And then we'll perform exploratory data analysis and feature engineering. So guys, now let's go ahead and read the data set. So obviously I have this data set over here in the CSV format. So I'll just go ahead and read this. So before that, I will quickly import all the necessary libraries. Now I think you are very much familiar with all these things. Cborn, matplotlib, numpy and all. Okay. Now quickly we'll go and write pd_read_csv. And here I'm going to just give my CSV file name. Just a second. I'll just copy the CSV file name over here. And this will basically be my data set over here, right? So this is the entire data set. And the reason I've taken this because this definitely has more than 10,000 records. So if I see df.head, you'll be able to find these records, right? So here you have the app name, you have category, you have ratings, you have reviews, size, installs, type, price, content rating, genres, Android version, and many more things, right? Now see, why I've taken this particular data set, because this looks completely different when compared to the previous data set that we have seen, right? So how we can probably handle this? And over here you can see a lot of special characters like M, there'll be different special characters, there may be a question mark somewhere in between, some of the data set may not be clean. So how we can probably go ahead and clean the data set, that we will probably start with, okay? So generic information, first of all, if I go ahead and see my df.shape, it is having 10,000 records with 13 columns, right? And if you want to probably see the general information, I can basically write df.info. This shows that almost all the features are basically object type. Only one feature that is rating is basically your floating type because it is a numerical value. Then if you really want to see the summary of the data set, so for this we can basically write df.describe. So whatever will be the numerical feature, only that summary will be getting. Right now we just have one numerical feature, right? So all this information is definitely there. Now let's go and see whether you have any missing values, and we'll try to handle those missing values also. Sum, if I do the dot sum, then here I'll be seeing that in ratings I really have many missing values. In type I have one missing value. In current version I have 8 missing values. And Android version I have 3 missing values. We'll try to see. Obviously from this we can make a conclusion. Again, it's all about insights and observation. I'll not say conclusion, it should be observation. In EDA we just make observation. Okay, so observation is that definitely the data set has missing values. Okay, so this is my information that is present, so I'm going to make it as a markdown. Okay, so this information is definitely there. Now what we'll do is that we will catch up every column, and we'll try to find out some of the other information out of it. Okay, so let's consider this reviews column. So if I probably go ahead and write df.head of the 2 records, right? So here there is something called as reviews column. I have actually checked this data set, and it's all about how well you properly analyze. Okay, I found out in this reviews column, right, by probably seeing in this particular data set, and obviously initially it becomes difficult, but as you go ahead and cleaning this, you'll find out all these kind of issues. So if I write, probably I want to check if all the values in numbers of reviews numeric. Okay, so definitely I have reviews, right? So if you forget about this, I will just go ahead and write df of reviews dot unique. So if I probably go and see dot unique, okay, so usually we see this kind of dot unique itself, right? In this dot unique, right, all these values that you'll be seeing is basically in the string format. Okay, string format, right? Now if I want to find out inside this, is there a numerical value? Because I could see that. Okay, I could see that it took a lot of time to probably find it out, but I made that observation later on once we were actually trying to handle the missing values or trying to see the data set in detail, right? So if I write df of reviews dot str, okay, dot is numeric, and I'm just checking is numeric dot sum. So here you'll be able to see that I am basically getting 10840. That basically means all these values that are there, this is basically in the numerical format only, but it is in the string format. Okay, but the total number of records that were actually present, if I probably see the shape, it is 10841, and this is right now how much? 10840. So 840 definitely this all belongs to a numeric format only, but it is in the string. One column is basically not in the numeric format. Okay, then in order to find out how I'll find out, so I will basically write something like this. See this? I will copy this and I will try to find out over here. I'll just give one notation which is like this notation, which is like not of this, right? Which is not numeric. You just give me that specific record. So if I write df, so here I'm getting, and here the reviews is 3.0m. Okay, all the other values had this kind of values, right? Over here you had 3.0m, right? Now this is the thing, guys. This is the challenges that you will probably face when you're working with a real world data set. Somewhere something will be there, and sometimes you'll not be able to even understand why this problem is happening. Because let's consider that I convert this reviews column into integer. Okay, then what will happen? See this. If I probably go ahead and write df of reviews dot as type, and I just make it as int. So here if I probably try to execute this, I'll be getting an error, right? See 3.0m, and this is how I found out, right? And then probably I fixed this issue, right? Then we got this. Now for this, what we can do, we can basically drop it because the 3.0m is there, right? And I can also convert this into 3 million. So 1 or 2 records will have definitely this kind of problems in this. Okay, so always understand that this kind of scenario will definitely come. Okay, now obviously I want to delete this record, so what I will do, I will just make df underscore copy, and we're still in the data cleaning process. This is what we do in data cleaning. So let me just go ahead and write over here something called as data cleaning. Okay, I'll make a cell which I will say it as data cleaning because we are focused right now on data cleaning. We need to clean the records, right? So here I've seen this kind of thing. So I'll keep this error like this. Okay, so here what I will do, I'll make a df underscore copy so that I can make the changes in my original data set. Okay, basically take copy of that data set and probably do it. So I will write df.copy. Okay, now inside this what I will do, df underscore copy dot drop. So there will be a drop functionality, and which index I have to probably drop. Here you can definitely see this, right? 10472, right? So 10472. So here also I'll say df underscore copy, and I will say dot index, and I want to delete this specific index. Just a second. It is 10472. This specific index I really want to drop. Just a second, please. Yeah, this specific index I want to drop. I'll make it a little bit zoom so that you'll be able to see this. Okay, so this specific index I want to drop, right? So if I write df dot copy dot index of this, I will get that record and we'll try to drop it. So I will just go ahead and probably insert that in df underscore copy. Now if I go ahead and execute the same thing and try to find out whether that numerical value is existing or not in the copy variable, okay, you will be able to find nothing will be there, right? So this kind of scenarios will come. This is the cleaning process, right? And I'm not saying that it is easy to find out because you'll only be able to find out when you probably check this, right? As type int, when you're trying to convert that into int, right? And that is where I got this error, and that is the reason I'm fixing it. Okay, so I hope you got an idea with respect to this. Now what we can do, we can convert this reviews, convert the reviews data type to int, right? Data type to int. Okay, so here I will write df of copy of specific reviews. Okay, and I will say df underscore copy, and this reviews will be as type int, right? So done, and I will basically get over here. And now if I probably see df underscore copy dot info, you'll be able to see that one feature will basically be reviews. It will be an integer value, right? So I hope you are able to get or understand this. Okay. Now let's go and catch some other features which can be numerical, and we'll try to see whether we are able to get this numerical or not. Okay. So let's go ahead and see this. Okay. Over here you have one feature called as size, right? So if I probably say df underscore copy of size, so any changes, any data cleaning, I will basically do in this df underscore copy dot unique, right? So dot unique will basically give me see so many different unique values are there. And these are also like numerical values. But you have over here m 8.0 m that is in million, right? If k is there 1000, right? So obviously we cannot have this million k 1000 like this, right? We really need to convert this into a proper numerical value. So I have to probably change this m into probably millions, like triple zeros or 6 zeros, right? So all these kind of things will be definitely there, right? Let's say that in this particular case, what I can do, I can probably write this code. So I will write df of underscore copy, and here I will say size is equal to, okay, and I will write df underscore copy of size. Now see what I will do. You know how to probably remove that m, right? So I will write dot str dot replace, okay, and this replacing, right? If I probably replace this particular m with, let's say, to start with some 1, 2, 3, 4, 1, 2, 3, 4, or let me do one thing. Let me convert this into k units, okay? So whatever values will be there, I will try to convert this into k units, okay? So if I want to probably convert this 19 million into k units basically means 1000. Then how I'll do? I'll basically write, so if I probably consider this as an example, see, what is 19 million? This is 19 million, right? So we have 6 zeros, 1, 2, 3, 4, 5, 6. So this becomes 19 million, right? Now what I'm actually going to do, I'm converting this into k units, right? Now if I want to convert this into k units, so I can probably remove this last 3. So it will be 19,000k, right? 19,000k, and that is what I'm actually doing, right? So this m, I'm basically converting only into 3 zeros, right? Initially, see, m will be 6 zeros, right? But if I want to convert this into k units, then what will happen? 3 zeros will go off, right? So this entire value is nothing but 19,000k, right? It is just like k is nothing but 1000, right? So 19,000k. This is nothing but 19 millions. This is equivalent to 19 millions, right? So both these values are actually equal, right? So this is what I'm actually planning to do. Oh yeah, we'll try to keep all the units in k because we have most of the values in k. Otherwise, you can directly convert that into numerical values, but I will just try to make it as k. Okay. So this will get converted into triple zero. So here you'll be able to see I'll be getting 19,000, 14,000, wherever millions are there, that all values will be there. Okay. So this I will go ahead and probably write df underscore copy of size. Now why I'm doing this? I want to make sure that my numerical features, right, it be in that specific manner, one specific format we will basically be doing. Now similarly, what I will do, I will go ahead and copy and paste over here with respect to k also. Wherever there is k, I will just remove that and keep it blank, right? So whatever k is, but that is the by default unit. Okay. So quickly we can definitely do this. Now one thing I will just do over here, df underscore copy of size. I want to also check whether it is basically having null values or not. So null dot sum. So here you'll be able to see that 0 null values. Okay. With respect to unique, do you see anything other characters other than this? So no unique is also there, right? So I think nothing we can see with respect to other unique values. Okay. One thing is there. See this? Now this is the problem, guys. You know, data scientist job is not that easy. If you get a clean data set, that is fine. But usually the clean data set will not be there. So what should I replace with this? Varies with device. So this is the value that is coming suddenly over there. So for this also we need to handle this, right? We need to probably handle it in a way. Now I can probably replace this with an AND value. And then later on probably change that AND value with something else, right? Something can happen, right? So this is the problem. Now I can probably see varies with device. So for this also I'll try to handle it. So I will just copy it over here. And I will say, instead of this k, I will take this entire varies with device. And this is scaling process, guys. Trust me. Everybody will think that this is easy. It is not that easy. And this I will try to replace it with np.nan. Let's say that I'm taking an AND value, right? And finally, what I will do, I will just try to place it over here and we will try to convert this into float. Okay. As type float, right? So done. Let's see whether it will get executed or not. Hope so it gets executed. So guys, here I can definitely see some error and it says that replace must be a string or callable. So let's check what exactly this is. Okay, so here I don't have to use string because understand that we're not trying to split it or do anything as such. Directly we know that that entire thing is a string itself, and directly we can write with replace. Okay, so here I remove that, and now if I probably go and see my df underscore copy dot info, so here you'll be having all the values, and the size is also now a floating value. And if I probably see the null values also, the null values have also got removed. Okay, so quickly if I probably go and show you df of copy with respect to size. Okay. Now you'll be able to see that there's a NaN value over here, right? Now what we can do, we can probably replace this NaN value with something else, right? And once we replace the NaN value with something else, I think our work will be done. And that we'll probably do it in the feature engineering after we save this particular data. Okay. Now let's go with the other feature. Let's see what all features we can probably do it more now. See, every feature we need to see. Installs is also there, right? So if I probably go and see df.head, and here installs is there. Here also you can see, right? There are different values. So if I probably write df of installs, okay, df of installs dot unique. Right? So there are so many different unique values with all this plus written over here. So we need to handle this obviously. And there's also one string value which is called as free. Okay. Similarly, if I probably go and see with respect to the price. So price is also one feature, right? So price is also one feature. Here also you'll be able to see dollar is there. Then again dollar is over here. Everyone is there. See different values. So this is the challenge that you'll see, right? I've already done this, so I'm able to quickly say to you. But when you start exploring as a data scientist, right, these all problems will be coming somewhat the other way. Okay. Now for both these features, two common things that I'm probably able to see: plus is there and dollar is there. Okay. So we'll try to replace this plus dollar, and I think there'll also be like commas, wherever commas will be there. I think some fields are with respect to commas also. Okay. And there is also like everyone and all, right? So what I will do is that I will try to replace all the special characters with blank. Okay. So plus anywhere it comes, we'll try to replace it with blank. Dollars anywhere it will come, we'll try to replace it with blank, right? So that is what we are going to do over here. So first of all, I will just go ahead and write characters underscore to remove. What are characters we specifically want to remove? So the first character will be plus. The second character will basically be comma. The third character will specifically be dollar. Okay. And then I will just go ahead and write what all columns I want to clean. So columns underscore dot to underscore to clean. And here I will basically give my installs column. Okay. And price column. So we are finally cleaning the data set. Understand one thing. Okay. So far, item in characters dot to remove. So every item will go ahead and take it, and we'll iterate through all the columns for columns in columns to clean. Columns to clean, and here what I'm actually going to do is that I'm basically going to write df underscore copy, okay, and I will take the column, and then we will just try to write df of df underscore copy dot sorry, not dot, of column dot str dot replace all the special characters. And this characters is basically there in the item, and I will replace this with a blank, right? So once I execute this, column is there. Let's see, for columns it is columns, okay, columns. Let's go ahead and execute it. So now finally if you go and see df underscore copy of this particular value, this installs dot unique. Okay, so we should have write an underscore copy over here and underscore copy over here. Don't please try to do it in df because any cleaning that we're doing, we're basically doing it in df underscore copy. So once I execute this, here you can see now I don't have any special characters like dollar or plus. In installs also, if you probably go ahead and see, okay, I will be removing that. So this is some of the cleaning process that I'm doing. The cleaning is basically done to probably find out if there is any special character. Now here also all the special characters gone, right? This is so nice, so good. I've also used this comma, so wherever the comma is, that is also got removed. Great. And we have this entire clean data. Okay. Now with respect to this, now what I can do is that now I don't find out anything, right? Anything over here as a special character, everything is gone. Now we can convert this entire into an integer value. If there are any special character, it will give us an error. Okay. So df of copy of installs. Okay. And this we will try to convert this into a floating value or integer value because here I don't have any decimal in installs. So I will write df underscore copy of installs dot as type. And here you'll be having integer. Okay. And finally, you'll also be copy and pasting this. This will basically be my price. And here also we'll have df underscore copy dot price as type integer. Okay. So price has a decimal values. So I'll not make it as integer. I'll make it as float. Okay, so done. Great. So if I write df.info, now all the other features are also become, df underscore copy. So always this problem will happen, guys. So please make sure that you write it properly. So this is become integer, float, integer, and then you also have this price, which is becoming float. Okay, perfect. Now let's go and handle some more features like last updated. You can do line by line every features, but I'm just giving you an idea about it. Okay, so now we are going to handle the last update feature. Okay, and this still we are in the data cleaning process. So here I will write df underscore copy of last underscore updated. Okay, dot unique. Okay. And here you'll be seeing that I'm having January 7th, this. Now we really need to convert this data into date time. Okay. So if you know about date time, we will be able to convert this. It is very much simple. So for this, I will be using Panda. So if I write pd dot to underscore date time and probably give my values over here as df underscore copy of this particular feature, last updated. Okay. So here you'll be able to see that I'm able to get all my date time. So I'll try to convert this like this over here, and I will store it in the same variable df underscore copy over here with respect to my last updated. Okay. Now, obviously we have the entire date column, right? But I require the dates and the months also. So what I will do, I will create some additional column. So I will write df underscore copy of day is equal to df underscore copy of last updated. Okay, last updated dot dt dot day, right? So if I write dot dt dot day, automatically from this the day will get picked up, right? And similarly for month, what we'll do, we'll copy this entire thing, and here I will go ahead and write month, and here last updated dt dot month, right? So this is how we basically take out all the day, month, and year. And again for year, I will just use this. So I'm basically creating 3 columns, and then we can later on, if you want, you can drop this column also. That is last updated. So once I execute this, now if I go and see my df underscore copy dot info, so here you'll be able to see some very important information. See, first of all, the last updated has become a date time, and then this day, month, and year has become an integer values. Okay, so definitely good. I've done so much different kind of cleanings. Okay, and once we do some set of cleanings, right now, probably this, if I probably go and see df dot head, okay, the top 5 records. Here you can see app is basically a categorical feature. Category is also a category feature. Rating has become noted into this. Size also we can do something like that. Okay, so size is also there. So if I probably go and see, is it df or df underscore copy? Just a second. So it should be df underscore copy. So here you can see categories app. This will be numerical. Categorical feature. Rating has become a numerical. Review, size, install, type is a categorical feature. Price, again, I'm having this floating values. Content rating becomes a categorical feature. This date has also get changed. So we are almost very good because we have done most of the data cleaning process that is required. Now the next step will be that I will try to save this data set. Okay, and always try to save this data set after cleaning also. So this will get converted into a CSV file, and the CSV file name will be, let's say I create a data folder, and I'll write Google cleaned CSV. Okay, .csv. So once I execute this, let's see, my error will coming. I've not created a data folder. It's fine. Not a big worries. I'll create a data folder. New folder. Data. It's fine. Great. Let's go ahead and execute it. And now if I go and see my data folder, you'll be able to see this entire clean data. Isn't it amazing? Yes. So we have done the first task with respect to the data cleaning. That is so good. Now my second task will be that I will try to perform EDA after cleaning the data. And then after that we'll perform feature engineering. So I hope you are able to understand this video. I hope you like it. We'll divide this into multiple parts. Thank you. I will see you all in the next. So guys, we have completed the data cleaning part. Now let's go and perform some EDA. Okay. So now we're going to probably start the EDA and EDA full form everybody knows that is exploratory data analysis, right? So here is what we're going to basically start. So right now my df underscore copy dot head, and please make sure that you keep a CSV file ready also, so that if probably this particular data gets messed up, you can probably read that particular data from the CSV file. So over here you'll be able to see I have all these features. Now one by one we'll try to understand with respect to this particular features. We'll try to divide this into categorical and into numerical features and many more things. Okay. So first of all, in the EDA as usual, let's go and check df of app. Okay. And what I'm actually going to do is that first of all, with respect to app, one thing that I'm going to see is that whether it is duplicated or not. So is duplicated. We'll try to see. So let's see whether this will work or not. It'll give us an error because there are so many records. Series object has no attribute, is duplicated. No worries. So what I'm actually going to do over here is that I will write df dot duplicated of app. Okay. So if I probably try to see this and see the output over here, I'll be either getting false or true. So if I really want to find out how many records are duplicated, so I will probably go ahead and write df of this one. Because see, app, if there are duplicates, those data points, like if there are duplicates data points with respect to that, then I think we will almost be getting the same information in the entire data set itself, right? So if I write like this, and if I probably see this, so these are probably the duplicate app names that are available, right? And if I go and see the shape, and this shape will basically be 1181 records. The total number of records are 10,000, and 1181 are basically duplicate records. So from here, the conclusion that we can make is that, I'll not say conclusion again, I keep on saying conclusion, you should say about observation, that the data set has duplicate records, right? So here I have all my duplicate records. So I will go ahead and make this as a markdown so that this observation I can definitely see. Now what I'm actually going to do, obviously drop all the duplicates. So in order to drop it, I will write df dot drop duplicates. And here I have to give my subset parameter, which will be basically my feature name. Okay. And I'll just make sure I'll write another parameter, which is like keep is equal to first. Okay. Now this keep is equal to first basically means the first record will be kept. And if there is a duplicate record similarly, it'll get dropped off, right? And after this, what I can actually do over here is that, and okay, let's see for df underscore copy. Okay. I have to probably check it for df underscore copy. Yeah, same thing. Here also, I have to make sure that df underscore copy. And let me just save this in df underscore copy. I can do like this, or I can also use a parameter like in place is equal to true. So fine, I've got executed. Now if I go ahead and see df underscore copy dot shape, I will be able to see that many number of records is removed, and now we have 9,651 records, right? Now let's go ahead and probably explore data more. Okay. since we are doing the EDA and we know all the steps, probably so many examples we have done, right? Now, first thing with respect to exploring data, obviously, is to find out how many numerical columns you have and how many categorical columns you have. And we know how to do that. So I'll just directly copy and paste it for you. And like this. So feature for feature in df underscore copy.columns underscore copy.columns. And I'll say df for feature dot data type is not equal to object, is equal to object. If it is equal to object, that becomes categorical features. If it is not equal to object, then it becomes numerical feature. Again, we have discussed a lot many times, so I'm not going to again discuss about this. So I'm getting an error which is basically saying day. So in which line df of feature? Okay, so for feature in df.columns if df underscore copy. So that is the problem. I had written df because I had copied it, but we have created another variable. Now I think we have 9 numerical features: rating, review, size, installs, price, last updated day, month, year, and we have 7 categorical features like app, category, type, this, that, right? So all this information is basically there. I'm also going to give all the information of the feature that you have over here, okay? So that you can keep this for your own, for your own. Let's say you want to know about, more importantly, you want to know about this features, you can refer this entire features, basically what this features basically say, okay? Just to give you a good idea about all the features that we are going to use. So 9, 10, okay, I'm just using some numbering, okay? 11, oh, sorry, I have to use this as 11. This will be 12, and finally I have this 13, okay? Done. So I'll make this as a markdown, and probably we are going to keep this feature's name. This is basically giving you the entire feature information. Now with respect to categorical features, now since there are like 7 categorical features, I'm just going to do one thing. I'm going to basically find out what is the proportion of count data on categorical columns for every different kind of features itself, every different kind of categories itself, right? So for categorical columns, okay? So for this, I will say for column in categorical features, and here I'm going to basically print df of column dot value counts, value underscore counts. And this value underscore counts will basically give you how many, each category, how much values is there. Now, if there's also one feature which is called as normalize. If I probably set up this feature as normalize is equal to true, instead of giving in the form of numbers, it will give us in the form of percentage, okay? So this entire value, I will just try to multiply by 100 so that you will be able to see that entire thing in the form of numbers, right? And finally, I'll just print like this so that I give it in a better way and you'll be able to see this, okay? Now see the advantages. When we do normalize is equal to true and when we are multiplying by 100, this is what we are basically getting. So Roblox that you can probably see over here is basically this much. CBS is this much. ESPN is basically 0.06%. So it is nothing but 6% in short. Meet you, family, this all the information is basically available, right? So this is with respect to all the proportion that we are able to see, okay? And over here, you will be able to get an idea like how it looks like and what are the features, what are the categories with respect to this, okay? So this was one thing that you can specifically do with the categorical data. Now the next thing that I'm probably doing is that we can compare different categorical columns also, okay? So let's do one more thing. I'll write a comment. In visualization diagram, we will try to see the proportion of count on categorical column. So let me just quickly copy and paste one code. Now I think you'll be able to understand this is the figure size 15,15 univariate analysis of numerical feature. Okay. So for I in range with respect to this numerical feature, every numerical feature. Okay, sorry, this should be numerical columns, not categorical columns. So that was my mistake. So now if you probably see this, I've used KDE plot to probably take all the features and compare that. So with respect to the KDE plot, the X variable, but one of the numeric and data type is required. So I have to use df underscore copy somewhere. Let's see. So this will be df underscore copy. Perfect. Now, if you probably execute this, so this is how a univariate analysis of the numerical features are there. We are using KDE plot. KDE plot basically means kernel density estimated plot. And this is how your entire plots look like. Okay. Now, from this, what kind of observation you can make through, right? So, if I probably consider rating with density, right? Over here, you can see that this is left skewed data. If I probably see rating with, let's say rating and year. Where is rating and year? Year is over here, and rating, day, month, year, install, price, last update, rating, reviews, and size. Okay. So if I probably see with respect to rating, this is left skewed. With respect to year, this is also left skewed. Okay. And some of the data is looking like this. Last updated is also basically left skewed. So this is the observation I can definitely make out of it, right? So observation, I'm going to basically make over here as rating and year is left skewed. Okay. Left skewed. I'm just writing my observation, whatever is basically coming. While reviews, size, installs, and price are right skewed. Let's see whether this is true or not. Price reviews, this is also right skewed, perfect. Right skewed, yeah, perfect. So this is like price is also kind of right skewed itself, right? So all this information we are able to see that, yeah, some of the data points with respect to the price, this is obviously right skewed, installs is right skewed, and reviews is also right skewed. So this is the observation that we can probably make out of it. And here I'll just make it as a markdown. So since there is right skewed, obviously we can also come to a conclusion that outliers are definitely present. Okay. Now similarly, we can basically do it for categorical features. So let me just go ahead and probably write it down over here. So again, same figure size, category I've taken type and content writing, length of category I've used plot, and whenever we have categories, we have to use count plot, and I've set some palette size. Okay. X label is this, Y label is this with 45 degree. If I execute this, so here you'll be able to see that this one left one is there with respect to free. What is the count with respect to paid? What is the count? And over here you can see everyone teen, every 10%, everyone 10 plus mature 10 plus with respect to different content rating. We are also able to see the count. So quickly we can also make the quick observation. That is what we are actually looking for, right? And over here what we have done, we have used count plot, right? Count plot with respect to category, and the next one that we are probably plotting is with respect to this values, right? So here again, this particular diagram, now you can probably make the conclusion out of it. Just see to this, just with respect to the data, you can see free is basically having a huge count, and over here with respect to different categories on content rating, you'll be able to see over here, right? So type and content rating, that is what we are looking at. Okay. Now let's answer the main question, which is the most popular category. Okay, popular app category. Okay, so this is my first question. Okay, and for this we will try to use a pie plot. Okay, which is the most popular app category. So if I probably write df of copy dot head of 2, so obviously most popular category. So this category we have to actually look at, and in order to do this, there are different categories. I'll just go and see how much percentage it is, and then we'll be able to find it out. Okay, so here I will write df of df underscore copy of category dot value, dot value underscore counts dot plot dot pie. Okay, so here I'm going to basically use the pie chart, and here I'm going to basically write df of category See this, by using this pie chart, I think we are not used pie chart anywhere in the EDA, but I really wanted to show over here. So this will basically be my fixed size, and here I'm going to mention my fixed size as 15,6. Okay, so let's go ahead and execute this. Plot as takes one position argument but two argument. No worries. Let's see this. What is the problem over here? So this basically will be my y value, and this will basically be my fixed size. Okay, now it should work. Now here you can basically see, yeah, so many different categories are there, so many different values are there, and the type of fixed size that I've actually used is 15,6, and you make it to 15,16, then you can actually see this very clearly, right? So most popular app category, obviously family is there. If you want values over here, I can also use one more parameter which is called as auto PCT, that is percentage, and this will be percentile 1.1 f. Okay, so once we set up this value, you'll be able to see this. So this is like all the features that you can use in visualization. So family is basically having 19%. Then you have game 9.9, tools 8.6. So definitely the observation that you can basically make, the insights that you can basically make. Let me go ahead and write the observation just by seeing this pie plot. Okay, observation, insights. They are, so first observation to this is that, and this is basically my second observation. Okay, I've already seen this data set and done it, so I'm writing the observation directly. There are more kinds of app in Play Store which are under categories of family, games, and tools. So family, games, and tools, maximum percentage are there. Beauty, cosmic arts, and other kinds of art are very less in the Play Store. Okay, and this can also help you to decide your next startup. Okay, you can probably use this. Now let's go ahead and go and see the top 10 app categories. Okay, if I really want to see this, and with the help of EDA, we can also do that. For this, I'll just simply use this code. That is, let's go and write like this: category PD.frame, value underscore counts, and then we are basically going to name it with respect to the count, right? So once I see the output over here, this will basically be my category. Okay, so just see the code, guys. I think you'll be able to understand. So family has 1972 counts, game, and top 10 if you really want to take, you can just use index, right? So what I'll do with respect to top 10, right? I'll try to create a bar chart. Okay, so for creating a bar chart again, now see guys, you don't tell me to again write all the code line by line. I will just directly copy and paste it. So here I'm using a sns.bar plot, the category.index of 10. I want just a top 10 apps. So here I will just want top 10 apps. So definitely check it out. You'll be able to see it over here, right? And finally you'll be able to see this. I've taken y is equal to count, data is equal to category of this, and palette I've used anything. You can use different palettes there are, right? And then finally you can see over here, this is how my bar chart looks like. And here also family is given the best, family has the maximum count. Then again, with respect to the insights, I've already written it over here. So over here you can see family, game, tools, medical, business. So these are my top 10 famous app categories. So let me make this as a markdown quickly. Insights that I will probably get out of it is that family category has the most number of apps, with 18% of apps belonging to it, followed by games, and which has 11% of the apps. Least number of apps belongs to the beauty category, and this all the information is there. And obviously you can actually check it out. Okay, now there's some more assignments that I really want to give you. Internal assignments. Okay, internal assignments. So first thing is that which category has largest number of installation. Okay, this is my first question to you all. Okay, which category has the largest installation, and then I will also keep some more questions for you all. And here I will give the code, but I really want you all to try, okay, by using the things which are the top my 5 most installed apps in each popular categories. I will give you the entire code over here, don't worry about it, but I'm just going to ask you some 3 to 4 questions. Okay, so here is my third question. Okay, so consider this as an internal assignment. Write the code and probably post it in the discussion forum, but I will give you the question, I'll give you the answer after this one by one. Okay, and then you can probably have a look with respect to the answer whether it is matching or not. Okay, so these are the 3 main questions: which category has the largest number of installation, which are the top 5 most installed apps and all in each popular category, how many apps are there on the Google Play Store which gets 5-star rating. So yes, do it, think over it, consider the data set, and then I will write the code in this, okay, for you all. I'll make it easy, but first of all I want you all to try. Okay, so this is an internal assignment for you all. Please try to do it. Here I've already shown you, right, how to get the top 10 apps, how to probably get the top 10 app categories. Everything is there, right? Here also we saw with respect to that which is the most popular app category based on the maximum percentage. Okay, so just try to do it. I will give the code anyhow, and you just try it out. In this video, we are going to discuss about the basic differences between artificial intelligence, machine learning, deep learning, and data science. Probably you have heard about these terms, and many people still have a confusion. What is the exact differences between them? So in this video, I'm going to cover the entire differences so that you'll never have any kind of confusion. So let's begin. The first thing is that let's consider the entire universe. Let's say there's a universe with respect to in this specific field, and I really want to talk about this specific universe, and let's call this universe as AI. Okay, so this universe is basically called as AI. Now, if I really want to understand the definition of AI, it is basically to create an application, which can perform its own task without any human intervention. Okay, without any human intervention. So this is the basic definition of artificial intelligence. Okay, so the specific thing which I've actually written it over here. It is basically to create an application which can perform its own task without any human intervention. So for this specific thing, we call it as artificial intelligence application. Some of the coolest example which you basically use on to day-to-day basis, right? So the first example that I would like to talk about, Netflix recommendation system. Now, whenever I talk about Netflix recommendation system, over here you will be seeing that, suppose let's say you have seen some kind of action movies, right? Now, whenever you see some kind of action movies for a couple of time, then after that you get a recommendation of action movies only. Okay, you get a recommendation for action movies. So this is one specific example with respect to the recommendation. One super very simple example whenever we see in this kind of situations. The second example, and again, Netflix has an AI module which will specifically do this recommendation system, and it does not require any human intervention. Human will keep on clicking different movies. Automatically, those applications will be able to understand what is the next thing that we must actually recommend to the person. Coming to the next example, self-driving car. I hope many of you have actually seen this self-driving car. So in self-driving car also there is a specific AI module which in turn will actually help the car to be driven by itself without any human intervention also over there. It will be automatically be able to detect the traffic lights. It will be able to detect the objects that is coming in front of them. How it is possible? It's basically an AI module is integrated in that specific car. So these are some of the examples. Even in Amazon.in, if you probably go and do some kind of shopping there, also you get some kind of amazing recommendation system. Now coming to the next one, I hope you are very much clear with artificial intelligence. Now let's go ahead and let's discuss about the next one, which is basically called as machine learning. So if I talk about machine learning, I can definitely say machine learning is a subset of AI. Okay, let me make this circle a little bit bigger, and machine learning will be falling somewhere inside this, which can be also called as it is a subset of AI. So this specific thing we basically talk about machine learning. Now what does machine learning is? It provides stats tools to analyze the data, analyze, visualize, do some kind of prediction or forecasting. I'll not say or, because forecasting can also be one type of functionality within this. It can also forecast the specific data. So here, with the help of various stats tools, which we also say as machine learning algorithms, which we are probably going to see in the specific course, it utilizes all those things to analyze the data, visualize the data, to do some kind of predictions, to do some kind of forecasting of those specific data, right? That is what machine learning is all about, and it is a subset of AI, right? At the end of the day, whether you work as a machine learning engineer, whether you work as a data scientist, at the end of the day, you will be creating an AI application. Okay. Now, similarly, where does deep learning fall into it then, right? So let's talk about deep learning. So deep learning is another specific thing, which is a subset of machine learning. So this is specifically deep learning. Let's say I'm writing it out over here, deep learning. Now, in 1950s, scientists thought that whether we human beings can train the machine, like the scientists were thinking something much amazing during 1950s. Can we train the machine also like how we human being gets trained, right? Like suppose if you're learning something, how do we learn those specific things, right? So can we also make the machine learn in a similar way, like how we human being learn? So for that, in short, deep learning was basically getting implemented to mimic the human brain. Okay. And here the main aim, again, let me repeat it. It was very simple. We really wanted to make the machine learn how we human being usually learn things, right? So for this, the implementation, deep learning was implemented, and they used something called as multi-layered neural network. Okay, multi-layered neural network. And with the help of this multi-layered neural network, we were able to make the application learn like how we human being learn specific things. So deep learning is again a subset of machine learning. Okay, but again, at the end of the day, even though you're working as a deep learning developer, at the end of the day, you try to create an AI application, and that specific application will be able to perform its own task without any human intervention. Now coming to the next one, which is data science, right? Where does data science fall into in this specific universe? Where does it fall, right? Now, as a data scientist, always remember, we like I have been working for somewhere around 7 to 8 years, right, in various industries, in product-based companies, service-based companies, right, as a data scientist. And as a data scientist, you should remember that, okay, data scientists will probably overlap each and everything over here. Let's say they will be overlapping each and everything. Why I'm saying overlapping each and everything? Because tomorrow, if you're probably given a machine learning project, you really need to know, need to know machine learning. Probably tomorrow you're given a deep learning project, you really need to know deep learning projects. At the end of the day, you should also be knowing how to create an AI application. And over here, you really need to use math, statistics, and many more things. That is the reason why I have actually created this circle, making sure that it overlaps each and every sector, right? Even machine learning, deep learning, and finally the AI part, right? So this part is basically the data science. In short, data science utilizes or is used in every sector of this. And over here, again, some more overlapping will be doing with respect to different techniques or tools or subjects that we use, like maths, linear algebra, stats tools, and all. Okay, but in short, here I have given you the basic difference between AI versus machine learning versus deep learning versus data science. I hope you have understood. In short, tomorrow, if you're working as a data scientist, you may be given a task that may be related to just EDA, feature engineering. It may be related to tasks that may be related to deep learning, or it may be related to creating any kind of AI application. Okay, at the end of the day, any role that you fit in within the specific divisions that I've actually made, you have to really create an AI application at the end of the day. So yes, in the next video, we are going to continue and understand about what is the differences between supervised and unsupervised machine learning. Okay, which is a very important thing in both machine learning and deep learning. So yes, let's continue the next video. Hey guys, in this video, we are going to discuss about 3 types of machine learning techniques. Usually, all these machine learning techniques are related to some kind of problem statement. First of all, let me just call out all the names. So the first type is something called as supervised machine learning technique, and the second type is something called as unsupervised machine learning technique, and the third type is called as reinforcement machine learning technique. And all these techniques that we will probably be discussing will be with respect to some specific problem statement. Okay, so let me go one by one and let me explain you. So first of all, I'm just going to consider supervised ML. Okay, supervised machine learning technique. Supervised ML technique. Now, in supervised ML technique, what happens is that, let me give you a very basic example. Suppose my task is to predict the house price. Okay, so I really want to predict the house price. And let's say I have a specific data set. Okay, in this particular data set, I have some features. Let's say I have features like the size of the house, okay, number of rooms in the house, and then I have my third feature, which basically indicates the price of the house. Usually, in a supervised machine learning technique, you get this kind of features, and you divide the features into 2 different categories. The first category is something called as independent features. Okay, so both the features are basically called as independent features. Okay, and one more feature that you see over here is something called as price. This price is basically called as your dependent feature or your output feature. Okay, similarly, when I say independent feature, these are also my input features. Now let me give you some of the data points as an example. Let's say that the size of the house is 5,000 square feet and number of rooms are 5, so the price of the house will be $450K. Okay, similarly, let's say your size of the house is 6,000 square feet, number of rooms are 6, then this will become $500K. Like this, you will be having a lot of data points, and this will basically be your data set. Okay, in short, over here, why this feature is called as dependent or output feature, because this value keeps on changing as your input value changes or as your independent feature changes. One more very important thing to understand about supervised machine learning technique is that there are 2 types of problem statement that we usually get to solve. One is regression problem statement, and the other one is something called as classification problem statement. Now, what is the basic difference between regression and classification problem statement? Okay, in regression problem statement, whatever dependent or the output feature you will be having, all those feature values will be continuous. Okay, it will be continuous. Okay, so 2 important things with respect to supervised machine learning technique is that, first of all, you will be having a specific output or dependent feature. Okay, so first point is that in supervised machine learning technique, you will definitely be having a dependent or output feature. Okay, the second point is that if it is a regression problem statement, then your output feature will be continuous. If it is continuous, you can directly consider that this will be a regression problem statement. Okay, but if this is not continuous and if this is categorical, then what kind of problem statement this will become? This will become a classification problem statement. Let's say I'll give you a basic example. Okay, I have one classification problem statement as an example. So here is my classification problem statement, and let's consider I have features like number of study hours, number of play hours, and here with respect to this specific output, let's say the person is either passing or failing. So let's say I have a data set which has these features. Here my input features are number of study hours, number of play hours, and based on that, we really need to determine whether the person is going to pass or fail. So this becomes my dependent feature. dependent feature. Okay, and this all becomes my independent feature. So here, let's say if the person is studying for 7 hours, if he's playing for 3 hours, that basically means he's going to pass. Okay, if the person is probably studying for only 2 hours, he's playing for 6 hours, he may probably fail. Okay, so this kind of features. Now here, the output feature is fixed number of categories. If there are only 2 categories, we basically say it as binary classification. Okay, if there are only 2 categories, then we specifically say it as binary classification. Or if there are multiple categories, suppose let's say there are also one more category, like maybe he may pass or fail, he or she may pass or fail, then this becomes our multi-class classification. Okay, so usually we get 2 types of problem statement even in classification. It can be a binary classification or multi-class classification. The basic difference between binary and multi-class classification is that in binary classification, you just have 2 fixed categories, that is either pass or fail. That is binary, right? 2, right? In the case of multi-class, you may have more than 2 categories, and you really need to train the model with respect to the specific input, and you need to probably predict it whether the person is going to pass or fail, right? So this is the basic difference, or this is the types with respect to the supervised machine learning. Again, let me revise it. In supervised machine learning, you basically see 2 types of problem statement: regression and classification. And why do we say supervised? Because here specifically you have a dependent feature. Okay, dependent feature should be there. Then only we will be able to say it as supervised. Then only we will be able to train our model with this specific data set, and later on, whenever we give a new input data to that specific model, it will be able to predict. Okay, so this is with respect to supervised machine learning. Now let's go ahead and let's try to talk about unsupervised machine learning. So the second type is something called as unsupervised machine learning. Now what is the basic difference between supervised and unsupervised? Okay, let me again give you a basic example. So this example is related to something called as customer segmentation. Okay, whenever we work with respect to unsupervised machine learning, one very important thing that you should know, that we do not know the output feature. Over there, we don't need to predict anything. Instead, we need to find out similar clusters or groups. So if I take an example with respect to customer segmentation, and I have a specific data set, let's say this data set is something like salary. I have a feature like salary. Then I have something called a spending score. Okay, spending score. Let's say I have this 2 specific feature. The spending score is given between 1 to 10. That basically means how much the person is spending. The more the value towards 10, the more that specific person is basically spending. Okay, so let's say the salary is 20,000 rupees. Okay, 20,000 rupees INR, $20,000, and let's say the spending score is somewhere around 9. That basically means this person spends more, right? Suppose if I say the salary is 45,000, okay, it can be in dollars or INR or anything as such. Okay, then let's say that spending score is 2. What does this basically indicate is that obviously the person is earning more when compared to this person, but his spending is less, so he does not like to spend much. Similarly, I may have a lot of data like this. Okay. Now, in this particular data set, I just have my features. Here we don't say that, okay, this is my output feature. Okay, I don't have to predict that based on the salary, what will be my spending score. No, that is not the aim. Tomorrow, let's say I want to launch a product. I'm an e-commerce company. I'm running an e-commerce company. And this e-commerce company, I've launched a product. And I want to send a mail with some discount coupon, to this people based on the spending score. So how do I send it? What I do is that with the help of unsupervised machine learning, we create clusters. We create clusters. Now, let me give you an example of clusters, how it will be. So let's say that, okay, what we do is that we create similar clusters. So let's say this group basically is the group which has higher salary and which are spending more. Okay, let's say I have one more group. These are basically having less salary and they are spending. See, if I probably say salary over here and spending over here, right? So these are the people who have median salary and they spend more, right? These are the people who have less salary and they spend less, right? So these are the people. And so we are going to make this kind of clusters or groups over here, right? Let's say this is another group which has huge salary and spending is median, right? In the median, like in the mid, right? If I have one more cluster, I can have one more cluster which is somewhere here, and probably these people are having the highest salary and the spending score is also high. So why we do this specific thing is that tomorrow, let's say that if I'm launching any product, I would definitely give this people some discount so that they will be able to buy my product because their spending score is obviously high and salary is also high. So in short, in unsupervised machine learning, we create something called as clusters. Okay, clusters, and there are various kind of algorithms that we specifically use. I'll talk about different kind of algorithms as we go ahead. Okay, now let me talk about all the algorithms that we are going to learn in supervised machine learning and in unsupervised machine learning. Okay, so in supervised machine learning, we will start with something called as linear regression. As I said, 2 types of problem statement we will be solving. One is regression and one is classification. So first we'll start with linear regression, then we will go with ridge and lasso regression. Again, this is basically to solve regression problem statement. Then we will be learning about elastic net. This is also used for solving regression problem statement. And then we will move towards classification. So classification, we will be seeing something called as logistic regression. Okay, so this is basically my classification. Okay, then we will go with some algorithms, and this algorithm can actually help us to solve both regression and classification problems. So here we'll be learning about decision tree. Okay, we'll be learning about something called as random forest, ADA boost. Right, we'll be learning all these algorithms slowly. We'll also be understanding how to implement it practically. Then we will be seeing something called as XG boost, random forest. These are something called as bagging and boosting, and with the help of this kind of algorithms, right, we can solve both classification and regression. Okay, and regression problem statement. We can solve both of them. Okay, and ADA boost, XG boost, cat boost is also there. So we'll try to solve all this thing. In some unsupervised machine learning, we will try to learn about algorithms like k-means, hierarchical mean. Okay, hierarchical mean algorithm. Then I also have something called as DB scan. DB scan clustering. Okay, so these are all clustering algorithms. Okay, specifically we'll be using something called as unsupervised machine learning technique so that we can create some amazing clusters and groups. Right. So this is with respect to supervised machine learning and unsupervised machine learning. Okay, and let's go ahead and let's talk about something called as what about the third one, which is called as reinforcement learning. So in reinforcement learning, this is also an amazing module altogether, and it is completely different when we compare it with supervised or unsupervised machine learning, because here the application will learn things by itself, by getting some amazing rewards. The best example that I can probably take with respect to reinforcement learning is that, just for right now, because we'll be having a separate module for this also, is that whenever we consider a baby, right, you have seen a baby, right, when it is very small, it will not know anything, but as it keeps on growing, right, it learns
learns new things. So let's say it is trying to walk for the first time. So when it is walking for the first time, he or she may fall down, and when he may or she may fall down, at that time what happens? He or she may cry, right? Because when she or he is actually falling down, they may get some kind of sore in the leg and all, and they may get hurt, right? Later on, what they do is that they make sure that they slowly learn things so that they should not get hurt. So that basically means they will try to do things by getting some amazing rewards, right? And you've seen children, right? If they bring good marks in their high school or college, the parents gives them some kind of rewards, right? So based on that specific action is actually done, right? So similarly, reinforcement learning also works in that way. Don't worry about it right now because we will be having this module as we go ahead. Okay. So this is what the basic difference in making you understand between the three types of machine learning. We'll start with supervised machine learning technique. Probably our first algorithm is linear regression, which we specifically say is a simple linear regression, where we'll be learning what exactly how this algorithm works, and we'll be learning about ridge, lasso, and all, and we'll go in this specific order, and we'll convert first supervised machine learning, then we'll go with unsupervised machine learning, and then we'll be learning all the things, right? So yes, let's continue with the next video. Thank you. In this video, we are going to discuss about the equation of a straight line, and we're also going to understand about 3D plane and hyperplane. Now, this is a super important topic before we start any machine learning algorithm like logistic regression or support vector machine. Let us consider over here an example. Suppose if I have two axes, one is x and y, and if I probably try to create a straight line, we can represent or we can provide the equation for this particular straight line, which is called as y is equal to mx plus c, right? And I hope you've seen this formula probably in your 10th standard, 8th, 9th standard. Similarly, I can also give some different kind of notation like y is equal to beta 0 plus beta 1 into x, or I can also give some other notations like this, which is ax plus by plus c is equal to 0. Okay, both the equation are almost same. First of all, let's go and understand what this equation basically specifies. Over here, there are two things. One is the x and y coordinate. Obviously, you can definitely see this. X and y axis. Here you have first component which is called as m. M is nothing but it is called as slope. Now over here, what the slope denote is that in the unit movement in the x-axis, what is the movement with respect to the y-axis? So with respect to this, if I try to see what is the unit movement in y-axis, this will basically be giving me the slope value. Okay, this is basically giving me the slope value, right? Now this is with respect to slope. What about c? C is basically called as intercept. Okay, intercept. Now when I talk about c, let's consider that in this equation, if my x value is 0, so suppose if my x value is 0, where does this particular straight line meet the y-axis? So if I probably draw this, it meets somewhere here, right? So this point is basically my c or intercept. Okay, very simple. Slope basically says that with the unit movement in the x-axis, how much movement is there with respect to the y-axis. The second thing is that when my x value is 0, then obviously you can see y is equal to c, right? Because if this is becoming 0, so this basically indicates that at x is equal to 0, where does the straight line meet the y-axis? Okay. Now you might be thinking, Krish, how this and this particular equation are one and the same. Let's consider over here, guys. Let's say that this is my equation, and now I can basically write something like this, right? So let's consider this. I will write dy plus c is equal to minus x, then by is equal to minus ax minus c, and finally y is equal to minus a by b. This is one component multiplied by x minus c by b. Now over here, you know that this also follows the same equation, which is like y is equal to mx plus c, right? Y is equal to mx plus c. Now when I say this is basically my m value, and this is basically my c value, right? The slope and the intercept. So almost both this equation also represents the same thing. Okay. Now just for the easiness, what we can also do is that let's provide one more equation of over here, and it's almost similar. Okay. Let's say that I have my x-axis x1 and x2. The reason why I'm writing x1 and x2 because if I have multiple axes, like say if I have multiple dimension, over here I just have two dimension, right? Now in this particular two dimension, I can represent it by x and y. But if I have many dimensions, so I'm writing it as x1, x2, something like that. Okay. Now in this particular case, let's say I can also give the equation of a straight line which looks something like this. So here I'm going to mention it as w1 x1 plus w2 x2 plus b is equal to 0. Now this equation also matches this specific equation. Here you can see instead of a I'm writing w1, instead of x I'm writing x1. Similarly over here, instead of b I'm writing w2, instead of y I'm writing x2 plus b is equal to 0. B basically becomes the intercept. Okay. Now in this particular case, you can see I have two important things. One is w1, w2. w1, w2 is basically my coefficients. So I can also give this representation as w transpose x plus b is equal to 0. Right. So in the upcoming any algorithms we will probably discuss, I will be using this particular equation regularly, like w transpose x plus b is equal to 0. And this is nothing but this is an equation of a straight line. So equation of a straight line. Super important. And understand this representation are almost one and the same. Now this is fine. What happens if I have three dimensions or three axes? So here let's say I have x1, I have x2, and I have x3. Now in this particular case, we don't draw a straight line. Here specifically we draw a 3D plane. Okay. So let's say we are drawing a 3D plane, and this plane will look something like this. Okay. So this is how a plane will look like. The plane can be here, it can also be here, or it can also be here. Now with respect to this, the equation will again change a little bit. Okay. Now with respect to a 3D plane, this equation will become w1 x1 plus w2 x2 plus w3 x3 plus b. B is basically my intercept is equal to 0. Right. So here I have three axes x1, x2, x3. And with respect to that, I have basically three coefficients w1, w2, w3. And again, as usual, I can also represent this as wx plus b is equal to 0. Right? The same thing, right? Here, w will nothing be, it will be w1, w2, w3. And obviously, you know that when we do matrix multiplication with w and x, one of the metrics we have to basically transpose it. Okay. And similarly, x will be nothing but x1, x2, x3. So when I probably, sorry, just a second, let me write this in another way, that it will look like x1 transpose. Right. So this is my w and this is my x. So if I really want to do this a dot product over here, so here you'll be able to see that I have to do the transpose of one of the metrics. Similarly, now this is with respect to a 3D plane, right? And 3D plane, we basically create a 3D plane like this. What about an n-dimensional plane? N-dimensional plane. Now in this particular case, I can again give a better representation which looks like this: w1 x1 plus w2 x2 plus w3 x3, like this up to wn xn is equal to 0. So here you'll be able to see again I can represent this as, sorry, I missed out b plus b is equal to 0 plus b is equal to 0. So this again becomes the same equation. Now let me consider one case. Okay, one case over here. Let's say I just have two axes x1 and x2. And obviously in this case, I can represent my equation as w1 x1 plus w2 x2 plus b is equal to 0, right? The equation of a straight line. What if my equation passes through origin? Okay. Now when my equation passes through origin, over here you can see that obviously we can find out coefficient. That is not a problem. But with respect to b, that is our intercept. B basically means in this case, if my x1 and x2 are 0 over here, let's say in this particular case both are 0, right? Now in this case, what will happen? It is basically this line is passing through the origin. Now in short, b will also be equal to 0, right? So whenever there is a straight line that passes through origin, I can also represent this as w1 x1 plus w2 x2 is equal to 0, which is nothing but w transpose x is equal to 0. So equation of a straight line passing through the origin will have this particular equation. So equation of a straight line passing through an origin is nothing but it is given by W transpose X is equal to 0. Okay, this is nothing but the equation of a straight line. So let's consider now the equation of a plane that we have basically got over here. Equation of a plane is usually given by a notation which is pi, and this is not at 3.142. We're just saying it as pi in nine dimension, and this is represented as W transpose X is nothing but it is equal to 0, since we have considered that our intercept is basically our line is passing through the origin. And in this particular case, obviously my W value, it will be what, W1, W2, W3 like this up to Wn, and my X value will similarly be X1, X2, X3 up to Xn, right? And specifically when we do the dot operation, we are going to get this specific equation, that is W transpose X is equal to 0. Now forget about the equation of a plane. Now in this particular case, let's consider W multiplied by X. This W and X, let's consider that these are my two vectors. Let's say this is my W and X, okay? And if this W and X are there, and because over here obviously we have considered some values over here, right? Here we are basically doing some matrix multiplication by W transpose X is equal to 0. But if I just talk in terms of linear algebra, and if we try to see how this dot operation can be specified mathematically, here I'll specifically write W transpose X. It is nothing but magnitude of W multiplied by magnitude of X multiplied by cos theta. And this cos theta will basically be giving my angle between them, right? W and X vectors, if I'm specifically talking about this as vectors, right? This in turn will be equal to 0, okay? Because my W transpose X is equal to 0. Initially my W transpose X is equal to 0. Through linear algebra, we can definitely represent this equation as something like this, where we are considering magnitude of W multiplied by magnitude of X multiplied by cos theta. Now you need to understand when will cos theta be equal to 0. Obviously when theta is equal to 90. Suppose if theta is equal to 90, then my cos theta will be equal to 0, right? So in this particular case, we can definitely make a conclusion like something like this. Let's see this conclusion, okay? So if suppose I have an hyperplane, let's say this is my plane which is mentioned as pi, then geometrically I can definitely mention W as that it will be a vector that will be parallel to this specific plane. Okay, so this is basically my W, right? This is my W, and X coordinates that you can see over here. It can be this point, it can be that point, it can be any points in this particular plane. Now this is with respect to a 2D line. Now similarly with respect to a 3D line, how does a 3D line look like, or how does a 3D plane look like? So let's say consider that this is my 3D plane. Okay, let's consider that this is my 3D plane. Now in this particular point, if I probably try to create a straight line, this is basically my W, and this will be always perpendicular to every points that I see probably over here in X1, X2, X3, X4, X5, whatever plane we are basically creating. This will always be perpendicular, right? So mathematically, we can definitely mention that W will always be perpendicular to my plane, right? And this is what is the equation that we basically use to represent this. And this basically shows that at every point of time, whenever we are considering W, it is going to be always perpendicular to plane. And this W can also be represented, because you understand in this equation, it also follows this, right? W transpose X plus V is equal to 0. At this point, this is basically passing through origin 0, 0. This point is again passing through 0, 0. Now suppose if my coordinates, or if this line is not passing through 0, 0, or if this plane is, basically why I'm using 0, 0, because my intercept is equal to 0, right? So if I specifically say that if my intercept is not equal to 0, then it does not need to have that, it needs to always pass through the origin, right? Now this is with respect to a 2D line, 2D plane, right? This is with respect to 2D line. Sorry, I'll not say 2D plane, because I'll say plane with respect to a 3D, right? So here definitely origin is passing. Let's say this is my 3D plane. Here the origin is 0, 0. The W is always going to be perpendicular to every points that we see with respect to X1, X2, X3, anything as such, right? So this is how we represent the equation of a line, 3D plane, and hyperplane. I hope you have understood this. If you have not, please do make sure that you revise. And yes, this topic will be super important when we're discussing about logistic regression. We'll be discussing about support vector machines and all. So yes, this was it. Thank you. I'll see you on the next video. In this video, we are going to understand this linear algebra topic, like how to find out the distance of a point from a plane. Okay, so let's consider that I have a plane over here, and this is specified by pi. Okay, now with respect to this, and you know that if this particular plane passes through the origin, we can definitely use an equation which is like W transpose X is equal to 0. We just discussed this in our previous video, right? Now, when W transpose X is equal to 0, what is W over here? We can definitely say W is a vector that is perpendicular to this X-axis, that is this plane, okay, or this plane specifically, okay? Now, let's say if I have a point, okay, and let's say this point is specifically specified by X, and this has some coordinates like X1, X2, X3, like this up to Xn. Let's consider that this is an n-dimensional plane, okay? Now, how do I try to find out the distance between this particular point to this particular plane? And this is super important because in some of the algorithms like logistic regression and SVM, we are going to use this, because in logistic regression, we usually solve a classification problem. Classification problem basically means I have some coordinates, like some classes over here, some classes over here. And our main aim is to basically find out a best fit line such that it should be able to split these 2 points very easily. So that if suppose my new point come over here, it should be able to categorize in this particular group. Okay, that will probably be seen as we go ahead. Now, our main thing is that how do I find out the distance of this point S with respect to this particular plane? And let's say there is one more point which is over here, and let's say this is mentioned as S dash, and this is mentioned as X2, X3 till Xn, considering n-dimensional plane. So I also want to find out the distance between this particular point to this particular plane. And here you should note that W is perpendicular to this plane in this direction. Okay, so when I say perpendicular, it is 90 degree, right? Now, usually in this particular scenario, if I really want to find out the distance, again, I'm not going to prove you the formula that is basically used to calculate the distance, but in short, I'll try to write down the formula. So this D distance is basically calculated by W transpose S is basically my point, this point, that is x1, x2, xn, like this up till xn, divided by the magnitude of W. Okay, so this is the equation that is basically used. Again, proof, you can definitely refer some of the topics related to this even in Google. You'll be able to find out the proof. Like if I really want to compute the distance, considering my W vector and the S vector, which is again perpendicular to this particular plane, and W is in this direction, it is basically given by this particular equation. And obviously, from this, you know that if I try to calculate W transpose X, this is nothing but magnitude of W, magnitude of X multiplied by cos theta. So in short, if I really want to find out the distance of this point from the plane, I may also consider this W and X, right? So in short, I'm going to use this, right? And whatever angle is basically getting formed, and obviously this angle that you'll be seeing that is getting formed is less than 90. So if it is less than 90, that basically means I'm going to get a value between 0 to 1. So it is always going to be positive. So if I do this entire computation, this is going to be positive. You can see this angle between this W and X vector, it is always less than 90, right? In this particular case. So if I'm trying to calculate the distance with respect to this, right, I'm also always going to get a positive number. So that basically indicates that suppose if I have any other points, and if I try to calculate the distance between from this particular point to this particular plane, on top of this plane, I'm always going to get a positive number. Okay, that is the indication that we can come up with. Now similarly, what will happen about this D dash? That is below this plane, there's another point which is called as S dash, and we really need to find out what is the distance between this particular point to this. And you know that W vector is in the opposite direction. So in this particular case, my my D will be W transpose H dash divided by W, right? Magnitude of W. And this in turn, if I just take W transpose H dash, it is nothing but magnitude of W multiplied by magnitude of S dash cos theta. Now you know that over here in the above case, my theta was between 0 and 90 degree, right? It will always be less than 90 degree because it is above this particular coordinate. But what about in this particular case? If I try to contact this W and if I try to connect this W and S dash, here the type of angle that we are going to get is always greater than 90. And whenever we have any angle that is greater than 90 and less than 270 or less than 180, you know that we are going to, so here we are going to get greater than 90 and less than, or I can just consider greater than 90 and it can also be less than 270. Here all the time with respect to any angle that I get greater than 90, here I'm going to get a negative number, right? So this indicates that any point that are below this hyperplane, right? And if you try to calculate the distance, this is always going to be negative. Okay, super important point. Any point that are above this plane, and if you're trying to calculate the distance by using this particular formula, which is basically my distance formula, in short, all the time. And why this is happening? Because above this plane, my cos theta value will be between 0 to 90. Here it will be always greater than 90. Okay, so in this particular case, always this is going to be positive. The distance above this particular plane is going to be positive, and similarly, distance below this particular plane is going to be negative. This is a super important point in order to calculate the distance of a point from a plane. And two important points that yes, anything above this particular plane, which is in the same direction as the W vector, will be seeing that all will be having a positive value or positive distance. This will basically be having a negative distance. Why we are saying negative distance is just it's not like negative distance literally means something like negative distance, but instead it is just saying that it is in the opposite side of the plane. Okay, so this is how we basically indicate. And the same concepts we're going to use it in support vector machine. So I hope you got this particular idea with respect to the equation of a straight line. Distance of a point from a plane. Equation of a straight line was already covered in our previous video. So yes, I'll see you all in the next video. Thank you. In this video, we are going to discuss about instance-based learning versus model-based learning. Now guys, whenever we solve any specific use case, right, and let's say that for this particular use case, I really want to create a model, and this specific model will be, let's say I'm creating a machine learning model, and this machine learning model will actually help us to solve some problems, let's say a regression or classification problem, right? Let's say I'm trying to solve a regression or classification problem, right? Now in this, if I really want to find out what is the exact differences between instance-based and model-based learning, usually this machine learning model learns about the data in various ways, right? The first way is basically through the instance-based techniques, and the second way is basically through the model-based techniques, right? Now, when I am actually dividing this two, I'd also like to probably, and this entire differences is based on the learning patterns of the model. Learning patterns of the model. That basically is how the model are able to understand the data. If my model is completely dependent on my training data, let's say if it is completely dependent on my data, and for doing every prediction, it will be dependent on the specific data. So based how the data actually exists over here, based on that, we will be getting some specific output. But in the case of model-based technique, whatever data we use over here, what this model-based technique does is that it tries to understand the pattern within the specific data. Okay, pattern within the specific data. And once it understands the pattern with respect to the specific data, it creates a generalization method to make the prediction for new data, right? And this generalization method is far more better when compared to this instance-based techniques, because in instance-based technique, the model is just dependent on the data that it has currently, and whenever a new data basically comes, based on this particular data only, that tries to predict the output. It's just like a domain expert kind of thing. Let me give you an example, okay? So that will help you to understand. Now, let's say that you have features, and the specific features are like number of play hours. Okay, let's say I'm using these features: number of play hours, number of study hours, and the last column is there whether the person is going to pass or not, okay, or pass or fail. Now let's say that if I have these three specific features, okay, and these are the features with respect to whether for a student, right, how many number of hours he's playing, he or she's playing, how many number of hours he or she is studying, right, and then we need to predict whether the person is going to pass or not. Now if I probably take this particular data points, right, and if I just try to plot this particular data points over here, okay, so let's say this is play hours, this is study hours, okay, and you know that this will be inversely proportional, right? If a person is playing more, right, and if he's studying, or if a person is studying, if a person is playing more and he's studying less, then I can suggest that he may probably not pass, right? So I may have different data points over here. Let's say these are some of the data points, okay, let's say these are some of the data points, right, and let's say there are other data points where the person is studying more, and based on that, this red mark that you'll be seeing, it is basically saying pass, and this yellow mark is basically saying fail, right? Now in this particular scenario, obviously there will be some kind of outliers also, okay, like even though the person is playing more, he may his study hours may also be more, and because of that he may pass, right? So there may be obviously some data points from this particular data points, even though he's studying less, he's able to pass that specific exam, right? Now in this particular use case, what happens is that in the case of instance-based learning, okay, this will be just like a domain expert. Just imagine this, okay, this will just be like a domain expert, like how this specific model works. Now in this, just imagine that suppose a new query point comes. Let's say the new query point is somewhere here, right? It's somewhere here. Now what happens in instance-based learning? The model knows the training data. What it is going to do, it is not going to understand the pattern within this data. It is just going to see the surrounding data around it. Let's say if this particular data point is coming, it will see that how its surrounding is basically behaving. If the surrounding is behaving in a way that most of the points are passed, at that point of time, this will actually become passed. Otherwise, if most of the data points are failed, then this will probably be failed. Now here you can see within this circle, most of the data points are failed. So this will actually behave in that specific way, and this will, the new test data will actually show it as fail as an output, right? So here specifically, it is focusing more on the training data, or you can just say that it is learning religiously from this particular training data, okay, religiously, right? Now, this is what basically happens in instance-based learning, right? Here you will not be getting any patterns, right? The model will not learn based on some specific patterns. Here you just have a training data, and based on this particular training data, you will try to learn it, and you'll try to find out the different kind of outputs. Now, this instance-based learning, there are a lot of different techniques, right? One of the techniques that I would definitely like to talk about is KNN, right? K-nearest neighbor is one of the algorithm which uses this instance-based learning, right? And we will discuss about this, okay? And there are some kernels also which we are going to discuss about instance-based learning. But if I probably consider the same problem statement with respect to model-based learning, now let's say if I had a specific model-based learning, okay, and if my machine learning model learns based on this model-based learning, and let's say if I have some of the data points over here,
here what will happen is that my model will understand a pattern in this data, right? So it basically understands the math intuition behind this. So it is able to create a generalized model. A generalized model basically means that it will be able to perform well even for any kind of data it may probably come in the future. So generalized model basically means it's trying to understand the pattern, what pattern is basically used in this and how it is basically behaving. Let's say these are all my data points. Now in this particular case, what will happen is that my machine learning model will probably try to create this kind of line. Let's say it will try to create this curve. Let's say this curve is basically called as decision function or decision boundary, right? That basically means anything that comes below this particular decision boundary, we are going to consider it as fail, and anything that comes above the decision boundary, we are basically going to consider it as pass, right? So this is the basic difference between instance-based and model-based learning. Here, you create a generalized format to learn the data. Generalized format to learn the data, right? To learn the data. That basically means this model is going to behave based on this decision boundary because it has understood the pattern, okay? And this pattern, it is going to basically be used for any future new data to predict whether the person is passing or failing, right? But here, it is completely dependent on the current data that it has, Based on this data, let's say if you probably get another point, another new query point, again, it will try to see the surroundings, and based on that, it will try to take a decision whether it should be pass or fail. So this is what is instance-based learning is and generalized-based learning. In terms of a student, just imagine this is more like by hearting the data, right? By hearting the data, that basically means memorizing the data, okay? Memorizing the data. Okay, by heart basically means we usually say, right? Again, I should not use this word, but here focus that the model is trying to memorize the data. Here the model is trying to learn the data. Okay, here learn the data. The model is trying to learn the data so that from this learning it is being able to create a decision boundary. Or I can also say learn the pattern of the data. Okay, just not learn, otherwise it will be a wrong word to basically use. So here I can definitely say learn pattern of the data. Learn pattern of the data. So this is the basic differences between instance-based learning and model-based learning, and I hope you got an idea about it. Now let's go ahead and understand some of the differences. Here are some of the differences. So usual convention machine learning model basically means this is model-based learning, right? This is model based, this is instance based. Okay. So first of all, prepare the data for model training. Obviously, you'll require the data over here also. Here also you'll be requiring, no difference over here. Then the second point is train the model from training data to estimate the model parameters, like discover patterns. So here, as I said, this here you're trying to do the generalization. You're trying to learn the decision boundaries, right? And this is only possible when you will be learning the parameters, or when you'll be learning the model parameters within that. And from that training data, is being able to identify that. This is a super important one, which is basically discover patterns. Okay. Here, do not train the model, pattern discovery postponed until squaring query received. So that basically means whenever you get a new data point, then only we will try to square this, right? Here, no pattern recognition is there in the instance-based learning, right? Whenever new data comes, then only we'll be able to identify based on the surrounding data whether it is yes or no, or whether the person is going to pass or fail. Okay. Store the model in suitable format. So in most of the models that we'll be using, we will be able to save them in some pickle format file. So this will be able to store it in the hard drive, or we'll be able to store it in any folder location or any cloud location. There are different types of file format like pickle, HDF5, H5 format, and many other formats. Okay. We also say it as H5 format, right? So definitely we store the model in some suitable format, and whenever we store this particular model in this format, it is basically stored in a serialized format. Serialized format. That basically means, see, internally some math equation is there within this particular model. So whenever any data comes to this model, right? So let's say this is my model, which is in the pickle format or serialized format. Whenever we give our input over here, we will be getting some kind of output. So internally here, you'll be having a lot of mathematical equations that will be serialized in the serialized format. Okay. So there is no model to store. Generalize the rules in the form of model even before scoring instances. This is super important because since we have decision boundaries, to generalize the entire rule. No generalization before scoring. Obviously, you have seen the difference between them. Predict for unseen scoring instance use models, right? We'll be able to even predict completely new data because since we have created a decision boundary so that it gives us result in a generalized manner, both for a training data set or for any new kind of data that we're going to get. Predict for unseen scoring instance using training data directly. Okay. So here you'll be able to see here we are specifically only using training data. Okay. To do even the prediction of the new data. Can't throw away any input or training data after model training. So here you can throw the input and the training data even. Okay. Once the model is trained, you can just throw it completely. You don't require it. Why? Because now you have a specific model, and this model is in some format. It is in the serialized format, and it has all the decision boundaries and pattern recognition within them. So whenever a new data comes, it will just be able to predict the output. But in the case of instance-based learning, you always require the input or training data. Okay. So let's say after I get my input data, and if I train my model using this model-based learning, and what will happen? I will be able to get my score, the accuracy. Okay, just don't worry that what are all these things. We will learn as we go ahead, right? Now, after training our model, we can remove this input data because everything is stored inside this, right? The decision boundaries and all. So any prediction that we give with respect to a new data, it will be able to do it. But in the case of instance-based learning, we always require the input or training data. Okay, requires a known model form, may not have explicit model form. This is the basic difference. Storing model generally requires less storage because this model pickle file that is created, it will either be created in KBs or MBs, right? Since we even don't store any training data, so we just create the serialized format of this pickle file, and inside this, you know that it is being able to recognize patterns and decision boundaries it is able to create, right? So these are usually stored in KBs or MBs. Whereas in the case of storing training data generally requires more storage. Obviously in instance-based learning, just imagine in your training data you have 10,000, 1 million records. So it is obviously going to take more storage space. And scoring for a new instance is generally faster. Scoring for a new instance may be slow. The reason I tell you, the reason this particular point is mentioned that scoring for a new instance is generally fast because our model is in a serialized format. So whenever we get any kind of input, internally all the mathematical equations will quickly get triggered and automatically we'll be able to get the output. But in the case of instance-based learning, it will go and first of all see the surrounding data points, and then it will use some parameters like Euclidean distance, some distance parameters, and then it will be able to finally tell you the output. So obviously the model-based learning is faster than the instance-based learning. That is what is the outcome that you can actually get from here. So I hope you have understood this, the basic differences between instance-based learning and model-based learning. And the main thing is that from the instance-based learning, you are just learning from the data. You're just memorizing the data. So here I want to make one point that the learning of the model usually happens by two ways. One is memorizing, one is generalizing, right? And generalizing is a better way when compared to memorizing. But yes, for some of the use cases, you can use memorizing techniques. So memorizing technique is basically my instance-based learning, and generalizing is basically a technique with respect to model-based learning. Okay. So these are the basic differences between memorizing and generalizing. So yes, this was it for this particular video. I hope you're able to understand what is the basic difference between instance-based and model-based learning.
we'll learn our first machine learning algorithm, which is called a simple linear regression. This is a super important algorithm because the techniques that we're going to learn in this will also be applicable in deep learning when you're probably learning the first neural network, which is called an artificial neural network, right? So it is super important we try to understand this. And remember, this machine learning algorithm, I'll try to break down this into separate modules so that you can understand it in a better way. Now, what kind of problem statements do we solve with simple linear regression? As the name suggests, regression. So definitely in supervised machine learning technique, if you have a regression problem statement, we can definitely solve it with the help of simple linear regression. Now, what exactly simple linear regression algorithm is all about? Let's say that I have a specific and easy data set. Okay, let's say I have a data set, and this particular data set has features like age and probably weight. Or instead of writing age and weight, let's basically just write something like weight and height. Okay. Now, as I said, regression problem statement, obviously I will be having some data points. Let's say if the weight is somewhere around 74 kgs, my height may be 170 centimeters. If the weight is 80 kgs, the height may be 180 centimeters. If the weight is somewhere around 75 kgs, the height may be 175.5 centimeters. Let's say this kind of data set I have. Okay. Now, in this particular data set, our main aim is that we need to train a model, and this specific model, whenever we give our new weight, it should be able to predict the height. Okay. This should be able to predict the height. And now you just see this. Okay. So this feature is basically our independent features. And this feature is specifically our output or dependent feature. Okay, dependent feature. So this is what we are planning to do. And this model that we're going to train is with the help of simple linear regression. Okay, simple linear regression. Now, why do we say it as simple linear regression? Understand over here how many input features we have over here. We just have one input feature and one output feature. Whenever we just have one input feature, then we say it as simple linear regression. If we probably have multiple input feature, then we can basically call it as multiple linear regression. But it is very important to just understand simple linear regression, then automatically whatever terminologies and maths that you probably learn in this will get applied to multiple linear regression also. Okay. So in short, what are we trying to do? As I said, for this specific model, we will train it with this specific data. Okay. And later on, this model, whenever it takes new weight, should be able to predict the height. Okay. If I really want to show you in a geometric way, what are we trying to do? Let's say this is my weight and this is my height. Okay. Now, with respect to this particular data set, let me plot some points. Let's say there are some points which is plotted like this. Okay. So with the help of simple linear regression, what we are trying to do is that we'll try to create a best fit line. Okay. And this best fit line will actually help us to do the prediction for the new weight. So let's say, how does the prediction happen? Let's say once we get this best fit line, okay, and this best fit line should be created in such a way that, that the distance between the true points. The true points basically means these are my true output, right? These are all of my true output, 170 centimeters, 180 centimeters, 175.5 centimeters. So the distance between this and this predicted point, this and this predicted point, distance between this and this predicted point, this and this predicted point, this and this predicted point, this and this predicted point. If I do all this distance, and this is basically the error, right? Because these are my 2 points and these are my predicted points. So right now, just understand till here, I will again explain in more detail, right? So this distance should be, if I do the summation of this distance, it should be minimal. And that is the technique we basically use to select the best fit line. Now, once we create this best fit line, whenever we get a new data point, let's say with respect to this particular weight, how do we predict our output? What should be the height? All we do is that we try to just put this line on this particular, and we just try to see where this point meets this particular line, which is my best fit line. This is basically my best fit line. Okay. And then we try to see where in the y-axis it is basically meeting. Okay. So suppose if it is meeting at this particular point, so this specific is my output for this specific weight. This is what we actually do in simple linear regression. Okay. Over here, the main is that we just try to create a best fit line such in whenever we give our new weight, we should be able to predict what should be the height. Okay. Now, as we go ahead, let's understand what is the mathematical equation of this particular best fit line. And when I spoke about this error, what is this specific error? We'll also try to understand, and we'll try to understand in a very amazing way. Okay. So let's go ahead into the next video. Thank you. We are going to continue the discussion with respect to simple linear regression. We have understood, what is our main aim, what we are actually trying to do with the help of simple linear regression. We are actually trying to create the best fit line. But before we go ahead and understand the maths behind it, we really need to understand some of the notation that I'm actually going to use while explaining this entire machine learning algorithm. So let me go ahead and let me again consider this. So let's say that in the x-axis, I have my weight, and in the y-axis, I basically have my height. And I do make sure that I populate some of the points, which are like this. Let's say I have just randomly created some points. And these points basically mention our data set, right? Whatever data set we have, right? And these points only we are going to train our specific model, and what we are planning to do is that we are planning to create a best fit line in this, right? We are trying to create this best fit line. Now, in order to create this best fit line, we basically provide some equations to this best fit line. You can basically use the equation of a straight line like y is equal to mx plus c, or if you've seen some of the research paper, they may also use something like y is equal to beta 0 plus beta 1 multiplied by x, and you may also have another equation, which, Andrew Ng also uses this specific equation when he teaches it, So he uses h theta of x, which is nothing but theta 0 plus theta 1 into x, right? So this equation. So in this entire simple linear regression that I'm actually explaining, again, some amount of credits, yes, definitely goes to Andrew Ng. Is quite amazing with respect to teaching any kind of topics. So I will also be using this specific notation, which is basically nothing but h theta of x is equal to theta 0 plus theta 1 into x. Okay. Now here, if I talk about x basically means my independent feature. Now in this particular case, it is weight. Okay. Now let's go ahead and let's try to understand what is theta 0 and what is theta 1. That is the most important thing that you really need to understand in this best fit line. Okay. And what is this h theta of x? Okay. So over here, let me write down the equation. H theta of x is equal to theta 0 plus theta 1 into x. Now first of all, what exactly is theta 0? So theta 0, we can definitely say it as intercept. Why do we say it as intercept? In short, let's consider that if my x value is 0, then what will happen? If my x value becomes 0, then what happens? H theta of x is nothing but theta 0. Now this basically indicates that when my x value in this particular, in this line that I'm actually drawing, right? Weight is my x in the x-axis, right? So when weight is 0, where does this particular line meet at the y-axis? Okay, so this particular line you'll be seeing it meets somewhere here at the y-axis. So this particular point is nothing but this particular point is mentioned as intercept. So in short, what does theta 0 basically indicate? It basically indicates the intercept. That basically means when x is 0, what is the value of theta 0? Okay, so theta 0, wherever it is meeting the y-axis, that is basically called as intercept. Okay, so this is the first thing that you really need to know. Very, very important. Now let's go and understand what is theta 1. Theta 1 is nothing but it is called as slope or coefficient. Okay. Now, whenever I talk about slope or coefficient, what does this basically indicate? This basically indicates that with the unit movement in x-axis, suppose if there is a unit movement in x-axis, so if I try to plot this over here in the y-axis, we are just going to try to see that what is the movement with respect to the y-axis. So in short, what is the slope movement? Okay, so this is the movement that we are trying to see. So with the unit movement in the x-axis, what is the movement with respect to the y-axis? That indicates something called as slope. Okay, so very simple. This is also called a slope or coefficient. That is basically indicated by theta 1. Okay, suppose if I have many independent features, then this equation becomes something like this: h theta of x is equal to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, like this up to theta n xn. So I can just write theta n xn. So this basically indicates that I have many features. So definitely I'll be having that many number of slopes, like theta 1, theta 2, theta 3 till theta n. But here, since I just have one independent feature, so I'm just going to basically say that okay, I have just one slope. Okay, one slope. Now, this is the basic understanding with respect to theta 0 plus theta 1 x, right? So x is nothing but my data points with respect to the x-axis. Now, one more very super important thing. Now, as I said that, once we create a best fit line, whenever I get a new data point, let's say this is my new data point with respect to weight. Okay, with respect to weight, this is my new data point. Then how do I predict my height? All I do is that I try to project this over here and I try to basically see what is my y value. Okay, so this is basically my y value. So this point, I can say this is my predicted point, right? Predicted point. So whatever points I'm actually predicting over here, that is mentioned by h theta of x. So h theta of x is nothing but this is basically my predicted point. Let me give one more notation. This notation is nothing but y hat. Okay, so y hat I'll be using to basically specify my predicted points. Okay, predicted points. Very simple. Okay, now let's go and understand what exactly is error. Can I say error over here is nothing but the difference between, see, this orange point is nothing but y point, right? Y point, why I'm saying? Because over here in my data, right, this is my output. Let's consider this is x, this is y, right? So this basically is my output, right? And the points that I probably get, let's say this is my y point, and let's say with respect to this, my my predicted point is somewhere here, right? So if I do this difference, then with respect to this specific data point, this should be my error, right? This should be my error. So error over here, nothing what I'm doing, I'm just subtracting y minus y hat, right? Y minus y hat. So in short, I'm just trying to find out the difference between these 2 points, and that actually specifies my error. Again, let me talk about like what is our main aim. Our main aim is to basically come up with a best fit line, wherein when I try to calculate or do the summation of all this error, it should be minimal. If it is not minimal, suppose there is another best fit line that actually brings up this error or minimizes this error, I'm just going to select that specific best fit line. Okay. So I hope you have got the idea about error, what h theta of x is, what y hat is, and what all with respect to theta 0, what is theta 1 and all, right? So these were some of the notations that you will need to know when we start learning about the simple linear regression. Now, as we go ahead, we will try to understand how this best fit line is basically created, because we cannot just go ahead and randomly create many best fit line and then probably try to check each and every what is the error once I do all the summation of the error, which is less, and then try to select a best fit line. No, this is not efficient. So we'll try to find out an optimized way wherein first of all we will try to create one best fit line, and then we'll try to rotate this best fit line by changing the values of intercept and coefficient, right? We are going to change the value of theta 0 and theta 1, theta 0 and theta 1, and then try to find out the best fit line with minimal error, right? So this is what we are going to learn, and we'll try to see how this optimization technique will basically happen and how we are going to perform all these things, right? So yes, I will see you all in the next video. Thank you. We're going to continue discussion with respect to the simple linear regression. And in our previous video, we have already seen what is our main aim, and we have understood about the notation. And we also found out that, okay, let's try to find out an optimized way to actually get the best fit line. Okay. Now for this, we will be using a cost function. Now here I'm just going to mention about this specific cost function. And this cost function is basically given by a notation. Let's consider this specific notation. J theta 0 comma theta 1 is nothing but 1 by 2m summation of I is equal to 1 to m h theta of x of I minus y of I whole square. Now what is h theta of x of I minus y of I whole square? As I said that we have to make sure that we have to create a best fit line in such a way that when we do the summation of all the specific errors, it should be minimal. So that is the reason we are taking up this cost function in this specific way. H theta of x of I is nothing but these are my predicted points, right? These are my predicted points, and these are my truth points. So basically the true output, right? And I'm going to do the summation, basically do this when we do subtraction, we basically get the error value. And the reason we are squaring it because the technique, the cost function that we are using this, we basically say this cost function as mean squared error. Okay, mean squared error. And there are a lot of advantages of using mean squared error, which we will probably discuss as we go ahead. Now you may be thinking, Krish, is there different kind of cost function also used? Yes, absolutely. You also have something called as mean absolute error, root mean squared error. We will all try to discuss about all this type of cost function and what is the advantage and disadvantage with respect to that. Okay, but here right now, the reason I'm taking up this cost function because we really need to minimize this cost function, and we need to minimize in such a way by changing the theta 0 and theta 1 value. Theta 0 basically tells us about the intercept, and theta 1 basically talks about the slope. Okay, so what is our final aim? I'm just going to write out final aim, what we need to solve. Okay, what we need to solve. This is super important. Then only here I basically use the cost function. So our main aim is basically to minimize the cost function j theta 0 comma theta 1, which is basically denoted by this specific equation, that is 1 by 2m summation of I is equal to 1 to m h theta of x of I minus y of I, okay, whole square. Okay, since we're dividing by m, so we are getting this as mean, right? Mean squared error. We basically say this cost function as mean squared error. And how we are going to minimize this? By changing the value of theta 0 and theta 1. So we really need to continuously change this theta 0 and theta 1 and try to find out the best fit line wherein we do the summation of this particular error, and this should be minimal. Okay, minimal as possible. Okay, so this is what is our final aim that we are looking at. Okay, and how we are going to do this? Let's try to discuss about it. Now I hope everybody knows what is the equation of my straight line. This is nothing but h theta of x, theta 0 plus theta 1 into x. So that basically means if I probably consider this, okay, the best fit line, whatever straight line I'm actually getting, let's consider that I'm getting this specific straight line. So this line is basically indicated by this equation. Now one important thing, guys, since there are two variables, right, theta 0 and theta 1, let's consider that theta 0 is 0. Okay, let's consider. There is a reason why I'm saying, because I really wanted to show you everything by drawing it in a 2D diagram. So let's consider theta 0 is equal to 0. If I say theta 0 is equal to 0, that basically means when my x value is 0, it is basically passing through the origin, right? This line is basically passing through the origin. So this intercept is exactly 0. Okay, so now my equation becomes h theta of x is equal to theta 1 multiplied by x. Let's consider that what I'm doing over here, my intercept is basically passing through the origin. I'm just considering it so that I can draw a cool 2D diagram to make you understand more in depth. So currently I'm going to just use this specific equation. Okay. Now let's consider some of the data points. Let's say this is my x and y. I'm just going to write 1, 1, 2, 2, and 3, 3. Okay, let's consider that this is my entire data set. And for this particular data set, I really need to create a best fit line because this will give you a clear idea that what we are trying to do. So what we will do, we will just try to create this line like this. Okay, this is my x, this is my y. So let me create it a little bit straight so that it looks cooler and good. So this is my x and this is my x and this is my y. Let's say these are my values like 1, 2, 3, and with respect to like y also I have 1, 2, and 3. Okay. Now let's start. Okay, and obviously everybody knows what is the equation. It is nothing but s theta of x is equal to theta 1 multiplied by xy because theta 0 is equal to 0 because we are considering it passes through the origin. Okay, so I have my data points. My data points are 1, 1, 2, 2, 3, 3. So let's go ahead and plot it. Okay, so here is 1, 1, then this is 2, 2, and this is basically 3, 3. Okay, now if I have this particular data points, I'm going to use this equation of a straight line to make sure that I plot my best fit line. Okay, now let's consider we need to initialize theta 1, right, to something. So let's consider let theta 1 is equal to 1 because this is my slope, right, and we have to initialize the slope and later on we will keep on changing the slope to get the different best fit line. So if theta 1 is equal to 1, then when x is 1, what will be my s theta of x? So my s theta of x will be actually 1 when my x is equal to 1, right? I hope this is very much clear, right? So let me just put this points, then this will be basically my predicted points over here with respect to s theta of x. Now when x is equal to 2, what will be my theta h theta of x? Now h theta of x will be, since I've initialized theta 1 as 1, when x is equal to 2, that basically when h theta of x will be 2. So my second point will be somewhere here, right? The predicted point, h theta of x, okay? And similarly, when my x is equal to 3, when theta 1 is equal to 1, that is my slope is equal to 1, then h theta of x is equal to 3 because 3 multiplied by 1 is nothing but 3. So my third point is somewhere here. Now if I try to create a best fit line, so this is going to pass through all these points, right? All these points. So it is going to exactly pass through all these points. And obviously it will also pass through the origin, okay? So in short, these are my predicted points and over here I also have my truth points, right? I also have my truth points. Now let's go ahead and apply this cost function, j of theta, theta 1. This is the entire equation. So what is my cost function over here? My cost function is very simple. I will write j theta 1 because theta 0 is 0, right? It is passing through the origin. So I will write 1 by 2m summation of I is equal to 1 to m, and here I will basically say h theta of x of I minus y of I whole square, right? So how many points I have totally? I have 3 points, right? In my data set, I have 3 points, 1, 2, 3. So I'm just going to basically write 1 by 2 multiplied by 3, and I'm just going to basically say summation of I is equal to 1 to 3. Okay, so it will be the entire summation of 1 to 3, right? So no need to write 1 to 3. So I will start expanding this. So first thing is what is h theta of x of I when I is equal to 1? So over here you can see when I is equal to 1, h theta of x of I, the predicted point is also 1, right? So I'm just going to basically write 1 minus what is y of I at that particular time? So y of I is also 1, and here also we have plotted it. So 1 minus 1 whole square. Okay, then plus we'll go to I is equal to 2. I is equal to 2. Over here you can see when the x value is 2, h theta of x of I is also 2 and y is also 2, right? So over here I'm going to write 2 minus 2 whole square, and similarly this is 3 minus 3 whole square. Okay, so overall if I try to find out, it is 0. So what does this basically indicate? My cost function is 0. This is absolutely right, right? Because obviously there is no error. Exactly, the best fit line passes through all the points, right? Now this is one way. Okay, now let's go ahead and consider, let's change our theta 1 value. Let's say that our theta 1 value is now, let's consider that our theta 1 value, let's say our theta 1 value is 0.5. Now if it is 0.5, then what will be h theta of x when if x is equal to 1? So it will be nothing but theta 1 is 0.5, 0.5 multiplied by 1, right? So this is going to be 0.5, right? So when x is 1, so my h theta of x will be 0.5. So let me just denote this particular point over here. It will be 0.5. Okay. Now similarly, when theta 1 is point, and if x is equal to 2, then here you'll be seeing h theta of x will be 1 because here we are just multiplying theta 1. Theta 1 is nothing but 1. Okay, 1 multiplied by 2. Sorry, 1 multiplied by theta 1 is 0.5. So in this equation, h theta of x, theta 1 x, right? 0.5 multiplied by 2 is nothing but 1. Then h theta of x is equal to, when x is equal to 3, this is going to be 1.5. Okay. So when your x is 2, I'm actually getting 1. So I'm going to basically note this particular point. And when x is equal to 3, h theta of x is nothing but 1.5, which is basically mentioned at this particular point. Okay. Now here you'll be able to see that I'm just going to draw this next best fit point. So I'll make it a little bit better so that the point is basically drawn. So this is my best fit line for the next one. Again, sorry. So 3, 5. Okay, now this time I should be getting a best fit line. Okay, so this is my best fit line. Okay, now here you should be able to understand that these are my predicted points. This are my predicted points. Okay, now with respect to this, again, let's go ahead and calculate j theta. Okay, j theta of 1. So here I'm basically going to write what is j theta of 1. J theta of 1 is nothing but 1 by 2m. Again, I'll apply the same formula. So this will be 1 multiplied by 2, 1 divided by 2 by 3. And now let's go ahead and try to find out. So when my theta 1 is 0.5, let me write it down below. Okay, so that you will not miss anything. Okay. So for the first case, let's consider I've also drawn this specific point, and let me draw one more amazing graph. Okay, and this graph will be mentioning something very important. So let's create one more graph over here, and we will continue. We'll continue with respect to different values. This graph is between theta 1 and j of theta 1. Okay, and let me denote it some points like this: 0.5. This is basically 1, 1.5, 2.0, 2.5, right? And similarly, this is 0.5, 1.0. Okay, and this is 1.5, and this is 2.0. Okay, so this points I'm just creating along with this a different graph over here, and this graph basically indicates the graph between theta 1 and j of theta 1, the relationship between theta 1 and j of theta 1. Now in the first case, when my theta 1 was 1, what was my j of theta 1 in this particular case? It is 0. So I'm just going to basically plot this particular point. Okay, when my theta 1 was 1, and here you can basically see my j of theta was 0. So can I plot this particular point somewhere here? So I'm plotting it somewhere here. Okay, so this is my first point that I've got. Now with respect to theta 1 is 0.5, let's go ahead and compute my j of theta 1. So j of theta 1 is nothing but, I will start writing it down over here, and you also make sure that you write this particular equation very much easily. So it will be nothing but 1 by 2 multiplied by 3. And in the first case, what is h theta of x when theta 1 is 0.5? So over here you can see when if x is equal to 1, so here you can see that h theta of x is 0.5. So here I'm going to subtract, write 0.5 minus 1 whole square. Okay, 1 how I'm getting? My true value 1 is over here, right? Still my real point is over here. So 0.5 minus 1. So this is the error that I'm actually getting, right? Similarly, this is the error I'll be getting here, and this is the error that I'll be getting here. And we really need to write that specific error. So 0.5 minus 1 whole square, then I have 1 minus 2 whole square plus 1.5 minus 3 whole square. So once I try to find it out, so this will be when my theta 1 is equal to 0.5, right? When my theta 1 is equal to 0.5, the j of theta 1, just try to compute it, you will approximately be getting somewhere around 0.58, okay? Once you do the calculation. So over here, when my theta 1 is 0.5, I'm just going to get j theta 1 as 0.58. So 0.58 will come somewhere here. So I'm just going to make this point somewhere here, okay? Not here, sorry. somewhere here. With respect to theta 1 is 0.5, I'm going to get the point somewhere here. Okay. And this is that. Okay. Now let me consider one more thing. Let's consider what will happen if I consider my theta 1 is equal to 0. If I consider theta 1 is equal to 0, that basically means when x is equal to 1, that basically means what? Theta 1 is 0, 0 multiplied by 1 will be 0. So my first point will be here, my second point will be here, my third point will be here, right? So this will basically be my next best fit line. And obviously the error will still be higher. Then obviously I consider that when I probably try to calculate j of theta 1, if my theta 1 is equal to 0. In this particular case, what will happen? J of theta 1, just try to compute it. It will be very simple. Here I will write 1 divided by 2 by 2 multiplied by 3. And theta 1 is first 0, 0 minus 1 whole square, then 0 minus 2 whole square, then 0 minus 3 whole square, right? So I'm just going to write like this: 0 minus 1 whole square plus 0 minus 2 whole square plus 0 minus 3 whole square. And obviously this is not the best fit line. Obviously I am going to get my error quite high. So it will be somewhere around 2.3. So J theta 1, when theta 1 is equal to 0, it is nothing but 2.3. Now here, if I try to plot this, when my theta 1 is 0, and I'm getting somewhere around 2.3, which is somewhere over here, right, at this particular point. Now if I keep on continuing doing with different theta 1 value, after some points you'll be seeing that I will be getting this kind of curve. Okay, this kind of curve. And always remember, when we are trying to get this kind of curve, okay, the main point that I got over here at this particular point, you know that the best fit line was this line, right? At this point of time, my error was very, very less. So I can definitely say this is the point, this is the global minima. This point is basically called as global minima. And we really need to achieve this particular point, or at least near to this point, to say that my error has definitely minimized. My error has been minimized. Why? Because at this particular point, I am actually getting my best fit line. So this entire curve is called as something called as gradient descent. Okay, so this curve is something called as gradient descent. And this gradient descent is super important even in deep learning techniques. Okay, we have to come to this specific point by changing our theta 1 or theta 0 values. Okay, so unless and until we get this particular point, that basically indicates that we are going to get our best fit line. So here you can clearly see that when I had this specific point, and over here the cost function was 0, so that basically indicated that I did not have to move much weight over here, and this basically indicated my global minimum. Okay, global minimum. So our aim is that we should definitely try to come to this particular point by moving along this particular gradient descent. Okay, and that is how we should try to change our theta 1 and theta 0 values. Right now, since theta 0 is just passing through the origin, we don't have to change it much, but yes, definitely got an idea about gradient descent. And our aim, what were we actually planning to do? We were planning to minimize the j theta 0 comma theta 1, since theta 0 is 0, so I have not written theta 0 specifically over here, but we had to minimize this by changing the value of theta 0 comma theta 1. In this particular case, theta 0 was already 0, so we changed theta 1 value and we minimized this value, right? So here you could see that when we minimized, because see, when my theta 1 over here in this particular case, my j of theta 1 was 0, the cost function was 0. When my theta 1 was 1, right? So at this specific instance, I was getting my cost function as 0, and this was the point where I got my best fit line. Okay, so in this way, we should definitely change these things. But again, I cannot keep on just randomly selecting different theta 1 value, right? That is not at all possible. So we should apply some kind of convergence algorithm. Now, in my next video, I will try to make you understand what exactly is the convergence algorithm, because we cannot randomly initialize theta 1 value. We should select one theta 1 value, and we should try to find out a mechanism of changing those theta 1 value. Okay, so yes, in the next video, we're just going to discuss about the convergence algorithm. So I hope you're liking it. I hope you're able to understand it. If you have any queries, please make sure that you write down in the comment section. Thank you. We're going to continue the discussion with respect to simple linear regression. In our previous video, we had discussed about cost function and how we could actually find out different cost function by changing our theta 1 value. And we also saw that we could form a gradient descent curve, which is this kind of curve. And our main aim is basically to come up to this global minima, because in this global minima, when we come near this global minima, that basically means we are very much near to the best fit line, because our cost function is quite minimal. But when we are trying to find out a cost function, we were randomly changing our theta 1 value, which is our slope. First time I took 1, then we took 0.5, and then I selected at 0. This is not an efficient technique. So I told you that we will be discussing about the convergence algorithm, which will actually help you to initialize one theta 1 value, and automatically, based on this gradient descent, it should be able to, increase the theta 1 value or decrease the theta 1 value. So let's understand the convergence algorithm. So over here, I'm just going to mention the convergence algorithm, which is super important for the optimized technique. Okay, so this is the convergence algorithm, and this convergence algorithm main aim is to optimize the changes of theta 1 value, which is my theta 1 value, okay, which is my slope, okay, in this particular problem statement. So what does convergence algorithm basically say? Convergence algorithm basically say repeat until convergence, okay, until convergence basically means until we reach the global minima, this specific global minima point, okay, this specific global minima point. So here you can see that when we reach this global minima point, we got the best fit line, or at least if we come near this, we will probably get the best fit line, okay. So repeat until convergence, and here I'm just going to write a simple equation, which is like theta of j, okay, theta of j is equal to theta of j minus, okay, alpha. I'll talk about this, what exactly is alpha, and then we are going to basically write derivative of theta j with respect to the j theta 1, okay. Or here I'm just going to basically write theta j. Now what exactly this is, okay. Now try to understand, okay. This theta j, initially we'll initialize something, and then we'll try to find out the cost function. And obviously you know that with respect to the cost function, how does the cost function basically is created? So here, if I initialize and create a graph with respect to theta j and j of theta, okay. So this is what we created, this graph, right over here. You could see this, right? You know that we usually get this kind of gradient descent, right? Let's say with respect to, and this equation will definitely work, okay. Well, this equation is definitely going to work. That basically means this equation actually helps us to change our theta value, specifically in our problem statement, the theta 1 value, much more efficiently. So we are going to change this theta 1 value much more efficiently. How? Okay. So let's consider my theta j value is somewhere at this specific point. So j of theta will be coming somewhere here. Okay. Let's consider that this is the point that I'm going to probably get. Okay. Now you need to understand what exactly this is. Okay. Derivative of theta j with respect to j of theta j. Okay. With respect to in short, we are just trying to find out the derivative of this specific point. Now, whenever we say derivative, in short, we are going to calculate the slope. Okay. Now, let's say we have initialized one theta 1 value randomly at this point. We got our j of theta at this particular point. Now, our main aim is that we need to come to this specific point. Okay, because why this specific point we really need to come? Let me just draw it much more betterly. So let's draw this curve like this. Our main aim is to come to this point. Okay, this point is basically my global minima or near to this point. Because this point, if I come, which is my global minima, then we are basically getting our best fit line. Okay. Now, initially my theta value got initialized at this particular point. I got j of theta, but I have to make sure that I come to this specific point. My j of theta should come to this point so that my cost will basically minimize, right? Now, my theta of j, how do I make sure that? How do I make the changes such that my j of theta will come over here that we are going to look at? Now, as soon as it comes over here, this derivative of j of theta with respect to theta j is nothing but we are trying to calculate the slope at this particular point. That is what derivative specifies. Okay. Now, in this particular case, how do we understand what is the derivative of this particular value? Okay. In order to find out the derivative, one important thing that you really need to find out is that whether this is a positive slope or negative slope. Because derivative is nothing but we are actually trying to calculate the slope. Okay. We are trying to find out the slope. Okay. So for this particular point, what we do in order to calculate the slope, we create a tangent line like this. Okay. Let's say that we are creating this tangent line. So this tangent line will probably get created like this. Okay. Now, when we are creating this tangent line, first of all, you need to find out that see the right side of the line. Okay. Because one important thing that we need to find out over here that whether it is a positive slope or a negative slope. Because if we are able to find out whether it is a positive slope or negative slope, then we will be able to understand whether we have to reduce our theta j value or whether we have to increase our theta j value. Okay. Now in this particular case, at this particular point, if I really need to understand whether this is a positive or negative slope, just see the right part of the line. The right of the part of the line is facing downwards. Okay. If it is facing downwards, we will be saying this as negative slope. Now, when we say negative slope, that basically means whenever we try to find out the derivative, this value is going to be negative. Okay. This value is going to be negative. So what we are going to do is that we will just suppose I get a negative slope. So in short, I will write theta j is equal to theta j minus some learning rate alpha. I'll talk about why alpha is used, and this will be my negative value. Okay. This will be my negative value. So in short, this basically indicates that my theta j, I have to probably add with some positive value, right? Because negative into negative will be positive. So I have to add this specific positive value. And it is true over here because I need to basically increase my theta j value. So if I do this iterative process again and again, wherein I'm continuously getting a negative slope, that basically means I have to increase my theta j value so that I reach my global minima. So this equation is going to add some value into my theta j. How much value? We don't know. Since this is an iterative process. Our main aim is to basically optimize this process of selecting different theta 1 value, right? So in this way, what will happen? We are incrementing or we are increasing our theta j value. Then in the next theta j, whatever will be my cost function, again, that specific point will come over here. Let's say it is coming over here. Then again, I'll try to go and find out this slope. Again, if it is a negative slope, we keep on adding. So slowly, you will be seeing that we will be able to converge it towards the global minimum. Okay, this is one process. What about now in this particular case I got negative slope. What about if I get another point over here and this particular point is actually a positive slope? How do I get a positive slope? Because if I try to create a tangent line, just see the right part of the line. Right part of the line is pointing upwards, so this becomes a positive slope. Now in the case of positive slope, I really need to decrease my theta j value, right? Let's say that initially my theta 1 was over here and I got my j of theta 1 over here. So here I have to decrease it. Okay. I have to decrease it. Then only I'll be able to reach the global minimum. So does this satisfy? Yes, it does satisfy because if I write now theta j is equal to theta j minus alpha, and now this is my positive slope, right? So here with respect to this, whenever I try to find out the derivative, it is a positive slope. Now whenever it is a positive slope, all I'm actually doing, I'm subtracting with some value, some positive value. When I subtract with some positive value, that basically means I have to basically decrease my theta j value. And if I continuously perform this process, after some time you will be able to see that I am going to basically come at this specific point. Okay. So obviously this convergence algorithm will obviously work because what I'm actually doing is that we're trying to calculate the slope in such a way that where if it is a negative slope, the theta j value is going to increase. If it is a positive slope, the theta j value will decrease. Okay. So this is what is a convergence algorithm all about. Okay. Now, there is one important parameter that we did not discuss about is something called as alpha. So what exactly is this alpha? Alpha is nothing but this is specifically a learning rate. Learning rate usually is a smaller value that is basically initialized. Let's consider the learning rate that may be initialized for my problem statement is 0.001. Now, what is the importance of this learning rate? Learning rate controls the speed at which the convergence should happen. Okay. If it is a very, very small value, then it will probably take more time to converge. If it is a very big value, then it may happen in such a way that it may continuously jump here and there and it may never converge. So you always have to make sure that you try to select a smaller value, but it should not be a very, very smaller value. It should be like 0.001, which is a very good practice that you should try to select. Okay. In simple linear regression only, alpha is equal to 0.001 in a scale library that we use is basically getting selected. So if anybody asks you in an interview, like what is the importance of learning rate, you can definitely say that it actually controls the convergence, like how slow the convergence should happen. Okay. So this is what it basically says, right? So I hope you have understood about the convergence algorithm, and this process continues unless and until we don't come near this global minima and we don't basically converge over here. As soon as we converge at this particular point, you will be seeing that we will try to get the best fit line, which is this specific line with respect to any kind of data points. So this is the most important optimized technique that we should use with respect to the convergence algorithm. Okay. And this basically gets applied in an amazing way, and most important interview questions when you're learning machine learning algorithms. So yes, in the next video, we are going to also continue and understand about the performance metrics. Thank you. Finally, in our previous video, we have seen till here, we have understood what is the convergence algorithm and how we can actually update our theta value, which is my coefficient, based on the positive and negative slope. And this was the theta or coefficient updation formula. Here, alpha also we used it, and this specific alpha was nothing but learning rate. Now, I really want to make one final conclusion and probably write some more equations, and we can just consider that till now, we saw that we have actually covered something called as gradient descent, right? And gradient descent, whenever we talk about gradient descent, so in short, we're talking about that curve. Okay, so in short, we're talking about this specific curve, and this curve is basically we get it from when we try to plot with respect to theta and j of theta, right? So over here, you'll be seeing that this is the curve that we usually get, and our main aim is basically to come to this global minima, right? So this global minima, and we try to update our theta based on this, right? Basically, we try to find out whether the slope is positive or negative, and based on that, either I need to update the weights, increase this specific coefficient, or decrease the specific coefficient, which I've actually explained over here. Now, for our example, we had actually considered, what that our intercept is 0. That basically means our best fit line passes from this to this, and since it passes through this intercept, so we considered theta 0 is equal to 0, and we were changing theta 1 value. Okay, so this was basically changeable, right? We did not focus more on theta 0. The reason why I did this is that because I wanted to show you the gradient descent in the 2D diagram. So over here, when I'm drawing this is basically in the 2D diagram. Let's consider that theta 0 is not 0. That basically, let's say that if it is not passing through the origin, then this 3D diagram may look something like this, right? So let's say this entire diagram will look something like this. I am just creating for an example, so it may look something like this. Okay, it may looks something like this. Let's say consider that it looks like this. So one theta 1 may be somewhere here, okay, theta 0 may be somewhere here, and our main aim is basically to merge towards this global minimum, right? So our aim is basically come to this global minimum. So this will also get updated like this, and this will also get updated like this, and finally we reach the global minimum. So that we usually do in a 3D diagram. And obviously I cannot draw a 4D diagram. Just understand it's like an inverted mountain, and from the bottom, from the top, you are basically coming to the bottom, right? So bottom at one single point. So this particular point will be the global minimum. Now, if I consider theta 0 and theta 1, let me go ahead and write my convergence algorithm. Okay. So what was my convergence algorithm again? So I'm just going to update my convergence algorithm. Okay. And the convergence algorithm was pretty much simple. Here I will say that repeat until convergence. The same thing what I have written on top, okay? Repeat until convergence. But here my theta j will get updated something like this, right? So theta j is, see, this symbol that I'm using, right? This is a continuous iterative process. So that is the reason I'm writing this colon and equal to. So it will just get updated with respect to this theta j minus alpha, which is my learning rate, and then derivative of theta j. Okay. And one point I have to use is nothing but j of theta 0, theta 1, right? Now, since my theta 0 is not 0, so I have to basically find out the derivative of both these things. Now, and you know that what is j of theta 0, theta 1? Okay, we already explained it. So j of theta 0, theta 1 is nothing but our cost function. So if I know my cost function, it is nothing but 1 by 2m. Summation of I is equal to 1 to m. M basically means how many number of data points I have, and then I have h theta of x of I minus y of I whole square, right? So this is the cost function that I specifically used for j theta 0, theta 1. Now, my main aim is basically to go ahead and calculate this, right? Derivative. Now I'll try to just show you. It's okay if you don't know derivatives also, guys, but understand our main aim is to basically converge to the global minimum, right? So here I'll just go to write something like this. I'll just try to calculate this, and over here you know that since you have theta 0 and theta 1, your j value will be 0 and 1, right? 0 and 1. So let me just go ahead and write it over here. So derivative of theta j, okay, with respect to j, theta 0, theta 1 is equal to derivative of theta j. Okay, and I have over here 1 by 2n. I'm just replacing j theta, 1 with the cost function, right? Whatever cost function I'm writing. So 1 by 2n, summation of I is equal to 1 to m. Okay, and then I have over here h theta of x of I minus y of I whole square, right? So this is my entire derivative of j theta 0, theta 1. Okay, and let's go ahead and try to find out the derivative of this. Now, guys, it's simple, right? If I take an example, if probably in high school you have learned about derivative. Derivative basically means you're trying to find out the slope. Suppose if I really try to find out the derivative of x square, right? So what I will be getting with respect to 6. See, over here I'm trying to find out the derivative of x square with respect to x. So this will be nothing but 2x, right? It's just like n x to the power of n derivative is nothing but n multiplied by x to the power of n minus 1. So this is what is the formula, right? So similarly, I'm going to apply this derivative for this particular equation. But when I'm finding the derivative, I have to find it for j is equal to 0 and j is equal to 1, right? So I'm just going to write over here if j is equal to 0, right? So if j is equal to 0, this entire equation, what it will become is this entire equation, this top equation, this entire equation will be becoming derivative of theta 0, j of theta 0, theta 1, which is nothing but derivative of theta 0, 1 by 2m. And here I'm basically going to use summation of I is equal to 1 to m. And this will basically be, I'm just writing the same thing, right? H theta of x of I minus y of I whole square, right? So this will be my entire thing. Now here you can basically see that fine, I'm getting this exactly. Now I'll just go and find out the derivative with respect to theta 0. So if you know this equation, always remember this is just like your x square. Let's consider this is my entire x square, right? So x square will be nothing but 2x 2 minus 1, right? Something like this. So whenever we have this x square, whenever I try to find out the derivative with respect to this, it will be 2x 2 minus 1, right? This is what is the basic formula. Okay. So these are simple derivatives, guys. If you don't know, don't worry. Okay, but just I'm trying to write out the convergence algorithm with respect to theta 0 and theta 1 because now we have a 3D graph, 3D curve, which will try to converge in one single point. Okay. So finally, here I can basically write after this, in short, if I really want to write, so this entire value will get converted to something like this. So it will be nothing but 1 by m because 2 will be there. This 2 will come down, so 2 and 2 will get cancelled. And here you can basically write summation of I is equal to 1 to n h theta of x of I minus y of I whole square. Okay, so here, sorry, not whole square because 2 will go down, right? So this is my entire derivative. And h theta of x, you know, right? What is h theta of x? H theta of x is nothing but theta 0 plus theta 1 x, right? So if I try to find out the derivative with respect to theta 0, so this will be 1 and this is actually a constant, right? This entire thing is basically a constant, right? So this will basically become 0, right? So theta of 0 will be 1, so it will be multiplied by 1. So in short, we will just be getting this specific term, okay? So I hope you are able to understand it. What we will do is that while finding derivative, right, we'll replace this h theta of x with this equation, right? And since we are trying to find out the derivative with respect to theta 0, first of all, it will be 2x, okay? And then we'll try to find out the derivative of this particular equation, okay? And here we know that if I try to find out derivative of theta 0 with respect to this 0, so here I'm going to get 1 and this is a constant, this will become 0. That is how derivative actually work. Now similarly, with respect to j is equal to 1, I'm just going to find out the derivative and this will now change as derivative of theta 1, j of theta 0, theta 1. Okay. So here you can see derivative of theta 1. Okay. And then I'm going to just apply for this specific equation and it will be same thing, summation of I is equal to 1 to m. And let me just equate this as theta of x with theta 0 plus theta 1 into x. Okay. Theta 0 plus theta 1 into x. I could have replaced it over here, but it's okay. This is what I will be getting, right? Now, you're just going to find out the derivative with respect to this specific equation. Now, in order to find out the derivative, it's very simple. Again, I'm going to take this entire 2 down. So this will be 1 by m. And here I'll be getting summation of I is equal to 1 to m. H theta of x, which is nothing but theta 0 plus theta 1 multiplied by x. Okay. Then it will be plus, minus y of I. Okay, so this will be my entire thing. Then this entire thing will be going to the next step. Okay, and from this you know that now theta 1 is not a constant, right? Because we are trying to find out the derivative with respect to theta 1. So just imagine, like if I'm trying to find out the derivative of theta 1 with respect to theta 0 plus theta 1x. So what will happen? So here theta 0 will become constant. Theta 1 will be basically getting a derivative. So here, in short, if I try to find out the derivative, this will be x. So I'm going to just multiply by x over here, right? So this in short will be actually helping us to find out the derivative with respect to theta 1, right? So this is my entire derivative with respect to j is equal to 1. Okay, I have just taken this and found out the derivative, it is x, so I multiplied with x. Okay, so these are the two things that we really need to write. So finally, I can quickly write something called as repeat until converge. This will be my final statement and final conclusion with respect to simple linear regression, repeat until convergence. Okay, and here we will be basically using two important equations. First of all, we need to keep on updating theta 0. So theta 0 will be nothing but theta 0 minus learning rate 1 by n, right? So what is theta 0? See, with respect to theta 0, this is what over here I need to replace derivative of theta 0 with respect to j of theta 0, theta 1. What is the derivative of j of theta 0, theta 1 with respect to j is equal to 0? This is my entire equation, right? So I'm just going to write this entire equation over here. So it will be nothing but 1 by m, summation of I is equal to 1 to m, and here I will be seeing h theta of x of I minus y of I. Okay, and then theta 1 will get updated as theta 1 minus learning rate, and derivative of j theta 0 comma 0 theta 1, what is the derivative we got over here? This particular equation, right? So here I'm going to basically write 1 by m summation of I is equal to 1 to m, and again I'll be having h theta of x of I minus y of I, and here I'm going to use x of I. Okay, so this is my entire equation that I specifically get, and this convergence will be happening unless and until we get the best fit line, or we basically get the best fit line, or we converge to the global minimum. So this is the entire thing that we relate to. I know there are a lot of equations that has been used, but again understand the phenomenon. What we are actually doing, we are converging in this gradient descent, right? If I use theta 0 and theta 1, then it becomes a 3D curve, right? 3D curve, and at the end of the day, theta 0 wherever it is, we have to come to the global minimum. So I hope you have understood it. If you find any difficulty with respect to the equations, don't worry, okay? Because implementation, some amount of theoretical knowledge is required. If you don't know the equation, also implementation will be quite easy with the help of a scalar, right? So yes, this was with respect to simple linear regression, and in the upcoming videos we'll see some kind of practical implementation. Thank you. In our previous video, we have actually seen the convergence algorithm of the simple linear regression. In this video, we're going to talk about multiple linear regression. We're going to just understand what is the basic difference between simple linear regression and multiple linear regression. In our previous example, when I consider our data set, right, we have taken the example that my input feature is probably, weight. So I really need to predict height, okay? And for this, this is specifically one input feature over here, one input or independent feature, and this is specifically my output feature. So what we did with the help of simple linear regression is that we tried to find out the best fit line, and we understood the equation cost function is the convergence algorithm of updating the slope. Now in this particular case, since I just have one input feature, so if I talk about the h theta of x, which is the equation of the straight line, which we have actually discussed, we are indicating something like theta 0 plus theta 1 multiplied by x, right? Now over here, this x basically indicates my input feature, right? Input or independent feature, right? And obviously you know what is theta 0? Theta 0 is basically intercept, and theta 1 is nothing but slope, right? Now, what we were doing is over here is that we were trying to change theta 0 and theta 1. We will not change x, whatever is there in this training data set, that only things we are going to take and probably train our model, right? So in this particular case, what we'll do is just change theta 0 and theta 1, and we'll try to find out the best fit line. Now, what if in your data set, you have multiple input feature? So let's consider one simple data set. I call this particular data set, which is called as house pricing data set. Okay, now in this house pricing data set, and probably I'll show you this all kind of data set when we do the practical, right? Let's say I have multiple features like this: number of rooms in the house, size of the house, okay, and let's say what is the location of the house, and finally I have something called as price of the house. So over here in this particular problem statement, here you can see that I have four features over here, 4 features in total, and this first 3 features are basically my input features, right? This first 3 features are basically my input features or independent features. So I'm just going to write this as independent features. Now in this particular case, you can see that I have more than one input feature or independent feature, and this is my output feature. Now in this particular case, when we try to find out a best fit line, how does the equation of the best fit line look like? So now I'm going to basically use the same equation, h theta of x, which is nothing but theta 0. Theta 0 is always an intercept. There will always be one intercept for any kind of regression problem, or if I'm basically using a simple linear regression or multiple linear regression, there'll always be one intercept that we really need to use it. Along with this, based on the number of features, right? Let's consider number of rooms is my x1 feature. So for this, we will be having another slope, which I'm mentioning over here as theta 1. Then I will be having for my second feature, theta 2. So theta 2 is the slope for size of house or coefficient of the size of house, okay? And similarly, location will be theta 3, x3. x3 basically indicates location, right? And theta 3 is basically the coefficient. So this equation basically indicates my multiple linear regression. Okay, so in the case of multiple linear regression, one important thing that you really need to understand is that we will definitely have many features. Okay, here in this particular case, I've taken 3 features. So with respect to these 3 features, I will be having 3 coefficients. So over here, theta 1, theta 2, and theta 3 are basically my 3 slopes or coefficients. Okay, so as the number of input features increases, that many number of coefficient will increase. But your theta 0 will always be the intercept, and you will have only one intercept all the time. Now in this particular case, if I probably talk about our gradient descent, let's say since there are 3 input features, in this particular case, when I draw with respect to theta 0, it's not theta 0. So let's say theta 0 is here, then I have theta 1 over here, and probably we cannot draw 4D diagrams. So let's consider just 2 features. Here I'm just considering theta 0 and theta 1. Okay, and with respect to this, suppose I have j of theta over here, right? So we usually get a different types of diagram, which will be looking like a inverted mountain. Okay, so let's say that this is my gradient descent curve. Okay. And here you'll be seeing something like this. Right? And our aim is to basically come over here. So theta 0 can start from this point, theta 1 can start from this point. And let's say if you're using theta 2 or theta 3, it can probably start from this point. But everybody's aim is basically to merge or converge to this global minimum. Okay, so this is how we basically solve multiple linear regression. Obviously, I cannot show you some kind of simulation and all. Let me see if I get any simulation tool in this particular course to put up. But just understand that in this particular case, we have many coefficients, and we have to keep on changing theta 0, theta 1, theta 2, theta 3, and try to reduce our cost function j of theta. Now over here, I can basically write j of theta as something like this. So I can have j of theta 0, theta 1. Now in this particular case, since I've taken theta 0 and theta 1, so I'm just going to mention it like this. Okay, so this is what multiple linear regression is all about. In multiple linear regression, we are focusing on, right, like our input features will be more, not just only one. If we just have one input feature, we basically say it has simple linear regression. If we have more than one input feature, we basically say multiple linear regression. Okay, so this was the basic difference. I hope you have understood this. In the upcoming videos, we're also going to understand some amazing assumptions about linear regression, and these assumptions are very important to understand. So let's go ahead towards the next video. Thank you. In our previous video, we have understood about the mathematical intuition behind linear regression and multiple linear regression. Now we're going to understand some of the performance metrics that is used to determine whether the model is good or not for a specific problem statement. And the metrics that will basically be used is something called as R squared and adjusted R squared. Now let's understand what exactly R squared is, and what is adjusted R squared, and what is the exact difference between both of them. Now first of all, let's go ahead and understand about R squared. And R squared is basically given by the formula, which looks something like this. So this is R squared is equal to 1 minus sum of square residual. I'll talk about what is this residual and all, and this is sum of square total. Okay. So here, a simple definition that you can probably see is that R squared is nothing but 1 minus SS residual, that is sum of square residual, divided by sum of square total. Okay. Now let's understand what is the sum of square residual. Suppose if I say this is my problem statement, let's say this is my x-axis, y-axis, okay, and I have some of the data points which looks like this, okay. which looks like this. Okay, I'm just drawing some data points over here. Our main aim is that we need to find out the best fit line. So if you are trying to find out the best fit line, with respect to this orange points, these are my two output, right? I specifically say all these points belongs to y of I, right? Y of I are basically my two outputs, right? Now similarly, with respect to this particular point, the predicted point is nothing but this part, right? So this I can basically say it is y of I hat, right? Y of I hat. Y of I hat are my predicted points, right? So this is my predicted point, 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 this is my predicted point. So I'm just drawing all my predicted point. Now whenever I try to find out the difference between them, then in short, I am basically saying that as this is basically my residual, okay? Residual or error. So if I probably try to find out this particular distance, this particular distance, this distance, this distance, this distance, and this distance, this is basically the residual, okay? Now understand the definition over here. I'm basically writing 1 minus sum of square residual. So I can basically write this as with this notation, that is summation of y of I minus y of I hat whole square, right? So in short, what I'm doing, I'm basically trying to find out the difference between y of I and y of I hat, okay? And I'm doing all the summation of all this particular residual or error. I can also say this as errors, okay? Now this will be divided by sum of square total. Now what is this sum of square total? Now with respect to this particular point, I hope everybody found out, okay, this is my best fit line. But with respect to the y-axis and with respect to all these y points, if I try to calculate the average, okay, so if I try to calculate the average, then you may probably seeing that y of I average will come with respect to the specific point, okay? Or let's say I'm just trying to calculate all the y of I points. I'm just taking all the y of I points and I'm just calculating the average. Now with respect to this kind of distribution, let's assume that my y of I is basically getting passed over here. This y of I hat I will say, okay? So this basically indicates this is nothing but average of the true points, that is y of I, okay? Average of all the y of I. Now, this sum of square total basically means, if I really want to give it in a mathematical notation, this is nothing but summation of y of I minus y of I hat whole square. So this basically means that we are trying to find out the difference between the true point and this specific point, which is basically indicated by y of I hat. Y of I hat is nothing but it is the average point, okay? So from here to here I'll calculate the difference, then from here to here I'll calculate the difference, similarly here to here I'll calculate the difference, here to here I'll calculate the difference, here to here I'll calculate the difference, here to here and here to here, okay? So this orange line that you see, this is basically the mean of all the y of I points, okay? So this basically will be giving my r squared value, okay? Now, here you can clearly see that, obviously just by simple understanding, right? You can definitely see that y of I minus y of I hat whole square, this residual, this difference of the residual, because my best fit line passes through almost near to all the true points, right? So this particular difference will be smaller number when compared to this particular difference, right? Because this is with respect to the average, this specific line, and obviously the distance will be quite big. So here I can definitely write something like this. I will write that this y minus, let's consider this is a small number when compared to the denominator, right? So the denominator will be a bigger number, right? Small number divided by bigger number. So now when we do this kind of division, obviously we are going to get a smaller number itself. A smaller number itself, right? So let's consider this numerator is a smaller number and denominator is a bigger number. Obviously, when we try to find out the division of these two, obviously we are going to get a smaller number. So 1 minus smaller number will be, very much near to 1 itself, right? It will be approximately near to 1. So let's consider that suppose if I'm getting 0.70, right? So this basically indicates that I'm actually having 70% accuracy, right? Suppose if I get this specific difference is somewhere around 0.85, this basically indicates that I'm getting at 85% accuracy. Suppose if I say it is 0.90, I'm actually getting a 90% accuracy, right? So with the help of r squared, we are able to find out how our model is performing, right? And more this value, understand, more this value, it is towards 1, right? More accurate my model is, more accurate my model is, more accurate my model is, my linear regression model is, okay? But there is something called as overfitting, okay, which we will probably discuss as we go ahead. We are going to discuss about overfitting and underfitting. Just in some time, we'll discuss about it, how we need to identify whether the model is basically getting overfitted or not. For that, we really need to understand what is trained data, test data, validation data. Just give me some time, we'll discuss about that as we go ahead. Now, let's go ahead and understand about the second performance matrix, which is called as adjusted r square. Now, with respect to adjusted r square, okay, how it is basically different, that also we are going to discuss with respect to the r square. So here I'm just going to write my adjusted r square, okay, r square. Now, guys, if I consider this specific example, let's say I have in my data set, okay, I have in my data set one feature which is called as, let's say one of the feature is like size of the house, okay, size of the house. Suppose this is my data set, I need to really predict what is the price of the house, okay. So I need to predict this specific thing. Let's say I have one of the features which is called as size of the house. So I'm definitely going to write price over here. Now suppose if I have size of the house and the price of the house, as we know that as the size of the house increases, my price is also going to increase. So there is a direct correlation between size of the house and price of the house. And this is usually happens in any state or any region that you're probably staying, right? The size of the house as it increases, the price also increases. So and similarly, when the size of the house decreases, the price also decreases. So here we can definitely find something called as a positive correlation, right? Positive correlation, a good positive correlation. So when we have in this particular case a good positive correlation, then what happens? My r squared value probably increases, right? Let's say this value basically increases. Now let's say in this particular case when I'm using these two features, and let's say that I have actually computed my r squared value that was coming was somewhere around 75%. Let's say 75% is nothing but 0.75 with the help of the same formula. Okay, let's say with the help of this same formula that we have used over here, we got 0.75. Now what happened is that let's say I included one more feature. After the size of the house, I said number of bedrooms. Now you know that as the number of bedrooms increases, right, the price is also going to increase. So from this, I can definitely say as my number of bedroom, and this is just a domain knowledge, right? When the number of bedroom increases, my price also is going to increase. So here also, I can definitely see something called as positive correlation, right? So when I'm actually seeing this positive correlation, now if I go and probably find out my r squared value again, after I create my model and probably plot or get my best fit line and then apply this entire formula, okay, I am definitely going to see some increase. Let's say here, I'm just assuming that I got 80% accuracy. So this is nothing but 0.80. This is also perfectly fine. Now similarly, when I try to add one more feature, let's say this particular feature is location, and we know that with respect to location also, it is more positively correlated with respect to price. Okay, these two are more positively correlated. So there are again chances that my r squared value will definitely increase. Okay, my r square value will become 85%. Let's say, I'm just assuming it has now increased to 85%. Now, let's say that, okay, this many features I have, okay, this many perfect, so many independent features I have, and this is all my independent features, and this is my dependent feature, right? Now, let's say that I have added one more feature. Now, this specific feature basically says that which gender are going to stay in this house, okay? Whether they're, I'm just adding one feature, okay, that does not make any sense, okay? And obviously, you know that if I consider gender with price, obviously, just by common sense, there will be no correlation with respect to price, right? Anyhow, no correlation. Whoever gender stays over there, obviously, price is not going to get affected, right? But if we add this particular feature, which is not at all correlated with price, and again, if we try to probably solve this problem, which again, in the future, I'll be showing you with the help of practical example, if I try to see the r squared value, even though these two variables, this input feature and this output feature are not at all correlated, then also since we are applying this particular r squared formula, there will be chances that this particular value will still increase, but it will not increase by a bigger value. So here you can see that I'm actually getting somewhere around 87%. Let's say, okay, I'm just assuming 2 more percent it got increased because the formula it works in that specific way of R squared is that as more number of features you keep on adding, somehow the R squared value is going to increase. Okay, and these all things I'll show you in practical also, guys. So let's say this became 0.87. But now there is some kind of problem. Even though this particular feature is not at all correlated with price, here you can definitely see that my R squared value is increasing. Okay, I did not prove it practically yet because I'll do the practical and show you with respect to this particular problem statement also, right? So in this case, the R squared, you can see that even though this and this feature are not at all correlated, still it is basically increasing, right? So this is the problem with respect to R squared, right? So this is the problem with respect to R squared. Problem of R squared. Even though you don't have a feature that is directly correlated with the output feature, then also this particular value increases since the formula is in that specific way. We are just trying to find out the difference between residual and difference between the mean of which we basically say as SS of total. Now, in order to prevent this, we basically use something called as adjusted R square. Now, in adjusted R square, what it does is that it penalizes with respect to every feature that are not correlated with the output feature. Okay, so this is what amazing thing basically happens with the adjusted R square. Now, in order to define the adjusted R square, we basically use a very simple formula. So I'm basically using R square or the adjusted R square. So let me write down the formula over here. And again, you do not know how the formula is getting derived, guys. That is not at all important. But instead, we should directly use this kind of performance matrix. So it is nothing but 1 minus R square. And I'll talk about each and every term multiplied by n minus 1 divided by n minus p minus 1. Okay, now let me talk about what is this n, what is this p, and all, right? So n is nothing but, we basically say number of data points. Okay, number of data points. So that basically means in our data set how many data points are actually there. Okay, and p basically indicates number of independent features. Number of independent features that we are using. Now guys, whatever formula that we have written over here with respect to the adjusted R square, one amazing thing that you'll be finding in this, and later on when we do the practical implementation, that thing will be clearly visible to you. So let me just note it down over here, and in the later stages in the practical part, I will try to show it to you. Now, n basically means number of data points, p basically means number of independent feature. Let's say initially my p value is something like 2. So this basically indicates that let's say my number of independent features are 2. In this case, let's say my R square is 90%. I'm just assuming, I'm just giving you a hypothetical scenario, right? If my R square value is 90, then if I try to apply the same formula with respect to R square adjusted, then here you'll be seeing that I will be getting less than this particular R square value. So here let's say I'm getting 86%. Okay. Now as soon as I increase p value, then obviously you know that we have seen that the R square value will increase. Okay, let's say the R square value has got 92%. And let's say that additional one feature that we have added, the independent feature, is not at all correlated. Okay, not at all correlated, or it does not have a direct impact on that specific output feature. At that point of time, you will be seeing that the R square adjusted value will get reduced. It will be somewhere around 82, 83. It will be less than the previous one, that is less than the 86%. Here I'm just giving you a hypothetical number. Okay, this kind of scenarios you'll be able to see with the help of adjusted R square. Suppose if the additional independent feature that I've added is directly proportional to the output feature, one thing that you will be able to find out that it will increase and it will be greater than this 86%. If it is not at all correlated, then it is going to decrease. This is the assumptions I'm making it right now. Okay, later on when I try to show you with respect to the practical, you will be able to find it out. I guess like you may be thinking, okay, how did this specific thing happen? Just understand, guys, when I'm probably increasing the p value over here with respect to the denominator, and when I start multiplying or divide with this specific value, this kind of relationship will automatically be formed. So whatever problem that we had in the R square will basically get solved with the adjusted R square. Okay, so for right now, just make this hypothetical note that I've actually made in front of you. Later on, I'll try to show you with the help of practicals also. So this was about performance metrics. Most common performance metrics that we use is something called as R square and adjusted R square. And the same thing I will show you in the practical. And when I'm showing you in the practical, there are also some kind of assumptions that we need to make. Like over here, I've spoken about correlation, right? And here also I showed you about like how R square adjusted is basically getting decreased. This is the formula that gets applied instead of this. So because of that, that specific value is getting decreased. Okay, so let's continue the video, and in the next session we'll discuss about more practical implementation. Thank you.